Did you know the World Economic Forum predicts AI will create about 97 million new jobs? That's a huge opportunity coming our way. Isn't that interesting? To help you get ready, we'll start with the basics of AI, including its history and evolution. We'll then break down the difference between AI, machine learning, and deep learning and explore neural network advanced framework like TensorFlow. But we are just getting started. We'll explore computer vision, showing how AI helps machines see and understand images and how this technology powers everything from facial recognition to self-driving cars. Next, we'll cover natural language processing, where AI learns to understand and generate human language, and explore cutting-edge areas like generative AI and large language models. We'll wrap it up with real-world AI projects and case studies highlighting how these technologies are changing industries and our daily lives. Whether you are new to AI or looking to expand your knowledge, this video will guide you through it all. Stick around and let's explore the future of technology together. Let's dive into artificial intelligence or AI. Start with a real-world example or any example. AI enables machines to mimic human intelligence, performing tasks like learning, problem solving, and decision making. It's categorized into narrow AI like voice recognition in Siri or Alexa, and general AI, which is still more of futuristic concept. In the real world, AI powers recommendation engines on platforms like Netflix and Amazon, suggests routes in Google Maps, and even drives autonomous vehicles like Tesla's self-driving car. In healthcare, AI is used for diagnosing diseases through image analysis, and in finance, it's used for fraud detection. Imagine this: you are watching your favorite show on Netflix, and it automatically suggests the next series you will love. That's AI working behind the scenes, analyzing your preferences to keep you entertained. Or think about self-driving cars. AI is literally steering us into the future, making roads safer by reducing human error. In healthcare, AI is already saving lives by detecting diseases early, sometimes even before symptoms appear. And in finance, it's safeguarding your money by catching fraud activities in real time. But AI is not just transforming this industry, it's transforming the agriculture too. Imagine drones monitoring crops and AI system analyzing data to optimize water usage and increase yields. This is not science fiction, it's happening now, helping farmers feed more people while using few resources. AI is making everything from entertainment to healthcare smarter, faster, and more efficient. And this is just the beginning. As AI continues to evolve, it's poised to change the world in ways we are only beginning to imagine. Stay tuned to explore more about how AI is shaping our future and discover how it might just change your life too. So, how AI evolved from a theoretical concept to a technology that is transforming our world. AI roots go back to the 1950s with Alan Turing's question, "Can machine think?" and the creation of the first AI programs like Logic Theorist. In 1956, the term artificial intelligence was coined at the Dartmouth Conference, marking the official birth of AI. AI saw early successes in the 1970s with expert systems, but progress slowed during the AI winter due to limitation in computing power and real-world complexity. In the 1990s, AI rebounded with machine learning, highlighted by IBM's Deep Blue defeating chess champion Gary. The 2000s brought further advancement, integrating AI into everyday applications like search engines and recommendation systems. Today, AI is driven by deep learning, enabling breakthrough like Google's AlphaGo defeating Go champion Lee Sedol. AI is now everywhere, from virtual assistant to autonomous vehicles. AI's journey from theory to reality is remarkable, with exciting advancement and challenges ahead. Stay tuned to explore more about AI is shaping our future. We have explored the origins and foundational concepts of artificial intelligence and seen how it has evolved and shaped the technology landscape. We have seen how AI has evolved and shaped the technology landscape, but how do AI, machine learning, and deep learning differ from one another? These terms are often used interchangeably, but they have distinct roles in the world of technology. Now we'll explore the fascinating distinctions between AI, machine learning, and deep learning. We'll break down how these technologies work, their unique characteristics, and how they intersect to create powerful solutions. So let's jump in.
Artificial intelligence has been gaining a huge momentum in the recent world, and it's making a tremendous impact in our career outcomes. But before we delve into that, let's understand what is artificial intelligence. So, what is AI? Let me ask you a question. Look at the photo above, and can you guess who that famous personality is? I think most of you guys would have guessed that it is Albert Einstein. But it's not an easy problem. Think about how your brain processed that information and how did it recognize it. It might have noticed the facial features. It might have noticed the curly hairs. It might have noticed the distance between the eyes. It might have noticed another million features to come to the conclusion that it is Albert Einstein. So, can you make a machine to think the same way which you think? That's AI. The process of making a machine to think like how a human does is what is known as AI. However, humans' ability to think and make a rational decision in a critical situation is unparalleled. And even science is not able to crack that. So, what does machines have for them? How is it superior? And how is it doing good? What do they have is computational power. And this has grown massively in the recent years. Let me ask you, what is the square root of 200? You'll not be able to tell me in a second, but whereas the computers can. But if you were to ask a computer to take a bottle of water from your kitchen, will it be able to? Well, the computer needs to know what does a bottle mean, what does water mean, and how to move, and where is the kitchen. Whereas the humans don't have any problem in that. So, making a computer to learn about its surroundings, adapt, and then grow is also AI. The term artificial intelligence has been around since a long time. It was first coined in 1956 by Mr. John McCarthy at the DARPA conference. Though the conference was a hit and it garnished a lot of attention from a lot of players, well, creating these machines or creating the smart machines required a lot of computational power and hardware, which was apparently not there at that point of time. Well, the tipping point came in the late 90s, where IBM's Deep Blue stunned the entire world by defeating the world champion at a chess tournament. Though not a fully functional AI, we see fragments of AI implementation in our daily day-to-day life. Think of the next time when you type in Google to search something. Well, how does it come up with the fact what are you going to type next? Well, Google has tons of data based upon what have you typed so far, and its AI algorithms are running on the back to find out what are you going to type next based upon what have you typed. Netflix predicts what movies you want to watch next based upon what movies you have watched in the past, whereas Facebook detects all your friends in the same photo which you have taken and uploaded based upon the information it has gathered in the past about your friends in your own profile. AI is usually divided into two broader categories: machine learning and deep learning. Machine learning is the use of statistical methods to understand and analyze information from a given data, whereas deep learning, a broader area of machine learning or a broader subset of machine learning, mostly deals with neural networks. With computational power growing exponentially year on year, the scope of AI has become vast and is being used in almost all the domains, in all the verticals, and across all the industries. Be it IT, retail, telecom, BFSI, travel, e-commerce, any of these industries, AI and ML has a future in all the facets of these industries.
Now you must be clear about the differences between AI, machine learning and deep learning. To learn more about AI, machine learning and deep learning, be sure to subscribe to our channel to be notified about the latest releases. Next, we'll introduce you to neural network, covering how these models recognize patterns. We'll explore deep learning and how multiple layers enhance basic neural networks. Let's begin.
Neural network is one of the most used algorithm in today's world. But why it's getting popularity with days? What is actually inside them? So we have some of the coolest projects using neural network, that is object detection, face recognition, image classification, text to speech, and Google Lens as well. The Fortune companies like Facebook, Instagram, Twitter, Google are currently using neural network concepts. So let's have a look at what actually neural network is. Suppose if you take an example of just to classify between cat or dog, then why you should go for using neural network, not machine learning, right? So basically in the traditional machine learning, you need to do manual selection of the features. But for the deep learning, the neural networks comes under a deep learning. So in the deep learning, you don't need to go for manual selection. Your model will automatically select the feature which is actually required to classify a picture for cat or dog. And when comes the neural network, what is it actually? A neural network is a network or a circuit of neurons. A neural network is either a biological neural network made up of real biological neurons or an artificial neural network for solving artificial intelligence problems. The connection of the biological neurons are modeled as weights. A positive weight reflects an excitatory connections, while negative values mean inhibitory connections. All inputs are modified by a weight and sum. This activity is referred to as a linear combination. Finally, an activation function controls the amplitude of the output. For an example, an acceptable range of output is usually between 0 and 1, or it could be -1 and 1. So let's have a look at what is the history of neural network. A neural network is an interconnected group of natural or artificial neurons for mathematical or computational model. Neural networks are non-linear statistical data modeling or decision-making tools. Neural networks solves complex relationship between inputs and outputs or to find patterns in the data. Artificial neurons were first proposed in 1943 by Warren and Walter Pitts, who first collaborated at the University of Chicago. What we have the basic components of biological neurons. The majority of neurons input their activations or output as a series of brief electrical pulses, that is spikes or action potentials. The neuron cell body processes the incoming activation and converts them into output activations. The neuron's nucleus contains the genetic material in the form of DNA. This exists in most types of cells, not just neurons. So dendrites are fibers which emanate from the cell body and provide the receptive zones that receives activation from other neurons. Axons are fibers acting as transmission lines that send activation to other neurons. The junctions that allow signal transmission between the axons and the dendrites are called synapses. The process of transmission is by diffusion of chemical called neurotransmitters across the synaptic cell. Now, let's have a look at the human brains versus the neural network. In the human brain, we have dendrites, cell body, axon terminal, and so many. But in the artificial neural network, we have activation function, we have sound and the output, right? So in neural network, what we have the input layer, we have hidden layers, and we have output layers. So let's have a look at the components we have in human brain versus neural network. So in the human brain, we have cell nucleus, whereas the artificial neuron has node. We have dendrites. In the artificial neural network, we have input like X1, X2, X3. In the human brain, we have synapses, whereas in the neural network, we have weights or interconnections. In human brain, we have axon, where in the neural network, we have the mapping or activation function that is f of x. And lastly, we have in the human brain that is terminal axon. And in the neural network, we have output that is y1. Now let's have a look at what is neuron. This is a very simple element that has some limited number of inputs. Some weight is tied to each of these inputs, and the neuron simply takes and carries out a weighted summation of its inputs. So this is what actually neuron is. Now let's have a look at what are the components we have in neural network, that is artificial neural network. So we have input values, we have weight and bias, we have net sum and activation or state function. So what happened actually? When you give your image, so your image pixel will be converted as an input, right? So after that inputs will be added with the weighted sum and the bias. And lastly, we will use some of the activation function to pass those weighted sum. And then lastly, we will get our output in a probability form. Now let's have a look at working of a neural network. A neural network is trained by adjusting neuron input weights based on the network's performance on example inputs. If the network classify an output correctly, weights contributing to the correct answer are increased, while other weights are decreased. So what is an activation function? In neural network, the activation function of a node defines the output of that node given an input or set of inputs. A standard integrated circuit can be seen as a digital network of activation function that can be on or off depending on input. So this is what actually activation function is.
Let us start with a quick did you know. Now, deep learning is such a fascinating concept that I was, many years ago when I started my career, and even before me starting my career when I was still studying, this concept came to be told to me by one of my professors, where I had to research about it and put out a thesis on deep learning. Now, in that particular case, I did a lot of research, and this domain was so fascinating that ever since way back during the college days till now, I have been hooked onto this domain. It's my favorite domain in the case of in the case of data science, which of course again a lot of people agree with me. It's the gateway to artificial intelligence and all of that, right? So I'm sure you guys will appreciate this as much as me. Right, guys. So the first point that we have to discuss is, this is a concept. Deep learning is a concept where I told you that we're going to get towards artificial intelligence, right? What I mean by that is actually that we're going to take machines, train them in a way where, their thinking, their behavior, and the output that they give, when we furnish it with an input is going to be very similar to what a human being would do. Now, to do that, it takes this kind of a human-like thinking approach which you have to impart to your machine. Now, me and everyone else who are watching this video, right, human beings, and of course all the algorithms and all the artificial intelligence models in the back end of the video platforms that you're watching this as well, you have to realize that as human beings, we have billions of neurons which are like supercomputers on their own, and there is a connected network in between all of these neurons which make us the being that we are, right? Our conscious is the experience that we are living in. Now, to take these power of billions and billions of neurons and to make your computer understand it, which at the end of the day your computer can only understand zeros and ones to its fundamental level, as I've been explaining, it is a very tough challenge. But these days, with the amount of data that we have, with the immense amount of algorithms and computing power, we can combine all of this together and make sure that our machines can behave as humanly as possible, right? So that is one thing you're supposed to know. The second thing is deep learning is used literally everywhere around you, even though you might, not be aware of it. If you're watching, a video on an online platform, there is a lot of AI related models working there. Are you using social media? I'm sure, all of you, if not most of you, would be using one form of social media or the other. Well, deep learning algorithms are at play there, even though you wouldn't recognize it at first. And then it is not only this, right? It is as simple as you looking at your mobile phone, asking the Google Assistant, asking Siri, asking Alexa, Cortana, whatever are the new personal assistants we have in today's world, right? You are literally talking to your computer and your computer is talking back to you in a human voice. How amazing is that, right? That is what deep learning is all about. The output of this, the applications of it, as you're going to see, we will discuss, is extremely trending right now. There was a time when people thought, hey, you know what, you cannot have your mobile talk to you or order a pizza for you as well automatically without you having to do anything. Now, all of that are a piece of cake. It can be done very easily, right? So when people said it couldn't be done, all the way to now that, hey, it's not really a tough thing, it can be done easily, the world has grown a lot in terms of how we can repurpose deep learning for other use cases as well, guys. So it's an extremely trending concept. And if you are proficient in this, your foundation as a person who's looking to become an expert in data science will be strengthened a lot. So I suggest you pay a good amount of attention to understand deep learning. So with that, you should have a question saying, okay, what exactly is deep learning, right? Deep learning is one of these subsets of artificial intelligence. Now, artificial intelligence is an application of data science, right? It's a domain in which we use this subdomain or the subset to get us to a solution. Right now, in AI itself as a subdomain, inside it we have machine learning and deep learning. Now, machine learning is a simpler version of deep learning, but the differences don't end there. We are going to discuss about it because the working is extremely different in these both cases. But as of now, you have to understand that deep learning is a way that we train our machines so that they become self-sufficient on their own in terms of learning and giving us a result which is almost human-like. Now, I cannot say 100% human-like, because if that was the case, then it would be very difficult for us to differentiate between a machine and a human being, right? We haven't gone to that extent yet, but we are getting really, really close to that point. Now, way back in the day, there was a test conducted called as the Turing test. It was named after the very famous mathematician Alan Turing, where he says that a machine can pass the Turing test if it can convince a person that the responses it gives is as human-like as possible. So the person on the other side of the test, if he or she cannot differentiate between the result given by a human being and the result furnished by an artificial intelligence algorithms, that is when that model or whatever is the entity in discussion has cleared the Turing test. Way back from the 60s until now, it has been an amazing feat that we are trying to get to teach machines to do it. It is not a new concept. It is not something that was born yesterday and that it is exploding right now. It is a very old concept, just that we did not have ample amount of computing performance to go on to process it then. But now that we do, it's going to be an amazing thing of how personally we can sit and teach the machines of how they can think on their own, how they can build logic on their own. We are logical beings, but the computers also have logic, yes and no, 1 and 0, multiple states, continuous values, discrete values. It is just that your computer does not understand and process emotions, nor does it have this complex network that is wired by itself, right? Of course, we are a product of evolution, and we are developing the computer to make sure that it can evolve into something better as well. So that's an important thing that you guys should know about. Now, deep learning is a name which comes from the fact that we actually use several layers of processing. Now, when we say deep, it means you have to go through a process, you have to go through multiple things to get to the depth of things, right? So your algorithm is going to touch the depths of what it can do. Hence the name, multiple layers on layers. It's called as a neural network. We're going to be discussing in depth about it in the next module as well. But for now, you need to have an understanding of the domain itself. So this kind of a way of learning, where we use multiple layers of learning at the end of the day to give us a fantastic product, which is very, very powerful and is amazing to use, right? That is deep learning on a whole, ladies and gentlemen. So as I've been mentioning right now, for a while, right? So it is an important thing you have to understand, that we are trying to imitate human intelligence here. We humans are very, very, very intelligent compared to our computers right at this moment. Even though you might say, okay, there's the world's fastest supercomputer that can, compute things faster than a human being. I will agree to all of that. There was a time when, Shakuntala Devi, the person who was called as the fastest, the human computer, the human calculator, right? At the end of the day, we set new benchmarks which our machines themselves beat. Nowadays, of course, when you look at programming power and the processing of computers, it is definitely a lot more than what it was in the past, because even if you go back to the time when the humans landed on the moon, right? When NASA put humans on the moon, the processing power of the computer had somewhere around 0.001 MB of RAM. 0.001 MB. That's it. It's not even 1 megabyte. Today, the phone that I use, the laptop that I use, and of course, the machine that I use to work on are powered with a maximum of somewhere around 64 gigabytes worth of random access memory RAM. 64 gigabytes. Right now, where is 0.001 MB and where is 64 gigabytes? Look at how much the world has progressed, right? Now is the right time to teach our machines and to make sure they understand everything there is to know about how what makes us intelligent, right? Now, there are many things you have to consider when you are trying to get your machine to imitate human intelligence. First of all, it is our programming which goes on to teaching these machines, right? Now, usually a question comes into picture whenever we talk about deep learning and artificial intelligence is that can machines learn on their own, get more stronger than the humankind, and sort of attack us and all of that, like how it happens in these amazing movies that we have watched in the past, right? The thing is, as I told you, your deep learning model, your machine learning model, your artificial intelligence solution at this point of time is only as good as the programmer himself or herself. So at the end of the day, if you are amazing at your programming skills, it means that you are your program at the end of the day, or your model is working efficiently, so it cannot surpass your intelligence. Of course, there has been cases where cryptic texts have been passed through which we do not understand as humans, and we perceive it as something like, okay, so the machines are talking to themselves, something is going on. It can be a fact which can be debatable, but of course that's a different discussion. But for now, you have to understand that one particular thing, that your program is as good as you, right? One important place where we can get the machines to imitate human intelligence well is pattern recognition. Everything you look around you is a pattern, and that is what builds your conscious experience, right? Now I am looking into my camera to sort of teach you guys on this. You are looking to your phone or your laptop or your TV or wherever it is that you are learning on. That is an experience, right? So there are certain patterns you know where to look at when you're learning. It's not like you're randomly staring at the wall and learning, right? You know what pattern you're supposed to know. You know what a square looks like, you know what a circle looks like, even to its most foundational level. That is the important thing here in discussion, ladies and gentlemen. And the fourth point, right? So in the case of deep learning itself, we take a little bit of machine learning, we complexify it. What is the word? We complicate it, and we apply so many different transformations to the existing machine learning solutions in a way where it becomes way more powerful than it already is, and that gives rise to and brings us one step closer to artificial intelligence, right? So using very complex machine learning concepts are an important thing here in deep learning as well, guys. So I hope this section was clear for all of you all. Now, let us actually talk about why we even require deep learning, right? Now, why we require deep learning is a question when asked to me, I can probably give you an answer hours and hours together to tell you why it is required. But, we can have a detailed discussion on the application of deep learning sometime else. But for now, to give you the highlights of all of these very important points, the first thing is we are generating an immense amount of data. You already know this, right? The world puts out somewhere around 25-26 lakh terabytes of data every single day. To handle this data, which is just adding on every single day, and to make sure that the data is available for further use and processing, we require more intelligence. See, manually, if you have to sift through maybe 10 lakh files which are full of data, physical files with papers in it, it becomes tough, right? You can take days, you can take weeks or months. A deep learning algorithm can do it like this, and maybe at the end of 5 or 10 minutes or maybe 1 hour, it has ran through 10 lakh documents and it knows what the documents are all about, right? Where is 10 minutes? Where is 1 month of hard work? That is an important thing you have to note. The second thing is that we are living in a world where autonomous systems are guiding us, right? Everything, from the most simple thing, you might have an aqua guard or whatever is your water purification system, right? If you're wasting water, it usually shuts off the power supply, your camera, the CCTV system at your home, it can detect movement and it can take photos as and when people sort of move through, in case you have authorized it to do so. And planes have their own autopilot systems. Defense systems use a lot of drones and unmanned aerial vehicles, or UAVs as they are called, right? Things have become intelligent in a way where you really don't need as much human care, as much piloting, not only in the case of aircrafting, but of course in other domains as well, to make sure that the job is done. There was a time when, of course, we're still living in that time where you have to drive your own car. But now we have come to a point, I'm sure all of you all watching this video already know that the systems we have, there are certain companies like Tesla, Google, and now even apparently Apple is developing a car, which I'm not sure of, is a fact that you should know that only thing that is stopping us to have complete autonomous driving is the law. Apart from that, the systems are here, they are ready to go on to do the driving for you. There was a time when cars would just back out of parking lots automatically for you, but now they can automatically take you from one destination to the other destination, do everything that you want to do. You can talk to your car. It is very, very intelligent these days, right? In this case, in the case of defense, for in the case of having robots to do a lot of tasks where human life is on the line, it's a very important thing. The third thing we have to discuss is how you can make use of large amounts of data to drive a good amount of information, right? Just the example that I gave you with the physical example of the files is exactly my point here in the third point. The fourth thing we have to discuss, which is very important, is how we can use iterative learning. Now, see, iterative learning is something that even we as human beings use. It is not a new thing for us. When you were in school, when you were in college, or even every day when you're learning something, right? Maybe you're learning to play badminton, or you're learning to code, or even you're watching this data science video to become, to become knowledgeable about the domain, right? If you just watch it once, yes, there's a good chance you can pick up all of the different things, but you can get more clarity if you do it 2 times, 3 times, right? You will not become a professional or an Olympic gold medalist the first time you probably play a sport. You have to give your time and effort to learn, to train, do the same thing again and again and again, that you remove all your mistakes and become efficient at what you do, right? That is iterative learning. Your computers also do the same thing. In the case of machine learning, again, in the case of deep learning, a common data set, your machine just runs through the data set, keeps learning. With every time it learns, there is some new insight that it picks up. It understands something new, something more than what it previously learned. Of course, in not in all the cases that it just keeps happening, that if you train for an indefinite amount of time, that your machines will keep learning. No, there goes until a point where it can learn new things. That is the key point in a discussion of why we require deep learning, guys. The next 3 points that we have to discuss talks about how immensely popular it is in all the domains, right? Self-driving cars, personal assistants, home security on your phones, social media, the TV shows that you watch, the music that you listen, the computers that you use, the search engines that take in the search entity element that you put on. Guys, again, as I told you, it is literally there everywhere. It is just that you have to find out. If you're ever confused about where deep learning is used in a certain domain that you think, quickly Google it out. If you're thinking about, hey, can deep learning work in finance departments? Can it work in the case of law? Can it work in the departments, or can it work in the domain of anything else which is not directly related to computer science, maybe arts, right? There is deep learning there. Trust me, there is. You just have to search and then you will find a ton of results, right? Now, the second point here, or the fifth point in discussion, a very important thing you have to understand is that we are a being where we want our lives to be more and more convenient, right? Now, we can also talk to our computers with zeros and ones, but we have to just type millions of zeros an hour or a day, which is not convenient for us to talk. So we want to use Windows, we want to use other operating systems like Mac OS, whatnot. It has to be as simple as possible. It has to be snappy. It has to make working fun for us, right? So we want convenience everywhere we go. Right now, I have a fan which is, swirling some air in the room as well. So even that is convenience. We have a roof over our head. Convenience. Nowadays, everything is talking about how you can make your phones convenient, right? There was a time in the past where if you held a brick And if you held a phone, it weighed the same thing. Nowadays, a phone is a pretty tiny thing which can fit at the palm of your hand. It can be a watch. Watches these days are millions, if not billions of times faster than the entire spacecraft that took humans to the moon, right? That's a fact. That is how amazing we have come through. So contributing to add more and more convenience to our lives is why people want to look towards these solution, guys. It adds so much value for us, right? Now, deep learning is used in a lot of different places, which we are going to discuss in the applications section. But understand this, it is very, very popular for the usage of face recognition. As I told you, security assistance, parking assistance, and all of these are extensively used. Even though you might not be the person who is actively using all of these, but everywhere across the globe, there's millions and millions of solutions, which are powered by deep learning. That is what makes this domain fantastic to talk about. The next thing we're going to check out is the applications of deep learning. So guys, as we have discussed, there are numerous applications of deep learning, but let us check out some of the most popular ones. First one, which you might not know of, is real-time behavior analysis. Now, it is a fantastic thing to know about and understand if you're a person who is selling a product, right? Now, let's say, let's consider the case of fidget spinners, right? They became extremely popular. People who are young, people who are old, everyone wanted to play with a fidget spinner, and of course, I myself had one as well. To understand about if you are a person who was selling something like that, people will definitely talk about your product on social media, right? They're going to give you their views saying how good is it, how bad is it, if they liked it, did not like it, all of that. So there is a sentiment which goes into what they type, and computers today, your models in the domain of sentiment analysis, which can read a message and understand if the person is angry, happy, sad, all of these emotions which we understand, right? We can train a machine to understand them as well, cross-reference it with data that exists to see what your what your customers are talking about the product. Now, 3 guys might be happy about it, 4 guys might be really unhappy, they're suggesting changes and all of that. So you can use that feedback to positively have a difference on the life of your product, right? Maybe they're giving you important feedback which you can use to further develop your product, right? So this can happen even in real time, as and when people maybe take on to social media platforms like Twitter or something, and they're putting their views on it. You can have a deep learning model here to analyze, assess everything in real time, and to give you a score saying, are people generally happy with my product or are they sad? That is an important thing in terms of real time behavior analysis. The second thing that we are going to discuss are symptom-based disease prediction, right? I am not sure if you know this, but medicine has really come a long way since the past, and now with the world of computing and medicine, it has come together in a way where doctors sitting on the other side of the world can monitor your parameters. They can suggest changes for you, and maybe look at your whatever symptoms that you might have, and then give you a medicine right from where they are across the world, right? Guess what? Of course, full credit goes to doctors because they are the experts in this domain, but computers are slowly catching up in a way where they can sort of look at symptoms, analyze what disease you might have, and eventually give you a prediction saying, hey, this person might have this kind of a disease. It might be something very specific, very generic, like a common cold or a flu or whatever it is, right? So it has come a long way where I'm not saying that it will replace doctors, but it can assist doctors for sure to help provide a better solution. Right now, if there is something which helps the field of healthcare, I am very sure that the doctors are going to take a positive note about it. There will be time spent, millions of hours on research on it before it has been put to usage in a human life critical situation. But yes, it is possible. That is the important thing that you're supposed to know. The third thing is autonomous car functions, right? Now, I am a huge fan of this, and I cannot wait for these autonomous cars to hit India, where, I definitely want to drive around in one of those in a way where, of course, even though it sounds very funny, like, how can you drive and how can you sit confidently if your car is driving for you? But the technology that goes into it, the immense amount of processing, and the way these cars learn to drive on their own, the autonomous aspect of it is something I absolutely love, right? You can check out multiple videos online of how cars can drive people around. It's already there in multiple different countries. These cars are there, they're on the road, they're already being used. Think about Tesla, right? Tesla is very popular for putting out these cars which come with a feature called as the autopilot. The autopilot can take you from one destination to another automatically. It can brake, it can turn, it can change lanes, it can do a lot of different things, right? Coming to the fourth point. The fourth point talks about data center security. As we discussed in a previous module, that if you are storing your data online, or if it's in a database or wherever it is, there is always a risk that someone might have access to it, someone might misuse it, right? In the case, if you're storing your data with a reliable data professional, maybe you think about Google's data centers, Amazon, Microsoft, all of these, their data centers are guarded in a way where, there is impossible access for you to go on to even touch the servers that are there which hold your data. Completely barring you from physical access, first of all, is the first way to defend against any sort of miscreants or misuse of your data, right? That is an important thing. These 15, 16, 17, 20 layers worth of security that you have to clear to even go close to the server is all in a human way. But nowadays it is becoming autonomous to a fact that, we can have a computer do this job of screening a person, seeing if he or she has authorized access to have, that kind of a security clearance, move ahead and all of that. It is very intelligent, it is fail safe, and it is being developed in a way where it is doing a fantastic job in this domain. That is data center security. The next thing we're going to talk about is the server optimization itself, right? See, manually, we have come up with methodologies of how we can store your data on a hard drive and in a server architecture. But nowadays, we use deep learning algorithms to make sure it is effectively stored based upon their usage. Maybe there is some data which you're going to store which you might not touch for the next 6 or 8 months, and your deep learning algorithm already knows this. It has learned the fact that you might not touch that data, so it will store it in a place which would not require immediate access to it. It understands that it is on the back burner and all of that, but there can be some data which you need on a daily basis which can actively store on a faster hard drive or a SSD or whatever it is, right? So moving these data around based on your usage, I'm not talking about 1 MB, 2 MB, 1 terabyte. This is thousands and thousands of terabytes every day, right? So this deep learning algorithm will run through the data, understand what it is, understand how you're using it, and then store it in a way where if required immediate access, of course you'll get it, but it knows how to store it effectively. That is the important talk about server optimization. Considering we are putting out millions and millions of terabytes out every single month, it becomes very vital, guys, right? The next application is self-driving cars. As I told you, self-driving cars are already in use today, but to go on to teach a car to drive on its own, it has to have, first of all, a ton of sensors which it can use to get a sense of the environment around them, right? So we have a lot of senses. We can see, we can hear, we can smell, we can touch, we feel pain. All of these things are sensory things which tell our brain that, hey, there is an activity that is going on. But for a car to do all of this, for it to sense that someone is crossing the road, to know that it has to go in that, and it has to have some sort of image recognition to understand that it has to go on the road and not on the footpath, right? So there is a ton of sensors and processing which goes on, in a very, very important way. As I told you, aircraft these days can be controlled from thousands and thousands of kilometers away. So there, a person sitting in his room can actually control an actual aircraft. This is usually very popular in the defense domain, but it is also trickling down to the commercial airspace domain as well. So in that particular case, again, another beautiful application, right? So in the entire automobile market, if you see that every day, it is not just Tesla, it is not just Google or Apple, it is just that everyone is looking towards coming one step closer to driving a better user experience, to giving you a sense that your car is more and more intelligent, right? Again, they're doing all of that by making use of deep learning itself. And if you look at cars these days, it will give you a personalized feel. As soon as you get into your car, you will realize that even though it is a commercially mass produced car, that it feels very close to you, it understands you, it talks to you, it welcomes you, it sets your seat, your temperature, your steering height, everything, right? Maybe even your suspension preferences if you're a person who likes to drive really quick, of course safe at the same time, or if you're a person who likes a slow comfort drive, it can pick music automatically for you. It can turn the wipers on and headlights on depending on rain and outdoor lighting. Guys, the amount of personalization that can bring together a lifeless entity and give it this kind of a human emotion, that is an important thing you have to know here, guys. And the next thing, right, the last couple of applications we're going to discuss in deep learning talks about recommendation systems. Recommendation systems are absolutely amazing. I am a huge fan of this particular domain because we sort of use it almost every day, right? Think about Amazon. Let me give you an example. On Amazon, let's say there is a flash sale or whatever they keep doing where they're trying to sell products. You get a phone, you put it in your cart. Before you check out, there is usually a pop-up or something on the bottom side that says, hey, people who bought this phone also bought XYZ, maybe a tempered glass, maybe a case or something like that, which adds value to your original purchase, right? That recommendation, product recommendation, comes from the fact that the website or whatever it is that is displaying information on the Amazon's page is intelligent enough to understand that when people buy that item, a phone, they also buy a tempered glass or maybe a case, right? That is product recommendation. And you might think, okay, but I usually take one product, I buy it, I check out, and I'm done. What is even the meaning or the validity of having a product purchase recommendation? You know that probably the co-founder of Amazon or Amazon itself as a business is grossing at number one or number two spot in the entire world, which is worth trillions of dollars, right? Now, Amazon themselves have said that 35% of their revenue that they sell on their website comes from product recommendation, guys. 35%, where a business is worth trillions. Of course, trillions, all the trillions are not on the Amazon sales thing, but think about it. It is still a huge number. 35% of a huge number is huge in itself, right? So it is adding a lot of value to, a lot of e-commerce sites. Amazon is just one name that I'm taking up here. Think about Walmart, think about Best Buy, think about all of these guys who are trying to catch up and use as much computing power as they can to solve problems. That is the discussion here. The second thing is Netflix. Oh my god, Netflix uses a highly complex recommendation systems, which is making sure that you stay on their platform, you watch nice content. Right, just a few minutes back I just told you about how personalization makes you feel nicer, right? Netflix is a platform where their goal is to make sure you watch more and more content. To do that, they go to extreme measures which are beautiful, at least for a person who's looking at it as a developer. Now, you might have a favorite actor, right? Maybe your favorite actor is Tom Cruise. Now, if you are a person who loves Tom Cruise, if you watched one or two movies of Tom Cruise on Netflix, it understands that you have a favorite. It knows, it has learned that this user watches a lot of Tom Cruise content. So what it does is, even if Tom Cruise is on another movie where he might be a supporting actor, he might have done a cameo, or he's just on the screen for a few seconds, the Netflix recommendation system is so intelligent that it can change the thumbnail of the entire picture, put Tom Cruise on it to make sure you click on it and watch it. That is how amazing it is. Changing these thumbnails based upon your favorite actors, making you want to click on it and watch it. That is intelligence, in my opinion, right? Of course, it's a good thing. It is giving you personalization. It wants to show you what you like, right? That's an amazing thing. The next thing is, maybe after you're done watching a movie or done watching a TV show, for a second you might have a crisis saying, okay, so this TV show is done, what do I do? But right the next second after the credits or the thing ends, it will start recommending you new TV shows and movies to watch right then. You might have watched a documentary, you might have watched a comedy TV show, whatever it is, right? Or a thriller movie or horror movie in that same domain itself, or using the same actors and the actresses. It will give you a recommendation which would make you want to watch the next thing as well. It is a brilliant thing, Netflix making use of deep learning, in my opinion. The third thing is Spotify. Of course, Spotify is one of these music streaming services, which again I use a lot personally. So, based upon the songs that you listen, it can automatically create a playlist for you, arrange them in the order of your liking based on how many times you've played it. Not only that, it will create playlists on its own, looking at the genres of music that you have listened to, what type of music are they, sad songs, happy songs, what emotions are evoked in you. It cannot be 100% accurate, right? So even a happy song can make me sad if that is the case, if it brings back a different memory, but it tries to a certain level to make sure that whatever it is that you're going through, your emotion, that there is a song that can be catered to it to soothe your emotions. That is a beautiful thing that these guys are doing as well. So be it Amazon, Netflix, Spotify, or millions of others who are using it, everyone every day is getting one step closer to making our computers and machines that much closer to us and giving us an amazing experience, right? Amazing. Now, in the next section, we are going to take a look at the prerequisites that are required for you guys to learn deep learning itself. So there's many prerequisites you're going to require for deep learning, but I'm going to give you the highlights of it and the importance of it. The first thing you're going to require is mathematics. The concepts of statistics, concepts of probability, concepts of calculus, and linear algebra are extremely important. Mathematics govern these algorithms. These algorithms are used to teach the model. Data plus algorithms gives your model a purpose to use, and that model is used to solve a problem. You see that change that I just built right now? That is why you require mathematics. If you remove mathematics from it, your algorithms are no more intelligent. Your model does not understand what data it is seeing. At the end of the day, your goal is not being met at all. So what is the purpose, right? So mathematics is foundational for this learning, guys. The second thing you're going to require is programming. Of course, you might have seen we have discussed a lot of things practically at this point of time. So programming is something which you are going to require. You require proficiency in Python or languages such as C, C++, R programming language if you're looking towards deep learning and data analysis and all of those. But yes, the point here being that you require a programming language, first of all, ladies and gentlemen. This is how you teach your machines. Your machines are as good as you and your program, right? So you effectively typing out the best logic, the most powerful logic, using the maximum amount of computing resources allocated is human intelligence, right? That is a point to be discussed here. The third thing is today's world is very intelligent in a way where we use a lot of cloud computing technologies, right? Be it Amazon's web services, be it Microsoft Azure, Google Cloud Platform. We use a lot of different things. We have used GCP to a point where we have shown you all the demos on Google Colab, right? It's a free and an open source Jupyter notebook. Where do you think the processing power for that is coming from? It is coming from the Google Cloud Platform itself, right? So you have to know that you can use a lot of deep learning, develop systems right there, cater to custom audiences, provide customized solutions, even in the domain. You even using a computer which is probably sitting 10,000 kilometers away from you in a very well protected data centers, or Microsoft has gone on to put data centers even in the ocean as well, is what I've read. So yes, so you are talking to a computer which is underwater. How cool is that, right? So it's an important thing that you're supposed to know, and these three things form to be the most important knowledge, guys. If you have mathematics, you can understand the data yourself, you can drive statistical insights out of it, and your algorithms can use it to learn. If you know programming, you can develop and put out these algorithms in a way where it uses data to train and learn and understand something. After programming, if you have an output which is working really well, you can take it to the cloud computing platform and give it out to the world to actually solve the problem, right? You might be catering to a client who's sitting very far away or right next to you. It is possible to use the computing power, the resources, and whatever it is that you require to drive that solution. You might require maybe 150, 300 computers, very powerful computers to do it. You might not be able to afford buying all of these at once. Well, you do not have to buy them anymore. With cloud computing, you can just pay as you go, use as many computers as you want to drive that solution to see if it is worth. Maybe at the end of the day, you might actually buy it. But to get to that point, it is highly convenient, right? So if you buy 300 computers, it is not just you paying money, bringing it to your office and sitting. You have to cool them down adequately. Heat kills electronics. You have to maintain them. You have to make sure that all these softwares are upgraded. Everything. It's a huge headache to do things offline. And now that is the reason why people just prefer cloud, guys. That is among I just gave you 5 or 10 reasons among probably hundreds of reasons of why people want to prefer cloud computing. So in the domain of data science as well, there is an amazing scope for that. So coming to a little bit of technicality of how the domain of deep learning itself works, right? How do you guys think deep learning works? Now, I've been giving you clues all until this point of time, but let me divulge it to you. The first thing is deep learning works based on iterative learning, guys. Iterative learning, as I've already mentioned, is how we humans learn as well. And the goal of deep learning is to make sure machines can learn like humans, right? So that is how we are teaching the machines as well. It sees a picture of a cat, it sees a picture of a dog, and if it's the first picture it sees and if it doesn't know what it's seeing, it'll be like, meh. The moment you start training it, showing it 100 if not 1,000 images of a cat and a dog and say, hey, all of these are cats, all of these are dogs, please learn it, and eventually you create a model that does it, at the end of it, it can say, oh, okay, so now I understand that this is not the only cat in the world that exists. Even if I see another image of a cat, I can understand it's a cat. If it sees another image of a dog, it knows it's a dog, right? Even in these motion sensor things that happen, maybe people nowadays, it's very common that due to the COVID-19 restrictions, you have to maintain a minimum distance between two people, right? 6 feet or whatever the distance is as per your country's guideline. There are machine learning models, and of course nowadays machine learning for image processing is slightly coming down because deep learning is way more powerful in that domain, where these deep learning models can assess if you have given that extra gap, if people are wearing the masks or not, right? The pandemic is not yet ended at the moment we are recording this particular video, so it becomes very vital to use technologies to make sure people are kept safe, right? So that is one thing. We make sure it trains and trains and trains and understands, and then it can provide beautiful solutions for us like this. The next thing is iterative learning is one part of it. The second part of it is hierarchical learning. It learns one thing, understands it completely. It uses that learning itself to build upon the next thing, the next thing. It uses previous learning to go up and up and up. And at the end of the day, this kind of a hierarchical given with iterative learning methodologies makes it extremely intelligent and brings it pretty close to human level intelligence. That is our goal, and these are the things that are taking it there, right? That answers the question of how the domain works itself. One important thing is that in the case of deep learning, in 99% of the cases, the more the data the machine has access to, it keeps learning it understands data better the more it does one thing again and again. So with every different level, it picks up new data, it knows something about the data than the previous iteration, guys. That is an important fact that you guys should know about. Let me give you an example to give you more clarity about how deep learning works, right? Think about this personal assistant, Alexa. Now, as soon as I say Alexa, of course, my phone wants to light up, and I have numerous products in my home which uses Alexa itself. So in that particular case, this is a personal assistant that can do everything. If I say, hey Alexa, turn the light on, it can turn the light on. If I say, hey Alexa, play this music, or turn on my home theater, whatever it is, it can keep everything ready. It can set the temperature on my air conditioner, open the door for me, and well, it can do a lot of different things. It can water my plants, right? There's so many things that I personally use this personal assistant Alexa for. So how does it learn? How does it understand? So we feed it with data. We say, hey, this is the requirement, this is what you're supposed to learn, and it knows a lot of different things. It knows the differentiation between when I'm speaking, it has to understand intonation, it has to understand that I am talking to that particular entity, it has to know inundations, right? For example, there might be certain commands that I give to Alexa which she'll follow only if I say it, not everyone else, right? She has to figure out that it is my voice that is coming, and once it figures out that it is my voice, the next thing it has to figure out is the content of my voice, right? All of that. If you just go on in depth and depth and depth, we can discuss so many things, but its basic nature of understanding our grammar, our vocabulary, of course, it is not 100% there yet. And I'm sure the team at Alexa or any other personal assistant out there are developing to better their products. But the work is going on. It is intelligent enough in a way where it is fascinating to me, at least, and I'm sure you guys can use some of these solutions yours itself. So having a common input, training on the current situation, and giving you a customized response based on this data and input is something that they are aiming for, and Alexa or Siri, in fact, is doing brilliantly as well, guys. So I absolutely love how deep learning works, and I hope with this now that you guys appreciate deep learning as much as me, right? So you go back to the second where I told you that we humans use billions of neurons to go on to learn things, and it's like a small tiny computer in itself. Well, in the case of deep learning itself, there's a domain called as neural networks where we use neurons as the foundational concept. A lot more detail about this is coming for you guys in the next module. But for now, you have to understand that just like how neurons work in your brain, where it stores certain information, it passes information to the other neuron, it processes it, multiple neurons work together to give a common output and all of that. We're getting our machines to do it for us in a very, very similar way as well. That's the beauty of deep learning, guys. So whenever you're assigned any sort of values into each of these neurons, that is when you have the capability to differentiate. Hey, there's neuron number 1, neuron number 2, neuron number 3, and all of that. So they get their own numbers. It's called weights and all of that. We're going to discuss this in detail in the next module. But for now, you need to know we have the capability to discern and differentiate between one neuron and the other, guys. So there's multiple ways of how these neurons connect to other neurons around them, how they map things, right? So for example, if you're a person who's learning to play a musical instrument, for example, I am trained on playing the guitar, so my brain's neurons are wired up in a way where it knows how to play a guitar. Basically, since it knows how to play a guitar, I can play the guitar. That is how I hope that made sense for you guys, right? So these neurons connect to each other in a way where they have trained, they have learned, and they have retained that learning of me playing a guitar, right? So based on a lot of things called as transfer functions, node connections, activation functions, and all of these, we get our deep learning model to learn something and hold whatever it has learned in its memory as well. That's a very important thing that is governing the basis of deep learning, guys. So as I mentioned, activation function, right? Now, see, whenever you're using multiple neurons, it is mostly the case that you have to find out if a neuron has to fire or not, or has to work or not in its terms. So if it has to do that, and if the data given to the neuron, the number that is assigned to it is a very large number, things can get a little confusing. So we use an activation function. An entity, what it does is it squishes down your value, this value which might be negative 1000 all the way to positive 10 million or whatever it is. It just squishes all of this down to bring it to a range of -1 to 1 or 0 to 1. So in that particular case, if it's 0, it knows that the neuron might not fire. If it's 1, there is a 100% chance the neuron is firing, connecting to another neuron and passing some information to it, right? To see if the neuron has to pass these values or not in its foundational level, we require activation function, guys. So once the activation is done, once the neurons are activated and is passing some values, there is a weight which gets assigned to each of these nodes. Again, we're going to see how activation function works, how these weight works, how they come together to provide a solution in the neural network module. But for now, you need to know that there is an entity called as activation function, and this is how it works, and this is why it works as well, guys. So after understanding activation functions, as I told you, one neuron connects to the other. So data moves in one direction or the other, right? In the case of deep learning as well, that is true. Data can move in the forward or the backward direction in this kind of an entity called as a neural network. When the data moves in the forward direction, it is called as forward propagation. When the data moves from the output towards the input direction in the network, it's called as backward propagation. Each of these has a very, very fantastic meaning. Forward propagation talks about how you can calculate all of these weights first, make sure that your neuron knows what it is supposed to do if it comes to its usage and all of that. The backward propagation talks about what the neuron has learned. It tries to verify it, compare what it has learned with what the output is, if it has learned something and all of that. So Forward propagation is like the neural network learning, and backward propagation is like giving the neural network an examination and saying, hey, what have you learned? Right? That is a very simplification of this concept of how deep learning works as well, guys. So with that, I hope you guys are clear, with how deep learning works on a functional level. The next thing that we're going to check out are the differences that exist between deep learning and machine learning. Now, as I mentioned at the start of this module, it becomes vital that you know the differences, even though these two domains sound very similar, deep learning, machine learning, and both of them are the subset of artificial intelligence. There are key differences here that you're supposed to know, guys. So here are some of the differences. We're going to compare each point and see how we can work with that, right? So the first point, the first criteria for our comparison is the data set size. Now, in the case of machine learning, you can get away with training a machine with a smaller amount of data, and you do not require a large amount of data. Of course, a large amount of data will help it learn better, but it is not a compulsory requirement. In the case of deep learning, that is not the case. It really might not work well unless you provide it with a huge amount of data, right? So, more the data works better in deep learning. It is a compulsory requirement there, but for machine learning, that is not so. Why is the case? Well, this is a very important thing you're supposed to know, because at the end of the day, how deep learning works itself, right? These interconnected networks means it is very complex, and your data is being processed in a very different way than machine learning. So to give it information, to make sure it understands what it is learning, you require a lot of data. So this complexity of deep learning asks for a bigger data set compared to machine learning, guys. That's an important thing that you should know about. Talking about the second important point here, it is feature engineering. See, what happens in the case of feature engineering is we try to see what column of data has how much amount of impact on the output, right? So in the diabetes example, again, that I've mentioned, maybe two columns of data have a huge impact, like age and blood sugar and all of that. Maybe there is another criteria which we haven't looked at until now, right? Hereditary can be one of those criteria, whatever it is, right? To know that this new feature can have an impact on it, you have to first of all know the feature exists and use it to get to the output, right? So in machine learning, we have to manually do this. We have to manually say, hey, here's a new column of data. Try to see what impact it has on the output. In the case of deep learning, it is intelligent enough to sort of figure this on its own. So it has the capability on multiple levels of complexity that it can, go on to learn things, understand things, create feature labels, use it to learn, and then provide an output. And all of this is done automatically, ladies and gentlemen. That is the magic of deep learning. And of course, with this, what happens is that, whenever you go on to teach the machine how things work, right, it becomes very easy because it sort of is very quick at learning. It will understand shape, it understands texture, it knows a lot of different features. As soon as it sees a circle, it will not say, hey, this is a square. It knows it is a circle, it knows it is a sphere, right? That is the important thing. Making your machine already intelligent so that you do not have to teach it again and again, sort of is the point here. Your machine will know the basics and you just have to train it on advanced things. If I have to break it down to the most simple level, that is why this automatic feature engineering feature that brings us out, that is shining in the case of deep learning, is very important, guys. So the next thing, the next important point that we have to discuss about is the hardware dependencies. In the case of deep learning, of course, in today's world, since we already have sophisticated high-end hardware, deep learning for its process, for its complexity. Now we are the most sophisticated beings out there. That is debatable, of course, but at least in my opinion, sort of, in our perceivable world right now, right? So we are very sophisticated, and nowadays computers are getting sophisticated, as we have discussed. So deep learning uses this kind of, there is a hard requirement of high powered computers and graphical processing units, GPUs as it's called, along with CPUs for it to learn and understand things. In the case of machine learning, even a complex machine learning algorithm can get away with low-end machines as well. So you do not require state-of-the-art stuff. You do not require the most fancy, most expensive computers to get your application created and done. Right? That can be a make it or break it things for a company who might not be able to afford a huge computer. right? You have to understand that it is not the fault of the technology, because that is how deep learning works. We are trying to imitate the most intelligent being in our senses right now. So all the mathematical operation which goes on, very very heavy matrix multiplication operations, high amount of computation rates, that goes on in deep learning, is what asks it, saying, hey, to do this I require high end hardware and high end computing technologies, right? So that is an important difference that you guys should know about. And then talking about the next thing is execution time. I think you would have guessed execution time by now, right? First of all, deep learning, whenever you're using it, it requires a lot of time to not only train, but also to give you an output based upon whatever it is learning in, and to furnish a usable output. In the case of deep learning, it might take a day, it might take 10 minutes, all the way until a week, a month, for it to learn and give you a usable output at the end of the day. So what happens here is that I'm going to show you a demo at the end of the next module, the neural network module, where you will see that it takes a comprehensive amount of time to execute, right? We have already discussed machine learning in a previous module. Now you would have seen that as soon as I hit play, it takes 1 second, 2 seconds, boom, the output is ready. That is not the case when you're training a deep learning model, right? You're going to check that out practically in the next module. So it requires, of course, I'm not going to take weeks worth of time to make you guys wait and show you that. I'm going to take a demo which will probably take 10 minutes instead of 2 seconds to go on to do the same thing in the case of machine learning versus deep learning, right? That's the thing. So it is not just the large amount of data that adds to this kind of a large amount of time, but it's also the complexity, the way machines get trained. But I'm sure execution time is something that you guys would have already picked up on, right? Now, to give you an example, think about creating an application where it takes pictures of people and sort of helps them find whatever clothing they like, right? So I just have a model in front of me. I take a picture of the model. So in the case of machine learning, you have to manually say, hey, this person is looking for a shirt. This person is looking for a hat. This person is looking for maybe shoes, a tie, a bow tie, whatever it is, right? So we have to create these features, and it has to be coded manually and say that is what we want. So learn based upon that. In the case of deep learning, you do not have to do all of that. So you can get it to understand features automatically, get things created automatically, and it will give you a feature at the end of the day saying, would you like a bow tie? Would you like a tie? Right? So it understands that is the requirement that is being asked of it. It learns based upon that and eventually gives you a result. This automatic way of feature extraction and feature generation is something which is, again, it is a constant amount of research that goes into doing it, but it is intelligent enough to give us the output at this moment in time, guys. Right, the next thing that we're going to discuss is the important use cases when it comes to deep learning. In the case of image classification, in the case of object identification and face recognition, wherever it is, right? Be it in a very simple usage of maybe Facebook's algorithm where you just put out a picture, it automatically tags your friend for you, all the way to knowing that, hey, this person might be who I thought that I saw maybe in some kind of an investigation, criminal proceedings, civil proceedings, whatever that is, right? So right from something which is very very vital all the way to social media, which I don't think is an extremely vital part of everyone's life, is where these things are popular. Be it object identification, you show an apple to your computer, and if it sees it, things like Google Lens and all of these things understand what it is seeing. It knows it is seeing an apple. It can see if it's a ripe apple or if it's still a raw unripe apple. Is it good to eat? If your apple looks maybe black or something, or if it's not edible, you can show your phone the apple and say, can I eat this? And it can be intelligent enough to tell you, hey, it is good for consumption, it is okay for consumption, and all of that. So guys, computer vision is a brilliant use case where you're making your computer see things and understand them, right, hand in hand, right? Multiple airports across the world have used a concept right now with face recognition, where if you're trying to check into the airport to get to your plane, to get to board the plane, there was a time when you had to show your passport. Of course, it is still there. You have to show your passport, you have to prove that you're there physically, and you have to go through a lot of procedures to get to your plane. Nowadays, the check-in is in a way where you just go look into a camera, the machine on the other side matches your photo with the passport or something, or whatever details that it has. It understands that you have checked in into the airport and that you're waiting to board your plane and all of that, right? Of course, I just simplified that entire process to you, but that is how computer vision is very popular. Now, I've already talked about text and sequential data in the case of speech recognition, in the case of sentiment classification. It is very, very important. When I say Alexa, that when my voice is said, Alexa knows that it has to recognize what I'm saying, why I'm saying it, and all of that. Sentiment classification, I told you, if you're a product seller, you want to analyze the sentiment of your customer, right? In the case of DNA sequence analysis, if you do not know what sequence analysis is, I highly recommend you read it. It is fantastic. We have DNA in our body, right, and our being itself. So it's a very complex term to explain it to you guys, but it is very interesting that you guys check it out after this video as well. The fourth thing is video activity recognition, as I told you, to check if people are wearing masks or not, to make sure that there is minimum distance maintained, to see if someone is intruding at the middle of the night, right? So you cannot have a security system of human beings, maybe, have 10 human beings to guard one building. You can have 10 different cameras. And if this camera captures a motion where a human is walking or something, it can alert people saying, hey, during the time of night when people are not usually expected to whatever office or government building it is, that people are coming there, then it is intelligent enough to understand all of that, guys. Right, coming to the last section of this particular module where we'll be discussing the top libraries for deep learning. We'll be taking a look at these libraries which are extremely popular for Python, guys. We have 6 amazing open source libraries which I absolutely love to work with. They are TensorFlow, we have Microsoft CNTK. CNTK stands for Cognitive Toolkit, so it's Microsoft's Cognitive Toolkit. We have Cafe, we have a lot of different things. We have Theano, we have Chainer, we have Keras, we have Deep Learning for J, and we have at least 20 amazing deep learning libraries out there, but these are the ones which get used a lot. So I thought it is worth to mention to you guys the top 6 open source libraries for deep learning, right? To talk about the first one, TensorFlow, right? Now, TensorFlow is amongst the world's most used framework for deep learning. It is the most popular in the case of natural language processing, speech recognition, image recognition, and all of these different things. It is a framework which comes with multiple libraries. It is very flexible to work with, and it also provides you tools that you require in the case of machine learning and deep learning to deploy your applications automatically, right? So to build and even handle deployment, TensorFlow offers multiple options to users. And TensorFlow is a framework in which at the end of the day, the syntax that you use in Python itself is very easy, as we have been checking out. But even in the case of TensorFlow, that is the same thing as well. Here, using TensorFlow's syntax in Python is sort of very easy. Of course, you require some training to get started, but once you're trained, eventually you will know what your deep learning algorithm is trying to do, guys. That is the point here. So TensorFlow is extremely popular. It is a brainchild of the people at Google. The next thing that we're going to check out is Microsoft's CNTK, or the Cognitive Toolkit. This is Microsoft's offering, of course. It is amazing. It works really, really well whenever we're doing any sort of image recognition or pattern recognition kind of applications. It works with 2 types of neural networks called as convolution neural networks and recurrent neural networks. We're going to check out what these are to a good amount of detail on the next module. But for now, you need to know that CNTK supports both of them. And in this concept of deep learning, where things can get really complex even for the programmer, CNTK offers a way in which you can break down complex concepts into simple stuffs, into building blocks, tiny Lego blocks, work with it, and then build upon a complex solution, right? The pyramids of Egypt were not just one rock which was just placed there and people shaped it, right? They brought tiny rocks and eventually put one on top of the other, and then it became a pyramid. That is the approach that people at CNTK sort of take too. Right, then we have Cafe. Cafe is one of these amazing frameworks which will help you to scale up rapidly if that is your requirement. It is built keeping in mind that today you might have a deep learning solution which might you might be catering to 10 applications. At the end of the day, if you want to build 100 if not thousands of applications, or have one application used by 1,000 customers to give them some sort of personalization, Cafe is the framework that you're supposed to use. It is used with Python in a modular way. It's an amazing user interface. You can work with it in Python, C, C++, and all of these, and it is very, very, very popular to work with one type of neural networks. It's called as the convolutional neural networks, or CNN as short, guys. So Cafe is meant, it's a tool, it's a framework that is built if you are looking towards to scale. Right, guys. The next thing that we're going to discuss is Chainer. Now, Chainer is again another amazing, it's a fantastic framework which is again built if you have dynamism in your head, right? So, not all the things in deep learning cases are static. It keeps learning, it keeps changing things, and you don't have to do the entire thing again, teach it again and again every day to make sure that it knows a new thing or it understands a new thing, right? It perceives a new thing. So in that case, with Chainer, to do all of these things to make sure that it is a very dynamic, snappy framework to use, it uses a lot of what we call as auto differentiation APIs, and it uses approach using computational graphs. It uses define by run approach. All of these amazing concepts which you guys should learn about if you're very serious about a data science career, right? So you can build amazing neural networks here using high level APIs which are not very difficult to code with, but at the end of the day, a small amount of effort from your side will get you an output which is fantastic, guys. That is what Chainer is all about. Then Keras is again a very, very popular offering. It is it is basically a framework which runs on top of using TensorFlow as well. It's a tool which has the capability to run on top of TensorFlow and increase its capability. It works both on convolution neural networks and recurrent neural networks. In the case of how Keras is built, Keras is actually built, the framework itself is built using Python. It works fantastically in the case of Theano, in the case of CNTK, and works really, really well with TensorFlow as well, guys. So if you're a company who is into rapid prototyping and experimentation, right? So maybe you have a concept right now and you don't have a lot of time to take it to a product where you have a short amount of time which you can invest to make sure you can take this prototype, right? So a prototype is this first thing that you create which eventually gets converted into a product. So if you want to rapidly do it, if you want the methodologies, the tools, the techniques which goes into rapid prototyping and experimenting a lot of different things, Keras is something you definitely should be looking at because it provides a very simple API to help you develop new things rapidly. And of course, if there are bugs on the way, which of course as a programmer you're going to see a lot of bugs, it will make sure that you can find out these bugs easily and solve them easily as well, guys. That is the magic of Keras.
Now, let's learn about that what is back propagation and what is the forward propagation. Okay, back propagation, you are already aware that what is that. But with respect to the forward and the back propagation, what's the minute thing which comes there in between? Let's learn about that particular thing. So here we go. If I talk about the back propagation and if I talk about the forward propagation, so what happens in the forward propagation? It is a process to move from the left to the right in a neural network. Left to the right means from the input layer to the output layer, and that's known as the forward propagation. So that's completely a process in which we move from the input layer to the output layer. It means from the left towards the right in a neural network. That's called a that's called a forward propagation. Okay. Now, secondly, what if about the back propagation in the same manner? Back propagation. So when you move from the output layer towards the input layer, it means when you move from right to the left, that is called as your backward propagation. I would again repeat it out. Moving from moving from right towards the left in your neural networks is known as the backward propagation. Okay? Left to right is your forward and right to left is your backward. Now, left to right, I did already mention up a few minutes before into the same diagram. I did told you that onto the left we have the input layer and onto the right we have the out. Have a look over this diagram once again. Onto the left, that is onto the point number 1, that's your left, and into that you are having up the input layer. Where the point number 3 is there, that's your output layer, and yes, obviously that's onto the right hand side. So here in the diagram, have up a look for this as well, back propagation output layer. Okay. So what happens that when you move from the input towards the output, from left towards the right, that's your forward propagation in the neural networks. And when you move from the right towards the left, that's from your output to the input in the neural network. That's known as the backward propagation. Okay, now for the intermediate variables in a neural network, for the calculation and the further storage from the input to the output layer. Right here, what we meant up is that why to move from output to the input or input to the output. So it happens that for the intermediate variables in the neural network, what are the intermediate neural net? What are the intermediate variables? The variables which are in middle. Okay, whatever the variables you are having in the intermediate, and even for the calculation and for the storage from the input to the output layer, these respective things are taken up the place. So for the storage from input to output, for the calculation from input to output, these respective back propagation and the forward propagation takes place. Okay, so hope I am clear with what is backward and what is the forward propagation. How do these things take place and how are these respective things making up and what is the use of these things up here? Okay, so great. Hope I am very much clear with what is back and what is the forward propagation. So now next our second topic of discussion is that how does the back propagation algorithm works. We did are very well aware now that what back propagation algorithm is, right? What's the use and what is that actually? Now let's learn about the working. Okay, so let me take you to the further deck here. Before moving forward with that, what are the algorithm? What is this algorithm? How it works? So firstly, I just wanted to let you know that in the back propagation, we have three main layers. Okay, three main layers are there in the back propagation and the complete working of the back propagation algorithm takes place in respect to these three layers. So the very first layer is your input layer, the second one is your hidden layer, and the third one is your output layer. The three respective main layers which you have up in the back propagation. Okay, now so here what is the case is that in the input layer, in the hidden layer and in the output layer, whatever the functioning, whatever the things are there, simply all of those works in respective to these three of the layers only. Let me give you a very quick idea of this respective diagram and then I'll be taking you forward and the complete idea for the algorithm working. So have a look here on the on the left hand side, you have the input layer above which the number 1 is written and that is your input layer. Okay. Next, when you move forward where the point number 2 is written, that's your hidden layer. And when you move towards the point number 3 where 3 is written, so above that it's the output layer. So the first one is your input layer, the second one is your hidden layer, and the third one is your output layer. So these are first of all the layers, these are the respective layers, the three main layers for the working of your algorithm. Okay, first of all, this is very much clear. Next, from the input layer, in the input layer, we have the denotions for the X. Okay, and when this input reaches up till here, so here we have the like alphabets which are written as W, and here we have the final ones. Now, actually, there is some difference in the desired values and in the actual values also. So, yeah, I'll be discussing through all of those respective things. But first of all, see, what are the input layers are? They are in complete black. Right? What are the input layers we are having? Those are in the complete black color. Now, if I talk about the hidden layers, so all my hidden layers and this respective ones as well, these all are in the dotted form. So this dotted form is depicting, it is actually showing that whatever the layer I am having up here, it is completely the hidden layer. Have a look. All of these are dotted. And Now when I'm talking about the output layer, so yeah, that's again in the black and the red color. Okay, so yeah, that's a thing right here which we are having. Okay, great. So that's the red one. This is the back propagation output layer. Okay, so yes, this is the respective idea. This is the respective keys which we have up here for this algorithm. Now let me take you further for the discussion of this, how this algorithm works. Now, whatever the image which we just saw right a few seconds before, what does that respective image tells us? What does that respective summarizes? What is the functioning of the back propagation? Let's discuss that out. Now, whatever the input layer which we saw up here, that input layer receives the X that I told you here in the these circles which are made up here. So this input layer receives up the X. By further, the input is modeled using weights that is W. Now, whatever the input we are having, that are modeled. Whatever the modeling has to be done, whatever the sort of functions or the things have to be done, they are modeled using the weights. And that's the reason here into the circles we did throw up W. Fine. The X is your input. After that, that respective input has been modeled using the weights with the W here. Okay. Next, each hidden layer calculates the output and data is ready out the output layer. Now, whatever the hidden layers we are having up, each and every hidden layer calculates the output. Okay, and whatever the final output we are having, that respective one is shown to us into the output layer. So here the hidden layers which you are able to see, the dotted lines which you are able to see, all of these respective things, these are calculating up the output. Now after the calculation of the output, on this output layer, the final output whatever is there, that respective output is to be displayed. Okay, further, difference between the actual output and the desired output is known as the error. Now that thing I did already mention up, that whatever is your uh, like actual output and whatever is your desired output, okay, that respective one is known as the error. The difference between actual value and your desired value is known as the error. Fine. Go back to the hidden layers and adjust the weight so that this error is reduced in future runs. Now, after this, go back to the hidden layers, whatever are there, and adjust them using the weights. Why? So that whatever the error is there, that is reduced up in the further runs. Error means the difference between the actual and the desired output. So how to reduce that out? So for reducing, what you do, you simply go to, again you go back to the hidden layers, adjust out those respective hidden layers in a form that for the future runs, there the whatever the error is, it means that whatever the differences in the desired value and in the actual value, that gets reduced out. Okay, so for that, this respective hidden layers are actually like edges, and the process is repeated till we get the desired output, and this respective procedure is repeated up till the point you get out your desired output. Okay, so for getting up your desired output, till the time you don't get it out, this respective procedure is completely repeated. The training phase is done with the supervision. Once the model is stable, it is used up in the production. So whatever the training phase is done, that is done with the complete supervision, means that like complete carefulness and all those things. And whenever the model is stable, reliable, it's completely used up into the production. Okay. So how does this work? The input layer receives the X. After that, the input, the X which has been received, that input is being modeled using the weights, that is the W. Then your hidden layers actually work and they give up the output, and that perspective is gone up, is shared up here into the output layer. Now if you get up any difference between the final between the actual value and between the desired value. So that respective difference is called as the error. And next, for reducing up that respective error, what we do, we simply try to adjust up these respective hidden layers, whatever we are having, we try to adjust those hidden layers so as to get up the complete, so as to reduce up that respective error, so as to reduce up the difference between the actual values and the desired values. Okay, so the first one here is your input layer, the second one is your hidden layer, and the third one here is your output layer. So as I did as we mentioned it, that in the back propagation you have three main layers. Okay, that were your input layer, your hidden layer, and your output layer. So I would summarize that out very quickly, that whatever your input layer is, that it's there, it receives the X. Okay. Next, your input is modeled using the weight, that is the W. After that, each hidden layer calculates the output and the data is ready at the output layer. The difference between your actual output and the desired output is known as the error. And go back to the hidden layers and adjust the weights so that this error is reduced in future runs. Okay, so this respective procedure is applied up till the point we get the desired output. The training phase is done under a supervision, and once the model is stable, it's completely used up into the production. Okay, so hope I am clear with this, very clear with this to you, that how does this algorithm actually works out, what are the main layers, and how are these actually categorized. I hope that you're clear with this diagram as well and with this summary as well, which I did mention up here. Right, so this is how this respective algorithm works, and this is how this actually takes place. This is how the error is reduced, and all of these respective things. Okay, next let's move forward to the third topic of our discussion under this back propagation tutorial. Now let's learn about that what is back propagation and what is the forward propagation. Okay, back propagation, you are already aware that what is that. But with respect to the forward and the back propagation, what's the minute thing which comes there in between? Let's learn about that particular thing. So here we go. If I talk about the back propagation and if I talk about the forward propagation, so what happens? In the forward propagation, it is a process to move from the left to the right in a neural network. Left to the right means from the input layer to the output layer, and that's known as the forward propagation. So that's completely a process in which we move from the input layer to the output layer. It means from the left towards the right in a neural network. That's called a that's called a forward propagation. Okay. Now, secondly, what if about the back propagation in the same manner? Back propagation. So when you move from the output layer towards the input layer, it means when you move from right to the left, that is called as your backward propagation. I would again repeat it out. Moving from moving from right towards the left in your neural networks is known as the backward propagation. Okay, left to right is your forward and right to left is your backward. Now left to right, I did already mention up a few minutes before into the same diagram. I did told you that onto the left we have the input layer and onto the right we have the out. Have a look over this diagram once again. Onto the left, that is onto the point number 1, that's your left, and into that you are having the input layer. Where the point number 3 is there, that's your output layer, and yes, obviously that's onto the right hand side. So here in the diagram, have up a look for this as well, backpropagation output layer. Okay. So what happens that when you move from the input towards the output, from left towards the right, that's your forward propagation in the neural networks. And when you move from the right towards the left, that's from your output to the input in the neural network. That's known as the backward propagation. Okay. Now, for the intermediate variables in a neural network, for the calculation and for the storage from the input to the output layer. Right here, what we meant up is that why to move from output to the input or input to the output. So it happens that for the intermediate variables in a neural network, what are the intermediate neural net? What are the intermediate variables? The variables which are in middle. Okay, whatever the variables we are having in the intermediate, and even for the calculation and for the storage from the input to the output layer, these respective things are taken up the place. So for the storage from input to output, for the calculation from input to output, these respective back propagation and the forward propagation takes place. Okay, so hope I am clear with what is backward and what is the forward propagation? How do these things take place and how are these respective things making up and what is the use of these things up here? Okay, so great. Hope I am very much clear with what is back and what is the forward propagation. Now let's learn about that. What is a feed forward network? Okay, what is a feed forward network? Let's learn about that right here. So first of all, let's learn that there is one another name which is actually there for the feed forward network. Okay, so that respective another name which I'm talking about is multi-layered network, MLN. So if you say feed forward network, uh, or if you say multi-layered network, both the things are absolutely the same because it's the another name for the feed forward network. Okay, now first of all, it's one of the very type of simplest type of the artificial neural network. Okay, feed forward network is one of the very simplest types of the artificial neural networks. Okay, further, what happens that the networks, this respective network is known as a feed-forward network. The reason for that is the data travels forwards in the NN through input node, hidden layer, and finally to output nodes. What happens that whatever the data we are having, that travels first of all into the input node, then it goes to the hidden layer, and finally it goes out to the output node. And this is the reason that why these networks are called as feed-forward networks. Because whatever the data you are having, whatever data you are having, that travels in the neural networks. NN is for the neural networks. Okay. So whatever the data you are having, that travels forward in the neural networks. First of all, through the input node, then comes your hidden layer, and then finally it goes to your output node. So as we saw into the back propagation algorithm, that first of all, it was going into the input layer, then that was the hidden layer, and then it was your output layer, right? So in the same manner, the feed forward network is known is like that because whatever the data you are having, that respective data travels forward in the neural networks through the input node, then comes your hidden layer, and finally your output nodes. Now this respective one travels in a very simple path, right? Travels in a very simple way, and that is the reason as well why it is said as one of the simplest type of artificial neural networks. So yes, the process of the data traveling is very much simple. Simply it goes to the input node, then your hidden layer, and finally it goes to your output nodes. So this respective process which we are having up here, that's likely a very simple one. So that's the complete reason that why we say that this is the feed-forward network is one of the simplest type of artificial neural network. Okay, and we have the another name as well for the neural for the feed-forward networks, and that is the multi-layered network (MLN). Okay, so great. Hope I am clear with that what is a feed-forward network. So these networks are known as feed forward because the data travels forward in neural networks through input node, hidden layer, and finally towards the output nodes. And this one of the simplest type of artificial neural network is a feed forward network. And the another name for the feed forward network is multi-layered network (MLN). Okay, so great. Hope I am very much clear with this respective thing to you that what is a feed forward network. Now let's move forward with the next topic under this tutorial of back propagation. So now let's learn about that what are the types of the back propagation network which we are having up here. Okay, so let me take you forward here. Great. In the very starting as well, I did mention of this one thing that we are having of the two types of back propagation network, right? So the very first type of the back propagation network is a static back propagation. And if I talk about the second type, so that's the recurrent back propagation. Okay, the static back propagation and the recurrent back propagation. So what happens up into these respective back propagation networks? In the static back propagation method, what happens is that what are the static input data is generated? Okay, that is mapped with the static output. Okay, whatever the static input data is being generated, whatever the static input is being generated, that is mapped up with the static output. So this is the thing which happens up in the static back propagation. Next, if I talk about the recurrent back propagation, so what happens? So into this, what happens is that this recurrent back propagation is conduction till the certain threshold is met. It basically is conducted, it basically like works till the point a certain threshold is met. And after that, the error is calculated and it is propagated backwards. So in the recurrent back propagation, what happens? That the condition that it is conducted till the certain threshold is met. After the meeting of the certain threshold, the error is calculated and then it is propagated backwards. So these are the things. This is how the recurrent back propagation works about. A certain threshold is met, a certain condition is met. You could say I say that out in simple terms. Okay. If you want to say this certain threshold is met in the simple terms, so you could simply add till the certain condition is met. Okay, so after this the error is calculated and it's propagated backwards. Fine. So for the static back propagation, in this method respectively, the mapping of the static input is generated and in the static output. Okay, mapping of the static output generates the static output. So that happens in the static back propagation. And for the recurrent back propagation, the conduction, it is a conduction till the certain threshold is met. And after this, the error is calculated and it is propagated backwards. So till to a point a certain condition, a certain threshold is met, in that the recurrent back propagation is conducted, and after the certain threshold is met, after certain condition is met, the error is calculated, whatever the error is there. Now again I would say error means it's not the syntax or the indentation error. Error means up here that till the point the difference between the output, the difference between the actual output and the desired output is known as the error. So same goes up here as well, that whatever is the difference between the desired output and between the actual output, that's the error. So after the conduction till the certain threshold is made, the error is calculated, that is the difference is calculated between the desired output and between the actual output, and it propagates backwards in the recurrent back propagation. And nothing sort of like this happens in the static. Simply, the static input is generated, and that static input which is generated, that is mapped up towards the static output. Simply, this happens up in the static back propagation, right? So great, hope I'm clear with that, what are the two types of back propagation networks which we are having up here, and how these respective back propagation networks actually work about, and how do these respective things take place. I would once give you a recap that there are two types of back propagation networks. The first one is your static back propagation, and second is your recurrent back propagation. So what happens in the static back propagation? That in this respective method, mapping of a static input generates the static output. And in the recurrent back propagation, what happens? That in the recurrent back propagation is conduction till the certain threshold is met, and after this the error is calculated and propagated backwards. This is what happens up here in the types of back propagation network, right? So hope I am very much clear that what are the types of back propagation, and what are the types, and what do these respective types mean, and what do they do, right? Hope I'm clear with that. Let's move forward with the next topic. Now let's learn about that what are the key points of the back propagation. What are the key points which we have up in the back propagation? What are the points that you shall take care of? Let's discuss them about right up here. Okay. The very first key point for the back propagation is that there are two respective rules. First one is the power rule, and the second one is the chain rule. So actually, a back propagation takes the advantages of these two rules, first of all. And what do these rules do? These rules permits the back propagation to work with the different number of outputs. So back propagation takes up the advantage of these two rules, that is the power rule and the chain rule. And what do these rules permits or allows? So these rules are permits the back propagation for working with a different number of outputs. This back propagation, these respective rules which are power rule and the chain rule, these permits the back propagation. The very first key point which you should remember up here. Second goes for the error-prone projects. Whatever the projects which are in which you have to deal with the errors, whatever are the error-prone, in which basically there is some of the errors. Now, errors do not mean up here that syntax error or any indentation error. The error means here that there is a slight difference. There is a difference between your actual outputs and between your desired outputs. The difference between that is called as the error. Okay, so please do not relate these out with some syntax or some indentation errors. It's a sort of error in which when you have up the difference between the actual output and between the desired output. Okay, so for these sort of projects in which there is some error and with some some difference between the actual and the desired outputs in the deep neural network, so especially onto that respective project, in that respective cases, this back propagation is very, very, very much useful. Okay, so the reason is that we have up the hidden layers. So in that hidden layers, the hidden layers adjust them and try to reduce up the errors which you are having up, right? We studied this when we discussed that how this algorithm works, right? There we discussed that the difference for the actual output and the desired output, first of all, is known as the error. And after that, the hidden layers, whatever are the hidden layers, they kept on adjusting, they adjust. And the reason for their adjusting is that they try to reduce up the error. So that is the reason that backpropagation is very, very, very much useful for the error prone projects. Okay, so for the projects which are dealing with the errors in that respective case, this backpropagation is very much useful. Now, for developing the relationships between the input and the hidden layers. Okay, when you want to develop up the relationship between the input and between the hidden layers, so it's important for you to study about the group of input and the activation layers. So after the study of all of those respective things, then only it will be you will be able for the developing the relationship between the input and the between the hidden layers. What are the input layers? What are the hidden layers? What are the output layers? That all we did discuss up in very detail in some previous minutes, right? So, in the development of the relationship between the input and the hidden layers, you need to study the group of input and the activation layers. So, these are some of the key points of the backpropagation that are really to be taken care of. First of all, there are two rules which are power rule and the chain rule. So what do these rules do? These rules permits the backpropagation to work with the different number of outputs, and backpropagation takes the advantage of these two rules for working with the different number of outputs. Secondly, if we talk about that what is the best case for applying of the backpropagation algorithm, so the best case for applying and using the backpropagation algorithm is the error-prone projects in the deep neural network, in which there is some sort of error or that things are expected. So yes, in that backpropagation algorithm is the one which is essentially used. And third goes that for development of the relationships between the input and between the hidden layers, it's very much essential, it's very much needed for you to study the group of input and to study about the activation layers. Okay, so hope I am very much clear with all of these respective key points for the backpropagation which I did mentioned up here. Now let's move forward and let's discuss about some more things under the backpropagation tutorial. So right here further I'm going to write up np.exp, okay? And inside this exp I'm going to put up the bracket, and inside that I'm going to simply write out here minus of x. Okay, pretty much sorted, fine. So 1 plus np.ex in the bracket goes my this. Now I'll be writing up one more function. So let me make that function right here only, and then I could simply move forward with the things. Okay. Now into that respective case, now further what is required for the sigmoid function only? Now further I'm going to make up a function which is sigmoid derivative, okay? So let's make that out very quickly. So here it's dev. Let me leave out one line. Dev. It will be sigmoid underscore, and that will be derivative. Derivative. Okay, Tive. Fine. Now into the bracket, what do I have? A def. Okay, let me just get up some space here. Yeah, sigmoid derivative. Okay, and into the bracket, I'm gonna pass up here x. Fine. Let's put the colon. Get down. Here I have to simply return one thing, that is sigmoid function. Okay, sigmoid sig sigmoid underscore func. Okay, into the bracket we have here x. Okay, multiply that out by 1 minus, here we have sigmoid, 1 minus sigmoid underscore func. Okay, and into the bracket you have to put up as x. Fine enough, right? So the sigmoid derivative is completely done. Return the things which are to be returned up here, those are pretty much sorted. Now next comes, okay, I would just run out this very quickly. Fine, yes, it's completely okay. Now further I'll be making up a function which is normalize, and now that will be helping me in the normalizing of my data. Okay, so here goes div normalize, okay, and into the bracket I am going to put up the capital X. I'm going to set up the x's as -1, okay, and the order will also be set it up as 2. Fine. Let's get down, and here I am going to put up some variables like L2 is equal to, okay, it is np dot at least underscore 1, okay, np dot at least underscore 1g, and further I'm going to use up the numpy array, and here I'm going to use up the linear algebra, LINEALG, okay, this linear algebra function, and with the help of that I'm going to use up the norm, which is going to help me for the normalization. So x comma further order, and further we have here the x's. Fine, pretty much sorted. Further I have L2 is equal, L2 not like that, it will be L2 is equal to 0, and that so is equal to 1. Fine. And what next I'm going to return up here? I'm going to return up here the capital X divided by np dot expand underscore dims dimensions, and we have 12 comma, and I'm going to set up here the x's. Okay, simply done. Now this one as well I'm going to simply run out. Fine, very much clear. Next what I'll be doing is that I'll be having up all of my columns, and with that columns now I'm gonna do up some stuff. Okay, so here I have first of all my columns. So here it is, 1 second. Okay, here it is columns is equal to, I'm going to put up all of the columns we have. Just let me check that out very quickly. Sepal length, sepal width, petal length, petal width, everything in small. Okay, it's 1 second. Okay, it's sepal dot, okay, where is it? Okay, like this first of all, and here goes my sepal dot length. Okay, sepal dot length, here I'm going to put up a comma, then goes my sepal dot width, then goes again my sepal, it's not, it's time for the petal, right? So petal dot length. Okay, I'm going to cross this out first of all. Okay, how come this bracket came up here? Right. Okay, so petal dot length is done, and after that further I am having one more, and that is my petal dot width. Fine, so all of these fours are actually done up here, and now I'm going to write up here x is equal to pd dot read okay, that is pd dot data frame. Okay, and into the bracket I'm going to put up here the erase comma, and for that columns is equal to columns. Fine, further getting down I'm going to set up the x once again. So in that case will be the normalize. So a normalized function we did already made up above, so for that I'm setting, and that will be x dot as underscore matrix and the brackets like this. Okay, now further after that we are having up the columns. That columns is equal to, and here I have the variety, because variety was the column which we were having, right? Once let me check that out. Yeah, variety. Okay, so we have this variety here. Further now I'm going to do this for the y. So for y I'm going to write out pd dot data frame, and into the bracket I'm going to put up here the iris comma, I'm going to set up the columns is equal to column. Okay, and for the y as well I'm going to set up normalize. Okay, not like this, it will be y dot as underscore matrix, and into the bracket simply it will be like this. Okay, now this thing is done. Further now I'll be again using y variable only. Okay, so it will be y is equal to, and now I'll be using up the function y dot flatten. Okay, y dot Latin. Done. And next will be y is equal to, I'll be calling up the function which we did use above. So it was 2 underscore 1 underscore hot, right? And into bracket we will be putting up a small y. Okay, up till this particular point, I hope that it's very much clear, right? Now, further, what is needed? Further, the need is of the splitting of my training data set. Okay, so further now what we'll be doing is that we'll be splitting up the data sets, and now further after the splitting everything would be done. Okay, so now I'll be splitting up the data to the training and the validation data. Now it's x underscore no, not like that. Yeah, I'll be writing that x underscore train. Okay, 1 second. Let me simply run this out. Okay, init got columns. Fine, let me check that. Columns is equal to, I guess it's columns is equal to columns. Data frame has no attribute as underscore matrix. Okay, so x is equal to normalize. And into the bracket we have x dot as underscore matrix, right? So let's check that out. X is equal to normalize. Into the bracket you have x dot as underscore matrix. Okay, let's do out one simple thing. Let's comment out this respective line for now. Okay, and this one as well. Okay, let's now run that out. No attribute flatten. Okay, let me comment these two as well. Okay, fine. For now, let's just simply comment that out. Then we'll check out further that whether like at what place we just need to uncomment them out. Okay. Great. Further, we'll be now be splitting up the training and the validation data. Fine. So it will be x train, comma. It will be x underscore test, comma y underscore train, comma y underscore test. Okay, and that will be equal to train underscore test underscore split. Okay, train and test split. Okay, into the bracket we have x comma y comma its test underscore size is equal to, I'm going to put up the size, it's 0.13. Okay, now I'll be making up a variable w0. Okay, so into that I'm going to use 2 multiplied by np dot random dot random. Okay, and further we are having 4 comma 5. Okay, pretty much done. And I'm going to set up here minus 1. Okay, so 4 will be my output. And okay, so in that case what we'll be having? We'll be having 4 inputs and 3 outputs. That's the reason. Okay, for w1 I'm going to do up the same thing somewhat. So 2 into we have np, yeah, we have np dot random np dot random, and into the bracket we have 5 comma 3. Okay, in the bracket we have 5 comma 3, and for this as well we are going to do out the minus 1. Fine, and here we are going to set up n is equal to 0.1. Okay, now further I am gonna do up some more things, like I'm gonna set up the error, and for that, into that we'll be putting up a range and further things will be applied out. Okay, now here I'm gonna put up the value for n. So n is equal to 0.1, right? And here from here it is my learning rate. Okay, and error I am gonna set up as blank here for now. Okay, now goes my for loop. So for I in range, and you could put up a range according to, let's say I'm going to put up is as 1, 2, 3, 4, 5. Yeah, let's put that out this much of range. Okay. So now further after writing up this for loop, let's move forward. Okay. Now what I'm going to do is that I'll be making different layers, and there so I'll be using some different functions. Okay. This is what I'm going to do. So I'll be starting it from here. Layer is 0 is equal to, okay. I'll be giving up different sort of variables, and onto that I'll be using different types of functions. So layer 0 is equal to, it will be x underscore string. Okay. further. Okay. Further, I'll be making my second variable, which is layer 1. Okay. And that too will be equal to my sigmoid function, which we just made, right? Above sigmoid function. Okay. And into the bracket, I'll be using up the dot function with the help of my NumPy library. So it will be np dot, and here in the bracket, it would be layer 0, comma, it would be w0. Okay, comma w0. Okay. Great. Now further what I will be doing is that I'll be writing up here layer 2. Okay. That again will be equal to sigmoid. Okay. That again will be equal to my sigmoid function, which we just made it above. And that will be equal to np dot dot, and here will be my layer 1, comma, w1. Okay. This is what it will be here for my layer 1 and for my layer 2. Okay. I need to do one thing. Actually, there's a certain time. After that time, the runtime gets out, and simply sometimes the runtime gets out, and your data which you did uploaded that gets removed out from there. Okay, so I again need to go to my data sets, and from here I have to do for the erase data. Great. Now it will do that out. It actually loaded up my erase data, and what I have to do is that once I have to go up above, I have to run up all of my respective cells once again. Because as I told that many a times it has the run out of the time. So when the time run out thing comes, so after that you will not be actually able to check up the things and all those respective ones. Okay. So onto that case, you have simply to be to run again all of the cells. Now there's one simple function as well for running up all of the cells. Okay. I would let you know that particular as well. But if you just want to do that manually, so yeah, manually is as well allowed. You could just choose out anyone from your respective easiness. Okay, all of them have been run. You just go to here. Okay, here you have runtime and click on runtime all. Okay, run all. So it will automatically run out all of the cells for you. This is the idea. Okay, let's get back to the program that we were writing up. Fine. So here this layer. Okay. Next, I am having up now. I'll be writing up the back propagation using my gradient descent. Okay. So here will be layer 2 underscore error. Okay, layer 2 underscore error. It will be equal to y train. Okay, y underscore train minus, and then will be the layer 2. Okay, pretty much clear. Further, we are having layer 2 underscore delta, my second variable that I'm making. Okay, and that will be equal to my layer 2 underscore error. Okay, layer 2 underscore error multiplied by my sigmoid function, sigmoid underscore, it will be that derivative. Okay, multiplied by sigmoid underscore derivative, and into the bracket here we have the layer. Fine. Further, I'm going to write up layer 1 underscore error, my next variable, and that I'll be sitting with that dot function. I'll be applying up the dot function for this respective next variable. Okay, so onto that case, what I'm going to do is that I'm going to write up simply very quickly layer 2 underscore delta dot, and I'm going to write up here this dot function, and into the bracket I will be writing up here some sort of other things, like I'll be writing it up here variable which is w1 dot, and I'm going to use up this capital T. Okay, pretty much clear. Now further I have to use up my layer 1 underscore delta. So layer 1 underscore delta is equal to, now that will completely be equal to layer 1 underscore delta. Okay, yes, layer, okay, we just made the delta for the layer 2. Layer 1 we haven't made up till now, right? So layer 1 underscore delta, and that will be equal to my layer 1 underscore error. Okay, multiplied by sigmoid underscore derivative. Okay, multiplied by sigmoid underscore derivative, and in the bracket I'm having layer 1. Okay, that's pretty much clear, I guess, right? So these were for a few lines actually, first for which you need to mention it up here. Now further we will be making 2 more variables, and into that also we will be using up the dot functions. Let's do that out. W1. Okay, it will be somewhat plus equal to. Okay, now W1 plus equal to. Here you have layer 1 dot E dot, and here you have my dot function. Okay, dot is somewhat making and multiplying of two numbers. It's somewhat like that particular thing. Okay, dot, and into bracket I'm going to put layer underscore 2, and it will be delta s, and that too will be multiplied out by n. Okay, n was a variable which made up here, that is n is equal to 0.1, right? Multiplied with that. Next we'll be making W2. So again W2 as well plus equal to W2, sorry, it will be W0. Okay, plus equal to, and that will be again layer 0 dot T dot. I'm going to write up the dot function, and into the bracket we are going to use up layer. It will be layer 1 underscore, it will be the delta. Fine enough. And I'm going to multiply that with n again. Fine. Okay, layer 0, layer 1 dot dot, layer 2, layer 1 underscore delta. Pretty fine. Let's get down here, and now further what I'm gonna do is that I am gonna write up here the further things. Okay, that will be equal to my error. Okay, so my error will be equal to, okay, my error will be equal to my mean function of the layer 2 error. Okay, so np dot mean, inside that you have np dot abs. Abs is also a function which is used up here. Okay, into the bracket. Further you have layer 2 underscore, you have error. These are respective things which you are having up here, and error is as well calculated. One thing is left. Here it is to be left out. Errors dot, and it will be append, and into the bracket what to append the error. Fine, let me run this out, and let's see that what is happening up here. Okay, invalid syntax dot. Okay, okay, this came inside here. 1 second, let me remove this out. Fine enough. Okay, okay, the unable to course the frame shape must be 130 comma 1 given 130 comma 3. Okay, so here, right, we're writing up this particular thing. One thing has to be changed up here is that when I just wrote up the test size 0.13, so instead of that, it would be 0.33 actually. Okay, so this will be the size which we have to take here for writing out our code. Fine enough? Great. Now we'll be moving forward, and we'll be now just writing up the rest of the things. Okay, so that we were already written up. Sorry, yeah, we just completed up this particular thing. Okay, so yeah, now let's move on to the next line of our code, and let's see further that what's gonna happen about here. Right, so now I will be having up a variable which is accuracy underscore t. Okay, this will be training. Accuracy underscore training is equal to, I'm gonna do 1 minus error. Okay, that will be ERROR. Okay, I'm gonna do 1 minus error, and I'll be multiplying that out with the variable with the number which is 100. Okay, further this is the thing which has to be done. Next I'll be plotting up now is my respective plot. So for that I'll be writing plc dot plot, and what I'll be plotting, I'll plotting up the errors. So into that, when I just wrote a plot, so in that case a line plot is gonna come up as an output. Okay, so plt dot plot, and into the bracket you have the errors. Fine enough. Then what the x label and y labels you want to give? So plt dot x label, and into the bracket you'll be having the x label as string. Okay, next goes your plt dot y label. Okay, and that too will be your error. So x label will be the training, and y label will be your error. And at last here I have plt dot show. That respective this particular will be helping me to show out my respective plot for my output. Okay, this is what is actually done up here. Now further this further after this particular thing, what is left out is that we simply have to do out one simple thing, and that is to print up a statement. So what that respective statement will be doing, that respective statement will be giving us the accuracy, that the training accuracy of the particular model. I'm going to run up all the cells at one single go because it will be more clear to you when we run up the cells at one single go. Okay, that's the reason I'm writing it out, and further we'll be running. Okay, so here it goes my print statement, and inside that print statement we have to write up somewhat like that training accuracy of the model. Okay, the training accuracy of the model, I'm going to use up the plus sign, and here we have str, and I'm going to round that off, round, and into the bracket here goes my variable, which is accuracy training. Accuracy underscore training, yeah, accuracy underscore training. And now I'm going to put up a comma 2. Okay, and further I could just put up a plus sign, and then I could put up a percent sign also, so it looks a little bit more better, right? So percent sign, pretty enough, fair enough, right? So now let's get down, and now further I have to do I have to write up the validations of the test. Okay, so for validating of the accuracy, so that will be done up here at this particular place. So let me get down here, please, first of all. So now it will be layer 0 is equal to, and that will be x underscore test. Okay, so layer 0 is equal to x test. Then we have layer 1, your layer 1. Now that will be equal to your sigmoid function. So sigmoid underscore function. Okay, into the bracket you have np dot, and into the bracket you have your layer of 0 comma w of 0. Fine enough. Next, getting down here, you have your layer 2. Okay, that will be equal to your sigmoid underscore func. Okay, into the bracket you have np dot, and again here into the bracket you have layer 1 comma, here you have layer 1 comma w1. Fine, layer 1, layer 2 is then we have the layer 2 underscore error, so that will be equal to your y underscore test subtracted by layer 2. Okay, getting down here you have your errors, so error. Okay, so error will be equal to np dot mean, and into the bracket you have np dot mean, and into bracket you have np dot abs. Abs is the function. Okay, and into the bracket you have layer 2 underscore error. Okay, now next, getting down here you have your accuracy validation. So accuracy underscore validation. Okay, accuracy underscore validation, that will be equal to 1 second. Yeah, that will be equal to 1 minus, and here we have the error. Fine, multiplied by, here we have 100. Fine, and at last I'll be printing up a last statement, that is print, here will be validation accuracy of the validation accuracy of the model, plus here we have the str of and I'm going to round that off, and into bracket I could simply put up accuracy underscore validation comma round off up till 2 decimal places, and plus I could put up a simple percentage sign. This perspective, here I completed up writing up my complete code for the back propagation algorithm. So right, I guess that you are having now a pretty clear idea that how do we write up a back propagation code, and what are the things that are included, and how are the things actually gonna be, and how are the things actually written up here, right? So hope this thing is pretty much and very much clear to you regarding the writing of the back propagation. Actually, how do we implement of the back propagation with the gradient descent? Hope that is very much clear to you, right?
Having covered neural network, deep learning, let me ask you a question before moving ahead. Which of these concepts do you plan to apply in your projects? Share your answer in the comment section. Now we'll explore artificial neural network, the foundation of deep learning model. Then we'll introduce you to TensorFlow, a powerful framework that make building and training neural network accessible and efficient. So stay with us till the end.
Now we will have a look at when we talk about neural network, right? So what is the difference between human brain and the neural network? We all know this, that a human brain is like the neural network is like a human brain. Most of them who actually starts their career or who starting learning this human brain and neural network, artificial intelligence, they have that doubt in their mind that how actually this neural network can be a human brain, because human being is actually a complicated version, right? So in that case, there are some part we actually can consider and compare with human brain with the neural network, right? So in that case, our human brain has dendrite, our human brain has axon terminals, but in the neural network, what we have activation function, we have input layer, we have hidden layers, right? So basically we have three parts in a neural network. Artificial neural network, basically we have a hidden layer, we have input layer, and we have output layers. So this hidden layer is actually working as a black box thing. So if you don't know the mathematics behind that, so in that case you can say it's a black box. But if you know the mathematics behind this, so it is not a black box. This is one myth we know, that artificial neural network is a black box, but it is not a black box. It is a proper mathematical implementations, right? So basically scientists want to make an artificial neural network that works as our human brain works, right? So it is quite similar with that, but not fully similar with that. Now we will have a look at what are the thing we have in our human brain, for that we can compare with the artificial neuron. So in that human brain we have cell nucleus. So in that case, artificial neural network have node. In human brain, we have dendrites, right? So in the artificial neural network, we can replace them with input layer. That's the inputs, right? X1, X2, X3. Okay. In human brain, we have synapses. So how can you replace that synapses out artificial neural network? So in that case, we use weights or interconnection. This weight and bias helps us to actually calculate the inputs. This is the main part for an artificial neural network. Now we have axon in our human brain. So in that case, neural network has mapping, activation, and learning. So lastly, we have terminal axon. And for the artificial neuron, we have output. That output layer. Why go for human brain versus neural network? So basically, we all know that neural network is basically a replica of human brain, right? So who are actually new to this domain, they want to know what is the similar thing we have in human brain and neural network, right? So in that case, I just want to clarify you guys that what are the thing we have in human brain and what are the thing we have in neural network, and how can we compare them, right?
Now, ladies and gentlemen, what is super important here is that you have to understand what TensorFlow is, why did it come into the picture, and why are we even using it today. I take an approach to understand saying, hey, where would we be? What would we do if we never had TensorFlow today? And that we're going to discuss in this section as well, right? Now, to give you a little background story about how TensorFlow itself came into the picture. Now, what happened is that a couple of years back, developers were hunting around for a library which basically makes it super easy for the developer to actually go on to use and understand and try to figure out what is the best way that they can use to effectively solve deep learning challenges out there, right? Now, Python offers very good syntax to go about doing this. But you have to understand that a language such as Python, right, it gets all of its powers by these beautiful libraries, which eventually make your life as a developer super easy, right? Now, you can have a lot of functionality. That doesn't mean you have to write a lot of code, right? That is why we have functions. That is why we have helpers. That is why we have frameworks, libraries, toolkits, so much more, right? Now, TensorFlow belongs to one of these categories, which eventually help us get to that point. Now, if you've clicked on this video, I assume that you guys are aware of how to work with Python. You know the basic Python syntax and maybe even basics of neural networks, right? Now, what is more important for you guys here is that knowing that TensorFlow is a deep learning library, first of all. Second of all, its popularity comes because there was this huge initial demand, as I just mentioned, right? Developers and especially researchers, right? Now, any of these big libraries that have become super popular, if you actually trace it back to its roots, it would have been a research problem which eventually became commercially available, right? Now, in this case, there is a specific thing that's mentioned on your screen right now. Developers were looking for open source solutions. In the world of programming, ladies and gentlemen, or in the world of deep learning and AI, if you try to use niche products or closed-ended products, what happens is that you're limiting at least 70% of your audience in terms of reach. Not all the people would love to pay for a product which eventually someone else might give it in terms of open source for free, right? So of course, you have to understand that Google, being the top giants that they are the ones that are behind TensorFlow, right? And of course, they decided, they used it, they created a beautiful prototype and in fact a working version of TensorFlow, and they eventually put it out to the world. And it is so well optimized. It is so it makes your job as a developer to such an easy extent where at the end of the day, if you're trying to solve a problem, solve a deep learning problem, your head and your important logical space will eventually be to just try to figure out the problem rather than think about any complex syntax that might follow there, right? That makes this library, that gives power to this super amazing library, in my opinion. First of all, it is open source. Second of all, it is really powerful, because when you take a look at any other library, we have one or two that stands up to TensorFlow, and they're good at what they do. But when you're thinking about a general tool which works for researchers, students, which works for IT professionals, which works for beginners, works for experts, and more, if you just have all of these requirements at once to cater to it, eventually we have TensorFlow, right? Now, what happened is that, let's quickly go back 5 years down the line. We are at 2021 right now. If you take a look at 2016, right? In 2016, the Google Brain team actually released the TensorFlow. Now, the Google Brain team is renamed to the Google AI team now, but you have to understand that this is a team which is responsible for the most innovative artificial intelligence based applications from Google, right? So whenever you think about any of their G Suite products, which is super well tuned, be it the Google Assistant, be it Maps, be it anything else, this team has a good amount of contribution there. Now, what happened in 2016 was, again, when the world was looking for a library and it was hugely in demand, Google stepped up to the challenge and said, hey, we have a prototype, here's a version that you all guys can use, and it was open source as well, right? So in 2016, when it was completely free to use and open source to use, I remember very well that a lot of people just started hyping this up. Now, as a person who's working on data science, who's working on deep learning at that time, I was super interested to see what all the hype was about. So I myself installed TensorFlow. I was taking a look at their documentation, and I was blown away by the amount of simplicity and at the same time how powerful this library was, right? All the contributions, in fact, I want to say most of the contributions that we have in today's world where Python and deep learning might have been used, there's a very good chance TensorFlow had something, either a small part in it or it had a huge role to do, right? So that is super amazing, because we have millions of AI based applications with millions of ideas cropping up every single day. Knowing that the demand is virtually endless for our hunt of artificial intelligence in the future, we have a library which is very strong, and its foundations are really strong to take us probably 10-15 years into the future, right? That is how well TensorFlow is coded, that is how well TensorFlow is written, and again, it speaks to its popularity, right? So the Google Brain team came up with it in 2016 to give you guys a bit of history. Now, what happens is that when you think about TensorFlow as a library, as a framework, you have to understand what it is exactly, right? Now, TensorFlow gives you the ability to emulate neural networks by making use of Python code. Now, when I say emulate neural networks, the term neural networks itself came from us actually trying to understand how the neurons in our brain work and try to get our computers to do something on the same lines of it to, of course, make it intelligent as us, right? Now, to do that, they required one simple library to do, and TensorFlow catered to it. It's a very powerful open source framework for deep learning that works really, really well in Python. Now, you might be asking a question at this moment of time saying, hey, can TensorFlow be used with other programming languages, or is there a compulsion which says, hey, if you have to use TensorFlow, you have to use Python? Is that the case? Well, to answer that particular question, it is not just Python that is used for TensorFlow. Now, TensorFlow is a fantastic library which will work, well, of course, it is built to be used with Python, right? Now, there are many reasons of why TensorFlow would want to work really well with Python, because of how Python works in its fundamental sense, and TensorFlow was made to talk with a popular language, right? It was built with a purpose to make sure it is as effective and efficient when speaking to Python. But this does not mean that it will not work with other programming languages, right? There is multiple third-party support that is provided for programming languages such as C#, MATLAB, a super popular data analysis programming language called as the R programming language, and the last one that you see on your screen right now is a programming language called Rust. Right? So not just Python, there are 5 or 6 other libraries, 5 or 6 other languages where you have complete usage of TensorFlow, but then of course official support is only provided to Python, because again, you cannot just have one library and it takes a lot of development to make TensorFlow what it is, right? So making sure that you're focusing the developers to work on making that tool the ultimate one-for-one programming language, I think that is what Google were aiming for, and that is exactly the result that we see today, right? So now we know what TensorFlow is, now we know when it came about, who's responsible for TensorFlow, and what programming languages can be used, right? Now, since you guys are watching this video, let me know which programming language is your preferred one in the comment section below. I believe that most of you will say Python is your preferred programming language, because at the end of it, again, Python's popularity rose really well. Alongside that, to mirror it, TensorFlow's popularity was going up and up and up as well, right? People realize the power of Python. People realize that TensorFlow is a library that makes your life super simple by giving you fantastic syntax to work with. Eventually bring it together, you have a very well-rounded product, right? Pretty simple and straightforward. But the most important thing that we're trying to answer with this is, why is the name TensorFlow? What does a tensor even mean? Does it have any meaning? Flow is okay. Flow is an English word, but what is a tensor, right? You might have not heard of the name. If you have, well, here's a quick refresher for you guys as well. Now, one thing you guys really have to know here is TensorFlow got its name basically because of two things. One is tensor, the second part of it is flow. Now, when we speak about tensors are nothing but multi-dimensional array structures, a very specific type of data structures which are required to create nodes in a neural network setup, right? That's the reason why there is a name tensor. But what about the flow? Why is there a flow of tensors there? Well, to answer that question, when I say flow, basically how a simple neural network works, or how a tensor itself works, is that we take multiple numerical computations and we convert it into something called as computation graphs. These computation graphs is what denotes the flow of numerical data in the form of a network, right? When you have the data flow, that is where you've got the name flow. So when they just picked up the idea of tensors, when they realized computation graphs and data flows, they just brought it together. Hence the name TensorFlow, right? It is very easy to understand and remember this. And if you're a beginner who might be looking forward to learning TensorFlow as well, there's a very good chance this might be asked in an interview to see to what level of depth you might have had, you might have researched with respect to TensorFlow, right? Now, when you're thinking about a neural network itself, it becomes important that you understand what is required to get the neural networks to work. Of course, we have a section where we are going to be discussing the same thing. Now, to give you a bit of clarity, I just told you that there are nodes which are used to create a neural network, and to calculate and give you an input output for these nodes, we have something called as tensors. So it is very simple to understand that tensors are these little blips. Tensors are these little data storage entities which will eventually give some sort of storage, understanding, meaning, and a network flow wherein data can move around in the network, and eventually you can go from just having data or maybe raw input all the way to having a popular output, right? That is important for you guys to understand here. Alright guys, now it's the time we actually get started to work with TensorFlow, right? We understood the theory to a good extent, even with respect to neural networks, even understanding what the mathematical aspects of weights are, biases are, and how they have an insight to say and what role they have to play in a neural network, right? Now, once we took a look at all of that, you must be very curious at this moment of time to actually understand what a tensor looks like. How does it work? How can we programmatically write a tensor and eventually get this tensor to perform operations for us, right? I am sure you all are curious on that note. Well, to answer all of these questions, we have to start out by telling you one thing, guys, here. Now, whenever you're practicing anything from this point on in this tutorial, just make sure that you're practically working alongside me as well. Because be it TensorFlow, be it any other deep learning library, this happens a lot, and this happens even with experienced professionals. When you look at the piece of code, it'll be like, oh, okay, so it's very simple. I can do it too. And probably you can. But when you're actually, when you close the piece of code and when you try to implement it yourself, that is when things will slightly become difficult. Now, this is a common pattern with beginners, intermediate users, and sometimes if it's a very complex program to implement, even with advanced users, right? So to make sure that you are up to speed with all of these, make sure you get your theory completely straight and set, and eventually get started with practicals, because with the practical aspect of things, when you walk through and understand the code and when you do it multiple times, that is how you become proficient in this concept, right? Fantastic. Now you should be asking a question at this moment of time, and this question is, what is the process of writing TensorFlow code? We've discussed about the theoretical aspect of things, but when you have to build a tensor, when you have to make your computer understand what a tensor is, and eventually you have to understand what a tensor is to make sure you can implement multiple of these in a neural network, right? So there are actually two important steps that we're going to take a look at whenever you try to say, hey, I want to write TensorFlow code. Now, we looked at the introduction, we looked at installing it. At this moment of time, all of you all should have it set up for these two steps. The first step is for us to understand that having these tensors eventually means that a computational graph, the flow of data, as I explained previously, will actually be the reason of how data moves around, right? Data entities get converted into computational graphs, and these computation graphs eventually get to be the solution and get to be how a channel, a pathway for the data to flow around, right? So to get to the point where we will have a computational graph in hand, it is important for you to understand that to do this, we require two steps. One is to actually create these computational graphs for us from tensors. The second thing is to actually run these graphs to make sure that you can work with any sort of graph related operations, right? Now, once your data goes into the form of a computational graph, moving data around becomes really simple, becomes trackable, and eventually you will understand in a very complex neural network, if there's one or two nodes which you think you can tweak and tune and do it, it is possible to do so. Why? Because of the mathematics that is behind it. You have a trackable metric there, and eventually to get to that point itself, your data was converted into computational graph, right? Okay, fantastic. Now that we know that we have to create a computational graph from a tensor and we have to run these to ensure we have an operation, I think it's high time we take a look at our first tensor operations, right? Now we are clear with the usage and understanding of the basics of tensors, but here is a piece of code on your screen which says x equal to t dot constant of 10, y equal to tf dot constant of 15, z equal to x plus y. Now, ladies and gentlemen, Now, ladies and gentlemen, there is one important thing that you have to assess and analyze here. Doesn't this look very much like a mathematical operation? We have a tensor which has a value 10. We have another constant value which is 15. So what do you think happens when we add this? Is it 25? Or do we get something else as an output, right? We have never performed a tensor operation, so it is high time we check this out practically, right? Let me go back to Google Colab now and we can check it out there. Now, let me just open up this tensor demo that we have, right? Let me zoom in so that all of you can see, connect to my runtime, and I can zoom in a little more, right? Superb, guys. Now, let me actually go on to quickly clear the output as well so that you guys, stay a little bit curious. Okay, fantastic. Now that we can see this, ladies and gentlemen, for the first step is to always import TensorFlow, right? You can write this piece of code alongside me. We have X, which is a variable. This is basically a constant tensor, right? We can have constant tensor, placeholder tensor, variable tensors, sparse tensors, and a lot more. In this case, we're using constant. What does it mean? Well, I'm trying to say that, hey, this tensor has a constant value of 10.0 and it will absolutely not change. So regardless of where it is positioned in a network, the value of the constant is always going to remain same. So whenever you use X and Y, these are tensors with respective 10 and 15 values. So as soon as I run this, you will see the actual mathematical operation that happens, right? 10 plus 15 is what? 15. So 10 plus 15 is what? 25, right? But look at the output that you get. This is not just as X equal to 10, Y equal to 15, add it up. No, this is two tensor operations that we are trying to do here. And the output will tell you that, hey, this is a tensor and it has the value 25 and the data that you have set is a float value. Why is it a float value? Because we have 10.0, 15.0. Of course, it is the same as 10 and 15. Now, this is very important for all of you all to understand and to know that, hey, we can perform any operation. Now, there might be some of you curious out there saying, hey, why did you add? Why can't you multiply? Well, sure you can. All of these operations are possible on tensor. So make sure that you try a couple out, try multiplication, try division, try floor division, of course. So I want you guys to actually get your hands a little dirty out here and make sure that you're actually trying this out practically. And alongside Z equal to X plus Y, try these other operations that I just mentioned, right? Fantastic. Now that we understood, and I quickly told you about the three types of tensors that we have, right? Constants, variables, and placeholders. Now, when we're talking about constants, variables, and placeholders, one important thing you have to understand here, ladies and gentlemen, is that the answer to what they mean lies in what the name itself is, right? These are the three types of tensors. There's a fourth one, it's called as a sparse tensor, but eventually it gets a lot complex. So to make sure you guys have a simplified, structured start to your TensorFlow journey, these three are going to be the most popular ones that you will be using, right? So let's clear things up between constant, variable, and placeholder. Now, with respect to constant, what do you think when something says it's a constant? We just checked it out, right? If I store X equal to 10, let's assume that it's a tensor. It means it's going to remain 10 forever, right? Until I want to change it, until I've changed it, it's going to be the same. Pi is 3.1418, etc. And you can't change that. It's going to be the same thing everywhere, right? That's a good example of a constant. We use multiple constants in the world of mathematics, in the world of physics especially. So if you guys know any other constants, head to the comment section and put them down as well. Right? Now, constants are fun. We understood what they mean, but one thing you have to understand about these constants is the fact that they get initialized as soon as they are called. Now, there are two ways of how you can work with tensors, right? One is to make sure that you have initialized them, you're calling them. Think of it like a function. Right? If you have a function, you'll have the body of the function. You'll have to eventually call the function to make use of it, right? But here you don't have to do it as a separate process. X equal to tf dot constant, exactly what you saw there. That is all that you have to do. Well, if that is the case, and why is it actually initializing as soon as they are being called? As soon as that line runs, constants are initialized right then and there and not, right? Well, this is the case because we want slight flexibility in terms of how we can work with variables. Now, variables, it's a little bit different, right? Whenever you're trying to define any sort of variable, what are you trying to do? You're trying to provide an initial value that it can use, right? Now, x equal to tf dot constant is something that we understood as a constant, putting it into a variable for Python. Here we're talking about having a variable tensor as well. Now, what is more important about variables you have to understand is that constants are fantastic. Constants can be used everywhere. They will remain at the same value. But if you have a very complex neural network and your values are the same, well, it doesn't work in any of our favors, right? We'll always have new weights. There's a good chance we'll have new bias values. So there are so many things which are new, and eventually you can't say, hey, I want like a new variable, or I'm going to be using like 1,000 constants, right? It doesn't make sense. That is the reason we have variables. Now, variables is basically giving you one important flexibility. It is to basically telling you, hey, you can vary any input that you have, right? For example, you will have the same couple of inputs and eventually they'll be the same as constants. But what if you have same inputs? With the help of TensorFlow, if you can vary it around, store it, change it around, there is your flexibility, right? Same inputs, different output, and this is super important, not just in deep learning, but in many places where you're using AI-based applications, and of course, they are derived from neural networks itself. Right? So understanding that you can have extremely similar or exactly same input, and you can have a playground wherein you can work with these, change these values as and when required, right? The way neural network works, you know this, right? All the data moves in the forward direction once, and to tune and tweak the network and to make sure we bring down the losses, we have something called as backpropagation, where we keep going back into the network in an iterative process to make sure that we are tuning and tweaking these numeric values which are stored where? In the variable tensors, right? So I hope you have a complete picture on that. Now, whenever you're training something is where your values will usually change, but whenever you're trying to loop back into it in backpropagation, it changes as well. So hey, there is another advantage of making use of variables. Now, one thing you really have to know is that whenever you actually go on to define a particular variable, right? Now, if it is a tensor variable, you have to be very careful to make sure that you actually provide the initial value of the variable that you're trying to use. Now, if you just have a variable tensor, and if it's blank and if it's empty, it gets very confusing for a neural network and it is syntactically incorrect, right? If you have a variable, just put a dummy value, put a start value. The name itself says variable. You can vary it later down the line, but it is super important that you understand that there has to be an initial value while working with these variable tensors, right? So now we understand what are constant tensors. We understand what are variable tensors. But what about placeholder tensors? What are these, right? Now, one important thing you really have to check out here is the name itself again. When something says placeholder, it means that it's being just put there temporarily, or it is serving as a substitute or something like that in the real world, right? Here also, it has a similar meaning. Now, whenever we're thinking about a placeholder, all we are trying to do is basically saying, hey, these are certain entities which are not yet initialized. They do not have any sort of data, but we want them to be there because even if you don't use them right now, there will be a dynamic value that will be stored in them later down the line, which is probably required for the graphs to execute. When that is the case, you just want the structure to be there, but no initialization, no data, and you know that later, instead of creating it and being confused and not understanding what variable does what, you just do it at the start, do it in a structured way. So when you're actually working on the logic, when you're actually working on building the network, you don't have to break a sweat on any of these, right? So this will just serve as a structure eventually upon which you'll store values into it, you'll initialize it whenever it is needed. So guys, with this, I hope you're clear with constants, variables, and placeholder tensors as well. Because once you are done with this, it is high time we take a look at a couple of hands-on sessions we have planned for you, right? Now that we know what tensors are to a good amount of degree, you will be very curious now to actually get started, right? As I told you, when I was learning TensorFlow all those years back as well, the very first thing I wanted to do was, hey, show me the code, I want to start writing code. Now, I know you guys are equally excited to get to that point, but one important thing you have to realize is how you guys can go on to install TensorFlow. So how do you install TensorFlow? Is it complex? Sometimes installing Python libraries can be a hassle. So is it the same thing here, or is it very straightforward? The answer is the latter. It is super straightforward to go on to work with tensors. One very important thing you have to understand is that everything that you need to install TensorFlow, everything you need to install Python, everything you need to make Python talk to TensorFlow are all open source, are all absolutely free of cost. Again, for personal use, commercial use, and all of that as well. So everything that you need is available in one simple place, which is nothing but the TensorFlow official documentation. Now, what we are going to do is let's just take a look at the steps on your screen, and eventually we'll go and get started with how you guys can install it, right? The first step, of course, is to head to the official site and understand what the latest version is and the compatibility for it, right? Now, what I am going to do here is I have the browser open. I'll just type in TensorFlow in Google here. Now, as soon as I click the official website, that's tensorflow.org, let me just get to their website. And in fact, TensorFlow is one of these libraries which is documented so well, right? Just like any other Google product, they have a ton of documentation. They have a huge community. In fact, they have a small section wherein you can try to understand TensorFlow for its various usage. If you want to use it with JavaScript, if you want to use TensorFlow for mobile applications and all of that, right? You can see from these tabs that you can understand a lot about it, and it is even clear for a beginner to understand why it's required, right? As soon as you go on to open TensorFlow's page and you're scrolling down, they'll just show you why you have to prefer TensorFlow. Now, TensorFlow is from Google. There is one more computation element which is eventually super popular, as popular as TensorFlow, which is nothing but PyTorch. PyTorch is a fantastic deep learning library which is developed by the creative developing team at Facebook as well, right? So TensorFlow is from Google, PyTorch is from Facebook. Now, they'll give you some of these reasons of why you should consider TensorFlow, right? Easy model building. You can go on to work with machine learning production. You can have fantastic power when you're trying to find insights based on research, right? You find so many different things right here on their website, which will eventually help you understand TensorFlow. You can find out a lot about these companies that are using TensorFlow as well. So guys, moving around the TensorFlow site, you find a lot of information, right? Everything from the case studies that are solved using TensorFlow and who uses TensorFlow as well, right? Ladies and gentlemen, look at your screen right now. I wanted to put all of these in my slides itself on the PowerPoint to show you guys, but again, it just becomes a hassle because you cannot fit all of these companies. Now, just find the net worth of all these companies that are shown on your screen and you will understand that it's trillions of dollars, right? Trillions and trillions of dollars in discussion. So it becomes vital that you understand everyone from a company such as Coca-Cola, GE Healthcare, Intel, Bloomberg, Lenovo, Snapchat, and of course PayPal, Nvidia, right? Now some of these tools from these companies we use daily, but you have to understand that it is super popular right now. When these companies are using it, it is a trickle down to other mid-tier companies and mid-sized companies saying, hey, if these guys can make it work on an enterprise level, let us also give it a try. Now, when those guys do it, people who are entrepreneurs, startups, these guys are also super interested, saying, hey, if it's so powerful and easy, and if these guys can do it, we can do it too. And if they're doing it, students can do it. If every one of these guys can do it, it's because of the research that goes into it, right? So you'll find a ton of stuff. I love browsing around the TensorFlow website here, and you can find out so many things. The most simple and straightforward thing that we have to discuss right now is the ability to install TensorFlow. Alright guys, so hitting this install tab is basically what we are after right now, and you might be wondering how difficult it is to install TensorFlow. Well, let me tell you, it is very simple to install the latest version of TensorFlow, which is TensorFlow 2. Now, ladies and gentlemen, it so happens that you might be using resources online to actually study and work on TensorFlow. But if you're looking at some older content that is present, they would be using TensorFlow 1.x. Now, when you're thinking about 1.x, it becomes super important that there are certain changes in 1.x and there is a huge change between 1 and 2, right? There are many things that features that were working in 1 which will not work in TensorFlow 2. So it becomes important that while learning while using and while understanding you have the latest one in hand, right? Because when you want to take this to a next level, when you want to go from just learning for your sake, learning for a job, when you want to actually attend interviews and even understand and start using it practically, it becomes fantastic for you to know that, hey, having the latest version in your basket is going to attract a lot of employers as well, right? So quickly, to understand if TensorFlow 2 works for you or not, this is the criteria, guys. You're going to require Python's version either 3.6, 3.7, 3.8 or 3.8 or anything in between there. You're going to require an operating system which can either be Linux or Windows, of course. With Windows, you're going to have Windows 7 or 10. I think 10 is super popular, and of course support will be added for 11 as well, I'm sure. You can use this on Mac OS, of course, and Ubuntu as well. Right now, how do you actually perform the process of installation? Well, it is simple, guys. When you go on to use, and install something in Python, you have PIP, right? The built-in Python package manager. Now, Python's package manager is super simple to use. It provides a very readable syntax that you guys can use. Now, to make sure that you actually go on to install Python, first thing is you'll have to open up Python, get Python running. Once you have Python running, you have to make sure that you have the latest version of the package manager as well. Now, when you think about the latest version of package manager, this is important because Python works with TensorFlow 2. To get TensorFlow 2 to work and to install in itself, you require the latest one. So the first command is to update the package manager. Once you go on to update the package manager, it is a simple syntax that you can remember forever. Pip space install space TensorFlow. Right, done. And this is basically installing the stable release version which has been tested, cleared beta testing, and available for use. You can also install these nightly builds, as in these are unstable builds, experimentation builds. Maybe if you want a very particular version that you're after, you can install that as well, right? So if you have the latest pip and Python setup, pip space install space TensorFlow is everything that you're going to require to install TensorFlow. How simple is this, right? One line of code. Let me zoom in a little bit more so that you guys can take a note of this, or I hope you guys are also doing these on the website side by side as me, right? So pip install TensorFlow is literally everything that is required, right? Fantastic, guys. Now that we know a little bit about installing Python and installing TensorFlow, and once we have an understanding about what versions are there, which version works for me, do I need a developer build, do I need a stable build, the next thing you're going to decide is, okay, so where do I use this, right? When you're working with Python, there are multiple places where you can go on to use this. There are many IDEs for Python. First of all, PyCharm is a super fantastic IDE. You can work with multiple IDEs out there. But do you have to run through the entire process of setting up Python, setting up TensorFlow, and working with it? When you think about it, there is a very simple shortcut here, right? TensorFlow is from the team at Google. Of course, it is going to work really, really well with their other Google products. There is one Google product which is super fantastic, which is the Google Colab, right? It's called as the Collaboratory, and in my opinion, the most simple way of how you can use entire Python and TensorFlow is by making use of Google Colab, guys. This, to the people who might have never used Google Colab, is a very simple Jupyter notebook that is hosted on the Google Cloud platform. So all the resources, the CPU, GPU power that is required to work with all these libraries are pulled out from the Google Cloud platform. To a good amount of degree, you can actually have ample amount of resources to run all of your demos, and it's free to use, right? So the most simplest way, without you having to spend a couple of hours installing Python, understanding how everything works, messing around with the environment variables, remove all the complexity out there. The quickest way to get started is just go to Google, type in Google Colab, and you will have a beautiful Jupyter notebook to work with. Now I'm going to show you what it looks like. I'm going to quickly walk you through it. But once you go on to perform the installation, once you run that pip command wherever it is that you guys are running it on, be it PyCharm, be it any place else, you will be very curious to know, hey, I installed it, but is it working now or not? How do you check if something is working or not? You basically try to verify how you go on to do it, right? There's one simple command that you can do. Just like any other library in Python, just import the TensorFlow package as TF and you can get about checking, right? Now, as soon as you hit it, if there is an error, it means TensorFlow is not installed. But as soon as you run this, eventually you'll not get any printed output on the screen. But at the end of the day, you can, if it runs successfully, it means TensorFlow is installed successfully, right? Now, let me quickly open up my browser here. As I told you, this is the Google Collaboratory that we are discussing here, right? Now, as I told you, to install and verify if it is working or not, it's a very simple piece of code that you guys have to run. It is basically import TensorFlow as TF. Now, as soon as I connect to my runtime, this is just like another Jupyter notebook out there, right, guys? So if I run this, if I don't have any errors, I must have TensorFlow installed. Now, the beauty of this here is I am not using pip. I am not upgrading my pip. I don't have to do any of these things here because of the fact that this is a Google's product working on a Google product. So of course it is already installed. Now, as soon as I hit run, it is supposed to just run and be blank. This means that TensorFlow is correctly installed and TensorFlow is working, right? So this is the process for Google Colab, but for any other IDE out there, all you have to do is install it, run this command, verify if it's running. If it's running, you are good to go, right? Superb. Now, there are going to be two important demos that we're going to take a look at. And guys, we're going to be working completely with Python, just to reiterate for you guys. Now, you are going to require the understanding of Python syntax in itself as a prerequisite before watching this section. So make sure you're up to speed with Python. Well, even if you do not know Python syntax completely or the TensorFlow syntax completely, I'll try to break things down in the most simple way possible so that all of you all watching, regardless of being beginners, intermediate users, you guys will understand, right? Super. Now we'll discuss two important use cases, guys. One is digit classification using a super popular data set called as the MNIST, or we also call it as MNIST dataset, right? Done. Once we're done with that, we'll also understand and in fact take quite a deep look at understanding how convolutional neural networks work by performing some image classification, right? In fact, the first one is also a part of image classification, but once we take a look at it, you will understand the kind of images that we are trying to sort out there. Right, so let's get to the first out of the second demo that we have, digit classification using the MNIST dataset. Now, this is considered to be a demo which you really have to understand thoroughly if you're starting to build your journey in TensorFlow, right? Because once you're clear with really basic and simple datasets and understanding how you can work with these, later when you have an opportunity to work on really large dataset, it becomes super simple. Right now, the image that you see on your screen, for all the people who might have not been, who have not used MNIST dataset, it is basically handwritten digits. Now, it's common sense to know that not everyone has the same handwriting, right? Now, I might write 0, 1, 2, 3 in a very, very different way that someone else might do, right? Probably you just think about a couple of people, just find 5 people in your house, 3 people in your house, ask them to write a couple of digits and just compare if it's the exact same thing. The digits will be the same, the way they might have written the strokes, right? In fact, look at your screen right now. All of these are numbers and you will see, of course, with 0 to 9, we can have infinite numbers that we want, right? You can have 10, 100, all the way to million, billion, trillion, and whatever those numbers are. For all those numbers, you just require 0, 1, 2, 3 up to 9. Correct? Now you'll see, if you observe very closely, that all these zeros look very, very different to each other. All these ones look different. Twos are different. Even though we as human beings look at it and we're like, oh, okay, this is a 2. Even look at this. This doesn't look like a lot like 2. So if we had context, we would know this is a 2. If we did not, well, even as human beings, it becomes difficult. This is exactly the point here. If you have any handwritten document that you want your computer to analyze, and this is extremely popular in the world of, I think in the legal world, where you have a lot of actual hard copy documentation papers which need scanning, and computers need to sit and analyze thousands, if not millions and millions of these sheets and letters that are out there on those sheets, right? So it's super popular there, and your computer will be super confused if you give this value as a 6 and eventually ask it and train it with this and showcase what this is. It will say, hey, I have a low probability of thinking it might be a 6, right? If it gives you a 30% probability that it is a 6, well, you will be confused. Either your model is not working fine or whatever it is seeing is not a 6. Here, it is not both the cases, right? It is trained on something else. You're asking it to understand something else. Again, roll back to the same example where I told you your computer will understand only zeros and ones, right? Now, that is where you have to be very careful. What we are going to do is we're going to take an entire data set of each of these handwritten digits. We're going to take all these zeros, all these ones, twos, threes, up to nines, and we have separate files for them. And eventually, we will train a deep learning model based upon this. Now, once you go on to train a model, later you can perform an image classification operation, or you can perform an operation saying, hey, what percentage or what probability did you get whenever your neural network model figured the digits out correctly or incorrectly. You can train it, test it, and verify if it has learned something or not, right? And as I just told you, MNIST dataset is usually the go-to dataset whenever anyone begins their journey in the field of deep learning. Now, I'm not saying that you have to learn this to go ahead. Absolutely not. There's thousands and thousands of other use cases you can use to learn. But this is very popular because it just gives you a very strong foundation to understand everything that goes ahead, right? Fantastic, guys. Now let's quickly go back to TensorFlow that I have opened on Google Colab here and get started to know what it is that we are doing. Let me zoom out a little bit so that we have better readability, right? Guys, so we know what the MNIST dataset looks like. It's a couple of images where each image is a handwritten digit, a single digit, right? So we'll have to use a couple of steps to actually attack this problem and solve it in a structured manner. The first thing that we're going to do is, of course, import TensorFlow, right? Now, if you do not do this, wherever you see TF here, right? Basically TF.keras, TF. Model layers, TF.flat and dense. If you do not do this, you'll have to use TensorFlow dot as everywhere. So basically, we're giving it an abbreviation. We're telling Python, hey, import it as this. So wherever I have to use the word TensorFlow, I'll just replace it with TF and it'll work fine. Very simple, basic piece of code, right? Now, ladies and gentlemen, one thing you really have to understand about TensorFlow and MNIST dataset is that the dataset comes built in whenever you install TensorFlow, right? Look, even the people at Google definitely want you to learn MNIST. It's available on their official documentation, and this is the same data that you would be seeing there as well. So MNIST equal to tf.keras.datasets .mnist. So all I'm trying to tell the particular compiler here, the interpreter here is that, hey, just pull out this data set and bring it and call it MNIST, right? Now, the next part of the code where we're trying to say is we are loading the data and we are splitting the data into test and training this. In this case, we don't have to manually make a split because the data that we have at hand is already split into testing and split into training. Right now, as soon as I go on to hit play, so it will start downloading all of the MNIST dataset from the internet. Probably this is going to take a couple of minutes, 1 or 2 minutes, and eventually you will have it all downloaded and ready to get started with, right? So let's just give this a minute and let's tune back in as soon as it's done. And guys, that just took a minute of time and it is done. We have our values loaded and eventually our data set is ready to function. Now, what's the next step? The next step is you guys defining a structure to your neural network, right? We're using a neural network which basically has a couple of input layers, it has a couple of hidden layers and an output layer, right? Now, it can have one input layer, multiple hidden layers, and one output layer as well. So we have to give our program a structure saying, hey, use these many layers here and there. This is where we define the layers out here, right? Now you can see something called as sequential model here. The first question you guys are supposed to ask is, hey, so what is this sequential model? Sequential model is exactly what I just said. It's a structure wherein one input node can connect to any other nodes, and similarly this goes on as a one-dimensional chain all the way to the end of your output layer, right from the input layer, right? Having multiple layers in the middle is also possible. Now there's something called as activation function. Now, if you do not know what activation means, just make sure you're revisiting the theoretical concept, because if you want to use a methodology of understanding which neuron should fire at what point of time, you're going to have to give it an activation function, right? Now, more on this in the next demo that we're about to take a look at, because I'll be explaining how something like ReLU works there. So there you will have complete picture on this, right? But for now, understand that we have an activation function which is eventually squishing all of our values to a customized range to make sure that we can work with it. Now, why is this required? I will tell you when we're discussing the convolution neural network demo, because there I can show it to you with an example saying this is why. Okay. So at this moment of time, running this piece of code creates a structure. We are telling our neural network model that, hey, we want to be using the sequential model out here. We have a couple of input layers. We have a couple of output layers as well, and make sure that you're using the activation function. Which is the activation function? It is ReLU, or rectified linear unit. That is what ReLU stands for. Right? Fantastic. Now, whenever you're taking a look at the models, you have to understand what it is that your model is trying to do, right? So we'll just take a look at what the output is in terms of its predictions and in terms of what we can expect the model to do. As you can see, you will find an array here, right? So this array is basically telling us we have a lot of vectors on our hand. Now, remember the concept of scalars, vectors, and tensors that we studied previously here, right? So this is something what the prediction would look like based upon our training data set. Now, what we need to do is directly using these vectors will not be possible for us. What we want to have is a probability of each of these classes instead of having individual vectors at hand. Now, why is that done? That is done to make sure you have this kind of a continual network that is built in, right? It's not like one node will connect to only one other node in the network. No, just like how we have in our brain, one network can definitely connect to a lot more of these neurons as well. So to make sure we have a way to predict, to say which worked well, what worked, what not, which did not work really well, basically, right? So for that, we have something called as prediction. And in this particular case, we're using something called as softmax. Now, there are multiple ways of how you can perform prediction. And again, the most popular way for you guys to get started with is softmax. Here is one important thing that you have to understand, ladies and gentlemen. These are vectors with negative numbers in most of these cases. But if you take a look at after using our softmax, all these values are now positive, and of course they won't be the same because we're running predictions on them now. So it is fine. We understood from the first step, we loaded the data set, we understood what the model will look like physically, we understood what the output looks like in terms of vectors. We also understood we require the probability of classes rather than vectors. The next step is to make sure that you have a way to understand, you have a metric to help you tune the network out, iron it out, and make sure it is fine, right? For that case, we have something called as the loss function. The loss function basically is telling you how much of a mistake your neural network is making when it's classifying or whenever it's doing any task, right? To make sure that your neural network works really well, to make sure you score really well on your examinations in college, do you want your losses, do you want your errors to be at its maximum or at its minimum? Simple, it has to be at its minimum. Similarly here, what we try to do is we try to bring this loss value to its most minimal possible. That way, we understand that, hey, the loss of the model not able to understand what's going on is very, very less, and the accuracy will just go up. As the loss goes down, accuracy goes up. As the loss goes up, accuracy goes down. So it's an inverse proportional. Make sure you guys remember that. Now, as soon as I run these two steps, it is basically trying to find out the loss for each of these examples. And the current loss function that we are running is giving us a value of 2.4. Okay, this is what we'll have to get started with. This is not going to be the final loss value that we're going to have, because what's the goal here? The goal here is to make sure we bring these losses down to a complete minimum so that we have the highest amount of accuracy. Fantastic. Now let's just click on model compilation here, and as soon as I compile, you'll see we have another entity here called as an optimizer. And in this case, we're using something called as an Adams optimizer. Again, when we discuss the convolution neural network part, you will understand why all of this is required with an example on the screen as well. But for now, understand that there's multiple ways of how you can optimize the loss function. And why are we doing that? Again, to bring the value down. So as soon as I run this, we would have compiled the model. The next step is where all the magic happens. This is the step where we call model fitting. When we say model fitting, all we are trying to do is, give the training data to the actual neural network and get the neural network to actually, figure out what is going on. Train, this is the process where it actually learns. This is the process where it actually trains. Now, you must understand that this process of training is not it's not a one-time thing. You don't train once and you say no. Right? You keep training, you keep doing the same thing over and over again to get better. Similarly, if you're going for a run, if you're going to the gym, you would understand this concept. No matter what you do, if you keep doing it a couple of times, you'll get good at it, right? This is what the model is also trying to do. You see that we are trying to mimic human behavior here, but here we have a trackable metric to say, hey, you have to learn it these many times, and I want to track what's going on when you're learning it that many times. Right? Now you'll see a new term here which basically says epochs. Epochs, for all the people who do not know, is how many times I want this model to train. In this particular case, I've said, hey, please train the model 5 times. So as soon as I run this, it's going to take a couple of seconds here, and you will see that the entire model is training at each of these epochs. And let all the 5 complete, I'll let you actually track the accuracy and losses there, and you will have complete understanding of what is going on here, right? Now, 5 epochs are done, as in the model has trained and ran through the entire MNIST data set 5 times now, and when it did it the first time, the loss value was 0.29, but when it did it the second time, it was 0.14, 0.1, 0.08, 0.07. Ladies and gentlemen, do you understand at this moment of time that the loss is continuously going down with more and more epochs, and the accuracy as well is going up and up, even though the number is not that great of a difference. For example, 0.9728 and 9766, they don't differ a lot, but it means that more your epochs, more your accuracy. Is this always the case? If so, I'll just run this 10 million times and eventually have 100% accuracy. Would that work? This is where a concept of overfitting and underfitting comes into the picture, especially overfitting. When you train your model, when you ask your model to hunt so much into your data that it tries to find noise, it eventually finds more noise than useful information. This is the point where we call overfitting. What will happen, let's just say you're digging for treasure on a beach, you know where the treasure is, right? Now you're digging. Eventually, if you don't dig enough to get to the treasure, where treasure is at 10 feet, you've just dug at 5 feet and you give up. Do you get the treasure? No. That is underfitting. When you go on to start digging and you dig so much that you've crossed the part of the, you've crossed the treasure and you're eventually going further deep, and you don't have any clarity. You might just find a couple of coins here and there, but you will not find the entire treasure box. Similarly here, even though I might run it 25 times, there is no guarantee that accuracy will go up and the loss will go down. In fact, let us actually give it a shot as we speak. Since it's a very short demo, I can actually run this for 20 epochs to actually check if there is any sort of fitting that might happen, right? Now, now it would have run again. You'll see that the loss is also lower to begin with. The accuracy is already going up and up, 0.06, 0.057, 0.053, 0.48, and we'll just have to wait this out, right? 0.985, 0.986, right? So look at this. There will be a point of time where your gain will be very, very minute, and this is a very small problem, ladies and gentlemen. Every epoch is taking like 4 or 3 seconds at max. When this is the case, you can run it for any number of iterations you want. If you want 10,000 iterations, just put it and walk away. It'll finish and it'll be done in a couple of hours. But what if each of these epochs takes a couple of minutes or a couple of hours, right? This is the reason you would have heard the common statement where people say, hey, you require a very powerful system to run with TensorFlow. Sometimes you require a very powerful graphical processing unit to work with as well, right? That's the reason why we don't want to overwhelm the computer that we have at hand. Now, look at this. Here is exactly the situation that I told you, right? One situation is that these two accuracy values are exactly the same thing, right? In fact, the loss just went up here and the accuracy remained the same. Here is another fantastic case where your accuracy was 99.17%, but later it came down to 99.11% because here it has started hunting more into the data where it does not understand what exactly is going on. In this epoch, it is getting confused. But of course, since it's a very simple data set for a super powerful library like TensorFlow, this is literally nothing. It is no match for it in any regards. So you will see that, hey, even though we thought that one or two places it might get affected, of course it did. The loss initially that we started and the accuracy that we started initially is gone. The loss has gone comparably down and the accuracy has gone up from 97% all the way to 99.24%. Now, whenever you're working on this, it is very easy to get carried away. You can say, hey, Anirudh, it looked very nice that we did it for 20. Can you do it for 35 also? Ladies and gentlemen, you can actually work on these codes side by side, and I want you guys to give it a shot. See what happens when you run 50 epochs. See what happens when you reach 100 epochs, right? It'll take a couple of minutes. Every single epoch is 3 or 4 seconds at max, right? So I hope you guys understood one basic concept here is that no matter you can train something for days and months and on, it doesn't mean that it will get accurate. In this case, yes, there was 1 or 2 gains that we made, which is good enough, but this is very common to happen. Your loss will start going up again and your accuracy will start going down. Why is it the technical term? It's called as overfitting, and your model just runs through noise rather than useful data, right? So once we have trained our model, once we are done with this step, it's almost like you guys have your textbooks for your examinations if you guys are in college or school. So you can take a look at it, you'll be reading it, and eventually you'll close all of it, keep it outside, go write an examination. Now with model evaluation, we're basically giving an examination to our model saying, hey, you have never seen testing data before. It has seen what? Training data before, and testing data is brand new to it. Just like how you will find questions on your examination. So as soon as I give it this data, it is basically trying to find out if it can understand something at its accuracy. Look at this. This is absolutely fantastic, right? We have a loss of somewhere around 0.0950, and eventually our model is giving us a 97.98% accuracy. Now you can tune it to multiple epochs, you can evaluate to multiple levels of accuracy that you require, but it's a very simple data set. And if it's somewhere around 98, right, this is a percentage, ladies and gentlemen. 0.97 basically means 97.98% is the accuracy. What you can read about it is that if you have the MNIST data set, if you give it 100 digits, out of which it has the complete accuracy to give you the output for 98 of these correctly. So if you give it a 1, if you give it a 2, 3, 4, 5, if you give it all these digits like this, if you give 100 digits, 98 of them it will predict perfectly. 2 of it, it might get confused, right? I mean, we saw the digits. The 6 doesn't look like a 6. The 2 doesn't look like a 2 at all. If we as human beings can get confused, imagine the state of your computer. That is the reason why MNIST is a fantastic challenge. Even though it's a very simple one, it will help you understand how this entire process flow works.
We have covered artificial neural network and discussed TensorFlow. You now have a solid understanding of these two powerful frameworks that make building and training neural network more accessible and efficient. Next, we'll introduce you to computer vision and explain how machines interpret and process visual data. Then we'll explore OpenCV, a powerful tool set for developing computer vision application. Finally, we'll cover convolutional neural network, the backbone of modern computer vision tasks, and see how they revolutionize image recognition. Let's jump in and see how you can leverage these tools to push the boundaries of what's possible in your projects.
The short definition of computer vision is when a computer or a machine has sight. To get a little more technical, computer vision is the process of recording and playing back light fragments. The importance of computer vision is in the problems it can solve. It is one of the main technologies that enables the digital world to interact with the physical world. Keeping in mind the importance of computer vision, we have come up with this computer vision tutorial. Now, before we start off with the session, I'd like to inform you folks that we have launched a completely free platform called as Great Learning Academy, where we have access to free courses such as AI, cloud, and digital marketing. So let's get started.
That we talked about last week was how exactly sampling takes place here. Yeah. So if there is an image, I hope everybody is very clear. If I say image is 16 megapixel, or if I say image is 2 megapixel, or if I say image is 64 bits image, for example, or 644 bits or 64 bits or whatever. What does it mean is here there are more pixels. It means the array that is holding this is pretty big. It is of size 16 mega. And here the size is very less. So there is a problem in your current project. What is the size of the image? The size of the image is 32 cross 32, or what do you have taken? 120. 32. 32 cross 32 is the size. So 32 into 32 is what? 1024. Yeah. So it is okay for me to build a neural network which can take 1024 neurons as an input, and which can, do up and down of these things, and finally give me a classifier as an output. It's okay, not a problem. Correct? But what if now this was 16 mega? So when I multiplied these two, it became 16 mega. Now, is it possible for you guys to handle this? Yes or no? Can I have a 16 mega input neural network?
Memory problem will be there.
It'll be a memory problem, it'll be a computation problem, cost factor. A lot of things comes into picture. Agreed? So in this case, what do we do is we don't go ahead with simple MLP or FCNN. Guys, what is MLP?
Multilinear perceptron.
Correct. Multi-layered perceptron. Okay, which is nothing but another name of FCNN itself. Okay, so please don't get confused. I have seen many people, they say MLPA and FNN and all, they mean the same thing. Perceptron is nothing but a neuron. Whenever a neuron goes into hidden layer, that becomes a perceptron. God knows why, but this is what it is. Okay. Now this becomes very difficult to compute. So now what are we doing is, what if we just saw, we had a Python code, beautiful Python code we are writing. It is working good. What we did, we went on to a new software, or especially me, went on to a new software, and we got a diminished version of it, which does the exact job as what it does. I will say not as effective as this, but yes, at least I can say if I'm able to achieve 70% of what it does, I'm very helpful. Why should I code? I should directly do this. Why should I waste my time on coding? Agreed, everybody? So same thing you can imagine about images. What if I don't want to scan the whole image? So let us say this is an image, and there is one person standing in the image. Okay. Ignore my drawing. Yeah, let us say this is a person, and there is a flower over here. There is a flower pot over here, and say there is one picture. In that picture again, there is an image. Okay. Something like that. Let us say we have this. So if I ask you guys, what is the information that you guys can derive out of? You will definitely tell me that there are 3 spots of information. First is, there is an object, which is a frame. There is an object, which is a flower. There is an object, let us say, which is a pot. There is an object, which is a face. That's it, you can derive out of it. Let us say you've got 4. So if you tag this up, if you remember what do I mean by tagging? Your current project has got taggings. Agreed? Here also we have taggings. I will say object. I will say person. I will say object. Okay. Now there is chances, if you have designed it very nice, it will detect a person out of this also. Yeah. So if I want to do this, I do not have to scan these other empty parts. I hope you people are getting it. I don't need to scan this. What if I design small filters? Okay. What are these filters? These filters are some random filters, like your random weights that you have chosen or you have seen usually. Let us say these are some weights, some filters, which when you multiply with the whole image, we are able to get a diminished version of this whole thing. So there is a possibility that what if I multiply this filter to this, okay, and I will get one I will get lot of diminished feature maps like this. I can call this as a feature map. I can call this as a feature map, feature map, feature map. Now, what if I use this as one image? Now, this could be around, say, 4x4 image, for example. What if I could use this into my fully connected neural network to do a classification? What if I could use this separately, this separately, this separately, this separately? So I need to run my fully connected neural network 1, 2, 3, 4, 5 times to identify these 5 objects. Agreed? So rather than running neural networks megapixel time, I'll try to find out some features so that I will be able to classify them.
Yes, Krishna, clear.
Perfect. So this is what is your neural network. Convolution neural network. And this is what we are going to do down the line. So in convolution neural network, so whenever I say filter, you people should completely understand that we are talking about convolution. Post this, there are a lot of things I will show you down the line. And always a convolution neural network is backed up by a fully connected neural net. So this is not leaving us anyway. So whatever you guys have done in the first session or first module will remain with you guys through this complete convolution module. Okay, perfect. So now moving on, what are the other things I was talking about? So I will just show you directly that particular page. Okay, let me be fair now. Let me not be rushed because we have got good amount of time today. So these are my filters, which I am giving it to my image. Yeah, so my white portion I have named it as -1, and the colored portion where 1 is written, I have put it 1. When I multiply, I'm going to get a diminished version of this. So if you want to see what do I mean by diminished version, this 3x3, which is 9 numbers, I have diminished to one number called 0.33. If you still want to understand how it does it, I'll show you one small GIF which does it. Guys, just observe the GIF on the right hand side. A 5x5 matrix is now diminished to 3x3 matrix with one convolution. Everybody's okay with this? How we got this one number, I will show you. It's a formula, very simple formula. Manual multiplication is needed. Okay, so yeah. So this is what we have done. Good. Now when we did this, we got 3 matrices like this. Okay. Post that, this matrix, whatever we got, we will transfer it to an activation function, say ReLU. Now as soon as you pass through ReLU, you people know that zeros and anything below 0 will be omitted. Remaining, whatever is left will be processed over. So now I have got this as an output, and whatever I have hidden, that means it will be moved out of this matrix, negative numbers. Moving on, there is a technique called pooling, max pooling or average pooling that I do. I'm still not happy with this. I want to still diminish this image. So this is now, I will say 7x7 image. Now I will say the size of my filter was 2x2. So in this case, I will do a max pooling on this. I will say, find out the maximum features out of these 4, maximum number out of this 4. Obviously it will be 1, 2. This is called max pooling. So the whole 2x2 matrix now is represented by 1x1. That means I'm dividing the whole matrix by 4. Agreed? Guys, simple. Instead of max pooling, you can even do average pooling. Average pooling means take an average of all 4 of them. Put it over here. All right. So do it. Pass this filter to each and every portion of this matrix and do it. Good. So this is what it is.
So is it always 2 by 2 that we have to take?
No. It can be more than that also. We have to define that.
Okay.
We have to define our max pooling thing. But usually we take 2 by 2 because it is easy to decide. And let us say if we take 3 by 3, it will be this divided by 9. So there is a possibility that we might lose a lot of pixels out of it. Do you agree we have lost some pixels here? Information?
Yes.
Yeah. Now, why is this? So why am I happy with this? One question to all of you. If you people got this pooling part of it, quick question. What is the use of doing? Like, we are already happy. We have already diminished the matrix. We are happy with it. Our neural network can take it. Still, why are we doing this?
Optimization.
Sorry?
Optimized version of
Yeah, correct. But why? Still, why I want more optimized?
To prevent overfitting, kind of.
No, not exactly here. See, I'll give you one very simple example. Say I have currently I have 5 batches under me. Okay, all are my AI ML batches on. Now, from this 5 batch, if I want to, let us say there are 4 candidates who are the top performers. For example, let us say candidate number A, candidate number B, candidate C, candidate number D. From all 5 of them, let us say something. Now, if I want to represent how a batch looks like on an average, or what is my strength of my batch, can I say I will pull out the best out of these 4, max pooling, or I will take an average out of these 4 and pull it? Correct? Yeah. So what does it mean is this particular 4 things, when they come together, they kind of represent a single region. So it could be, let us say, an eyebrow of a person, like this. Okay, where if my scanner has gone onto it, or if my, say this is my, I will choose one light color. Okay, say this is my convolution. Say for example, we are talking about, say this is a face. Okay, imagine this is a face, and say these are my eyebrows onto that. Okay, now what am I doing is, let us say my scanner is currently hovering over one of the eyebrows, something like this. Yeah. Now, what if I'm doing max pooling onto this? What does max pooling do? We just saw it'll take the best feature out of it. Do I need all the features here, or do I need the best feature out of this? Can I say here the best feature is nothing but the black portion here? Let us take and pull it out, saying that when I scan through this, I find out this particular location, the color of these images black. Very simple. Note it down. So in future, when you are giving a new image, when this is going through a newer image at this particular location, if max pooling pulls out black, that means this image and this image is perfectly same. Let us say this person, I know it looks scary. Let us say this person has got one, what you call, mole on his face. And when in future you compare it at this particular location, definitely this mole is going to be there. So it's going to understand that yes, it is a same image. A very high level view, guys. We have not dived deep. Just trying to understand you guys that sometimes what happens is when you try to think that, okay, we are removing the pixels, not actually we are taking the best features out of these pixels. Take it that way. All right. Any questions onto this?
But Krishna, we might lose the information, right? And in images, mostly it's like black color is more dominant in any ways, right? So if there is anything that is having less information but also significant information, we might lose it, right?
Yes, kind of, yes. So that's the reason what we do is we strike this, we make sure that our filter that we have designed here, it goes through, let me change the slide. Yeah, I will make sure that the filter that I've designed, first of all, I'll make sure that I have done a good sampling. I have not done a waste sampling, first of all. And also I'll make sure that my filter goes through almost everything. I don't lose any of this. My filter gets multiplied with everything of it. Okay, so you are kind of right. Yes, when we try to diminish something, it happens. But also on the other side, when we oversample it or when we do a good sampling, we will not be losing any pixel in this case. All right. See, what do I mean by sampling? I will give you a very good example. Let me open up an image. If we have an image here, yeah. So there are chances that when I do some type of sampling, one pixel could look like this. And also there are chances that when I do very good sampling, one pixel might look like this. Also, if I try to do more sampling, one pixel could look like as small as this dot. So if I have good samples like this, more samples, it will be easy for me to remove certain part of it. It's okay. Because if you observe here, the same color propagates almost through a complete top part of the frame. Agreed? Yeah. So if I remove 5 to 10 of them, doesn't matter. Pixels. Yes.
Yes.
So guys, be very frank onto this. Are you people able to visualize or not? Because if we say, like, if we don't question right now, no, then down the line in second and third week, we are not going to go back onto this. So please be very clear onto that. Whatever I'm saying, are you guys able to understand? Amit,
So
Akash.
I just have one question, Krishna. How about the samples? Is it like, because we might have like 1 lakh of samples provided to us in the data. However, it might be an individual image which might not give the correct representation of that data. Could be like nose is coming on the left or it should be on the right in order for uh, augmentation and flipping and all those things. So how do we ensure that the samples are right in place as required for our analysis? Because we cannot check all the 1 lakh images if we are provided with that, right?
Correct. Correct. So for that, we will see something called metric learning in one of the weeks. I think it's almost last week of this month, where we'll try to find out the distance between the two images, how far they are. Similar images, but how far they are from it. Okay, a very good question. But let's hold on till the last week of it. Yes, we'll cover this also.
Sure, but I am clear on this, Krishna.
Perfect. Because this is one topic where majority of my batches, they don't get it, that how by filtering or multiplying a filter we are able to get an image. Okay, good. Second application I will show, why CNN. So if somebody will ask you why exactly CNN, so you can give a very simple example is whenever I show you, let us say if you look at a car, and let us say the car has the front part of the car is like this. 1 minute, guys. Really sorry. Yeah. Say the front part of the car has got 2 openings like this. Yeah. And definitely we know what car it is. Let us say this is a BMW, for example. Just imagine this BMW. Okay. Yeah. So do you go and check the car? Let me check the wiper. Let me check the steering. Let me check the hood. Let me check the seats. No. Visually, if you want to identify something, immediately from the bonnet, down the bonnet, when you look at these filters, you will get to know, okay, this is nothing but a, BMW. Also, if you look at the Audi part of it, right, and the filter, you might find the 4 manuals. So definitely this is enough for me to identify image. Same concept, you bring it onto computer vision. You don't need to scan the whole image. If in case you want a generic scanning happen. Let us say, I'll give you a very good example. I am currently working on this project where this is for my gated community there where I currently live. So we have got an app called MyGate. And what does this MyGate do is it helps us to track the vehicle. So somebody is coming in our community, it has to report, and there is a notification sent to the owner that somebody has come to meet you. Do you allow or not? We say yes. So everything is manual. The security guard has to get the name of the vehicle, get the type of the vehicle, name of the person, lot of things. Now what we have done is sometimes also it gets unnoticed because the person who's coming from outside doesn't know. He directly walks into it and security assumes that, okay, he's a part of the community. So sometimes they go unnoticed. So what currently I'm working now on is, let's install 2 cameras, okay, which will try to snap a picture out of these incoming cars. And as soon as they take a snap a picture, they should be able to locate where the number plate is. And if you remember your current project that you are doing, we can easily identify the numbers out of it. And from my central database, we'll get to know whether this car belongs to the community or is not in the community. If it is not in the community, the gate, let us say over here, there could be an automated gate which will open or close because of these triggers, for example. Okay, so far I am able to identify. So if I take a webcam and run around through the cars, I'm able to get the number plates. So I will show you guys shortly once you guys understand what I'm talking about. So probably second or third week of this session, I will show you this, where we'll take a webcam and we'll try to identify objects out of it. Okay, good. So this is what it is. So what I wanted to show you guys here is sometimes in computer vision, you don't have to identify the whole image. You just have to focus on certain part of the image. That's all. If you get it, do it. And how do we do it? CNN will help us to do it. In CNN, we don't scan the whole thing. We don't need the whole thing as an input. We scan certain parts of it and we take it as an input. And sometimes some of the parts are perfect image that we want. Good. So this is one example of CNN. I will give you one more example where this is used. Nowadays, if you go to these metro cities, there are malls. In malls, there are parking lots. And now right in front of the gate itself, the display. How many slots are empty on which floor, which level, and what size. Good. Earlier, what they used to do is they used to put sensors over here. So if there is a weight on the thing, it is car, there is a car. If not, there is no car. Actually, the sensors are very costly, and during maintenance and all, they get destroyed. They have to embed it such a way, very sophistication has to be followed over here. So now what they do is very simple. They put a camera. If they find some other color over here, that means there is a car present. The slot is not empty. The counter will be 0. What is this? This is called semantic segmentation. This is your week 3 content that we are going. We don't care what it is. We just see that there is one background color and there is some different color on top of that. Done. Over. This is occupied. I don't need to know what car it is, what color it is, what shape, size it is. That's not our application. Good. So this is where convolution neural networks will come to our help. Good. Now coming on to the weekly content. So this was a little extra. So all we do is we take the image, we go through convolution, we go through ReLU, we go through pooling. Again, we go through convolution, ReLU, pooling. If you still want more, you can go through normalization, your wish. Okay. After this, what did we get? There are 2 layers of convolution. What did we get? A bigger was converted into a smaller. Now, next, what to do? Next, flatten them up and push them on the fully connected neural network. That's all is your CNN. This is your flattened data, and just ignore this. 0.66 means 0.55. Actually, it's an Excel screenshot. So it did not do decimal adjust over here. Okay, so 1.55, 0.41. They are flattened completely, and that flattened thing goes here, and you know what happens here and how we classify it. That's it. That's all is your convolution neural network. And when you bundle all of these together, this is how it looks like. Image, convolution, pooling, convolution, flattening, and your fully connected neural network, or MLP, whatever you call it.
So, Krishna, I have a question. How many convolutions and pooling should we do?
Correct.
Is there any recommendation, or how do we determine when to start doing the flattening?
Yes. So there is a formula we are going to see down the line, which will help us to do this. But frankly speaking, I will tell you, what you have to do is you have to determine what should be your input here, first of all. And from there, we will go down the line. Okay. So if you want, say, 64 inputs, that means your flattened should be 64. And if, let us say, you are having, say, 10 features over here. Let us say 10 windows over here. Now, each window should be what? If you divide 64 by 10, you will get 6.4, which is not a good value. So what in that case, what you do is you make it 8, for example. So 8 8s are 64. So it could be 2 cross 4 each one. Or you can say 2 cross 2, many number of times. I think 2 cross 2, 4, 4 to the 8. I think 8 number of times. Good. I'll show you down the line how to do that. Don't worry.
Hey Krishna, can you repeat it? I don't think I got that.
See, what was the question here was how many times I should do this, plus what should be the size of each filter and all those stuff. So it completely depends on my input, first of all. So what you are planning here. So let us say you are planning an input of 64.
Right.
If your flattened data is 64, how many filters I should have? This is what the question is. Yeah. So how do we devise this now? So take the reverse engineering concept. Let us say if my each filter is 2 cross 2 in nature. So 2 cross 2 means how many numbers I have? 4. How many more I need? 16 fours are 64, right? No.
Yeah.
Yes or no?
Yeah. 16 for the 64.
Correct. In that case, I need 16 of these. 2 cross 2.
Okay.
Yeah. So now go reverse. If I need 16 of this, how much should be my previous value? How much should be my previous value? We'll keep expanding. I'll show you down the line. But this is what majorly we do it.
Okay.
Also, one hint for all of you is very less models we are going to use this. We are going to use ready-made models. VGG, AlexNet, GoogleNet, MobileNet, ResNet, RNN. Sorry, not RNN, RCNN. We have ready-made models, huge, big models, which can handle values up to 6 million parameters. Very few places we are going to do this. Okay, because now no, we don't want to take burden of this. Something like our KNINE, crime tool today. We already have ready-made models by some of our famous companies. Why not to import it and use it? Okay, good. Perfect. So overall, the whole module, what you will do, you will be given an image. You should be able to identify, first of all, the image. You should be able to detect the image, first of all. And post detection, you should be able to identify what it is. It can be a car, dog, human being, cat, object, anything which I give you, you should be able to do it. So just what do you say, overview to all of you. This session or this module will be around 7 to 8 weeks, to be very frank. It has got 2 projects into it, back to back. The first project will come after your 4th week, where you have to detect an object. You have to create a boundary around the object. And the second project is you have to check whatever you have created boundary around, what it is, what type of object it is. Good. So by the end of 8 weeks, I will say, or else 2 months, you should be able to be good at computer vision. You should be able to at least implement basic level of computer vision from your side, from scratch. Plus something extra from my side, I will show you simple versions of this. I don't want you guys to go and code huge. It's good, nothing wrong, you do it. But also what we do on industry side, I will show you smaller codes. We use ready-made models to do. Plus, I will show you something extra which is not covered here, which is called video, image identification, continuous image identification, CIA. Yeah, that could be a very good application, especially if you are from manufacturing industry, building industry, or I would say majorly onto construction industry. Some last time I gave you some examples from my side onto testing industry. So still we are exploring how to use this opportunity. Okay, good. Especially if you are from retail and manufacturing, this will help you a lot. I'll tell you frankly, I currently interviewed for one of startups who were into I will say manufacturing, and they were from a QA team, so they've got a very big project from one of these large automobile manufacturers where they want to pinpoint from their manufacturing line which product is defective just by looking at the image from the camera. So let us say there could be a lot of high definition cameras attached. Earlier what these guys used to do, they used to pass this stuff from UVs, or they will pass a laser light to check the deformities and all. But now, looking at the image itself, they want to predict it. Okay, a very sophisticated portion of this. Good. So day by day, this stuff is going on and it's evolving. So by, let us say, I'll tell you one more thing. The timeline for computer vision is at least it will take for you guys 6 months to get normal to this and start applying onto real time. So by then you can say this will be a learning curve. So please be very patient with it. It is not a simple concept. Okay, what is it we discussed? Why we discussed? Because of image size, cost, and all. We are doing this. More or less, this is what we saw in my handwritten image diagram where you have an image. You take a feature out of this, convolute it, flatten it up, put it onto a fully connected neural network, and get a prediction. So if you observe here, we have a prediction called car, truck, and van. Yeah, good. All right. How I just explained you how we do it. So please remember one thing. This is your static layer, forward propagation layer. This is your forward and backward propagation layer for learning. All right. So this is your classification layer. This is your feature learning layer. exactly where image processing is used. As I said, a lot of possibilities. One, as I said, could be onto something like object detection in any industry is good. Something like comparison. So nowadays, our government is using this, to compare images, find out a lot of things. So this is usually used by Interpol, FBI, and all. We would have seen in movies also, where they compare two images and try to find out what is the best match and try to find out where they are. Third application could be into retail industry, where let us say there is a product which is displayed on the website and there are a lot of attributes attached to it. Let us say there is a phone. So 2 GB RAM, this, that, and also. There are certain attributes which need to come from the technical person. But there are certain attributes which you don't need to manually type, like color, shape, size, what it is, which company it belongs to, a lot of things. So those things which can be easily scanned and put, they are automated. So some of my friends working with Amazon, Flipkart, Reliance Trends, and all this, that's what they do. They are hardcore into computer vision onto this cloth, objects. So whatever they see, they put it. So for example, there is a t-shirt which is displayed, let us say something like that. They can find out it's a V-neck t-shirt, is this color, this could be a probable size. Yeah, so some application. And then the final one I will say is onto reinforcement learning. Google car, Google glasses, a lot of examples you can take it up from this. Yeah, so it's a combination of computer vision plus reinforcement learning. Where what is reinforcement learning? It takes an image and learns it. It does not have to do all this. If it is not in the corpus, it should not reject it. It should try to understand what it is. Good. Okay. So these are the applications. Any questions onto this? Anybody wants to know anything more onto applications specific to your industry where you can use it? Do let me.
So, Krishna, have you come across any such usage in terms of HR services or payroll services industry?
Payroll. Yes. I will not say purely payroll, but yeah, one of my seniors has worked onto one domain. I'm not sure how relevant it is with your. So let us say there are a lot of invoices processed, no? Yeah. So from these invoices, they try to pull out the numbers they wanted. So might be you can do something onto your. Is it anything related? I'm not sure. Huh?
Yeah, so we have some kind of requirement right now in our company, but I don't think it's assessed fully of the capability.
Mm-hmm.
But it goes like this: so we get new clients, right? When it comes to implementation.
Mm-hmm.
So rather than going to clients asking them questions about how the current system is designed and what components, payroll components do they have, we actually scan the employee sample payslips, and from that we could determine that these are the components that are there and how they get calculated. The formula and everything gets derived out of that values that come.
Okay.
But it was a failure earlier. But if there is something that you have seen from your market industry or someone of your friends have worked in similar kind of.
Yeah, let me show you right away. I've got a very good example for you. Could help you. Okay, I'm not sure exactly what you're looking at. I have worked onto one of these where we try to pull out certain tags or requirements out of a document. So it was something similar to your thing, you can say. Just give me a minute. I'll not show you the whole case study because it's a part of your next module anyway. But give me 1 minute. Module number 10, NLP. I just finished this code, so good time to see it. If you observe here, I'm able to tag certain words out of this. Yeah. So you can, in your application, I will say you can use partly to identify the text, partly as a text processing. And wherever you find a formula or a process or something which has got functions and all, you can use NLP to find out which is the closest it belongs to. So for that, you need to have a very good corpus. Huh? Corpus is a backend data. You need to have all possible formulas. I hope that's what I'm talking in sync with you. Yeah.
Yeah. What I was trying to understand is there any way where we can have a mixed kind of database having images as well as the raw data that we get, which we were looking into machine learning databases?
No. So you need to have two separate corpuses. One is for text, one is for images. Separate.
Okay, and we should be able to correlate this too, right?
Yeah, definitely. If you want to work on this, no, do me a favor, give me some sample data. I'll not expect the whole data from your organization. Give me some draft, fake data, which you think is in sync with that.
Mm-hmm.
We can work together on this. Not a problem at all.
Okay.
I have done something onto text purely, but yes, we can include the images and we can combine both of them and tag it.
Okay. I'll try to get you some sample data.
Perfect. So what I do currently is I have done one of these implementations where we scan RFPs. Yeah, and we try to pull out requirements from RFP using image processing. So we can, using text processing. We can say which requirement is a functional requirement, which requirement is a non-functional requirement, which is a business requirement. Under functional requirement, what possible they are talking about? Are they talking about automation? Are they talking about functional? Are they talking about unit? Whatever it is. You know, it's very easy to pull this stuff out. The only thing is, luckily I've got a good corpus for this. Yeah, so I can do that. All right. It's a shutdown for me. One minute, guys. I'll just restart this. Okay, this is one thing. Anyone else? Everything is good then? Yeah. All right. So let's see what we can. What is planned for this particular session is we'll take an image and data structures and types. We'll see to it. What are they? Convolution filters, kernels on an image, convolution neural network versus fully connected neural network, convolution layers, average, max pooling. We'll see this, and forward and back prop in CNN. Yeah, good. So I think we've covered almost everything. Now let's see what type of images or what pixels can consist basically. So we can have gray or we can have an RGB or grayscale. Now if I give you an example, what do you mean by grayscale is, in here, the lowest possible value for pixel, let us say 0, and the highest possible could be 255. For example, 0 could correspond to white, 0 could correspond to black, 255 could correspond to pure white. And whatever numbers you see in middle will be the different shades that you are seeing. Okay. Good, everybody gets this? Yeah. Okay, so now moving on, what about this one? Here also same stuff. Here we'll have 3 different channels. One is called red, one is called green, one is called blue. Okay, let me go a little neat. Again, I started scribbling red, green, and blue. What are the numbers over here? Same thing. 0 could be darkest green, 255 could be lightest green. Yeah, different shades of green you can observe over here. 0 could be lowest blue, 255 could be highest. 0, 250. Now you may ask me, okay, fine, then how do I mix match? How do I get one color? So if it is purely green, we'll pick it up from here. But what if it is a combination of all 3 of them? In that case, there is a special function which will give us a calculation between all 3 and give us one number, which will correspond to one of the color matrices which is stored in our computer under computer vision. Yeah, so if you guys remember, there is a special type of plotting function called IMShow. Yeah, in that you put any matrix of your choice. Say create a 64 cross 64 matrix of your choice, no problem. You put it and try to plot it using IMShow. It will definitely give you some or other color out. So what does it mean is there are some predefined values stored in the computer which takes up these values. Okay, so this is what is 2 things which we'll deal with. Next, moving on, what type of images we can see. So we've got 2D and 3D matrices. What is a 2D matrix? A 2D matrix is your M cross N. And what is a 3D matrix? So I will say grayscale image could be a 2D matrix and RGB will be a 3D matrix. So in that case, I will say 32 cross 32 cross 3. That means it is a 3-channeled 32 cross 32 image. And if you want to make it 4D, I will say, if you remember in your model, we have 42,000 images, 32 cross 32. And that is a 4D. But don't take it up as a 4D, you know, we can ignore the first and the last part. 32 cross 32 is what we are interested in. Yeah. And please remember, pixel is the lowest form in which an image could be represented. It depends all on us how we are sampling it. If you want more samples, that means if your image is 16 megapixels, it has more information, it is more sharp. If the same image has 1 megapixel, you can understand how blur and vague it will be. If you want to see how it looks like, a very lowly sampled image, look at this. This is how it looks like. Each square over here represents 1 pixel. I could have done it in a very simple way also. Each dot over here could represent 1 pixel. In that case, what would have happened? We could have easily been able to see his eyes, nose, mouth, and beard. Look at the blurriness. Okay, so if you look at this, this is how an image looks like on the back end. So this is your front end. This is how we give numbers to this image, where black is 0, anything which towards white is 255. Now you can check it out. Look at this value and look at the darkest value. Where is it? Look at this value. They're perfectly sync. And then you remove whatever it does, and this is how it looks like on our Python side, backend part of it. Okay, what if I want to normalize this? I'm not happy with 0 to 255. What happens, guys, in that case? What we do is we divide it with the highest value. What will be range? What will be my range now? Can somebody spell it out? If I divide or if I normalize this, what should be my range?
Between 0 and 1.
0 and 2.
Perfect. Between 0 and 1. Very simple. This is how a digital image is processed in the backend part of it. Now, if you want to understand how a filter works, very simple. Just look at one particular corner of this image is being scanned or multiplied by the filter. This is my filter, and once if the filtering finishes, this is what we get out of it. So a 3 cross 3 is becoming one number. I can say I have divided the whole this thing by 9 basically. Totally 9 numbers are represented by one number. This is what is my convolution. And how does it happen? If you observe here, very simple. -1 into 3 plus 0 into 0 plus 1 into 1. Like that, you do it for all the rows and columns. At the end, we'll end up with -3, some number called -3. If you ask me what does this number represent, I will say it's just a pattern. So when I pick up one feature out of an image, the answer for that pattern or that image is nothing but -3. So tomorrow when you get a similar, you get almost all the numbers similar down the line to another image, you can say that this image and this image is perfectly same. Future. Okay, perfect. So moving on. Now there is a thin line of difference between convolution and correlation. So just now we were thinking about, okay, what is this filter? How do we decide this filter or not? Again, I will say filter is, let us say, some randomly chosen 3 cross 3 matrix here, for example. So what is the difference between correlation and convolution is? In convolution, what I do is, it is in correlation also we multiply, in convolution also we multiply. The only difference here is every time you want to use a filter, no, you flip them. You flip them. You don't use the same filter every time. You keep flipping. Now, what do I mean by this? Let me show you an example on this. Let me restart my kernel. Yeah. Okay, so let me take you to that place. Yeah. So let us say this is one image given to us. Okay. These are the filters that I am going to multiply this image with. So have a close look at this particular filter. This is how it looks like. Now, just see what I do. So when I change, sorry, I'll show you guys how do I play around with these numbers and all. What I'm doing is both my extreme vertical ends, I'm making it -1, -1, -1, and whatever middle values are there, I'm keeping it 1, 1, 1. Look at the original image. Now let me run this. At least I need to run this. That's it. Yeah. Now let's try to plot this up. Okay. This is my original image. I have changed my filters. Earlier, if you saw, there was a different filter. It was vertical stuff. Now it is going to become. Did you observe this, guys? Yeah. Just by changing certain values in and out, I changed my complete image, how it is interpreted. Look at this. Yeah. So just by changing these filters, I'm converting this image into this image. One more thing I'll show you. Let us say I divide this by, say, 14. For example, some random number. It will be blurred. Okay, 1 minute. -1, -1, -1, -1, 1, 1, -9. Okay, let's try to generate this. See? Yeah, and what if I remove this, for example? Yeah, the complete image is changed. So please remember, when a filter changes, definitely the value of your pixels inside the matrix also changes, and because of that, you will get different images. So this is how we play around with images, and this is how what we mean by filters. Okay, good. So now let's see this one. Did you people see the implementation in the weekly video onto this, or yet to do it? Do you want me to do this image processing basics, or we know this?
No, we don't know this.
Know this? Okay, let's do it. See, very simple thing. We have seen this Snapchat, and what else we have? We have got Instagram and Facebook, and a lot of them now. If you just look at it, there will be glasses put on your face, or there will be some cap put on your face, or beard, and a lot of things are happening. And also sometimes it will try to change the color of the image. How do they do this? Very simple. Only they have to do is they have to design one filter like this. That's it. Okay, so this is an example of a simple filter. You can imagine they have designed a little bit bigger filter, such a way that they change certain background in and out, and they try to understand that this is your face, remaining things is not. Okay, so if I multiply this image with this thing, we are going to get this. Now, what is the pattern here? If I multiply this, if I want to sharpen an image, this is how I'm going to get. What is sharpening? You are highlighting the hidden features out of the image. This is what I call it, sharpening. If you want to do edge detection, this is how you are going to do. So you will see only edges over here. Okay. Where do you think we need this, guys? Just try to think about it. Except this Snapchat and all I say, not those examples. Apart from that, anywhere else you are able to visualize we need this.
Augmentation.
Okay, perfect. Whenever you want to augment an image in your corpus, you can use this. Good one. Anything else? Anything else, guys? Okay. Let us say we are talking about something about into medical industry, for example. In medical industry, let us say you have a snapshot or a microscopic image of a person's cells, and they want to detect whether these are cancerous cells or normal cells. In that case, what we do is we pass it through one of these filters, such a way that we get edges like this. And from these edges, we might come to know how big is the size of a cell and all these things. Could be one possibility, and I've seen extensively healthcare using this nowadays. Nowadays, even the sophisticated hospitals that we go to, they can no need to show the X-ray to the doctor. X-ray machine itself tags. Let us say if this is an X-ray. Okay, this is an X-ray of some part of the body. Basically, it tags itself where is the problem. It auto-detects the problem. How? By this kind of machine learning or by this kind of computer vision learning. Okay. Also, I will say not only computer vision, you can use even our KNN and SVM also over here to identify these things. Very simple. Moving on, if you take the image of Lena, this is a very famous model. So when I was studying my engineering, all of my textbook had this image. Okay, same image used years on years. What is this? Take an image, put a filter onto that. What is this filter? Sharpening filter. Now, is this filter in sync with our earlier filter? Look at this filter, guys. 0, -1, 0. Okay, and look at our earlier sharpening filter. 0, -1, 0, -1, 5, 1. Okay, so wherever you go, this filter is going to be same. Now, what if I want to sharpen my image more? What is the possibility? What you can change here? Anybody is able to get the pattern?
5 needs to be changed to
Let's say 10. Good, perfect. So just understand the pattern, you will get the processing. Take this example, edge detection. Now, this edge detection, look at this and look at our edge detection here. Is it in sync? Not at all. What does it mean is it's not necessary always to follow the same. Yeah. In this edge detection, what we have done is we have highlighted the extreme edges with zeros and ones. And in middle, we are changing it to minus. Okay. Same thing, if you want to more sharpen it, what we are doing, we are converting the complete third row to this zeros to ones and this to 2. Here also zeros are converted to -1, -1, and this one is 2. And these the middle one are all zeros. In that case, you will get a sharpened image like this. This is also sharp, this is more sharp. If I want to go one more level above, I could have done -2, 4, -2, 0, 0, 0, 2, 4, 2. It would give us a better one version above the sharpness. Okay, perfect. So this is what majorly in and out we do onto image processing, filtering. Now you may ask me, okay, fine, why did we do this? We did this because tomorrow you need to augment your image, or tomorrow you want to, basically compare two images. And let us say one of the images in some form, other one is in some form. What you do is you apply a single filter on both of them so that you bring them to a single level, and then you physically compare them one to one. Or you use distance formula to understand how far are the points. Okay, good. Perfect. So this was your image processing. Now let me give you one example on this. Let us say this is one image of me. Okay. Let us say this is one more image which I have taken. So this was usually, if you look at our ID cards, I don't know how many of you feel that. I have a 6-year-old ID card from Capgemini. Okay. If you look at my image before 6 years, and if you look at my image now, this is something like before and after. Something has happened to me, because of which this image is in no sync with what I currently look like. Okay, so let us say this is my old image and this is my current image. So let us say this is something on my ID, this is something which live my organization is taken. Now I want to say this is old and this is current. And there could be one more image from a person who looks almost similar to me. So I will say this is a positive image, this is a negative image. Positive in the sense it is kind of me, negative means I know it is not. What if I take this 3 separately through a convolution neural network? Say, what if I take this person through convolution neural network? Okay. I will get a set of matrix. Agreed? I take this image, I'll get a set of matrix. I take this image, I will get a set of matrix. Yeah? Now, what should I do to find out that these two are same where these two are not same? I need some patterns, right? I need something, some function. What according to you could be used here?
Facial features.
Sorry?
Facial features.
Yeah, but if you observe here, these are nothing but numbers. These are just numbers, some matrices. So what algorithm or what I should use here? Guys, you remember KNN? What was KNN? Yeah, I know you know KNN. Silly of me asking that. But yeah, what does KNN do? Distance? Yeah?
Yeah.
So what if I find out the distance between these two matrices? Give me one. Just have to plug in. Yeah. What if I try to find out the distance between these two? Okay. Let us say the distance between these two is alpha. And what if I try to find out the distance between these two? Let us say beta. Now tell me the relationship between alpha and beta. Guys,
Shortest distance
see,
between which?
see, when I subtract two similar things, what will be alpha? Can I say tending to 0?
Yes.
Yeah. And when I subtract two dissimilar things, this will be tending to infinity. Beta. So can I say alpha is always less than beta? Yeah. Or else can I say like this, alpha minus beta will be always less than equal to? Does it come to your, okay, fine. Let me not confuse you guys. What I was trying to say is, please remember at the end of the day, these are nothing but numbers. You can use any of your machine learning classification techniques to do this. Here, what I did was, here I use loss function as distance. We can definitely find out the complete distance and we can say which two are nearer, which two are far. So if I say, if if we say two images are similar, I will say, let us say the similarity should be around 0.5. So when I subtracted them, no, let us say I got a value of 0.29. That means the difference between them is 0.2, which is very less as compared to 0.5. I can definitely say that the distance is very less between them. But let us say when I compared this with this, I got a distance of 0.7. It is above my threshold value. So I can say that yes, both of the images are different. You can use even CNN into that level, very simplistic. You don't need to go and do all hi-fi stuff always. This could be as simple as this. This is called metric learning to CNN. Okay, so this is where you will need all this image processing skills sometimes to alter the data. I hope everybody is in sync with me. Yeah. Amit, Shakti, Akash, Dhruv, Harish, Kaushik, Kranti, Raghu, Vishnu. Are we good? Yeah. Perfect. All right. Great. So now let's see this case study where I'll say it's not majorly a case study, but yeah, some of the basic concepts which will help you to work on this. So what do I have? I have got NumPy. I've got skimage, okay, which has the data. There are some images pre-stored, and also it will help us to do some kind of I/O functions. Okay. Next, there are some predefined data sets which are stored inside Python. So inside basically a skimage. One of them is coins data. So I just have to call the data, coins data, and then push it onto image and find a type of it. So usually it is a NumPy array, because if you remember, I just said images are nothing but a matrix of numbers. Okay. And if you want to see how do they look like, first of all, if you want to see the shape and size of it, 303 cross 384 is that image, one image. This is how it looks like. So if you want to play around with it, if you want to see what is image 0 cross 0 has 47 numbers in total. Yeah, so this is nothing but your 47. Also, if you want to print the top, say print stuff from 100 to 150 on X side, and from Y side you print some from 25th to the 75th reading. If you do that and you print it out, you get an image like this, which is one of these what do you say, coins. Okay, now CMap defines what type of image it is. If you want a grayscale image, you can put a grayscale here. If you want a red, green, blue, you have to define reds, greens, and blues. I have shown down the line, or else let's do it 1 minute. Okay, so this is my grayscale. Okay, this is my image. So let us say if we say 0, 1, 123, say 0, 7, 1, for example, 130. Okay, so what do we do now is, let us say I want to show you a grayscale image. So I will say gray. Okay, in that case I'll get a gray one. If you want a green one, greens, we'll get a green one. Yeah, so these are some manipulations on CMap. Later on, there is one more set of image called data.coffee. So this is how it looks like. Now look at the dimension of it, 400 cross 600 cross 3. That means it is RGB kind of channel. Okay. Next is if you want to focus more onto the the red part of it. So what I do is I keep the third channel as it is normal, and I say reds. So for example, if I say greens here, okay, it is going to give me a normal image when it is green, how it looks like. That's it. I'm just changing the filter. Why? Because I have not imported the image here. Okay. If I want to make it more greener, if I want to focus more on the green part of it, so what do? Say I change this. Okay. So if I want to sharpen it basically from the green side, so when I print it, look at this. If I want to make it more green, instead of blue, I say greens. Yeah, it's going to become more sharper and sharper. So this is how we can play around with some of these numbers. Say I want everything, or else say I'm not sure. I've never tried this. Let me try. 2 from 1 to 3. Say 2, 3. I never altered the middle one. Yeah, good. Let's not play around with this. Yeah, so this could be some operations you could use it. Next is understanding the filters that we have shown. So this is one new image, and this particular image, if you observe, if you want horizontal bars, so this is the same image as this. The only thing is we have got a filter here. If you want to sample it, or if you want to edge detect it horizontally, the first and the last one, horizontal one should be -1s, other one could be 0 or 1, not a problem. If you want to do the same operation vertically, common sense, the first and the last column should be -1s, other one should be 1. Okay. What are we doing? Basically, we are multiplying this with our image. That's it. Next is if you want to sharpen if you want to edge detect it properly. So if you go to our PPT, the same filter is used for that camel. -1, -1, -1, -1, instead of 8. So let us say if I do 16 here, for example. Yeah, we have got back the original image almost. What if I reduce it to 2? Yeah. So at 8, perfectly it detects all the images and it does not show me black and white. You can easily see there's an 3D kind of cubes over here. Yeah. Second thing is if you want to blur an image. So if this is my original image and if you want to blur it like this, what you have to do is you have to multiply, or else you can say you have to divide something by 16 and multiply with an identity matrix. Or I will say not even 16. You can take any number here, say 1 by 5. Definitely you are going to get a blurred image as compared to this. As you keep going higher and higher, your blurriness is going to kind of vary. Yeah. Good. So this is what it is majorly onto your image processing part of it. Play around with these images, import your own image and try to play around with its filters and all. You will get to know. Now, one quick question is sometimes we are using 4x4 filter, sometimes we are using 3x3 filter. Okay, do not hesitate to use even 8x8, nothing wrong into it. The only thing is you have to know if you want what kind of feature you want out of it. That's it. Yeah. There could be many websites where these standard filters are defined. So you can download some of these filters and try to create your own values out of this image. Play around with it. If you're not able to find them on web, do let me know. I'll try to search. Okay. Good. So you can do some work on image, understand what it is. Now moving on to something complex now. So let's see how to do all this now, how to go ahead and do convolution out of this. So these all are the basics. Yeah, so just observe the animation that is happening on the right hand side. So on the left, we have got three bigger images where we are convoluting them layer by layer. So the first one was layer 1. Now we are doing layer 2 convolution. And finally, you will observe the green colored cells. These are the final outputs of your images over there. Okay, guys? And also you observe the right hand side how RGB is working onto it. Okay, so any image is nothing but a combination of RG and B, 3-layered. And finally, we are convoluting it and converting them into one particular value. So here 4x4 is getting converted into one particular value. So we are convoluting the image. Okay, good. Now, moving on, another simplistic version where you don't need to focus on all of them. So if you observe in our previous animation, we were going cell by cell. So if you see, we did not move anything extra. We are going to almost all the cells. Did you people see that? Yeah. Here, what are we doing? We are not going to all the cells. We are going to some focused areas, for example. Yeah. Now, how do we do that? There is some factor called stride. If you guys have seen your weekly videos, the professor talks about something called stride factor. What is stride? Very simple. If I have this, say 4x4 image, okay, just assume this is a 4x4 image. And if I have, I'll take a red one and take a dark color. If I say I have a 2x2 filter, this will be my first filter. If I say my stride is equal to 0, that means I have to immediately go to the next. But if I say my stride is equal to 2, so what I will do is, let us say this was, initially it was intended like this. Now, if I say my stride is 2, I will skip 1 and 2. I will go to the next one. So in this case, it's not possible because it's not there. But what we'll do it, just imagine there was one more column. I will skip 2 cells and move on to the next one. So these are the examples where you can increase the stride and focus only on to certain patches of your image. You don't have to worry about the whole thing. Okay, good. So this was your convolution. Guys, anyway, still this is basics only. I'm just making you comfortable with it. Now comes the real part. How to decide number of filters and this size and that size and all that. So please remember, you see two formulas here. One is called output width, one is called output height. And as I said, we'll go in reverse direction. Okay, so first thing is what output you need from your convolution layer. First question. So let us say from this whole image, if I just focus on this tires and let us say this door, it will be enough for me to identify that this is a bus. Okay, now that's not a problem here. The problem here is how to decide what filter size I should take about. So the first thing is I want to say I want to understand what will be output. So what you guys do is either you fixate on this or you fixate on this, whichever way you like it. We cannot have both the options. Say I fixate on my filter. Say for example, I use 2x2 filters 4 number of times, 4 filters out of that. My stride is equal to 2. That means I will skip 2 cells and move on. I don't want to do a very good sampling. Yeah. For that, what I will do is I'll take the width of my image, which is 32. Okay, minus width of my filter, which I have decided as 2. So 32 minus 2. So let me do it properly. 32 minus 2. 1 minute. So I will reduce the thickness, otherwise I will not be able to write. Width is 32. What is this width? Width of my image. Okay, a minus width of my filter, that is 2, plus 2 into padding. Padding in the sense, sometimes the image is not enough to scan because of our filter. We just saw just now when I was trying to do stride 2, it went out. So for that reason, what we have to do is we have to pad it up. Pad means add an extra layer of zeros around it. In our case, we don't need padding. So this will be 0, I will say. 2 into 0 is 0. Divided by stride. What is my stride? Stride is equal to 2. If you compute this, 32 minus 2 is 30. 30 by 2 is 15. 15 plus 1 is 16. This is how I got my convolution layer. Now, what I did was I froze this and I got this. What if you freeze this and you can get this? How? It's very simple. You say 16 over here and don't put anything here. So the equation will be 16 is equal to 32 minus filter width plus 2 into 0 divided by stride I set as 2, okay, plus 1. Take everything on the other side, you will get your filter width. So it will be 16 into 2 is 32. 32 is equal to 32 minus filter width plus 1. So I will set 33. Sorry, divide by, sorry?
First, I think you have to take plus 1.
Yeah, I did not take the LCM. Okay, now it's okay. Yeah. So 32 plus 2 is 34. So when 34 goes this side, it will become minus 34. That will be minus 2 is equal to minus of f of w. Minus minus cancel. So I will say my filter width is nothing but 2, which is nothing but your answer. So whichever way you do it, I'm okay with it. Yeah, you can check it up with this. Guys, quickly check it up. Is it matching here? I will not do it. You people compute it both the ways. Just check it out. Is it matching? Are you able to do it? Padding is 0 in this case, okay? So don't take padding factor.
Yeah, matching.
Matching, right? Good. So what if I would have taken 3 cross 3 then? Can somebody tell me the output layer width?
What 3 cross 3?
The filter here, instead of 2 cross 2, let us say I have taken 3 cross 3 as a filter. Now what will be my output width?
You need padding first.
Yeah. So that's all. Check it out. How will we do it?
It's an odd number. Can't compute.
Okay. 32 cross 32 is too big. Let me not confuse you guys. Let us say this is a let me put some brackets over here. Say 1, say 2, 3, 4 and 5. Okay. Similar to that, 1, 2, 3, 4 and 5. Good. Now, what should be my filter size? Such a way that, or else I will give you the filter size. Let us say 3 cross 3 is my filter size. Can you people tell me the output form? What output I'll get? What cross what? Use that formula. I'll give you 5 minutes. Just check it out. It'll be good, guys. You'll be able to, visualize the same thing in your convolution also, because you have to put hyperparameters there, right? What should be the width? What should be the size?
5 minus 3 plus 1.
Okay. 5 minus 3. Okay. Plus 1. Padding should be 1. What?
No, 0.
0, right? So 5 minus 3 divided by 2. So that is 2 by 2. That is 1.
Okay.
So what will be the answer?
2.
I want M cross N. You guys can type it out, not a problem. Type me on the chat one by one. I'll put the formula for you guys. Output width, okay, is equal to the width of your image. There is a lot of noise. Please mute up. Still a lot of noise. 1 minute. Who is it? Yeah. Okay. So width of the image minus filter width plus 2 times padding divided by stride factor plus 1. This is the formula for output width and output height, both same formula. Now tell me, guys, what will you do? You have to decide on padding, you have to decide on stride. How will you do it? Stride should be 1, stride should be 2, what it should be?
Yeah, if padding is 0 and stride is 2,
Okay.
then output is 2 cross 2.
Okay. So one answer I got is 2 cross 2. Okay, perfect. So did you see 5 cross 5 image? Now we've got the best features out as 2 cross 2. Okay. Next, anybody else change the padding and stride? Take it out. See guys, what here Dhruv said was he doesn't want to do any change in the padding and also doesn't want any stride. So sorry, stride is what, Dhruv? 2, right?
Just 2, yeah.
Okay. In that case, you can say this is one 3 cross 3, and if stride is 2, 1 and 2, it will come here as 3 cross 3. Then in the next layer, 1 and 2 will come like this. Agreed? And it will come like this. So do you people agree it's a 2 cross 2? Perfect. 1, 2, 3, 4. Because he has taken stride as 2. What if the stride was not 2? Then in that case, what will be the answer? Let us say
3
stride
cross
is 1.
3 cross 3.
3 cross 3, exactly. So you will get more features, 3 cross 3. What if you take a padding, Dhruv? What if there was a padding there? Let us say I take a padding of...
If it is padding and 2 stride, it gives 3 by 3.
Okay, perfect. Perfect. So now I hope you are able to get it. It is not always necessary that to pad or to have more strides and all. It all depends on your filter. So you baseline one of them. Either you baseline this or baseline this and then choose the other one out. I will always say baseline this. Easy way. Okay. Is everybody in sync with me? Everybody got this, guys? From next week, we'll not be able to discuss all this. Okay. So when I say something I've taken in the code, you people should be able to identify what is stride, what is padding, how I've taken this decision. Okay.
Padding and stride are higher.
So Amit, yeah, kind of, yes. Anything else, guys? Anybody wants me to repeat? No? All right.
If padding is 1, then what will be the effect on actual image?
See, if padding is 1 through, padding is like putting zeros. So you will get one extra white colored patch onto that. That's it. I will say padding personally is not good, but sometimes our images are of some odd size, no? To match up the filter, we have to do padding. Correct?
Okay.
Yeah. It is like a fake white colored layer unwantedly pasted onto that.
So Krishna, padding would be used if the image is not like in square in shape or something.
Correct. Agreed. So here we have taken 5 cross 5. Now what if it was 5 cross 6? So let's try that out. And guys, remember, it's very difficult to visualize all this. So don't strain yourself if you say, okay, I'm not able to get it. Definitely one shot will not be able to get it. Say this is 1, 2, 3, 4 and 5. Okay. Now if this was 5 cross say 3, for example, 1, 2 and 3. Okay. Now my intention here is to use a 3 cross 3 filter. Is it possible? First of all, just check it out, guys. A 3 cross 3 filter, how it will look like. So let me increase the thickness. So it will be 3 cross 3. Yeah. And if I say stride is equal to 1, now what's going to happen? To have one more 3 cross 3, do I have space? No. So in that case, what I have to do, I have to add one extra padding layer on the whole image. Okay. So usually you will see in all the codes is usually by default, they take a padding of 1 or 2. It's okay. Because we are not sure, sometimes we'll not be able to visualize this. It's okay to take an extra padding, doesn't matter. Sometimes we don't do it. If we don't do it, if it is an issue, it will throw an error. Anyway, it will notify. So once it notifies us, either we change the size of filter or we change the size of image immediately. Good. Vishnu, is okay now?
Yes.
Got it? Okay, perfect. Okay, so moving on now. So this is very important. Please remember, when I share this, keep it with you. And this is very handy also. It's not a big deal. Okay, so this is what is padding. What it will do is it will unwantedly add an extra number. Usually it is zeros, so it will not impact us much if we do pooling. Because if you remember what is pooling does is pooling will pull out the best features. So if I pull, let us say, sorry, If I pull, let us say, out of this, anyway, the 0 is going to be ignored somehow. Okay, so it will not affect much, but at least it will not hinder us from doing. Yeah. Next is pooling layer. So we have two types of pooling available. I will not say that's it. You can have your own version of pooling also, but these are the most popular ones. Max pooling, average pooling. So average in the sense you take average of all four of them and you pull as one number. Max is take the max of it. So in this case it will be 112. Okay. Good. Yeah. Guys, one more thing. Sorry. This is the max pooled image. From here it is got. So if you see 20, 30, 37 and 112. This is how we got. If you still want to max pool this further, then answer is 112. Okay, I did not see that. I'm sorry. This is coming from here. Okay. This one also, if you observe average pooling. So take an average of the first one. Let's check whether it's in sync. 20, so 32, 40, 52. 52 by 4. Correct? It's 30. All right. So what else we can do? Anybody? Any idea? We can use any other computation.
You could do min pooling too. I mean, since we're doing max.
I mean, see, here we want to extract the best features. For mean pooling, you're saying we'll extract the worst feature. Okay. If in case we want to blur an image, we can do that. Okay. Let's see. Let's see that. I've never tried it out. Okay. Let's see that. But yes, if you want to spoil an image, if you want to spoil certain part of an image as a blur part or something, yeah, you can take that mean value. Good one. Anything else out of these four?
Can we take min max?
Min max. How do we do that?
Or we can take a kind of maximum value minus the mean.
Okay, perfect. Perfect. Let us say in this case it will be 20 minus 37. Okay, nothing wrong. Yeah, but you have to design your own. At least it will not be present in the standard function. So you design your own function. The standard values are these two: max pooling or average. Good. So that's it. Yeah. So now how it looks like. So a fully connected layer. So what do we have? We have got your input.
Hey, Krishna, one quick question.
Yeah.
So where do you use max pooling versus average pooling? I mean, how do you make that decision?
Okay. See, use max pooling onto, let us say you have a low sampled image. So let us say the sampling here is 2 megapixel, for example, and the sampling rate here is 16 megapixel. In that case, what's going to happen is the images which are nearby, will be almost similar itself. So in that case, you can take an average, not a problem. But if you feel the sampling of your original image is not that great, you do max pooling, except the best out.
Okay.
Okay. See, I'll tell you why. Let's go back.
Are you saying that if the image is higher resolution, then go for
average,
and if it is lower resolution, then go for max?
Correct. See, if you look at this one, okay, this is only 2 0 or 1, or I'll say black and white. So now, if I have a filter which is focused onto this, which one you think is of our importance? Guys, max pooling or average? Max. Correct. We need to know where there is a black pixel. Definitely, we are going to get this. So this 2 cross 2 image now is represented by 1, which is called black, which is nothing but black. Now let us take one more example. Say, for example, you are having your stuff into this. Now, what is maximum number over here? All of them are ones. So if you do max pooling onto that, what you will get? 1. Or if you do, let us say, average onto that, what you will get? Average is
3 by
4.
1.7.
Yeah? Correct. So you can do this or you can do this. So anyway, the answer is we got to know that majority of the features over here are 1.
Yeah.
We know that. So this is some example of average. This is an example of max.
So I think The other difference is if you do average pooling, then especially where, for example, you have four black. I think that difference between the different values would be more of a range.
Okay.
Would-
Let's take an example. Say, where do we get 4? Here we don't have it. So let us say we take something like this. Yeah, we take something like this, 3 cross 3.
Yeah.
Okay. So if we take an average of this, yes, I agree with you. Yeah. Kind of. Yeah. Works out. So we have got 1, 2, 3, 4, 5. 5 divided by 9. That will be our average. Yeah, correct. Okay, good. So it's, guys, you understood what is he trying to say? He's trying to say that you will exactly get the number. How many blacks are there? How many whites are there? That's it. 5 by 9. So the denominator is nothing but your total number of whites available out of
9. Yeah. So the reason I asked that is, so in essence, you are getting more information, right, into the next layer, right, or into the next.
Correct. Correct. So we are basically taking the best information out of this and moving ahead. Here in our case, guys, best information means black. Worst information means white. That's it. You don't want white out of it. Now, are you guys comfortable a little bit with the filter part? Now you get the point why we need filters, what filters can do and what actually will do. We just need the best features. We don't need extra background stuff from this image. Let's not do it. Good. So this is one way to represent an image. If you want a little bit more simpler version, you can do this. What I feel this image is a better representation of where you can take out certain features out of an image and directly classify that it's a car, truck, or van. This could be we will see this little later in our course. You don't need to go and scan everything. Certain features will take it out completely. Okay. Good. So this is an example I will say of RCNN, Regional Convolution Neural Networks. You will see down the line. This comes in around third or fourth week. Good. So we have done almost everything which was needed. So next session, what I will do is we will start with implementation of the CNN, and then we'll move on to a very simple topic called transferred learning. So just to give you guys a very clear, quick 5 minutes idea onto next week's videos, don't worry. Those VGG, LXNet, FlexNet, then ImageNet, RestNet, all those nets that are produced, no, they are produced by some people who have done a lot of permutation combinations to find out the best combinations of convolutions here. You know what it does? It basically, whatever image you give, no, it tries to classify you properly. Now, what has happened since these neural networks have one certain computations, they are standardized now. What does it mean? Their weights are stored in an HDF format. Now on, what you can do is you can build up your code. You can download their weights. You can ready the architecture for them. You can automatically download their weights. And you can build your own FCNN at the end. So whatever you download, no, that will be only convolution neurals. The last layer, the last 3 to 4 layers that we are supposed to do, our own layers, that is your fully connected neural network layer, is what you have to design. That's it. Your network is ready. You don't have to take a pain of building your own CNN. This is called transferred learning. That's all is the topic for next week, whole week.
So which means the weights are already initialized?
Yeah, already, not already initialized, I'll say. The weights are already ready. The filters are already ready. All you need to do is pull it down and then rerun. See, it's like you cannot train them. You can train this. So when you do your fully connected neural network, when you train your model, these are non-trainable static stuff. This will be your trainable stuff. That's it. Do you think our problem will be solved? Yes, right? You don't have to take a pain of designing a very complicated neural network. Neural network is good. We get it. But you don't have to take a pain of designing all this. You are getting this ready-made, this part. This one, what you are supposed to design. And you people are very good at this now. Got it? This is called transferred learning. It's like one of you design a code, generic code, and give it to all of us. We just change the input data and run it as our classification model. That's it. So don't get confused if the professor is showing LXNet. LXNet is very big. You just have to understand that this is a ready stuff. We are importing it and running it on our model, so that I don't have to go through a pain of training my own model. And usually the parameters are something like 6 million, 10 million, 16 million parameters. That's the reason we don't need to train them. We have to directly get them. Ready-made codes.
Krishna,
Right?
can you explain with an example? I mean, so would you say that maybe you have a corpus of vehicles, right?
Yeah.
So you would get kind of a model which already can identify vehicles. Correct. Because it has learned, it has gone through a corpus, and then you just add maybe a few more layers on that just to look at maybe if your problem is to identify a Ford vehicle, then you work on that. Is that way?
Correct. See, Vishnu, have you heard about framework anytime in
Yes.
our industry? Yeah, what's a framework?
Framework is basically like a guideline of how to do work.
Yeah. Okay. So, for example, let us say you are doing lean.
Maybe skeleton, something like that. Yeah.
Okay. Or let us say, have you heard about A3?
A3, no.
A3 implementations under lean. It's a framework. Okay. Let us say you have a service and you want to improvise your service. So what do we have? We have current scenario. Let us say, what is your service's current scenario? What is the problem you are facing there? How you intend to solve it? And what is your timeline to solve it? Let us say there is one framework available to us. What you need to do when I give this framework to you, all you have to do is you have to put in your data. That's it.
Yeah.
Correct? Something like this, you can imagine that there is a neural network which has its own corpus, which was trained long back, which was approved by a lot of data scientists long back, which kind of is similar to what you are doing. Let us say the corpus over here was a lot of image or object identification. Any kind of object could be identified. Now we already have this neural network ready. So what these people have done is they have actually frozen their weights for us and converted them into an HDF format. Okay. Now what do? I take these weights as our framework. And now I just put in my data onto that. That's it.
Okay.
And use them. That's it. So I'll give you some of the popular ones which I am comfortable using is VGGNet, MobileNet. So what is MobileNet? You use it every day on your phone. If you people observe, your phone tags your face. It is not possible to put very heavy stuff on your phone because of computation. So we have simplified VGG into a very lightweight model called MobileNet, and we are using this ready-made. You can use ImageNet. You can use ResNet, ResNet. We will see down the line what are these things. But in the next videos, you are going to see this. Okay, good. So the video next week should be very simple. So once you have got the concept of filters and convolutions, next week should not be a tough one. All right. Week 1 I feel is the toughest, and week 5, 6 I feel is the toughest. So middle of these weeks are pretty easy. We should not be. Okay. All right, guys. So I think I'm done. If you have any questions, do let me know. Else, let's close down.
I want to ask one question on the project because I think when I was looking at the data, there were some missing values. So for neural networks, do we need to do any imputation?
No. Missing values in what? Images.
I think there was some data also that was provided in one of the case studies, I guess.
Okay.
And it has many values. I'm not sure if it was that project only or if it's
no. In this project, there is no missing value and there is no imputation to be done. Okay. Yeah. Okay. Before moving on, I just wanted to ask you one simple thing. Let us say I have an image, which is say 64 cross 64. Okay. And over here, I have a neural network, say The neural network is having 512 inputs, for example. Okay. And I will say again, they have their own hidden layers. And finally, we are converging this neural network to say one classifier over here or two classifiers. We don't care. So the pointer over here is we are supposed to input 512 inputs. My current input is 64 cross 64 cross, say it's a grayscale image, so 1. Can you guys help me to put how many convolutions I need and what will be the size of my filters, max pooling and all that? Can we do this quickly so that I get to know that you people are in sync and we can go further on? So let's start putting the blocks over here one by one. Yeah. Okay. So let's put the first block. So what I'll do is we will write the filter size over here, filter size and max pooling, and finally we'll put here what is the total number of we have got. Yeah. So let's start. How to do this? How to design this filter?
3 cross 3 filters.
Okay. So we'll start with 3 cross 3. Okay. And how many I need? For example,
64.
So how do you decide on that? So yeah. So one hint from my side is this particular term we have no clue onto how many we need and all. So for now, you keep it empty. It's okay. But at least let us say you have decided 3 cross 3. So if I have 3 cross 3 here, what will be my output here? So what will be the output of my what do you say, filters over here?
So it is 64 plus 3 minus 1.
Sure.
Yeah.
Okay. What is the formula? Width of the image minus width of the filter plus twice of padding divided by stride plus 1. This is the formula. Okay. Yeah. So now start putting it. So first of all, I will say, okay, stride is 1 only. I'm not changing my stride. And padding I have not done. 0 padding. So what will be the size here?
So 64 minus 3 plus 1.
Correct. 64. 64 minus 3 is
61.
61. 61 by 1, so 62. So I can say the output that I'm going to get will be 62 cross 62. Now, if you look at this and if you look at this, it does not make much sense to me. Why? Because we have not reduced much. So to reach to 512, the 512 means when I multiply these two, I should get 512 somehow. So if you multiply 64 and 64, you are going to get 4096. Yeah. So this particular thing is not going to help us. So in that case, what do I say is this transformation is not that great. Now to reduce it, what I will do is either I'll increase the size of my filter. It's not fair. Or else I will increase my stride. So let us say I increase my stride to 4. Okay. Now can somebody tell me?
So it's an odd number.
So
odd divided by 4 is point values.
64 minus 3, or else let's be fair. Okay. 64 minus 2, 2 cross 2 will do. No problem. So 64 minus 2, that is 62. 62 by 4, that will be 31 by 2, that is 15.5. So say 15 will take. So 15 plus 1, 16 cross 16 we can get. So that is a good transformation. So now what is the problem here, guys, is this is not an easy task to do. So on purpose, I took these numbers so that it is not an easy task that, okay, I have these things in my mind, I have some input, let's try to convert the input to something. And also it is not easy to decide how much is the size of the filter, what will be my padding, what is this. So it is good to know the formulas and do convolution onto simple images. But when you go on to larger images, say 1 megapixel image, for example, and if I ask you guys that, okay, my image is 1 megapixel, can you design a CNN for me, which should intake 512 over here? So it'll be, you can do it, not a problem. You will be able to put one by one all the filters, or else even you'll back propagate and try to change. Good thing, nothing wrong, but it'll take a lot of time. So to avoid these confusions, what we do is we use concept of machine learning. concept of transferred learning. I'm sorry. Now, what we do in transferred learning is, let's try to see that. Can any of you name one library from machine learning which is the best, like which has almost all the algorithms or all the functions that we dropped? Like I'll give you an example of SVC or KNN or decision tree or random forest. Which library we used for?
Scikit-learn.
Scikit-learn, right? Let us say we use that library to do that. Now, what is exactly scikit-learn? Can't we program a SVC using for and if loops? We can easily do that, right? But why don't we do it? Why? Because we already have a function, somebody has returned it, somebody has coded it in a generic way such that it will help us to input our unique data, and according to that, we'll get a customized output. It is solving my purpose. So what we do, we call this. Now, when we call this particular thing, what are we doing? We are getting the stuff ready-made from them. We are getting the hardware ready from them. The only thing is, I'm sorry, we are getting the infrastructure ready from them. Only thing what we are doing is we are putting our data. Now, keep this in mind. Let us say there are certain readily available convolution networks. I'll show you down the line which all are there. But say there is one convolution network which is readily available. And say you have stored the weights of this function in an H5 file or HDF file or whatever file we can. We have pickled all of these weights. I'm not saying the entire network. I'm just saying the weights of the network. Weights in the sense, what is the size of the filter and what is whatever we saw in the above example, which we kind of did not, if we're not able to clarify, weights are there. Now, what do? I ask or I request this particular model to import the weights to my model. So let us say this is your model. You have created an exact replica of this model. Now what you do is directly pick up the weights and drop it in your infrastructure. Okay. Once you drop it in the infrastructure, what is remaining now? So you have just got convolution weights. What you have to do now? You just have to build your FCNN here. That's it. Fully connected neural network. This is, we can easily do it, not a big deal. So this is what we do on the industry side. We do not write much of the CNNs. And even if we are successfully able to put a CNN of our own, training it and correcting it will take a lot of time, to be very frank. So I will say majority of your implementations on the industry point of view, you will be using transferred learning. But in this certification, at least for 1 or 2 or I think 3 weeks, we will be handwriting some of the CNNs. And after that, we'll start picking up CNNs of our choice as this. Okay. And that example that we saw, we will see it in the code. Let's see how we can solve it up. Okay. Any questions on transferred learning? The concept part of it, I will show you how we do it. But this is what overall goes around. We directly take the weights and use it. Okay. Any questions? No?
No, sir.
Perfect.
No.
All right. Good. So now let's try to use a PPT. So today I will use one PPT where they have mentioned a lot of networks. Now for first point, it will be very confusing immediately. So don't expect, I don't expect you guys to master this networks in one module itself. What we are going to do is I will pick up each network every week. So let us say in today's session, I will pick up VGG, which is the most important. Probably next session, I could show you something on LX, something on LENet, or I can give you something to do on LE. And post that, we can go to the complex networks like ResNets, Google ImageNet, and all those things. Okay. And this is not it. There are so many available. Okay. So let's start. Yeah. So for today's agenda, we will start with CNN architectures. So we just took an introduction of what is CNN. CPU versus GPU, we know this. I'll not go in much detail. And the most important, transferred learning. Now coming to the architecture of CNN, try to push our formula here, whatever we saw, right? So Harish, I think this will solve our problem, except I will say it will not just solve the problem of what is the math behind selecting the number of filters. I'm still working on this, guys, and give me a week's time. I'll try to find out some paper or some logic behind this.
Okay, Krishna.
Yeah?
Yeah, okay, Krishna.
Okay,
Even
so,
I will search for that.
yes. And also I will request our great learning I think the professor who is teaching this, if he can share some papers with us. So Frank, so far I'm not able to find any particular good reference where I can say that this is the math behind selecting these filters.
Maybe what I feel is, as you said, they have also decided first what is the fully connected layer, and then they decided on this number 6.
Reverse engineered it, right? Yeah. Right.
Maybe I also think that, but
Right.
I'm not sure. Yeah.
But still, there should be some logic because randomly I cannot put anything here.
Yeah.
I feel it is a little weird. Okay. Also,
Yes.
I tried. See, if you see here, what does it mean is we have 28 cross 28 6 filters. So what if I multiply 28 into 28? Okay, so let us say I have 32 into 32. Now, when you multiply 28 into 28 and then add it 5 or 6 number of times, I'm not sure we are going to get the same number back, to be very frank. So what is happening is, as per our analysis or as per our knowledge in CNN, what is happening is we are converting, say, if the stride is 1, then definitely you are going to have the network which look like this. So one particular image is getting converted into many features. That's what the 6 thing shows. So I used to take it as feature maps. I used to say there are 6 feature maps available. That means I can pick any one of them, put it to one of my convolution network, fully connected networks, and try to find some information out of this if possible. Okay, this is what I used to take, but now I feel that is not enough. I need also to know how to do this. So apart from this, in today's session, let's ignore this. But apart from that, you can directly see 35 minus 5, that is 27. We are saying stride as 1, so divided by 1, padding is done 0, plus 1. So if you look at it, 28 is the 1. If we still do it, 28 minus 2 divided by 2 plus 1, you are going to get 14 out of it.
Yes,
So the
yes.
formula holds pretty good onto this part of it. So at least 50% of the stuff is solved. Except now if you ask me, okay, how they came up with this network now. So I will say it is a lot of mix and match trials happening. So it's not a one-shot job that, okay, they decided this and they got the best accuracy. Because if you look at it, they are currently working on 60,000 parameters. Okay. Now, what are these networks and how we can use it? So if you look at the highlighted area that I am just drawing, this is what I am interested in. So if I have a ready-made network, open source network for all of us, which can identify handwritten digits. So your neural network project, you remember? 7, 6, 5 and all. I know they were not handwritten, but anyway, we can correlate this. If I can do this, what I can do is rather than writing KNN, rather than writing the neural network, what I will do, I will ask this alienate weights to be dropped onto my network and then design my own fully connected neural network depending on how many number of outputs I have and take it forward. Okay, so these are the features. Now, if you expect to use the readings onto a face recognition system, then it will not work, to be very sure. Why? Because please remember, this is what is important. So why am I specifying is tomorrow when you're picking up this, you should know what it will solve. Okay. All right. So this is it.
This only works for the handwritten digits. Nothing else we can apply.
Yeah. If you are importing the weights. Okay. If you are replicating this network and giving face as an input and trying to get an output and just check how it is. If you get a good output, then you can say that yes, it works for face recognition also. Correct? But for importing weights, it works only for handwritten because they are trained only on that data.
Okay. So it means like if we are using it ready-made, then we can apply it only for the handwritten digits. But if you are trying to replicate the same thing, same architecture, then we can provide the face as whatever inputs we can.
Perfect.
Correct?
Perfect.
Okay. Yeah.
Perfect. So when I deliver today's code to you guys, so in today's code, we are going to use VGG. We are going to import VGG and do it. So what you guys can do is you have the network in front of you. You pick up your older data, that MNIST or SVHN data from your previous project, pick it up, try to replicate this network and see what you are getting as an output. Simple. Okay. So how do you replicate? You use the same values. And at the end, when you're connecting this fully connected neural network, you multiply these things. That's it. That will be your input. As simple as that. Or else, if you don't want to multiply all three of them, 5 into 5, 25. And you give 25 as your batch size. Okay. So at one shot, 25 will be picked up, put it in and move. Or else if you want all of them, all the filters to be put in at one shot, you can do that way. Or else you can pick up one by one and do. Yeah. So try this out. Good. It's good if you play around with this particular network because it's a very basic one. So if you're good at this, then you will be good at the next one also. So if you look at the features, it is for handwritten. It was published in 1998. So I will say it is an outdated algorithm, but I have used this into multiple tasks where I have to identify simple digits. It works perfectly good. No problem at all. Yeah. 60,000 parameters. If you are looking at your current collab, then I will say it is not a very big network. If you're looking at Jupyter, yes, I will say it is a little heavy on Jupyter. The dimensions of the image decreases as the number of channels increases. So if you observe, the dimension is decreasing, but number of channels is increasing. Or else I will say, rather than channels, what happens is when we say channel, we get confused with grayscale and RGB. Another case, I will say, call it as feature maps. So each square that you see, 5 cross 5 square, carries some kind of feature. That's what it means. The activation function used in the paper was sigmoid and tanh. But now what we do is you don't have to use always sigmoid and tanh. You can use relu now. You can replace both of them by relu. No problem. It will work good. All right. So this was your, how do you say, this network. Okay. Moving on. Okay. So some pointers here is it's a 10-way neural network classifier. It works properly on 0 to 9 data. Handwritten digits, tolerant to various transformations like rotations and scale. So if you do augmentation also, it is going to work good. So our SVHN data will work pretty good onto this, no problem. Was used by banks to recognize handwritten numbers and digitized checks. So still on a very basic level, yes, they do it. So what they do is if there is a check, let us say return, if there are certain numbers written on the check about what is the payment, then let us say there is a signature over there or something. In those cases, if you want to identify the digits or if you want to identify the check number or the date, you can easily put the check below the scanner and pick up the data and process it. Very simple. You don't need a very heavy hardware for this also. And it's a 4 weights layer. So if you observe here, 1, 2, 3, 4. 4 weights. Okay. Now, if you guys have understood this, one quick question for all of you. Can somebody tell me if I put an Adam as my optimizer, let us say ADAM, Adam. Adam is going to work on this or on this. Take some time, think about it. How my back prop is going to work. Is it going to work on only fully connected or it's going to work on everything?
I think for everything.
Perfect. And what if, Dhruv, I do, okay, so in the first case, if you are using the whole network as it is, yes, back prop is going to work for both of them. I'll show you how back prop works for this. You people know how back prop works here. Okay. Now, leading to this, another question. What if I import the weights to my network and I use my own fully connected neural net and go for that? So in that case, back prop is going to work on both of them?
No.
No. You got my question? Let me repeat myself. What if you have imported, so this is my import of weights from the LENet website to my network. And after that, I'm building my own fully connected neural network here, something like this. And now if I put Adam, Adam is going to work on this, or Adam is also going to work on this also.
I think it will work only for that part which we have customized, not for the imported part. I feel so, not sure.
No, perfect answer. Why? Because if I back propagate and if I change my weights, there is no fun of importing the weights. Why we imported the weights? Because they were standard weights. These were already learned weights. So if I back propagate here, it's not going to work. So we have to make sure that If we do it, we freeze these panes. Whatever we have before this, we have to freeze them. They are not editable, and this side will be editable. So I think in third or fourth week, I will show you how to do it. Yeah, but this is a very generic question. So when you go for an interview or when you look at some of the most important deep learning, convolution, or CV questions, this is what they ask. Okay. So this is one concept. Now, keeping this in mind, let's try to complex, or let's try to make one more model out of this, which will be your LXNet. So LXNet is an extension of LENet, I think we can say. And why do we need this is, let us say the earlier one was able to identify 0 to 9. What if I want to identify some of the objects or some of the faces or any other thing which is not even number, which is more than a number? If I want to do that, I need bigger architecture. So what they have done is they have simply increased the layers of convolution and pooling, That's it. Okay, there is no other difference. And if you observe, even there, FCNN will differ because of number of changes. The goal for the model was the ImageNet challenge, which classifies images into 1000 classes, for example, has 60 million parameters compared to 60,000 parameters. So when this increased, okay, so when this increased from 60K to this one, even the capacity to classify images increased for us. Now it could be anything. If it comes under those 1000 classes, you can use the weights ready-made from this network to your network. It uses ReLU activation function default. And this paper was convinced the computer vision researchers that deep learning is so important. Fine, this is blah, blah, blah. And this is how they have done this. So if you want to see the tabular structure, they have taken 1, 2, 3, 4, 4 heavy layers. But if you look here, something is wrong in my diagram. If you look here, there are more convolutions. Give me 1 minute. So we have one convolution, we have one. Yeah, we have a convolution here, we have a convolution here. This is no convolution, no convolution. There is a convolution here, and there is a convolution here. So I have 1, 2, 3, 4, 5, 6 convolutions and 2 similar layers. Okay, there is no change over here. All right. So this is it. Okay, this is what is your LXNet. It's an extension. Please remember this particular number. It is very heavy. Okay, let's go to the extension of, okay, what made LXNet successful? So I will say architecture, I don't believe that, because anything you mix and match, definitely you're going to get something out of it. We can say overlapping max pooling. So if you observe here, what is overlapping max pooling is, if you observe, we are not doing in middle. We are doing for one, we're doing for another one, we're doing for another one. Okay, this is what. You don't have to do always max pooling after convolution. ReLU function was universally used. It was very simple. Dropouts, cropping, data augmentation, and inference augmentation. So inference augmentation, I will say, is okay. Let us today take the case study and revisit this particular part. But more or less, if you look at the important part, this is what it solves. This is okay. It's not a big deal. Not a big deal. Yeah, this is what you need to remember about max pooling. You don't have to do always. And I think architecture fine. So these are some important success factors of LXNet. Okay. Next, coming on to VGG. Now, increase still more number of pooling and convolution layers, you will end up with this particular network. And let's confirm what was the image size here, 227, 227, 3. And this was 9261. And here we have 224, 224, 3, and fully connected is 4096. Okay. So if you observe, again, what you do is you increase the number of convolution layers, modify LXNet to make something called VGG. 16 is not the latest version now. Now we are having 19, but both of them work equally. So for me, if I've done some implementation, if I'm using VGG 16, it gives me a good Accuracy, I don't go to 19. So 19 is a little heavier than 16. Yeah. Other all remains the same thing as our LX. No change. So what are these what are these networks? Is there were some challenges in which some of these people came together and built this. That's all. If you ask me how, it's about mix and match, to be very frank. Yeah. No use. Some of the important things is from 60 million, now we are jumping to 138 million parameters. Yes. It holds a total memory of 96 MB per image for only forward propagation. Most of the memory are in earlier. So if you just observe that you have two things, one is your network and one is your FCNN. So we can say that most of the memory kind of goes away here. This is the heavy part, this is the lighter part. Okay. Number of filters increased from 64 to 128 to 56, 256 to 512, and 512 has been made twice. So they are just replicating some numbers from the network. So you don't have to remember all this. Whenever you want to use it, just come back to this particular thing and try to replicate the network. You have the numbers ready. You just have to put it in the Keras add dense Keras. That's whatever that particular command you have to use. And if anybody is interested in paper, this is the paper attached. I will say it's a little heavy, so first get comfortable with all this and then go on the paper and have it. Okay. And as mentioned over here, there are two versions, 16 and 19, but more or less it does the same job, whichever you want to use it. Okay, good. Now comes a little problematic part. So now these were the three simple networks which we can visualize. Now comes a little different network. We call it RESNet, RESTnet. Now, my question to all of you is, what if I want to use this particular hardware, whatever we have done? Okay, it's a very good network, agreed. But now I want to use on a handheld device, and within fraction of a second, if I give an image, no, within fraction of a second, it should give me some output, or it should put a square around my face and say that, yes, we have identified it as you. Will your device be able to hold this up? Okay.
You mean computer?
Yeah, so if you have a mobile, for example, so will your mobile be able to hold this up, this heavy processing?
Maybe as you said, there is another architecture called mobile.
Mobile net. Oh, that's why you, okay, yeah. Mobile net is an alternate version of it, yes, but let's not go there. Let's try to think what we can do here, or okay, my example is not corrected. Let me try to create another example. So guys, let's take one more example. Let's not think about computation. Let's say I am currently having one image which needs to be given as an input, and immediately within some time limit t, I'm supposed to get the classification output along with some tagging or some classified output. Now, as you saw, the number of layers are more over here. So we had one layer, another layer, third layer, fourth layer, like that. Notice so many layers are there. And it is going in a sequential manner so far. We have not broken any of the sequential, flow as of such, correct? Now, what if I want to increase the speed of this network? What should I do as per you? Let us say I'll take 5 inputs from you guys. The current time is t, okay? I want to make a time period saying that t new. Now t new should be far less than t. That means it should be faster. What should I do?
Are you talking about embedding software like Coral,
No,
NVIDIA Jetson Nano?
No. Let's not go there, Dhruv. Let's say if I make some changes in my current network, I should get some good speed. I got it that this network is very good. Perfect. We got that. I don't want to lose it. What if I am not happy with the time part?
Maybe to increase the hidden layers, I mean, it might reduce the time.
If you increase the hidden layers, then the time will increase, right?
Yeah, right.
But simplify the input and output also.
Exactly. So how do we do that? You are perfectly right. How to simplify this? Distribute, okay. Okay. So Kaushik, you're talking about parallel processing, something like that? Yes? Okay,
Yeah.
fine. That could be a possibility. So let me write down. What if I have a parallel process? Or I am having a Hadoop environment where I'm doing parallel. Okay, fine. This could be one possibility. But we are not changing the architecture, right? What we are doing is we are distributing the data. I will split my data into many and then I will distribute parallelly onto multiple networks. Okay. What can I do in my network? Okay. Let me give an example. I think then you guys will be able to pull up something. So guys, let us say when this is my computer screen that you are able to see. Okay. And for example, in front of my screen, I show you half of the image like this. Okay. Now, as soon as you see, so just imagine that you are not able to see this particular part. So as soon as you see this thing in my screen, what do you assume it to be? What shape you assume it to be? Everybody will say, yeah, it's a circle. Okay. Or else if I just, in the time frame, if I am just scrolling one image onto my screen and you are able to see only half part of it, but yet you are able to describe it, right? What it is. You will have some assumption in your mind that yes, he is trying to show a kind of square. And as soon as it comes in the picture in my frame, everybody knows, yeah, it's a square. Keeping this analogy in your concept, what if I can give some early inputs? Say that I can take up the output of this and throw it to this. So definitely it's going to go here. So let us say the output from here to it goes here. It takes some time frame t. Meanwhile, parallelly, I throw the output here also. So what's going to happen? This particular network is going to make some outputs and start throwing it in future. So till our image is getting processed here, our output would have reached here immediately. So there are certain cases where if you look at certain parts of your image, let us say in this particular part, this, I'm sorry, one of the feature map looks like this. And as soon as I give this feature map, let us say the feature map was here, as soon as I give it to the next network, and if it gives next to this network, we could be able to identify that this looks like a cat, possibly it's a cat. So till I get all of my feature maps, all of the shrinking and all, I would have easily identified this. Are you able to get it? Kaushik, this is something similar to what you said, but here we are not splitting the data parallelly. I am forwarding the data. I'm avoiding one of them and forwarding it further. Able to get it, everyone? Amit, Dhruv, Shakti, Akash, Harish, Kaushik, Kranti, Raghu, Saurav.
Yes, Krishna.
Logical? Yeah?
Yeah.
Okay, good. So this is what RESTnet does. Now the only challenge, so nobody challenged me here saying that, okay, fine, if I do that, let us say, as I said, there is one convolution layer, max pooling layer, convolution, max pooling, convolution. There are so many like this. Now what I do is, by default, there is a sequential order. Yes, it will follow when till it goes to a fully connected neural network. But if I take an output from one node and give it to say this node, don't you think the filter is going to mismatch? Agreed? So let us say this is 28 cross 28 cross 3, for example, the output. And when we reach here, it could be 16 cross 16 cross 6, for example. Don't you think this is going to mismatch? Yes or no? Because in convolution, every step we are reducing the size. Agreed? So the output of this particular one is going to mismatch with the next or next to next one. So what we do to solve this is we keep the same stuff for all of them. That means we design a network which has same filter size, same activation. All right. This is how it looks like. It looks pathetic. If you look at it, it makes no sense as of such. But yeah, try to understand that we are giving an early output. We are skipping one convolution and we are going further. All right. So it's a very, very deep network as suggested. Because of vanishing and exploding gradient problem. Now, what do you mean by vanishing and exploding gradient problem? So I will show you down the line. So let us say I ask you, guys, you have done the model, all of you have cleared the model on statistics? Yes? The first module? Yes? Can somebody name the 3 distribution we have done in the statistical module? Can somebody name this?
Normal distribution.
Okay.
Poisson distribution.
Okay.
And there's a
binomial distribution.
Okay.
Binomial distribution, yes.
Okay, and one more. Okay, I underestimated you guys. Yeah, now 5.
Distribution, chi-square distribution.
Oh, bapre. Okay, good. Dhruv remembers everything. Okay, good. Okay, what if I say what were the statistical tests you people did? What are statistical tests we know?
Two-way.
T-test.
T-test.
ANOVA.
ANOVA. Perfect.
Z-test.
Goodness of it.
Sorry?
Goodness of it.
Okay, fine. Okay, then you guys are ruining my example. Okay, see what I was trying to show you guys was, okay, good, you people remember. My other batches said we don't know. So it helped me to explain my stuff. See what happens is, guys, when you have a particular data which is passing through a multiple neural networks, now let us say the data is entered here. It went through a lot of these convolution, non-convolution layers, whatever, pooling layers, whatever layers. Finally, it came here. Now say you found a loss here, dou L by dou of weight 1. So let us say this is weights. So what you do, immediately you go here and change the weights. If still in the next propagation, if you are not happy, we immediately go back and change the weights. At least I can say that at least till here, if I change my weights, I'll be able to at least control. So what do I need to say is, the weights which are there in the earlier part of the network, if you have a very deep network like this particular weights are going to vanish. More or less, they will make not much significance to the network, to be very frank. This is called the problem of vanishing gradient. We are going to revisit this concept in NLP next module. Under NLP, we have a network called RNN, recurrent neural network. So there is a problem, same problem. RNN is a deep network where we will face the same issue. And to solve this, we use a network called LSTM, long short-term memory network. So we'll have some memory where we are going to store these weights down the line. Okay. Now, if you look at our ResNet model also, this is a very deep network. And whenever you find the word deep network, always say that, or always remember that vanishing and exploding gradients are going to be a big issue. Vanishing gradient for these people, exploding gradient for these people. Their gradients are going to go pretty high because a lot of changes will happen, which is very near to the output itself. Okay, so this is what is your ResNet. Next, I think that's all you need, more or less. Yeah, so this is what is the important points. So the architecture of ResNet 34. Now you have many versions of this. This is ResNet 34. There is ResNet 150. I have seen ResNet 50 also. The concept is changed. Only thing is the number of layers that you are going to see here will be different. The deep layers. Okay. All are 3x3 convolutions and same convolutions. No change. So we keep a uniformity. Keep it simple in design of the network because we don't want to play around, because I want my output to work on any of these convolutions. So I will keep it as simple as possible. Okay, and if you observe, there are no fully connected layers. Okay, and I think that's it. That's all. And one thing to remember is the dotted lines in this case, when the dimension. Okay, one minute. Where is my dotted line? Okay, so there are two things. I'm not sure if you are able to see the dotted lines. If your input and output are kind of tracing each other, that means you can switch off some of these lines. That these are optional connections that we have given. It's not necessary to take each one of them and throw it. So if you are designing it that you are surpassing only one neural network, you can have some of them as dropouts, saying that we don't need them. So these are the dotted ones. So we will see. I will implement one of these ResNets. It's not in our course. It's not in our standard format here. But I don't want to leave this. I will implement this ResNet and I will show you once you are comfortable with first three networks. Okay, so we'll do this. Let's see how we can design take this. So first thing is we'll do design it. Second thing is we'll directly import the weights and use them. Perfect. So this is what is the expanded or zoomed version of RESTnet 34. Yeah, 34 represents the total number of how deep the network is. Now, coming to how to decide how many layers to take and all this part of it. So very simple. If you have around 5 layers in your network, it's a very easy network. Okay. So it's not a deep network at all. If you have around 10 layers, including initialization and batch normalization is included, I can say, yeah, it is still an easy one, but a little complex, a little deep as compared to 5. If you go to 30 and 100, these are the real deep networks, especially I'll say that this one is a very deep network. And in this network, if you are using this, you have to identify how to skip the connections because the time is going to be very long. So if you are planning to have 100 layers or even 30 layers, please make sure that you have skipping the connections, the one which you did in RESTnet. So more or less, I can say these are the examples of RESTnets, LSTMs, and all this. Okay? And anything above 1,000 layers, I'm not sure. I've never seen in my life. What? We have no idea about it, how deep it's going to be. So if you want to look at one of the layers, which is very deep, this could be an example of the Inception network from Google. Okay, look at this. And they have a lot of connections, a lot of skippage is happening here. So what is it? The Inception network consists of concatenated blocks of Inception modules. Okay. The name Inception was taken from the meme image, blah, blah, blah. We don't need this. Sometime a max pool block is used even before the Inception module to reduce the dimension of the input. So please remember, it is not always necessary to take the image as it is. The way we used to do PCA, same thing we can do it here also. Now, have I shown you any times how to reduce the dimension in image processing?
No.
No? Have I shown you anything on autoencoders anytime? No, right?
No.
Right? I'll show you today. So
No.
if you remember, we used to do SVD, PCA, and FA, and TSNE. I'm not sure even you have done that. Have you heard about TSNE, guys? All right. I will show you one more dimensional reduction technique in machine learning today. But apart from that, if you want to do same thing in neural network, how should we do it? The first way was nothing but your convolution layer. Correct? Convolution was something like shrinking the data itself. But if you look at convolution as data reduction, there is a problem. Let's see how. Let us say this image you are having here, which is say 64 cross 64. And after convolution, before flattening, you got an image, say, which is 5 cross 5. Or I will not say image, I got some data which is 5 cross 5. What we have done, we are able to shrink this up. Okay. Now, can I use this for future processing? If I give it to one of our networks, say LENet, LXNet and all, will LENet be able to identify that this is a part of a larger image like this? Yes or no? Can I do something like this, which I call it dimensional reduction? Is it possible to think about?
Yes, we can do that.
We can do that. Okay, we got one yes. Anybody else thinks it's not a good idea or it's a good idea?
It is possible. Yes.
Okay, fine. So from my side, you guys can try this out. If you can do it. If you put a FCNN at the end, yes, it is possible. It'll become your CNN again if you put an FCNN here. But what if I want to send this to some other networks? Other networks will not have the decodings here, right? You remember we have done some encoding here. We have used some filters to encode this data. Have we given them the decoder back? It is like that cipher. I'm not sure if you've heard about this. Let us say you want to secretly communicate something. So what you do is you implement your cipher. There will be a filter which you multiply with all the things and it will create some new numbers. It will look like junk data. Now this cipher, to decode this, you have to divide the whole data by the cipher again. then you are going to get it back. Correct? Now, this is what I call it as a cipher, whatever we have done here. Are we providing cipher along with that? So tomorrow, if you want to recreate this image, use this cipher. We are not doing it, right? So what if I want to reduce the size of the image, and if I want to recreate it, we should be even able to replicate it back. Okay, but in this case, what I will do is, if this was 64 cross 64, I cannot replicate the whole thing back. I cannot have the whole sampling done. So what I will do is, yes, if I want to reduce the size to 50%, I will say 32 cross 32. But still, I will be, let us say if the number 7 is here, I will be able to vaguely represent 7 back. This is called auto-encoder. I'll show you today one implementation also. But on a very high level, this is how it looks like. And if you ask me what is present inside these networks, there are two things which is present. One is called encoding. Okay. Encode. And one is decode. Okay. Now, anybody here from electronics and communication background, or at least especially DSP part of it? Anybody? Shakti, your camera is on. Huh? Yeah. Anybody from this background, or even from computer science background, you guys would have done it. Encoders, decoders, no? Cryptology or something like that.
I think I
Yeah,
have.
yeah.
So you can correlate. Correct. You can correlate these concepts there, saying that we will have something done on an image, we'll shrink it, and then later on we'll pass it, we will again recreate it and pass it to our network. Now, why do we do that? Very simple thing. I've reduced my dimension, I've retained the data. All right. Now, what are these encode and decode? Very simple. It could be your fully connected neural network. Design a network whose outputs are little lesser as compared to your original input. How many of layers you want it? How will you design these layers? Depending on this. So first of all, you have to decide the decoding size, how much you want to decode up to. Okay, and then finally you design inverse neural networks. Keep training them unless and until we are satisfied that both of them are almost similar. This is called auto encoding. It's not a very popular way to do it, because definitely in future, if I have 7, this image will not be 1 megapixel. Okay, I want to take HD images and shrink it. And if I take an HD image shrink like this, definitely I'm going to lose some data out of it. Everybody agrees to that. We cannot completely recreate this, no matter how good our network is here. Okay, so this is your neural network, simple one. This is also a neural network. You train the weights back and forth till they both sync up. All right, so this is an auto encoder. I'll show you one implementation down the line. Yeah, so what I was asking here, yeah, so so in other cases, what Google has done is they have done max pooling. So also you can think about max pooling as a dimensionality reduction. Yeah, so let us say if you have an image, say my favorite number 32 cross 32. Okay, now if I want to replicate this image into 16 cross 16, what I'm going to do, I'm going to max pool by 2. 32 by 2 is 16. Very simple. You can do this, or you can do the one which I showed you. Anything is okay. Okay, so this is your Google Net. We will take this particular network at the end of the module, so that you are very comfortable and you don't get confused, because by looking at it itself, it's pathetic, it's horrible. And to understand this, I'm not sure even if this is open source. I'm still seeing to it if we can download it. Else what I'll do is we'll do a very good in-depth theoretical review onto this. What is it and how they got hold on to this. Okay, and what is the application of Google Net? All right, now if you compare the most popular ready-made networks available, you will find them over here. If you look at this, the most stable one is VGG. So down the line, I think almost all of my implementations, you will find VGG itself. It's very simple to work with VGG. Okay, and look at the accuracy also. VGG is not very great. It covers around 65 to 75, but yes, from the parameters point of view, it is showing one of the highest parameters available. More the parameters, better will be your learning. Okay, LXNet and Google Net lies somewhere here. ResNet is somewhere here. ResNet 152. Okay, so 152 in the sense you are having more parameters. That's it. More number of deep layers as compared to 18, 34, and 150. ResNet 50, ResNet 101. So different versions are there. Okay, so this is how you can visualize this particular graph. So I will say, if you guys have decided to transition your career onto computer vision, then you need to know some of the most popular ones like VGGs. I will say LXNet, Base 1, and say ResNet 152. So if you know these three algorithms, you can say, yes, I know computer vision. Yeah, because they are the top performers, if you see, except LXNet. LXNet is the one very basic one, but these two are kind of top performers here. And also try to correlate them with the number of features available. Okay, good. All right. Now coming to concept of transferred learning. So too much of theory. We'll come down to this very simple diagram. I have got a source task, let us say some task, generic one. I am putting and I'm running a lot of hardware onto this, and I'm putting it to my knowledge. Now what do I do is I've got my target task. Yeah, let us say our real-time application, which I want to use it on. I get my data, I import your learnings onto my learning system, and I classify my stuff. That's it. So you don't have no more. We have to do the classical, traditional machine learning way of doing it. Train your model and then use your model. No need to do. Use ready-made learnings to move on. This is your transfer learning. If you look at the learning curve also, to be very frank, this is a better one, obviously. And majority of my implementations that I do, I take a ready-made network itself. I don't take a pain of doing CNNs. Now you may ask me, okay, fine, then why are we learning it? You will understand CNNs, the use of it after week number 4, where we enter RCNN, fast RCNN, YOLO, SSD, all the complex algorithms that we enter. No? At that time, again, we have to use CNNs. We have to use some part of it. So the concept of building CNN is important. Okay. Great. So I think we are done. Yeah, too much of theory. So what do we have today is we have got a very simple data set where we have got data splitted already into test and train. Okay. And what do we have inside? Both of them, we have same 5 folders, and each folder is having some flowers which belong to each one of them. Okay. So this is what is the data. Our job here is to classify the flowers from the testing part of it. So we'll train it using our training data, and we'll use this particular chunk to classify them. As simple as that. So the upper ones is the upper code is for the people who want to use collab. So I'll start from here. So this is my Keras. So now I think you guys are comfortable on the sequential part, convolution 2D. As soon as you say convolution 2D, max pooling comes into it, flattening it, dense and dropout. Now I'm not sure with version 2.0 whether this is going to work good, but I think from here it looks like something like this from TensorFlow dot Keras, and then everything goes through. Okay, so you have to make some modification. You might get some errors if you have latest version. Now moving on directly to the classifier. So if you look at this, I have got 32 3x3 what do you say filters, and I've got an input shape of 64x64x3. So very simple. Padding is 0, stride is 1. Just put the formula. 64 minus 3, that is 61. 61 by stride is 1 as usual, plus 1. That means answer is going to be 62. No. 1 minute. Answer is going to be
62.
62 only, no? Then why it's not working? Because the next one is 3x3, 32. Okay, so rather than taking this approach, what I will say is we'll take this particular approach. Say 64 into 64 is what? 4096. Okay, 4096, when you pass it through your max pooling function of 2x2, what are we doing? Basically, we are dividing it by 2. So when you divide 4096 by 2, you are going to get 1096. 1096, again, you max pool it. You are going to get, I'm sorry, not 1096. Sorry, you are going to get 20. How much? Can somebody help me here? I'll have to get my phone. 2048. 4096 divided by 2 is 2048. Perfect. Now 2048, when you again divide it max pool by 2, divide this by 2, you are going to get 1024, right? And 1024, when you again max pool it by 2, we are going to get 500. Correct? So now if you look at my activation, okay, there's a lot of noise. If you look at our input for fully connected neural network, our neural network ends at 512 as flat. Okay, to take this approach of solving this problem. Yeah, so as per me, this I'm not changing the filter size, it's working good. Now this is not an optimal solution. I'll create some problem statement and give it to you. You guys play around with the layers more and more, but make sure that at the end it should match with your input of your fully connected neural network. As simple as that. Okay. Now, if you look at it, what we have on the first layer, we have 32, 3 cross 3. This is my input, standard stuff I'm using, no changes here. Second one also standard, third one standard, same thing. This is 512. And once you enter a fully connected neural network, I'm saying give me some dropout. A dense layer could be, say, divide by 4 of this, for example, and activation function is relu. And finally, if you observe, I have got 1, 2, 3, 4, and 5 classes. So obviously, my total number of outputs is 5, and my layer is software. So now I think we are good at it. Right? So this is a simple CNN that I have designed. Now moving on, I wanted to show you something a little bit more here, wherein we are calling our Adam, okay, and we are putting into our compiler. But apart from our learning rate, if you remember, we have not used these functions so far. Now, what are these? How do you check this? So one way to go and check all of the activation thing is you can go to Keras documentation and go to optimizers. You will get list of all the optimizers available, which is SGD, RMS prop, ADA grad, AMS grad, ADA delta, Adam. Adam is the most common one, and SGD is also most common one. And if you have a deep network, you can use an RMS propagation, RMS prop. Yeah, I'll show you down the line how you can use this also. Now, what are these extra terms? So these all hyperparameters are defined there anyway. So the first thing is your decay factors. Now, everybody gets what is a decay, what decay I'm talking about. If you remember, the gradient descent that we have, is kind of decays down. So the standard values, if you don't even initialize them, the standard values are going to be this only. So I'm not playing around with this anymore. I'm just trying to show you that tomorrow, if you increase your learning rate, your decay is going to be more steeper. So if you look at it, beta 2 and decay rate, if you add them up, you are going to get standard answer is 1. So please keep a good check on both of them if you are playing around more with learning. And also, if you observe, there is something called beta 1 and beta 2. Both of them represent decay rate. So this could be the decay rate for the first estimate. First estimate, let us say it could be the first dou function that you do from your backprop. And this could be the estimate, the one from the second estimate, the second one. Yeah, usually we don't play around with this. Even on web, you will not find many implementations who have done this, but just wanted to give you some hyperparameters here. And the last one is epsilon. It makes sure that we don't misclassify anything, or we don't basically go into infinity state. So in none of our implementations, we are doing any operations with zeros. If you observe that, we are not adding or multiplying or dividing any of the zero part. Some of the neural networks or machine learning part of it, Keras, we do some manipulation with zero. So in this case, it will make sure that we don't do it. So by default, we keep it off. Okay, we are not worried about this. So these are some of the hyperparameters. And as usual, we are using categorical cross entropy because I have got 5 outputs and my matrix is nothing but right. Next thing, we have not done any data manipulation. That means we have not cleaned our data. So now what I'm doing is I'm augmenting my data. Now If you don't want to write a separate function for augmentation, and if you want to do it as per stuff, what you do is you import image data generator. This is the function. So it will give you a lot of parameters. Some of the important ones are these, wherein rescaling the image, you are rotating the image, you are zooming the image, you are flipping, horizontal flip, vertical flip, all those. Yeah. So this is the way you can create some kind of augmented images if you are not happy with size of data. Same thing you can do it with your test data also. Okay. Next thing, you call your test data from the directory and you say clip it to this size. Select one size. Why 64 64? Because you have designed a CNN which input 64 64. These are number of channels. Okay, so match it up. Next, total number of images you want to pick up in one run. So depends on your computer. If you have a high-end RAM for it, I will say increase the size of this. Now, can somebody tell me why do I need to focus on increasing my batch size? What difference is going to make even if I specify this or if I don't specify? What is your understanding of batch size? What do you mean by batch size?
How much data it processes per epoch?
Correct. So why should we take 32 here? Why can't I take a more number? Correct. So please remember, if you want to speed up total number of, so if you say 20 epochs, and in each epoch, say you are picking up around, your computer is keeping ready 32 images to be processed. What if I give more flexibility to my computer and say I will double it up? Just observe, by changing the size of batch, just observe your epochs. The total time taken by 20 epochs to run with 32 and the total time taken by 64, and let me know what did you observe.
It might slow down.
Kind of, yes. Okay, so again, it is very important basically to select this. So what I usually do is I divide this number by 2. I know logically it's not correct. I divide this by 2 and keep some familiar number. That's it. Okay, so there is no logic onto that, but yes, high-end computers can do it. My computer will crash if I take 64 or 128. Now moving on, same thing for your test. I'm taking the same part of it. And finally, you are fitting your data using the generator one so that we can get good augmented images and say this is my training set, this is my validation data. And in your epochs, say I want to run 20 epochs, you are seeing something new here today, which is called steps per epochs. Now, what do you mean by that? In one epoch, I want that particular epoch to run these many number of times. So what is 3823? 3823 is the total number of training images we have, divided by how many of them are picked up at a time? 32. From where? From here. So I'm saying is, even if it is not an integer, convert it to an integer, and each epoch, inside each epoch, you give me that many number of steps. So either you can have more number of epochs or you can have internal steps within epochs, whatever suits you. I gave you both the options. So far you would have seen only this, right? Okay, so this is what you can do it. I say this is a better option so that we get to know that if in case one epoch we are running 119 times again and again, probably I'll say within 4 to 5 epochs we'll be able to get better accuracy. So if you observe here, the amount of accuracy change is pretty high. So this thing is turning pretty good rather than having 40, 50, 100 epochs. You have to wait a longer time. Even this will be longer because we are inside each epoch and having these many steps. So definitely it's going to take longer, but the accuracy part of it will be pretty good. So if you scroll down the line, I ended up at 20 epochs. So after certain epochs, you observe it is not going further. Accuracy is going down. Now there could be multiple reasons for that. The first reason could be the way we have chosen the steps, but this is the only way to do it. Second could be we have done too much of augmentation, might be, so that we are not able to find some pattern. Third one could be our learning rate and the optimizer. And the most important reason could be the CNN layers that we have made. Okay, so I chose totally to make 4 layers. Why? Because our LENet had that option. So I did that. But what if I don't want this? I want to increase my accuracy here. So I give it to you guys by next Friday or Saturday maximum. Send me your inputs, how you can improve this. All right. You don't need to do this on the industry side because we have got ready-made networks. But anyway, if you play around with these numbers and also check the blog that Dhruv has given, will help you guys to formulate it. Delete one layer, add one layer, or I have taken a max pool size of 2 cross 2. You can take 4 cross 4 also, no problem. 3 cross 3 also, no problem. And I have taken standard filters here. You play around with the filters and see how it happens. But the only issue is don't run 20 epochs. You are going to waste your time looking at your monitor. So try to run less number of epochs and see how much accuracy is increasing down the line. Okay, so here we have got around 80, loss is 49, and validation loss is 90, and validation accuracy 64. So I will still say it's not a very good model because it's an underfit model. Okay, good. So this is one implementation on CNN. Now, what if we, so now a little different way of coding this. So giving you guys a hint of how you can save your model. So first of all, what you guys do is every time you kill your kernel, you come back, you have to rerun the model. If you don't want to do it, use this 2 options, wherein you have an option to save your weights, whatever weights you have, so that you can import it in the next network whenever you need it, or you can save your whole network as it is. So this is one way to do it. Another way is to do called what is called joblib. There is a library called joblib which does it, or there is something called pickling. If you want to see all these 3 today, I will show you down the line. If you are happy with this, usually in CVs, computer visions, we do this one. We don't do joblib and pickling. For machine learning, I can say these 2 are good. Okay. In machine learning, we don't have weights to be stored, but here we have an option. Either you store the classifier itself or the weights, any of them. So now what I've done is I've pickled them so that I don't have to rerun every time I open. Down the line, what I'm doing, I'm calling back my model, calling back my weights, both of them together. All right. Now, once I do that, what am I doing is I'm reading some random flower or set of flowers. Okay. And next, I'm changing the dimensions. Basically, I'm reshaping them. I'm changing the dimension. I'm changing the values of it by normalizing it. Finally, I'm saying display the name of the flower that I'm going to pick it up. Sorry, the dimension of the image that I'm going to pick it up. And finally, I run my classifier. I predict that particular image onto it. Yeah. So if you look at the output, this is the size of my image. This is the image after expansion. Yeah. Next, this is the set of options that we have. And out of these options, if you look at the softmax output we have got, can somebody hint out if this is my softmax output, which one of this is the classified answer? Sorry? Daisy, exactly. Why? Because look at the probability. Softmax is nothing but probability. The one with the highest probability will be the answer. So in this case, we identified, anyway, it's displayed here, but yes, please look at this stuff. So this is not needed, but anyway, we got the answer directly. So now whatever image we gave was a daisy. Now, what if I want to run it across the whole testing data and generate the matrix? So very simple. I'm just getting all of my test data from the path, putting the hyperparameters and running the model onto that. When I do that, I get a confusion matrix like this. And if you look at this, these are our flowers that we are talking about. And if you don't want to do that, there is precision, recall, F1, and support for us. Now, what is precision? We know, recall we know. What is F1? F1 is a balance between both of them. Okay, I kind of say average between both of them. And what is support? Support will say how many images of this class are present in the whole data, the frequency of it. So it's something like our target. We used to do dot value counts, if you remember, to check the target. Same thing like that. In this case, good representation. But if you observe the precision recall, they are not that great. So the one which gets classified the best is this one, sunflower. All right. So this is a very simple image identifier.
I have a question. How do we read that matrix that is shown above the?
Yes. Yes. So in this case, how you can read 67 of daisies have been identified properly. Okay. Now, out of that, 12 of them, which are actually daisies, are identified as the next one, dandelion. 13 of them are identified as rose, 3 of them as sunflower, and 5 of them as tulip. Okay, so find out, if you want insights out of this, you can find out the flowers which are very close to each other. In this case, you can say that daisy and rose, you can say, or daisy, rose, and dandelion. They look almost similar. Why? Because the misclassification is maximum. Or else if you look at the last 3 of them, which is rose, sunflower, and tulip, the misclassification is happening too much. So tulip, by mistake, is getting classified majorly as tulip, and rose are getting confused. Okay, so this is how you can read it. Good. And if you want to look at the correct classifiers, look at the diagonal elements. They are the correct values of your class. All right. Amit, okay.
Yeah, thanks, Krishna.
Perfect. Good. So this is one simple CNN example that you can see. Let's try to. So this is one way you can do transferred learning. One way I showed you, but that learning was not from any of the normal better networks. It was our own network. Now let's try to see one more data set where we can do.
Sir, I have a question on last.
Yeah.
Why we used padding as same?
We are not doing padding. That's what we mean by that. Okay. Padding is 0.
Okay.
Okay. So what I did was I kept it very standard. So I want you guys to basically do all the mix match possible and try to create your own net. Yeah. All right. Good. After that.
Right now in the case study that we just saw, it was a continuation, right? Where we were loading the model that we created at the upper part. So does that mean the kernel is restarting when we are loading the model again?
Yeah, the kernel is anyway.
It's the same workbook because.
No, see, what you can do is when there is a lot of noise. I mean, I'll just go into. Okay, so now you mean to say is that when I switch off my kernel and when I restart, will I be able to get the same model back? That's what you're trying to ask me, right?
Do I have to re-import the entire program, or it's just from the load model part?
Just load model part. That's it. That's it. But if you are loading your weights onto your new model, wherever you are loading, we have to make sure that the weights that we had over here, the infrastructure that we created here, should be same as this. So if your new, say, new network should look something like this. It should have at least these many layers to put the weights onto. Got it? So it is like your machine learning part. Let us say you trained your machine learned model onto 4 variables. Now, when your model is ready, when you're predicting it, if you're predicting on 3 variables, what's going to happen? It's going to crash. Why? Because it was not one more variable is missing. So you should match this. That's it. But yes, you are perfectly right. You can do it on any of the other codes, not only on this code, you can import it somewhere else also. All right. Yeah. Only thing we have to make sure is we have to get the good correct path of the file, or else what I usually do is I put it in a local directory itself, wherever I'm using the code, so that I don't have to take a headache of copying.
Yeah, so right now in this example, we saw there are images in the folder.
Yeah.
But in the case study or in the project that we have a H5 file, which I think is a conversion of images into some different. So I just wanted to understand why here we are, because we are also saving here in H5 part. But is it that we will get the coded part H5 file sometimes and sometimes images, and based on that we have to take it into account? Because the way this data set was loaded is something in a different way compared to how we load it.
Okay, so I think you were not there in my session when I explained the HDF format, right? I think this is your second session or third session, no?
My second.
Second, okay. So you were not there when I HDF basically. What is this HDF format? HDF format is a zipped file, you can say, okay, which will consist of lot of matrices. Okay. Now each matrix represents an image over here. Okay. And each image has a target variable attached to it. So in your previous project, if you remember, the target column was what number it is, and the sampled part of image was stored as a matrix. This is what is HDF format. Now in our case, what we are doing is, when we are storing it as an H5 format or any other format, what happens is it tells me, or it gives me some kind of mapping that this is, say, layer number 1, and these are the weights of layer number 1. This is layer number 2, and these are the weights of layer number 2. Whenever I import this, okay, Python interprets this and directly starts loading these weights in our current infrastructure. Got it, Amit? If you want to see in detail, give me some time. I will make one specific case study on what are the different varieties in which we can import and map the data. If you want to do that, we can do that also. We have zip format, we have tar format, we have got HDF format, we have got HDF4 format, we have got H5 format. Then we have got JPEG and PNG format also. Multiple ways we can. We down the line in one of the case studies, even what we have done is we have done embedding. That means we have directly imported the image and tagged it ourselves. That's our own format. If you guys want to see one specific case studies on all the imports, we can do that also. No problem. Let me know. Okay?
Yeah, sure. That will be great.
Perfect. All right. So can we move on, Amit? Is it good now? You're clear about it? Yeah. All right. Hey, one more. I did not ask any of you. Project is submitted, right, by all of you? I think even the score is out. Anybody wants to discuss the project solution? Do let me know. We'll do it. Okay. The previous project. Let me know. I'll dump the solution anyway, but I'm not sure whether I've discussed the solution with you guys or not. Please remind me. Okay. I might forget sometimes. Now, coming to, okay, we'll do this autoencoder last. Now, coming to this particular data set, we'll do one thing. We don't have enough time to go through the whole data set, so we will revisit it's a huge, basically huge case study. So for now, what I will show you guys is I will show you how to import findings and how to load it on the network. Okay, so just think about it, that there is a data set that I have which has different breeds of dogs. Okay, and they have the photographs and embeddings inside of these breeds. The same way we had flowers, now we have got different breeds. I think we have around 19 or 20 odd unique breeds available here. Now what are we doing is we are building our own convolution neural network as usual, my normal pattern of building it. So I'm starting with some number, say 32 5 cross 5. Okay, and my input size is exactly same as the size of my images, which is 128 cross 128 cross 3. All right. Next, say I'm having the filter size of 64 cross 64. Sorry, total number of 64 filters, 4 cross 4 each, kernel size. Yeah. And I'm keeping the standard functions the same. So I've got 1, 2, 3, 4 layers. And after that, I'm building my dense layer. Very simple. And the total number of unique outputs we have is 120. I'm sorry, I said 90, but its total unique breeds are 120. All right. So this is one example of a CNN that we are building. Now, when I run my CNN down the line, let me show you. So when we run the CNN, yeah. So when I run my CNN, say for example, for some number of epochs, say for one epoch, and each epoch I have taken a step of 8177. That means I'm running 8177 epochs as of such. When I do that, look at my validation accuracy and normal accuracy. I'm getting 0.08. That is 0.8% of accuracy, and validation is 0.01. That is 1.1% of accuracy. Underfit model, definitely. Yeah. Why we got this? Because of whatever stunt we did over here by creating our own CNN. All right. Now, what if we are stuck in this situation? We don't have time to play around with multiple stuff over here. So in that case, what we can do is we have got standard VGG16 weights. The only thing is there is a file which we have to store it. Either you can download it, yeah, from here. You can give the reference over here, or I can put it in my local directory and give a reference like this, whatever you wish. Yeah, I'm saying this is my new base model. This is my new model that I call base, and these are nothing but VGG16 weights. And here you define the location of your H5 file from where you are getting them. If you observe the format of this file, and if you observe the format of our this file, they're exactly same. So basically this format is used to store this up. Next thing what I get is I reinitialize, like put my X and Y again. So basically I reinitialize my target column and training column. Now in this, only one thing I wanted to show you guys something new was TQDM. Now TQDM is a method of generating this status bar. If you observe, what is the current status? You want to, because sometimes when the epochs are running, we are not sure how much time it will take. Definitely we have a timer here, but yes, if you want the whole stack, TQDM will help you to do that. All right. Now, next thing is, what are we doing is we are getting all the images one by one. And once we get the images, we are passing the images through our base model. What is a base model? Base model is a model that we have defined by building our VGG. So I am indirectly telling them, I don't want to take this through my neural network, my FCNN, or my normal network where I am doing forward and backward. For now, you pass on my inputs through my new weights. As simple as that. All right. And once we do that, we are building our fully connected neural network, the backend part of it, the final part of it. And then I'm compiling it. And finally, we are running it. Did you get it? How I froze the layers? Because if you remember, we are not supposed to backpropagate this. So if I would have put the weights here along with our model.fit, what's going to happen? It's going to do backpropagation and change all of our. I don't want to do that. So first itself, I'm running my inputs through our weights. I'm multiplying them. So it is nothing but your input is there. This is your input and these are your weights. You're directly multiplying it and making it as one particular matrix. Now you use this as your X train, basically, onto your final model. Got it? And when you run the model, if you observe, the last accuracy we got is around 98.39%. So it's a better model than the one above. Are we clear? Guys, any confusion onto this? The freezing part of it and non-freezer part of it?
Freezing is multiplying our current input with weights.
Weights, exactly. So what I'm doing is, in hurry, I'm having my images or my X training data. I'm saying it, whatever weights I've got, multiply with the inputs and make it a bigger matrix. And now use this as your training data with your FCNN to do front and back propagation. Now, even if back propagation happens, do you think it will change anything for training data? Nothing. It will change everything on your FCNN. Because it will not get it that this is a neural. And what are weights? Weights are nothing but some kind of matrix. Very simple. All right. It'll take some time. So it'll take a week's time for you guys to get normal to this way of coding. Yeah. So give some time, try exploring this. So now I will deliver both the codes to you. What you people do is, in this particular, the earlier code that I've shown you, instead of using my model, you use this VGG16 model and see if you are able to improvise. Okay. And this, from here down the line, it's a universal code. It will work for anywhere. No problem at all. Good. Everyone clear? Let me go through. Harish, Akash, Avmeet, Dhruv, Kaushik, Kranti, Raghu, Saurav, Shakti. Are we all clear on this?
Yes.
Yeah.
Krishna, for this one, you have imported OpenCV.
Yeah. So yeah, that will come to it. So the way we are getting the images will come to that. That's what I'm saying. We'll do this. We'll redo this case study in detail.
Okay.
So it's supposed to be a mix between week 2 and week 3 actually. It will be very heavy if I go through it right away.
Okay. Sure.
So we'll redo this, but I just wanted to give you the idea of transferred learning. This is how we do transferred learning majorly. I don't waste my time doing this. I'll directly pull out the data. Right? The only drawback of transferred learning is, first thing is you have to, I will say, completely depend on their weights. Tomorrow, if they remove the stuff from online or their support, we are helpless. The model will go down. And second issue is that if the weight is not trained on that particular set of images, let us say you want to build a neural network on space images, we should have some network pre-trained on that, right? If it is not trained on that, then we'll not be able to use it. That's the only two issues. Otherwise, everything works. Okay. Perfect. Yeah. So these are the two. We'll redo this. We will go through again, and if possible, we'll do live coding so that we get hands-on to the complete coding part. Yeah. And also, I want to give you the complete flow. So, what is the standard flow of a CNN? Okay. What do we do? What should we do? And all this. Okay. So this is one thing. Now let's come to something onto auto encoding. So if you remember that dimensional reduction technique that I was talking about, a very simple code where we have the same MNIST data, handwritten data, and this is the original image, and this is the undersampled image, or I will say the dimensionally reduced image. Good. How do we do that? Get the libraries, get the data, reshape the data, normalize the data. Decide that from this level of input, how much you want to come down to. So say I want to come down to 64. Depends on you how much you want to reduce the dimension to. Okay. So once I come down to that, you do all the resizing or reshaping thing on the image part of it. Next, we have to call our model. So if you observe here, what do we have? We have got an input. So I just explained you guys what is on the autoencoder. This is your real input. Then you will have some encoding part of it, and then you will have some decoding. This is encoding, this is decoding, and this is your output. Okay, so this is my input, this is my encoding layers, this is my decoding layers, and this is my autoencoder layer. So if you observe here, I'm not writing multiple layers, I'm just writing normal dense layers here. And other things I think are self-explanatory to you guys. All right, so this is another alternate way of creating a Keras dense model. 4 lines, enough. After that, what are we doing is we are calling our backprop and fitting the model. Now, while fitting the model, what are we doing? We are increasing the batch size. We are having some epochs. We are saying shuffle is equal to true. Shuffle in the sense, if you want, you can do some augmentation part of it. And test and train split we are doing here. We are saying 80-20 split, basically. Okay. So validation is nothing but our testing data. So when I run it through, and if you look at the accuracy part, I get around okay, there is no accuracy here. I'm really sorry because we did not put the metric over here as accuracy. I just wanted to see the loss part, how much loss we are having. And if you observe it, the loss percentage is not that great between both of them. All right. Now, how we see this image, how do we observe whatever we have done is good or bad? So in that case, we'll call the autoencoder.predict onto our testing data. And then finally, we'll plot the original data versus the testing data. So the only showstopper here is im.show. That's it. You are supposed to know this. Okay. How a matrix gets converted to an image, im.show. As simple as that. And what shape and size you want, even you can specify. So here I've got 28 cross 28. This is the original image. This is the dimensionally reduced image. Now, if we are not happy with this, so let us say if you are making a implementation where when a security guard, let us say, runs the device through some of the cars, they will get the number plate automatically, or by looking at the logo, they will get the make of the car, or by looking at the car, they'll get the color of anything. Here, you don't need a HD image. You don't have to compute or spend a lot of time and money on hardware on this. Reduce the image and then compute on it. This could be a very simple application. Okay. So this is your autoencoder. Good. There is one more dimensional reduction technique. I'm not sure if you guys have heard about it. Have you heard about TSNE?
No.
It's part of supervised learning. No? Yes or no? No, right? Okay, let me know if you guys are interested. I will show you something on this also. It's
Yeah,
not a
sure.
part of our course anyway, but it is. I feel it's a little important sometimes. So let me show you first of all why we need TSNE and where and all in deep learning you will need it. So something off the track, huh? Not as a part of our course. This is what we do in industry. I don't want you guys to miss it. Say I have module number 1 minute. Huh? Yes, got it. Okay, so it is a part of NLP. So I showed something extra to some of my batches. Now, if you look at computer vision, we saw today what all transferred learning can be done. That is VGG, ImageNet, LXNet, LeNet, and all. Same thing you can do it in your NLP also, where we already have some kind of encodings available, ready-made. So the first encoding that we can see here is glove. Another one could be Elmo. Another one could be word2vec. So word2vec is developed by Google. So these are standard embeddings that we have. We'll directly import it and start using it. This is what we mean by transfer learning. So again, it's an example. So what if I say that in our text? So what is this case study about? Is we have got a huge text available with us. Now I want to know that, let us say, I want to predict something. So I will say the prince, today's prince will be tomorrow's question mark. Okay. So what we can do out of this? So I will say today's prince is tomorrow's dash. What is it? So obviously you guys will know, okay, prince is nothing but tomorrow he'll be a king. What if I remove the prince and say today's princess or today's queen will be tomorrow's what? We don't know. So this is used when you want to do some kind of prediction. Now the best example I'll give you is LinkedIn. So when you are messaging on LinkedIn, you guys have observed now. So for example, if Harish sends me a message on LinkedIn, something. So it will give me some kind of tokens if you've seen it. It will first say, hi Harish, good morning Harish. Sure, depending on the data or what is written on that, it will also predict me, sure, we'll meet tomorrow, or sure, I will do that or something. How do we get these predictions? We use something called RNN. Okay. We use RNN to do this. Now, what is RNN? It's a different network, recurrent neural network. We'll do in NLP anyway. But RNN auto uses, or we can sometimes auto use glove. Glove is the way you did VGG and all in CV. In NLP, we can say ready-made network. So this is called global vectors, basically, and it is developed by Stanford University. Now, what I do is I will show you. What if I want to predict what is the nearest encodings to king? So from our corpus, if you remember what is corpus, I've showed you our chatbot. Corpus is a set of huge data available to train your model. Okay. Now, what if I say, give me the top 5 words, 1 to 6 means 5 words, which are very near to king. So if you observe queen, monarch, prince, kingdom, and reign, from our corpus, he is able to find these are the 5 predictions. Which one you want me to send? So I will say share the top 3 predictions always. Something like a recommendation system, I can say, for text. All right. Now, why am I showing you this? Because here, if I want to represent this, what if this is all backend? I'm sure you guys wouldn't have understood what is the data, what is he talking about. If I want to represent this, what if I represent my tokens from my corpus? Are you able to visualize this? Not very great, but you are able to see that yes, there are some words which are tightly packed. That means they are very near to each other. There are some words which are almost away, but yes, they are nearer. So if you can observe university and college, okay, school and education, hospital and health, you can observe that these words are tagged together. Now, if you ask me how, that's again a different topic, how I tag them together. But glove will help me to do it. Okay, so how I represented this? How did I convert a higher dimension image to a 2D image like this? We use TSNE over there. So let me go to TSNE. What is TSNE in a very simplistic way? It is a supervised learning dimensional reduction technique. So far, we have done unsupervised learning dimensional reduction technique, that is PCA, right? In this case, what we'll do is we will say there is a 2D data and we have got 4 points, say 1, 2, 3, 4. I will say this is point number A, this is point number B, point number C, point number D. Now I will say the distance between, okay, let me not give the answer now. I will ask you guys, what are the similarity measures that you have seen so far? Guys, how I can find similarity between 4 points?
Cosine similarity.
Distance.
Cosine similarity, Pearson similarity, and distance. This works majorly. Okay. So in this case, let me say that I'm saying distance could be one of the similarity matrices. So I will say, for our convenience, I will say each one of them is at a unit distance from each other, and the diagonal elements will be a distance of square root of 2 from each other. Agreed? Pythagoras theorem. Yeah. Now, how would I reduce the dimension? Let me ask you. I want to reduce the dimension to 1D. How should I do it? So to do that, okay, let me not ask you. Let me show you something, then I'll ask you. To do that, what I will do is I'll pick up a point of reference. Let us say I'll start with A. I will put A over here. Now, next to A, what do we have? We have B, we have B here at a unit distance, and we have D at a unit distance. So now, if I say the distance between A, D, and B. So now we are kind of close. So if I keep distance in my mind, and if I replicate them on a 1D space, I can transform them like this. Now, please remember, how am I transporting? I'm saying that I will make sure that I don't change the distances. And right now, the similarity matrix between all of them is distance. So I have maintained distances between A, B, and D. Agreed? Everybody agrees to that? Now, what about C? Where should I place my C? What if I place it here? Because if you remember, the distance between D and C is 1. Correct? And the distance between A and C is also square root of 2. So if I place it here, if this is C, what is going to happen? B and C is going to be far away, whereas B and C is kind of 1 itself. So what if I place C here? Now it's satisfied, but now D will be an issue. So A is anyway satisfied with both of them, but D and B are creating some issue for C. So this is a problem if we take this configuration.
Alright guys, on that note, let us get started with the first item on the agenda. Introduction to OpenCV. Now guys, OpenCV is one of these libraries that are present in Python, which has seen a lot of usage. Now, as you heard at the start of this video, how do you think your computer, or how do you think Facebook even knows that as soon as I upload a picture of me and my friend, how does it know whom to tag? How does it know that it's a picture of a person? And probably recognizing that it's a person can be easy, but recognizing who it is among millions and millions of Facebook users, and of course through your friends, that is what takes skills, right? So OpenCV is not a standalone thing wherein you're teaching your computer how to look at images, but 99% of the applications that we use is where OpenCV is a part of it. Right now, I can assure you all, even though you might have not uploaded a photo to Facebook and tagged your friends automatically there, I promise you that you have used OpenCV and you might have had a very good chance to take a look at it. Right now, every time you open up your mobile phone and go to scan a QR code, how do you think your phone understands that it is seeing a QR code and it has to only scan that part, right? Give it a thought. Every time you eat at your favorite restaurant, every time you step out, I hope all of you are wearing masks while you do. Now, when you go on to do that, when you're going to eat or something like that, you realize that paying with UPI is a very simple click of a mouse button or your phone click, right? Now, you might be not exactly zooming in on the QR code that is present on the UPI scanner, but at the end of the day, if you just point it towards that direction, your phone automatically picks up the UPI ID, the QR code, whatever it is, and eventually you can send or receive money, right? So how does this happen? Now, OpenCV actually stands for Open Computer Vision. The CV there stands for computer vision. So what is computer vision should be the first question all of us are asking now. Well, to give it to you in a very simple manner, computer vision is basically finding a very simple way to help your computer or any machine for that matter understand what it is seeing. Now you might be a person who says, hey, I have the latest and the greatest computer. It is the fastest one. It's a gaming machine. It's super intelligent. I agree. But at the end of the day, even the most powerful supercomputer that we have in the world, at its most functional level, right? The more in depth you go, you will realize that your computer does not understand anything apart from zeros and ones, right? Of course, we're hunting towards artificial intelligence, but you have to realize that your computer works on zeros and ones. Now, when that is the case, of course, it will know how to open images, how to read images, write images. You have done all of this probably in your childhood. All of this is done, but at the end of the day, not just opening an image on Windows or Mac or anything, but making your computer understand what it is that it is seeing is a key part of computer vision. Right now, there are many popular applications of computer vision, and one thing that pops into my head right now is the one where people are doing mask detection, right? Now, you might have seen a couple of trending YouTube videos right from the start of 2020 till now, where multiple developers are actually, devising algorithms together and logic together, which will eventually look at basically it's a webcam feed, and as soon as it sees a person, it tries to detect if this person is wearing a mask or not. How amazing is this, right? And if you're a person who travels often, you might have seen automated check-ins done at the airport as well, right? So you just look into a scanner, it realizes that it is you, and eventually you're cleared and you have to go through all the security and all of that. So how does it know that it is you, who's standing in front of the camera there, right? Again, computer vision. So basically what we are trying to achieve with respect to computer vision is we are bridging the gap that exists between computer software, which at the end of the day works on zeros and ones, and the actual visualization that it has to see and understand, right? This is very important. Now, you are trying to make your computer more intelligent even with a basic library such as OpenCV. Maybe you give it a picture of a fruit, right? Or you send it a picture of a cat, you send it a picture of a dog, and then you say, hey, what is it that you're seeing? Now, this is very popular in machine learning. We call it as a classifier. Let's just say you give it a couple of images of the fruit orange and maybe a couple of images of apples, right? Now, as soon as you train the machine learning algorithm to make it understand what an apple looks like, to make it understand what a orange looks like, it can figure things out on its own. You can give it hundreds of different images of apples and oranges and it can still try to figure it out, right? Now, that is with the power of machine learning, which again, OpenCV is 99% used alongside with. But you also have to understand you can use OpenCV in a standalone mode, wherein you can just work on basic image operations, you can work on resizing it, you can work on adding text, you can still work on face detection without having to use any other complex dependencies. Right? So getting your computer to not just look at a picture, but to understand what it has is everything you guys should know about OpenCV. Now, face recognition, as I mentioned, is the most popular application that has come out of OpenCV. Now, the name itself, OpenCV, is basically telling us that it's an open source library. When usually a library is open source, ladies and gentlemen, there are thousands, if not millions of developers who just add on to the tool, who just add on to the library to make it way better than what it is, right? Similarly, Python is an open source programming language as well. That's the reason you see millions and millions of developers and you see these rapid progressions in the versions of not just OpenCV, but also Python as well, right? Now, that is one thing about OpenCV. The next question you must be asking yourself right now is saying, okay, so it's OpenCV, it works based on computer vision. You know what computer vision is. But what are some of these programming languages that we can use with OpenCV, right? You might think that, hey, is Python the only programming language that will work with OpenCV? Now, I am sure that you guys might have watched other videos. I'm sure that you guys might have done a little bit of research on this. And 90% of the time, whenever someone talks about OpenCV, it has to be Python on the other side, right? Now, Python and OpenCV, ladies and gentlemen, they go hand in hand because of the fact that Python provides you a superbly easy syntax to work with, and OpenCV talks really well, and at the same moment it is also efficient when it works with Python. But to answer the question, no, it is not only Python that OpenCV can work with. It can work with programming languages like R programming language, and of course there are many other languages as well, right? So if you're on the data science and data analytics train, R programming language and Python is what you'll be primarily using. If you're doing face recognition, you want to do intelligent face recognition based on machine learning, AI and all of that, OpenCV should be your go-to library, right? Fantastic. Now to talk about on which platforms can you actually install OpenCV and work with, right? So what are some of these platforms? Does it work only on Windows? Does it work only on Linux? No, guys. There are a lot of features given to you in OpenCV, and most of these, if not all of these, actually work on all the platforms that we have today, be it Windows, be it Linux, and of course for all you people who use Apple devices, it's available on the Mac OS as well, right? So it's open source, it's free to use, it's very powerful, it talks to multiple programming language, and it is almost platform independent, because at the end of the day, these are the three major platforms that people use, right? So you should already have a concrete understanding of why OpenCV might be so popular. Now, if this was a very niche paid tool that was available to the market, you have to understand that not everyone would want to be willing to spend their money or maybe spend their time if it does not have a large scope. But OpenCV is not the case here, right? OpenCV, the second OpenCV came out, of course, it was open source, and everyone realized the power and the potential of it. Of course, back then when OpenCV came out, of course, we did not have a lot of computation power. We did not have very efficient ways of teaching our computers how to look at images. But now this is a piece of cake for the computers, right? Once they understand and once they know how to work with images, and there are libraries in Python, these are like the helpers that will basically help not just the computer, but us as the programmers as well, right? Superb. Now with this, you must understand where OpenCV fits into the picture, right? If we are talking about face recognition or face detection, let's just say. So you have an image, your computer looks at the image and it has to figure out where there is a face in the image, right? So where is OpenCV used, and if not, how is it even used in these steps? Well, ladies and gentlemen, let us start out by understanding the 4 very simple steps about how OpenCV sits into the picture. The first step, whenever you go on to do any sort of, let's just say, face detection again, is the fact that you're going to be gathering some information. What is this information? If you are actually going to do face detection, you're going to require a picture of a person. You're going to require an understanding of what a face would look like, right? Now, there's multiple instances where maybe you fed the face of a person looking straight into the camera, your computer understands it. But as soon as the person turns to the side like that, there's a very good chance your computer doesn't even know it's a face that it has to look at, right? So all of these things, you have to make sure that your data is very well intact, not just high quantity, but also high in quality, so that your computer can figure out what's going on. Once you have all the data in, the next thing is you have to bring it to a format and you have to do a little bit of pre-processing on it, right? Nowadays, what happens is all the pictures that we click on our mobile phones, on our DSLRs, on our GoPro cameras, whatever it is, these are images which are either in the definition of 4K or Full HD. These are really large images, right? Now, it so happens that you don't have to provide extremely high quality 4K, 8K images for your computer to understand. Absolutely not. Even an image such as 600 by 600 pixels is something your computer would understand. And in fact, it is something it would prefer because it is super fast for processing. And once you actually process it on a tiny part, on a small image, replicating it on a big one shouldn't be that much of an effort, right? So this is where you would think about getting your process to speed up. To speed it up, you just have to go down on the image size and eventually still hold the same meaning, right? You cannot skew the image and expect your OpenCV library to help you understand all the images or maybe figure it out on its own. So a little bit of pre-processing side is where OpenCV is also critically dependent upon. Now, once processing is done, the next thing that you will have to take a look at is model training. Now, model training is the part where you'll be using all the data that you have gathered and eventually telling, sending the data to all your algorithms that are running and saying, hey, here's the input data. Here's where you'll find all the faces. Now, you're basically training it to understand what a face looks like. And as soon as it figures out a face, for example, facial features include nose, 2 eyes, eyebrows, a jawline, beard, mustache, and all of that, right? So all of these things, if you train your computer to say, hey, if you find these kind of patterns, just understand that looks like an ear, that looks like a nose, that looks like an eye. Once you do this for hundreds and hundreds of images, eventually it knows what it has to be done, right? It is a very simple part that OpenCV can fit in all of these roles, but usually it's a step-by-step procedure, right? Now, after model training, what usually happens is you have to check if your model is working as expected or not. Sometimes you would have asked it to recognize a face, but there's a very good chance it would have, recognized someone else's shoulder. It might have picked up the neck area or something else, right? So something has gone wrong if that has happened. Now you can actually evaluate, assess, and trace the conditions upon which your OpenCV library is being used on to check where something has gone wrong. Once you figure out where which metric is feeding wrong data, or maybe you have a human error in you actually providing the data itself to the OpenCV library, in those cases you can figure out where it is, evaluate the performance of the model. You can even tune it to make sure that it works faster, it works better, and it understands how it can go on to not just recognize faces but understand computer vision to a good amount of depth. You can do all of this in a very simple manner using the OpenCV library. Of course, we are going to be taking a look at a good amount of practical sessions to make sure that you guys understand this, right? So I hope with this, we are clear about how OpenCV is used. So if OpenCV is used in that way and it fits in all of these different, different methodologies and different steps that we just spoke about, what is it that you have to know about OpenCV and Python, which is very important? Well, one really important thing that you should know about is that when OpenCV was built and at the same time when Python came about, of course, Python is very much older than OpenCV, but as and when development happens, OpenCV was developed to multiple versions, Python was developed again to stack multiple versions as well, right? Now, in that case, basically OpenCV was being developed to not just be used with Python, but to be effectively used keeping performance as the most important metric. Now, when you have performance as a criteria, it becomes a fact that you want OpenCV to work really well with all the existing data structures and the libraries that are present in Python, right? Now, if you have worked with Python, you will know that there are two very nice libraries to work with if you need an extended hand with respect to mathematical operations and statistical calculations. Now, these are the libraries called NumPy, which basically stands for numerical Python, and the Pandas library. Pandas library provides two beautiful data structures for us to use. It's the series data structure and it's the data frames, right? So when you go on to work with all of these libraries, or let's just say you're a person who already knows how to code in the Python programming language and you're jumping to the image processing side of things and you want to understand OpenCV. Well, if that is the case, if you already know NumPy and Pandas, you have to understand that OpenCV is built in fact to make sure that it works really, really well with these libraries, right? So having the understanding that you can use already existing libraries and bring in a new library which will again work fantastic with these will give you a lot of flexibility, because at the moment you'll not have to worry about any sort of complex syntax that OpenCV might bring, because that is solved with Python. The next thing is you really do not have to worry about performance tuning or getting started with performance tweaking right at the beginning. Again, why? Because OpenCV and Python gel really well together, and again, you don't have to worry about that for a good amount of time. So eventually you'll only be worried about the logic. It is about how you will get from your problem statement to the actual solution. And this should be hugely advantageous to you as a developer, especially a person who's working in OpenCV, because you will have the time and the effort to actually spend time solving the problem rather than breaking your head about complex syntax. That is again another huge advantage which put OpenCV on the map, and I'm sure you guys will appreciate it as and when you start working on it as well. So once we are set up with OpenCV, as you saw, it is very straightforward. It's a simple click of a mouse button and running one or two commands. Once you're done with that, you should be very curious to find out how the entire process of computer vision itself works, right? We spoke about OpenCV. We spoke about where OpenCV fits. We spoke about how OpenCV works in multiple steps, right from bringing in your data all the way to using your data to perform some data visualization or driving some metrics based upon that. We discussed that, but what we should also take a look at is to make sure how your computer looks at an image, right? Vision, we're talking about vision. So how does it understand that? It is very simple, ladies and gentlemen. There are 6 important steps of getting computer vision to work. Let's take a look at each of these steps. Step number 1 says inputting the image to make it accessible to the computer. Of course, you will have to input the image as in you might have seen a JPG image, you might have seen a PNG image, a GIF, which is basically a graphical image, right? Now, all these various types of images, you can find out the compatibility with respect to OpenVision. Of course, the most common files that we use is a JPG, and I'm sure it's a PNG as well, right? So when you're inputting your file to the computer, you're going to be having a file with this extension. You're going to send it and make sure your computer understands this. So how do you get to the point where it understands that? That's where the next step comes into the picture. Step number 1 is just giving the image to your computer. Step number 2 talks about extracting RGB values of each pixel. Let's break this sentence down, right? So let's just say there is an image on your screen right now. Of course, this is an image of a face detection example, right? So as soon as I see this, I understand it. But how do I get my computer to understand? Well, you have to realize that an image is composed of pixels, right? Now, when I say I can shoot in 4K definition or I can record in 4K definition, what I'm basically meaning is a definition. It's an aspect ratio, not just an aspect ratio, but the resolution that goes alongside with the aspect ratio, right? For example, you might have heard 1920x1020. Well, 19201080 is nothing but the resolution, the number of pixels that goes into making the standard, what we call as full HD or full high definition, right? So each of these points that you see here, there is one pixel that is basically lighting up to add purple color to this, to maybe add blue color to this, to maybe add yellow color here, right? So each of these colors, they're basically called as channels, and you have to understand that there are 3 primary colors, red, green and blue, and with just these 3 colors, it is possible to create any other color that we want, right? That is the reason we consider these as the standard. Now there are multiple other colors as well. When you think about cyan, when you think about yellow, when you think about black, with which you can also create multiple colors. But of course, the most popular version, the most popular model that we have is the RGB model, right? Now, once you go on to extract RGB values, as in, let's just say, for example, that this image is maybe a 300 by 300 size image, right? Now, what is 300 multiplied with another 300? That is how many pixels that you have. And each of those pixels will have one red value, one green value, and one blue value, which will eventually together work in hand. It will work together to give you a color, right? Now, if it is blue, just one shade of blue can turn on. But look at this. So on your screen itself, you have 4 shades of blue, right? Now look at this. The tab on the left that I have is a different blue. The one on the upper side of the title is blue. This is also blue. We have a blue in the OpenCV logo as well. And of course, we have multiple variants of blue, purple, and all of that put on the screen here. So instead of you just saying, hey, since it's just blue, just turn it on and just leave it at blue. No, that will not work, because it is not just one color that we're talking about. We can create millions and millions of colors. So extracting the RGB values for each of these pixels in an entire image is step number 2. Once you do that, once you pick up each of these values and you tell your computer that these are the values of these colors, it will have an understanding of what is going on. Now, if you're trying to send a picture of, let's just say right now what you're seeing on the camera feed, right? If I click a picture of it from your perspective and send it to the computer, it will know that there is a background here and there's a face here, right? So the background will be lit up because it looks white, it is bright. So there are a lot of background values. In fact, that is what your computer is doing at the moment right now. As soon as you're watching this particular video, you are loading these multiple pixels and it is showing you all these outputs, right? So getting your computer to know, not just to showcase this output, but also understand what it is, that is what comes in the next couple of steps, right? So at this moment of time, we have inputted an image to the computer. It knows that it is seeing an image, and we are also giving it the RGB values that are present for each of the pixel. It already has these values, but to use it, we'll eventually have to do all the magic that comes after this, right? Now, the most important thing that I already told you about regarding resizing of images, right? You can have 19201080 images, you can have 4K images, you can have 8K images, but for all that matters, your computer really does not need an extremely high quality image. And it is also easy to say that, hey, can I give it a very, very low quality pixelated image and get it to still figure things out? Well, no, there is a fine balance between quality and of course quantity as well, right? So if you look at an image and if it looks slightly pixelated, maybe you can figure it out. Now, if I give you a very pixelated image and you cannot figure anything out, well, if you cannot understand and think of the state of your computer, right? So it becomes very important that while resizing these images, you're still keeping the resolution intact, you're still keeping the aspect ratio intact, and you're making sure you're not skewing or messing around with the image, right? So if you just stretch the image in one direction, what do you think is going to happen? It's called a skewing, right? Now, skewing is possible with respect to OpenCV. In fact, it can also recognize and understand what it can do about skewing as well. But again, that is again out of the scope of this particular tutorial. But with respect to step number 3, it becomes important that you guys understand that you'll have to resize some of these images, not just for the purpose of efficiency, but to make sure it works faster and you can use the same learning for bigger images later on if required as well, right? That's step number 3. Coming to step number 4. Step number 4 talks about how you can go on to perform image recognition or be it image detection by making use of some algorithms which are very popular for this. Now, image recognition, as I told you, right, you're going to be using a lot of images to train your computer, and as soon as it understands what it is seeing, then you basically ask it for recognition, right? So first you do detection. Whenever you go on to learn OpenCV, that is what is suggested, right? You start out with the basic operations, you understand how it works, then try to get your computer to detect something on the screen. Once it detects, when it says, hey, there is a face in the image here, next get it to work on recognizing who is the person that is present on the face, right? Now, in fact, if you are a very active user on Facebook, you will see this is exactly how the concept was developed. Previously, Facebook really did not understand or gave you any features. You had to manually click on the tag option, go and click on the person's face and then do it. Then a couple of years ago, you would just hover your mouse around the face of the person and it would detect saying, hey, there is a face detected. Who is this? It would ask you a question saying, who's this, right? That is when it is detecting the face, but it is not recognizing the face. And I think it was 2-3 years ago, that's when Facebook completely implemented face recognition, wherein you don't even have to hover your mouse around it. You upload an image and it will automatically realize who it is that is present on the screen. So to detect who it is that it is seeing, it has to first of all detect that there is a person. It has to detect who it is seeing, which we call as recognition, right? So it's very common for beginners and for people who have never worked with OpenCV to dive right into the heart of the concept and to work on recognition. But if you do not understand detection and if you do not understand the basic operations that will govern everything going ahead, it becomes difficult, right? So with respect to step number 4, understanding detection, knowing how recognition works and feeding all of these to your algorithms, which will do the heavy lifting for you, is important. Now coming to step number 5. Step number 5 talks about adding artifacts that will help you with step number 4. Step number 4, let's just say I gave my computer an image. For example, this is the actual image that we are going to give to our computer, right? If you take a look at it, there is a rectangle that is drawn on the face. What is the purpose of this rectangle? The purpose of this rectangle is to tell us that there was something detected in that particular region, correct? Well, to do that, your computer must have the capability to not just recognize the image, but also be able to change the image. When I say change the image, it has to draw a rectangular box on this image, right? Now to do that, that is what we call as artifacts. Whenever you're running any sort of face detection algorithms or face recognition, it usually puts a rectangle box or a square box around the face. Now what it is basically doing is it is either editing the same image that you provided to it, or it is creating a copy of it and doing basically working on another image wherein it will use the exact same image, but now it knows the coordinates in x and y axis where the image is, where your face is. So it will basically go draw a rectangle around it, which will not just tell the computer where the face is, but it will also tell you in a very simple manner, right? Now, if I gave you an image and if I told you, hey, there is a face at the coordinate 400 by 400, 300 by 300, 200 by 200, something like that, if I tell you, you'll be very confused saying, okay, I don't want these. I want to see where it is, right? That's the reason why we draw an artifact as well. Once you are done with the artifact drawing, maybe you want to add some text. It's possible. Maybe you don't want to add a text. Maybe you just want to add rectangles, circles. You just want to add a frame to it, border to it. Anything such as these operations are possible. Step number 6 is very straightforward. If you're followed through from step number 1 to 5, step number 6 is just finding the best way to display the result. Now displaying the result, you can just show it on your screen, you can save it to the same file, you can save it to another file. A lot of opportunities are there for any sort of flexibility that is required for you guys to actually set up and go on to use these, right? Fantastic. The next step that we're going to take a look at the process of computer vision is to understand some functions that we have. Now, with respect to OpenCV, there's multiple helper functions which will basically ease your load about what you need to do. For example, let's take a look at the first function, the cv2.imread function. Imread basically stands nothing for image read, image write, image show, right? When you say image read, well, you're trying to use it as an input to just pass the image to your computer. If you're talking about imshow, or where it says image show, well, what are you trying to do? You're trying to show the image on the screen or in the working environment. If you're working in PyCharm or if you're working Google Colab, the output will be shown on your screen right there. But this doesn't mean that the changes that were shown on your screen, maybe you added a rectangle, right? Maybe it added the rectangle in the wrong place. So you just want to see it and not write it to the actual file. That is when you'll be using the show function. The show function basically just puts out a sample output on the screen so that you can see and verify if it has done something correctly or not. Now, once IamShow is done, the next thing you'll be taking a look at is IamWrite. Well, once you're done with looking at the image, the face either detected correctly or it didn't detect correctly, the next thing you're going to do is actually write it. You want to save it, right? This part is done very, very easily by this function called as ImageWrite or IamWrite, guys. So these are the three really important functions that you have to know. But how does one go on to use these functions? Well, to answer that question, let us quickly take a look at the syntax of these functions and understand what they do. Firstly, we have the IamRead function, the ImageRead function. So you are supposed to give an image to your computer here. Well, there are two parameters you have to take into account. One is the file path and the other one is the flag. File path basically tells you the location of where the file is so that your computer can go there and pick up these files. And flag basically specifies how you're supposed to read these images. Now, we spoke about RGB values back then. Now, RGB talks about colored images. But what if there's a case where you only have a grayscale image, right? Now, when I say grayscale image, we call it black and white usually. So there's only one color channel that has to be picked up there instead of three color channels. A color image will usually have three color channels. A grayscale image will only have one, which is nothing but black or white, correct? So a flag specifies if the image is actually a color image or if it's a grayscale image. And there is eventually one thing you have to understand is what does this function return when you execute it. So when you execute this particular function, it will give you an image that is nothing but loaded from the same specified location that you guys put in the file path, right? We are going to take a look at this practically, so make sure you guys are staying tuned, right? Now, once that is done, once IamRead or ImageRead is done, the next thing we need to take a look at is ImageShow. With respect to ImageShow, you're trying to get it displayed onto the output window, right? In that particular case, there are two important parameters that you have to take into account here. One is the window name and the other one is the image to be displayed. Window name basically talks about the name of the window which has to display the file in. Now, if I give it one image, I just call it face, and the output that I want from it after face detection is maybe like face detection.jpg. That is where I would call, I would use that name. So whenever you open that window, it will give you an output on the top having that particular title that you mentioned in the window name. And of course, the next parameter is the image that has to be displayed, right? So what is the return value that you get when you're using ImageShow? Well, there's no value or there's no Boolean operation that you get, but eventually what you see on your screen is nothing but the actual image itself. So it returns an actual image, but no return value is required for that function. Once we're done with that, the next function we need to take a look at is the IamWrite function, right? IamWrite or ImageWrite is basically you taking a file from a file path and saving it for your requirement. As I told you, you have given an image of a face to your computer, face recognition is done. You want to save the output now. To save the output to another file is where this is required. So of course, you have to give it the actual name of the file, as in what do you want to call the file as. One very important thing you have to make sure when you're giving the file name to be saved is to add the extension to it. It's going to be either JPEG, JPG, or it's going to be something like PNG, right? So you have to add the extension specifically, because it'll when it goes on to save it, if you have not added an extension, your Windows Explorer might have no clue about which type of file it is seeing. So it doesn't know what application it has to use to showcase this file to you, right? So file extension is very important. But if you just use the IAMWrite function, it will not give you an output on the screen. It'll just tell you if it has stored the image or not. So basically the return is a Boolean operation, and it'll say true if your image was saved successfully. But if something went wrong, your file name was incorrect, or you gave some incorrect parameter to it, or your syntax is incorrect, you'll get an error, or it'll say false, as in this image could not be saved, right? So it becomes very important for you guys to understand that the return types of these three functions differ a lot. With respect to IAMShow, you actually got the actual image as the output. With respect to IAMWrite, you didn't get the actual image as the output. Of course, the actual image was saved on your hard disk, but it gave you a true or a false on the screen to indicate saying if something was saved or if some operation was performed or not. Right? Now that we know what OpenCV is, we know that you have used it, we know how you can go about understanding it, how it works, where it fits, and how well it works with Python. Once we know all of these things, it becomes key, ladies and gentlemen, that you understand how you can go on to install OpenCV by yourself, right? Now, installing OpenCV is really simple. It is really straightforward, yet at the moment of time, it can get a little complex. It can give you a couple of errors. It might not work as expected with any of the Python IDEs that you might have. Some of you guys might be using PyCharm. Some of you guys might be using something else, right? Now, there are a lot of IDEs for Python, and you can be using any one of them. This is not IDE dependent or IDE specific, but at the moment while you're configuring it, things can go wrong. So just to make sure that you guys are starting to install OpenCV at this moment of time, you have to make sure of one thing, ladies and gentlemen, that you have the latest version of Python and the latest version of pip, which is basically the Python package manager. You have to make sure you have these in hand, because again, as I told you, right, OpenCV is developed along the sides of Python. So when there is something new, or when there is a bug fix that is done in Python, or maybe a new feature is added, OpenCV will ensure that it will make the full use out of all of these, right? So it is always recommended that you guys have the latest versions of Python, latest versions of pip, and of course, when you're installing it by running the command that you see on your screen, you will be installing the latest version of OpenCV, right? So pip install OpenCV Python is a very simple command to check it out. But are there any more easy ways to go on to install Python? Well, running one command, if that was not as easy as you thought, well, if you are using something such as Google Collaboratory is nothing but a Jupyter notebook that is hosted on the Google Cloud platform. Now, if you are a person who's using that, you do not have to install OpenCV specifically or exclusively, because it comes installed with that. All you have to do is verify if you have your piece of code ready and eventually start using it, right? Now, take a look at your screen. Once you go on to install it, be it on Google Colab, be it anywhere else, you have to verify that it has installed correctly or not. So just run a very simple command, import the library, and eventually run the second line here that you see, print cv2 __ version __. This will ensure that at the end of the day, if you have your OpenCV ready and working, this will print out the version of it, right? Now, let us actually take a quick look at the installation procedure and eventually about how you guys can begin working on this. Now, I'll do a quick Google search on OpenCV and let's head to their page right there, right? Now, as soon as I go on to the OpenCV page, they've given you a lot of introduction about their page, becoming they're giving you the GitHub documentation. They have a lot of forums in which you can go on to talk to a lot of people, ask questions in case if you have any doubts about it. You can report any bugs in case if you're a developer, their wiki, their services. So ladies and gentlemen, you will find a lot of different things about OpenCV. Right now, let's just search for installing OpenCV in Python, right? That is what we are after now. As soon as I go on to do that, you will see that no matter what website you go to, they'll just say, hey, it's basically pre-built to make sure that you can work on it. And all they say is, again, the same thing, right? Import CV2 and work with that. Now, I told you that with respect to Google Colab that it comes installed with it, so I don't have to install it manually, right? So this is what Google Colab looks like. It's a very simple Jupyter notebook. Now, if you have not installed OpenCV, you would run this first line that I just showed you, right? Pip install OpenCV Python. Now, in my case, I don't have to run this at all because of the fact that with respect to Google Colab, I have OpenCV already installed and ready. So what's the step after installing it? It's verifying and checking it, right? So I'm going to import CV2, which is a library, and I'm going to eventually print the version that goes alongside that. Now, as soon as I hit play, you can see that the version of OpenCV that is installed is 4.1.2. So if you have a similar output, as soon as you run the command and you have an output which gives you a version rather than giving you an error of any sort, it means that you are set up and you are ready to go on further and take a look at all the practical things we will discuss in this session as well. Right? So after we check out these functions, guys, the next thing you should be wondering about is what are some of these operations that you guys can do when you're working with OpenCV, right? Well, here are some really important operations that we are going to be taking a look at. For example, how do you read an image? How do you input the image and ask it to print its dimension, right? Dimension basically talks about the resolution of the image. So we'll check it out practically saying how you can go on to do this. The next thing is we're going to have to extract the RGB values of the pixels, right? So we're going to do that as well. We are going to understand how you guys can go on to resize the image in any dimension that you want. For example, if you want to keep it structured, you can. If you want to skew your image and you want to pull it up, pull it to the side and skew it however you want, you can do that. We're going to take a look at that as well. And of course, when you're working with any image, maybe you're doing face detection, as we're going to see later in this particular session, is if you want to perform face recognition and if you want to show that your computer recognizes the face, you draw a rectangle there, right? So let's just pick up an image and let's try to put a box in multiple places in these images as well. And after that, maybe you want to add a text to the image itself, right? You want to add an image automatically, maybe that says, hey, this person is wearing a mask or this person is not wearing a mask, something along the lines of that when used with complex algorithms. To showcase how you can add text for all of those complex applications, you'll have to start out by checking out these, right? Superb, guys. Let's get back to Google Colab right now and check out how you can do all of these things practically, right? So let me just quickly open these basic OpenCV operations box and we can go on to work on this, right? Now, ladies and gentlemen, what is the first thing that I told you about? The first thing I told you about is us actually having to read the image, right? Look at this. imRead is basically the function that we're using. Image.jpg. Remember that I'm giving it the full extension as well, right? This is the image I wanted to read from the current working environment. If you guys are using PyCharm or anything else, you might have to give the full path to the particular file saying C drive users your name /desktop /image.jpg. Now I don't have to do all of that because Google Colab basically uploads it to the same working folder or the same working environment. Now let me actually go on to delete some of these images that I've worked on previously so that we can show it to you from scratch, right? I'm going to delete it, okay. So now that it does not have any image on its hand, as soon as I run this, it will give me an error basically saying, hey, you were saying take the image and use it, but where is the image that I have to use, right? So let me just actually click on the upload button. Let me just go to my desktop and we have the sample image of a couple of flowers and a book. So let me go on to upload this image. First, you can see that it's uploading. It's spinning out here. As soon as the spinning completes and the logo vanishes, it has uploaded. The next time we go on to run this command, it will not only read and input the image, but also give us the height and the width of it, right? I told you that we're going to be printing the dimension of the image. Right now, this is uploaded. Let me close this, and here you will realize what is the the update that we have with respect to x. But x and y are calculated using a function called as image.shape. Let me run this again. Now, as soon as I run this again, the image was red, even though it is not showing. You remember we spoke about the return type of imRead. The return type, it does not have a return type because all you're trying to do is it is inputting the image. But here you see an output because I have explicitly said, hey, I want to also look at the size of the image. Now look at the pixels, look at the height and the width of this image, right? So let me quickly open up a calculator to show you guys how many pixels will be there in this particular image, right? Let me put the calculator to the right for a second here. Let me move it a little to the top. 1 second, guys. right? Yeah. Now it says 6720 number of pixels in the height and these many pixels in the width. Now, as soon as I hit run, these are the number of pixels that will eventually go into creating this particular image, right? There are 6,000 pixels like this. There are 4,000. There are 6,000 column-wise pixels, and there are 4,480 row-wise pixels. And when you bring each of them together in a combination, that is the number that you get. Right? Understand that this has no return type, but we are in fact giving the image to the computer. Now, what is the image that we send to the computer? Let me open the image to show you the actual one, right? This is the image that we sent. It's nothing but a white background. There's one book and a couple of beautiful flowers on the book. Okay, superb. Now, let me quickly go back to Collab here. And that was for step number 1. Basically, us trying to get the computer to read an image and print what its dimensions are. The next step talks about extracting RGB values that are present in the picture, right? Now, we saw the number of pixels there. To print RGB values for like millions and millions of values will be absolutely meaningless. So what is easily done is for us to print an RGB value of one particular part of an image, right? So I'll just pick saying, hey, at this pixel of height and at this pixel of width, basically try to find me the RGB value there. So in our image, even though we see that it is 6720 by 4480, I want to find what pixel is present at the point 250, 250. So when you say RGB equal to image of this, all you're trying to say is, hey, at this particular point, this is a point in space. This is the x-axis coordinate. This is the y-axis coordinate. Or again, this is the width and this is the height. So when you go on to do that, you're telling it, find me the pixel value that is present in that particular point and print the RGB values for me, right? This is what is doing. But we have one more part of it where we're saying, hey, I don't want the red value. I don't want the green value. I just want the blue value for that particular part. That is also required. Yes, you can have it. Now, as soon as I run this, it will say as, hey, at 250, 250 in your image, your RGB values are this. But if you just want the blue value at 250, 250, it is going to be something like 221, right? Just the value of B. This is super important for you guys to understand out here, right? Now, once that is done, the next thing that we're going to have to take a look at is taking a really huge image and eventually resizing it to the size that we want, right? Now, the example image is actually vertical, but 19201080 talks about a horizontal image. So when I use the resize function on a vertical image, I basically wanted to show you guys this particular thing. So what happens when I use this resize function is, of course, the image gets brought down into that particular dimension. And after it does that, if I don't run this particular line, it will never show me what the output is like, right? So I have to ensure that it gives me the output too. So I'm using the IamWrite function here to eventually create another file for me. And the name of the file is newimage.jpg. Let me run this right now. And what it is doing, it is taking my input image of this particular dimension 6720 cross 4480, and it is creating another image of this particular dimension. And it gave me a true. Now, why do I have a true? I told you this about in the return type that we spoke about when we looked at this function. So when it is successful in writing to a file, it will give you a true or a false output, right? If it is true, it means that there was an image that was created. And well, as you can see, right, the new image just popped up and our image is ready in the other dimension that we want as well. But what we are trying to hunt for is not just resizing the image. So maybe I want to put a box around any particular pixel that I want. Now, these are the values of my rectangle. cv2.rectangle is a function which will help me draw one rectangle at this point. It's basically a line. Eventually take a right, go to the left and find 4 points where it can draw a rectangle and draw a rectangle around it. And I'm going to write to the same file newimage.jpg, right? Well, let me run this function to show you what happens. We have in fact overwritten the same image that we previously converted it to 19201080. Right now, let me click on this, and as soon as this download, you'll see that it has added a box in the particular pixel that I have asked it to add a box for. Let me click on this and open it. And as soon as I open it, you might be wondering where the box is, right? It's a very small box that we might have added, but if I zoom in on the image, you can see that this is the box that has been added. Now, if you have checked out those mask prediction studies, or if you have checked out any of the applications where people have where the computer is in live, it is looking at a video and it is recognizing that if someone has worn a mask or not, what we're trying to tell that is, hey, here is a box, try to look inside the box to see if a person has worn a mask or not. Now, this of course is not that complicated. All we are trying to do is just create a box in one particular part of the file. Placing a box is very simple. The next basic operation that you guys have to take a look at is how you can put not just a box, but putting a text. Again, we have a function for this. cv2.putText is eventually the function that we're going to use. Output it as an image. What is the text that I want to put it? Where is this particular text that I want to put it? The name of the font I'll be using, the coordinates of which, where it has to start, and more, right? Now, again, I'm using the same cv-write2 function. Let me run this. And as soon as I run this, you will find out why we need to use all of these things, right? First of all, it's simple. To what image should you actually write it to is done. The next thing is what exactly that you have to write. The next thing is the coordinate that you're going to have to put where the text box starts, and later it's the font that you're going to use. Now it says true. It means that it has written the text to this particular file called new image. See, for the sake of simplicity, I'm using the same file name over and over again, and it doesn't mean that you have to do the same. You can just put anything. For example, let me just type new image with text. Right? So just for the sake of readability, if I hit true again, it's just going to put the thing here, and eventually it will give me one more image. It will create another image for me here, which will basically say new image with text, right? Now let me download this particular image here to show you what it is that we have taken a look at. Now, basically, new image and new image with text are same in our particular case because we saved it once for new image and once for new image with text. Now, as soon as I open this, there should be a box, and there should also be my name in that particular box, right? Look at this. Of course, it doesn't look aligned. Of course, it doesn't look like it has any meaning. But the point of the goal here, or the point here, is to make sure that you guys understand you can put a box of any size, any dimension that you want, any number of pixels wide. If you want a thicker box, you can do that. You want a thicker font, a bigger font, a different color, right? We're using the blue color to just put a box and showcase the name. If you want to use green, if you want to use orange, if you want to use any color that you want, all you're going to need is the RGB value for those colors that you want to use. Just put them into the text box, put them into the actual rectangle function, and you guys are good to go, right? Superb. So we saw how we can add a text to the screen as well. The next thing, in fact, the last thing that we're going to take a look at before diving into the demos, the face detection fantastic demo that we're going to be taking a look at, is to make sure that we also use this particular function called IMShow or image show. Now, every time we read an image, we wrote an image, it was basically telling us either it did it or it didn't do it. We never saw any image on the working environment itself, right? But with the help of this particular function, we're going to be reading an image and we're going to be showing the image cv2_IMShow. Now, as soon as I run this piece of code, it'll tell me that this is an image of the width, there's a height of this, and when it's a depth equal to 3, it's basically telling us it has 3 colors, red, green, and blue. If it was a grayscale image, depth would be 1. So since it's a very large 4K image, right, we saw the original image dimension here. The original image is 6720 pixels by 4480 pixels. So it's going to take a second for Google Colab to run through it, to read the image and eventually render it out. There's a process called rendering which has to happen, wherein it just shows you each of these pixels. Of course, you don't see it keeping one pixel after the other because it happens in a couple of microseconds, but it does take time to use use the library to understand the image and check if it's correct. If it is correct, it will eventually give you an output that you can look on the screen. Right now, this should take less than a minute, so let's just wait until we see the actual output. Now, the point for you guys, whenever I tell you that you have to reduce the dimensionality of an image, is exactly this. If it takes this long for one image to work, imagine that you're using hundreds, if not thousands of images for training a machine learning model or something like that. If it takes 30 seconds to open one image, it's going to take 30,000 seconds to open 1,000 images, right? So that's the reason why we keep it simple. We break it down. Now, this is the actual size of the image, right? Look, it is a huge image. Now, let me completely zoom out. look at the size of the text right now. I'm sure for the people who are on your mobile phones, you might not be able to see it, but look at the size of the image. The image is absolutely huge, right? Again, you can compress it to any small pixel value that you want to, which is still understandable, which is still recognizable, and eventually get all of these to work, right? Okay guys, superb. So this is how we can go on to install it. This is how we can go on to perform basic operations. Let's get back to the deck because we're going to be taking a look at a very interesting concept next, which is basically talking about face detection.
We have just explored the world of computer vision. Have you had the chance to experiment with these techniques? What breakthroughs or challenges did you experience? Share your experience in the comments below. Let's shift gears to another fascinating area, natural language processing. Next, we'll learn about text representation and how to convert textual data into a format that machine can understand. Then we'll look into TF-IDF, a key technique for identifying important words in document. Ready to harness the potential of language in your projects? Let's get started.
So let's have a look at what is natural language processing, a proper description for this particular technique. So NLP stands for natural language processing, which is basically used to understand and interpret human language to the machine. In short, it is the automatic way to manipulate the natural language like speech and the text by software for further analysis to get the required information from them. Yes, this stands for natural language processing. Now we will have a look at what are the examples of natural language processing. What are the fields where we are currently using NLP? So we use NLP for predictive text. We know about Gmail, right? Suppose you are writing a mail and it will automatically give you the prediction what will be your next words, right? How they can do that. So this is doing by the natural language processing technique. Now email filters. Suppose your email is a spam email or it's an important email. How Gmail do that? Yes, for this also they are using natural language processing. Now comes data analysis and language translation. What is language translation? Suppose you don't know the particular language we know, right? Suppose we were talking about if you don't know Bengali or Hindi, you only understand English. In that case, what you can do, you can use Google Lens to understand basically what language, like what is written in this particular language, it will convert it to English. How they do that? Again, by doing that, they have to use natural language processing. We will see this is really interesting part of NLP. You can do really cool stuffs using NLP, right? And last but not the least, smart assistants. When we talk about Siri or Google Assistants or Amazon Alexa, and there are a lot more we use as a smart assistants. How they understand our language, how they understand what we are talking to them. Yes, by using NLP, they understand what actually you want to mean by, right? Yes, this is the most used example we can say for natural language processing. So yes, this is more interesting technique, and you will learn lots of things. How can you actually make your own smart assistants using NLP as well. In this particular part, we are going to talk about what is tokenization. As we know, this is the part of database processing. So let's have a look at what is the actual meaning of tokenization and how can we actually implement them using Python. So basically, tokenization is a method is used to split phrase, sentence, paragraph, or an entire text document into smaller units. By doing that, we can get the individual words or terms. We will see how we can do that. Each of these smaller units are called as tokens, right? So this is what tokenization stands for. And to do the analysis of our human language, to understand our language in a proper way, we have to do the tokenization. It's a very basic part after you do the basic database processing, like removing null values or removing the irrelevant columns for your data. And how can you deal with the null values. After doing all these things, you have to go for tokenizing your data set. How you can use the tokenization. So tokenization is meaning, from the name itself, you can understand, tokenize your whole data set with each and every tokens, right? So now we have we have seen that what is tokenization. Now we will see why do we need tokenization. The most basic part of natural language processing, it helps to interpret the meaning of the text by analyzing the words present in the text.
count the number of words in the text? Yes. If you want to count the total number of words you have in your text, suppose the example we have, this is a cake. In a tokenization form, after you have performed, you will get this is a cake. So each and every word will be your token. The total number of count of word you will have, that is 4. And this is how we did the tokenization. Now we will see how can we implement tokenization using Python. So here also we are going to use Google Colab to do the line tokenization. So there are two types of tokenization. We are going to show you what we are going to do for implementing tokenization in Python. So to do that, we are going to import the library that is known as import NLTK. So we are going to use NLTK, the library we know that is used for natural language processing. So we have written import NLTK and our data will be a string, right? That is equals to welcome to great learning. Now we want to make it a line tokenization. So basically line wise tokenization, right? Let me add one more sentence for this. I am very happy to be the part of great learning, right? Suppose you have done this. Now I'm removing to this, okay? So you have a whole total string, right? Now what you will get? If you look at there, so you can have two total line, right? Welcome to great learning. I'm very happy to be the part of great learning. Now what we are going to do, our token will be a line token, not the word tokenization, right? So if you want to make a tokenization according to what are the total lines you have in your document, you can totally do that. Now you have written tokens equals to NLTK dot send underscore tokenize. So this is the function called that is named as that is from NLTK, which is known as send underscore tokenize. And you have sent your data, which is the data variable again, and you said, hey, I want to see my tokens. So after you do that, after you actually execute this one, what you actually get, you get welcome to great learning, and I am very happy to be the part of great learning. If you can see, this is the first token, welcome to great learning, and the second token is I'm very happy to be the part of great learning. So you can see this is how our line tokenization work. Now if we want to check how the word tokenization work, what do you need to do? You just need to call dot word underscore tokenize. So this is for word tokenization. If you just execute that, what you will get? You will get welcome to great learning. I am very happy to be the part of great learning. Can you see? All at the word you have, that is already what? That is already divided into tokens. All the words you have, that all the word in each and every word will be one token. Right now, if you want to check tokens dot count, right. After we did the tokens.count, we get an error. But why? It's saying count takes exactly one argument. Yes, before you go for the checking the count, you have to check token is what type, right? Type of the token. So what we have done, let me just write one more line for you, right? Now I want to check the type of the token, right? As it's giving the error for when we are going to use the count function. Right, let me do that. Okay, what I get, the type of the token is list. To get the total count of your list, what you need to do, you have to call the function called length function, not the count function. So if you write length of tokens, you will get the total count of words you have in your documents, right? I hope this is quite clear to you how the tokenization is done, what is tokenization, and why do we need tokenization, and how can you implement tokenization using Python. In this part, we are going to talk about what is stemming. Stemming is the way to reduce a word to its word stem that affixes to suffixes and prefixes. In simple terms, the algorithm works by cutting off the end of the beginning of the word while taking into account a list of common prefixes and suffixes that can be found in an inflected word. What is basically stemming stands for, we got to know. But how to do that? Suppose you have a word that is cats. So it is going to cut the S from cats and it will give you after the stemming as cat. Suppose you have birds, again it is going to cut the S from the word and you will get bird, the basic form of your word, right? So yeah, this is why we do stemming. But why do we need stemming? Because it's less input dimension. So when your words are cutting down and like in the basic form, your input dimension will be less. Machine learning techniques works better with it and makes training data more dense, reduce the size of the dictionary and helps to normalize the data in the document, right? So this is why we need stemming. So it also the part of normalizing your word. We will see when we are going to do the actual project that how stemming is going to help us. And it's also reduce the size of the dictionaries. So when we this is something related to how you are going to work with your long data set, and we will try to always cut it down to a less number of the dimensions. So we don't need a high computational power, and your technique will also work fine with a short data as well. So that's why we go for using stemming technique. Now we will see how to implement stemming using Python. So let's go to Google Colab. Right, so we came to Google Colab and I'm going to show you how to do the stemming. So to the stemming, we have to import NLTK. From NLTK, we have to import porter streamer. We are actually going to, call the porter streamer, and which is like, maybe you can give that port stem. The name you can give for port stem, the variable name, and you can directly call the function called porter streamer. After do that, you have a word list. What word list you have? You have like, liking, and likes. I want to see how it's going to work with stemming, right? After doing that, what we are going to write? We are going to write port stem, right? So we have a list and we are iterating through a list using for loop, and your I will go to each and every words you have in your list, and you have print I and port stem dot stem, that is your not W, the I, right? If I just execute this, right, I will get for like, it's like, for liking it is also like, for likes also it is like, right? So you can see how this stemming is going to work. So if you give different type of different ing after adding ing, or adding s, or adding like, right? So it's anyway it's going to give you the what? It's going to give you the base part of your word, right? So yeah, this is what stemming stand for, right? So yes, we have talked about that. What is stemming? Why do we need it? And how can you implement stemming, right? So yes, this is what stemming stand for and why do we need it. Now we will have a look into what is lemmatization in NLP. We know lemmatization used for the part of data pre-processing. But what is that? Lemmatization helps to do the morphological analysis of the words. It is important to have a knowledge about the detailed dictionaries which the algorithm can refer to the link, the form back to its lemma. But what is actually meant for, right? So let's have a look at the example of lemmatization. Now you have given helps. So this is what? This is third person singular number, present tense, help. So your lemma will be help. Now you are saying that I am going to give a word called helping. So ing form of the word you have with the help. So your base word will be again help. So you can understand lemmatization and stemming is quite same. We will see what is the difference between them as well. And also we will have a look at how can you implement lemmatization. Before going back to the how to implement lemmatization, let's have a look at what is the difference between stemming and lemmatization. The goal basically for the stemming goal is reduce the inflectional forms. Stemming refers to the crude historic process which chops off the end of the words in order to achieve the goal correctly. Whereas the case of lemmatization reduce inflectional forms, but lemmatization refers to the things do properly with the help of the vocabulary and morphological analysis of words. So you can understand there is a one catch point for lemmatization. It's actually use the morphological analysis, which in the case of stemming, they don't bother about morphological analysis. Now, if we go and check about the implementation, stemmers are typically easier to implement and run faster compared to lemmatization, whereas lemmatization is difficult to implement. Obviously, it takes time when we are actually it's going to work with morphological analysis, right? So let's see how can we actually implement lemmatization using Python. So again, we came back to Google Colab and let's have a look at how to do the lemmatization. So we have already imported NLTK. In this part, we are going to download nltk.download wordnet, right? So downloading the package wordnet to the root, you can see this is up to date, the wordnet, right? Now you have going to actually import that wordnet lemmatizer from NLTK. So you have made a variable called lemmati and you have called the function called wordnet lemmatizer. Now you have given socks and sons. Let's see how it's going to work. So you are going to write lemmati dot lemmatize. So what is lemmati? The function you have called, that is wordnet lemmatizer. Now you said lemmati dot lemmatize, then your word called socks, right? And you have called one more word, that is sons. So lemmati dot lemmatize, then sons. So what you will get as a result? You will get as a result sock and son. So it will chops off the last word, last character you have, that is s, and it will give you the base words. So you can understand this is what stands for lemmatization and stemming. Stemming is the basic way to do that, whereas lemmatization is doing the same thing but using morphological analysis, right? So yes, we have talked about what is stemming and also we have talked about what is lemmatization, difference between both of them, and how can you implement them in Python. Now we are going to talk about what are stop words and why do we need to remove them. Why it comes under data pre-processing. We will talk about that and how can you define and how can you understand what are stop words you have in your document, right? So common words that occur in sentence that add weight to the sentence are known as stop words. The stop words act as a bridge and ensure that sentences are grammatically correct. In simple terms, words that are filtered out before processing natural language data is known as stop words, and it's a common pre-processing method. Yes, we know this removing of stop words, it's a common pre-processing method, and we will see how can we actually implement them using Python and also using NLTK library. But I hope you understand what are stop words. Stop words is nothing but common words that occurs in the sentence, but that will not have weight that add weight to the sentence, but that is not that important while we are going to do any modeling technique, so we can easily remove them. So let's see the demo how using NLTK, how can you actually remove the stop words from your documents. So we have came to Google Colab and let's have a look at how to do that. In order to removing the stop words, what you need to do basically, just need to import stop words from NLTK, and then you have written import NLTK nltk.download stop words, right? Let me just do that. It will actually download the stop words you have in your NLTK library, and we will see the whole list of stop words we have in NLTK. Now we have a data called data, that in the under data variable we have written data science is one of the most training field to work with. It needs the data to be give prediction by using the past scenarios. So now what we have written stop word equals to set stop words dot words, and you want stop words in which language? In English, right? So you have written stop words dot words, and then in the bracket you have written English. Now write print stop words dot words. So basically it will show you what are the stop words you have in your library. If you just remove this particular part, let's have a look at what it's going to give you. Right. So basically, it's some other language. It's going to give you the stopwords that I cannot understand. Maybe some other language. But if you write 620 to 680, basically it's splitting the data. Like what you have in these total words, in like if the stopwords have the all stopwords from like the all language they know in the library, like in the library, whatever the language it has. So basically, particularly for English one, I want to look at. So you can see your, yours, yourself, he, him, his, all are stopwords, comes under stopwords, right? So now if you just want to see what are the stopwords you have in your data, before that you have to tokenize your data. We have talked about tokenization. What tokenization does is basically make all the word one token. So whatever the word you have in your data, it will make each token for each word. Right? Let me just make it just token. Let's do the tokenization. Okay, I'm getting an error because I need to download Pound. So yes, these are the few things you have to keep in mind when you are working with NLTK. Right? You can see it basically tokenize your data. You had written data will be one token, science will be one token, is one of the most, everything will be one token. You have made the tokenization. Now, if you want to check that, okay, what are the data? What are the basically tokens I have as a part of stopwords in my data after I have done the tokenization? So what you have written for word in data, if word in stops is basically the whole data, like the stopwords you have, right? Print word. So what are the stopword you have? You have is, of, the, most, to, with, to, by, the. So these are the words are not important to do the data pre-processing. So not data pre-processing, it's not important to do the modeling using natural language processing, so you can easily remove them. Yes, so this is how you can actually remove the stopwords. You can check the total list of stopwords and you can understand easily that what are the stopwords you have in your document. Yes, so if you have if you don't remove stopwords, it will basically add more weight to your data. It will take, make your prediction not that good. So we prefer to remove stopwords from our document. Right? I hope you understood about what is stopwords and how can you implement stopwords in Python. Now we are going to talk about the modeling technique in NLP. That we say that we will learn what are the modeling techniques we have in NLP, like bag of words, word to wake, and then we have TF-IDF. Right? So let's have a quick look at what are this modeling technique all about and what are the main history behind it as well. Right? So let's have a look at bag of words. What is bag of words? So bag of word model is used to pre-process the text or documentations. It converts the documents into a bag of words, which keeps account of the total occurrence of the most frequent used words. And bag of words is one of the most used method to transform tokens into the set of features. So basically, after you do the tokenization, you have tokens, but there is no features. But if you are going to use bag of words, basically we use count vectorization method to do the bag of words. So what it will do, it will keep a count of total occurrence of most frequent words, right? It will going to help you to do the data modeling and to understand the prediction, right? And bag of words, as we see, that one of the most used methods to transform your tokens into a set of features, right? I hope you understand about how and what is bag of words, and we will do the bag of words implementation in our project as well. That is also using Python. Then we will see what is TF-IDF. So as we know, TF-IDF stands for term frequency and inverse document frequency. This helps to measure the score in order to get the transformation retrieval, that is in short known as IR or summarization. TF-IDF is also used to reflect how relevant a term is in a given document. Yes, we do check that how relevant a term is in the document, basically help us to do the data pre-processing, right? And also data modeling. And procedure to calculate TF-IDF by multiplying two metrics. What are these two metrics? How many times a word appears in a document and the inverse document frequency of the word across a set of documents. Yes, there is a two type of metrics you will have in TF-IDF, and we will actually implement TF-IDF using Python. When we are going to do the project, you will see how can you implement TF-IDF as well. So you can understand about the modeling about bag of words and also What bag of word does, it makes a count of total occurring word in the whole document, and also it does shape that what is the, like, how can you make a features out of your tokens. And also in the case of TF-IDF, it works pretty much same, but there is some concepts of inverse document frequency of the word across a set of documents, right? So these are the model technique we use. But why do we need TF-IDF? TF-IDF helps to establish how important a particular word in the context of the document corpus. TF-IDF takes into account the number of times the word appear in the document and offset by the number of documents that appear in the corpus. Now, TF is the frequency of term divided by total number of terms in the document, and IDF is obtained by dividing the total number of documents by the number of documents containing the term and then taking the logarithm of that quotient, right? So this is why we need TF-IDF, and TF-IDF is the multiplication of two values. What are those? This is TF and IDF. Right, I hope you understood about what is TF-IDF and why do we need it, and we will do the implementation in our project. Then we will see what is word embedding. So basically the types of word embedding we have: word to word, glove, and first text, right? So let's have a look at what is, right, what embedding is. So word embedding vectors are one of the most common ways to encode word as vector of numbers. Those vectors can be fed into the machine learning models for inference, and also it helps to establish the distance between two tokens. If you want to check how actually you can do the distance between two tokens, you can do the word embedding. And we have talked about the types of word embedding: word to word, glove, and first text.
So before we go and discuss what is sequence to sequence model, let's try and understand various types of data do we get in machine learning or in deep learning space. So in deep learning or machine learning space, we can get data into a form of image, or it can be a number, or it can be a text. It can be again audio and video. Okay, so broadly saying, we can get most of the data that are belongs to either of these groups. Okay, and we also know that for image data, CNN or convolutional neural network works best. Sequence to sequence is also a type of neural network which uses RNN. But why did we require this RNN since we had CNN? So we know that in image data, we don't need the previous information, or we don't need the future. Okay, neither we need future nor we need present, past. We just need this present data. Okay, so on this data, convolutional neural network works better, or works best when we don't need to keep the information about the past or the what could happen in future. Okay, so now, but in text data, let's try and understand this with an example. Let's say we know that there is a very famous web series, movie series, that is Marvels, or we can say Harry Potter. Okay, if you have not seen Harry Potter first episode and you directly jump into season 2, you will find a few things that you will not understand because these are related to season 1. Okay, so there is a contextual relation between season 1 and season 2. Similarly, season 2 to season 3, and season 4, season 5, season 6, and so on. Okay, so these kind of a thing are known as sequential data. For sequential data, CNN models does not work well. For CNN data, we take help of RNNs. Okay, so then RNN came into picture. Now we can say that in RNN, what happens that they have no memory, or they have very less memory. Okay, due to which there is a knowledge preservation problem, as well as RNNs have a gradient vanishing problem. In order to tackle those things, LSTM came into picture and GRU came into picture. Okay, with this we can build sequence to sequence model. Okay, now let's jump into sequence to sequence model. Now moving on to the next slide. Now, before we understand what sequence to sequence model is or how sequence to sequence model, let's take an example to understand this. Suppose you stay in Bangalore and you are working in some MNC and your company asks you to go to France for some business conference or something like that. Okay. Now, the moment you landed to Paris, you started feeling hungry. Then you saw that there is a cafe where pizzas are available, various coffees, and then various beverages are available there. So the moment you saw the menu, you saw that it's written in French. Now you started scratching your head what to do since you don't know the French. So then you realizes that yes, I have my then you realizes that you have Google Assistant or Google Translator or various translator applications with the help of which you can translate the French to English. So you uses that app and you ordered and then you had your meal. So this is all about sequence to sequence model. So what sequence to sequence model does, it takes an input, it goes to a sequence to sequence model. Then from that sequence to sequence model, we get an output. So one of the most popular sequence to sequence model is encoder decoder based model. So what this encoder decoder model is, let's try and understand that. If we further segregate or if we go deeper into the sequence to sequence model, we can see that it has an encoder, it has a decoder. So what happens that this is our input as it's a text. So it will get converted into embeddings. And then from this embedding, it goes to this encoder. Then encoder encoded it and then gives a context vector to this decoder. And then decoder decodes the output. Okay, so this is how a normal encoder decoder based model works. But now let's see further. So what are the real life examples of sequence to sequence model? So some of the real life examples of sequence to sequence model are Google Translation, Google Assistant, Siri is there, Grammarly is there, Google's Smart Compose is one of the examples of sequence to sequence model, and the list is goes on. Okay. So now let's move on to the next slide. Now let's see various types of sequence to sequence model. So there are various types of sequence to sequence model available. So today in this course, we are going to see encoder decoder model and encoder decoder model with teacher forcing. So what happens to this? Like, let's say we have our input. This is our encoder and this is our decoder. Okay. So input gets converted into embedding and each input sequentially goes to this decoder. Okay. To this encoder. Let's say X1 goes to this, then hidden state. From this hidden state goes to the next layer. Then from this RNN, it goes to this next RNN with hidden state 2. And then this RNN returns a hidden state 3, which is context vector. Then this context vector goes to the decoder RNN. Then it outputs, and then it gives the hidden state to the next RNN, and then it gives the output. Okay. Likewise, it works. So what happens in normal encoder decoder model? We have input hidden state 1, hidden state 2, hidden state 3. But at the end, we are feeding hidden state 3 as a context vector to the decoder. Okay, so this is normal encoder decoder model. Now let's see what is encoder decoder model with teacher forcing. Okay, so in teacher forcing technique of encoder decoder model, it works same, that X1 goes to this, it returns a hidden state 1, then it goes to second one return hidden state 2, then this returns hidden state 3. Okay, this context vector goes to this and it outputs. But actually what happens here, that this output y1, okay, and we provide the actual output to the each RNNs. Okay, this is y1, this is y1. Okay, then this goes to this gets compared. Okay, the predicted output and the actual output, and based on the results, whether it's a correct or not, the optimization techniques happens. Okay, optimizer optimizes the weights of the neural networks. Okay, and then it predicts. Okay, this way it trains the entire model. Okay, so what teacher forcing does? Teacher forcing helps us in improving the model performance by feeding the actual output to the decoder model. Okay, now let's move on to the next slide. So what are the challenges do we face with sequence to sequence model? Although sequence to sequence model uses LSTM and GRU, which are having memory, but those memories are not very large. Okay, due to which they have a very limited memory. Okay, so if our vocabulary size is very large, or if we have a text length very large, it has been seen that models does not perform well. Okay, and it has a very bad character, that is, it overfits very easily. Similarly, since sequence to sequence model works sequentially, okay, let's say there are L1, L2 and L3, these are LSTM layers. Okay, so input 1 will go to this, input 2 will go to this, and input 3 will go to this. By not providing the input data as parallel, by providing it sequentially, what happens that we are not able to use the GPUs completely. Okay, this is also major issues with sequence to sequence model. Okay, in order to tackle such issues, we have transformers. So what is transformers? So you must have seen transformer movies or transformer. There are so many cartoons available in the entertainment industry. Then there are toys. Okay, so what these toys are, let's suppose there is a car. Okay, and if you press a button, this gets converted into army. Okay, so it transforms it from a car to army. Okay, similarly, transformers in NLP is a model which we train on a data, okay, which can transformed into various other tasks. Okay, let's say there is a transformer model which is trained on some corpus that can be converted into question answer model, that can converted into sentiment analysis model. Similarly, that same model can get converted into classification model by adding a transformer head to it. Okay, we will see those things in the course, how we do these things. Now let's move on to the next slide. So to understand transformer, let's understand this example first. So once upon a time, there was a farmer. He had 4 sons. They used to quarrel with each other. Okay, so let's suppose there is a story. I have just taken a very small snippet, and it's a complete, very long book. Okay, of let's say 1,000 pages. Okay, 1,000 pages are there, and we want to summarize it. Okay, so this input will go to the transformer. Then transformer does something for now, which is a black box to us, and it gives you a summarized text. Okay, to understand that what inside this black box, let's dig deeper into that. Okay, so now let's see what is this. So to understand this model architecture, we can say that it has encoder and it has decoder. Okay, so the input gets converted into embedding. These embedding goes to the encoder. Then this encoder encoded and gives output to decoder, and then decoder predicts the actual output. Okay, so now let's understand each encoder decoder boxes furthermore. So if we go further deeper, we can see that there are 6 encoder inside each encoder box. Okay, and there are 6 sub decoder box inside the decoder. Okay, so we saw that there is a encoder, there is a decoder. Okay, so it has 6 decoder cells, 6 encoder cells. Okay, so it was seen by the researchers that they applied multiple number of encoder and multiple number of decoders here, and then they realized that number 6 is the optimal number of encoder and decoder. So they went ahead with a number 6 as a decoder cell and 6 number of encoder cells. Okay, so now let's look further. So how this encoder looks. So this encoder has further 2 layers. That is, one is self-attention cell and the another cell is feed forward cell. For now, you can ignore the self-attention cell and feed forward cell. What happens here, we will see further down the line. Okay, so this is our encoder, which looks something like this. Now let's move on to the next. This is decoder. So decoder has one self attention. It has a new cell, that is encoder decoder attention, and it has a feed forward network. Okay, now let's look deeper into that. So how this encoder decoders are attached? This is our encoder, this is our decoder. Okay, so each encoder, there will be 6 number of encoders and there will be 6 number of decoders. Okay, each encoder will attach to all the 6 decoders. Okay, likewise, like here we can see it is connected to 1, but it is connected to actually 6 number of decoders. Okay, now let's move further. Now let's try and understand this encoder decoder. Okay, so this encoder is further divided into self attention, followed by a add and normalizer layer. Then it has a feed forward network, and then it has a add and normalizer layer, and then it goes to encoder 2. Okay, and there is a residual connection. Okay, what this residual connection does? This residual connection helps us in preserving the information, and it also helps in not happening of the gradient vanishing. Okay, which happens in recurrent neural network. Okay, we will learn about this positional encoding in a few minutes. Okay, so now this is basically encoded which looks something like this. Now let's move further. So this is our decoder. Okay, so this is decoder self attention, followed by a add and normalizer. Okay, so this is also known as masked multi head attention. Okay, so this is masked multi-head attention. Okay, and if you see closer, it has 3 inputs. Okay, we will learn about these 3 inputs. What are those inputs? Key, value, and query. Okay, and why do we use that? We will discuss those as well. Okay, and again we can see that there is a duplicate of encoder. Okay, like this, there are 2 same values are going here. Okay, so we will learn about them going forward, but for now just try and understand that the architecture is something looks like this. Okay, now if we combine both the architectures like encoder and decoder, it looks something like this. Okay, so this is encoder, this is decoder. Okay, encoders are 6 encoders attached here and 6 decoders attached here. Okay, if we stack them all, then we will get a beast, or we can say we will get a transformer. Okay, now let's understand what is attention. So what is attention? Okay, so in order to understand attention, let's take an example. Okay, let's suppose that you go to a web page, that is google.com. Okay, and you searched a term transformers in NLP. Okay, so this is nothing but this is your query. Okay, this query will go to the Google database. Okay, there is a database in Google. Okay, in that database it will search for these terms. Okay, so there are keys. Okay, so it this query will check with keys. Okay, and with the help of cosine similarity, okay, it finds the most like relevant queries. Okay, so it finds out what are the keys that are most relevant. Okay, then it gives you that, okay, yeah, these are the web pages that are having the more relevance in terms of the cosine similarity, and these results as a value will go to your google.com output. Okay, so this is known as query, this is keys, and this is value. Okay, so this is a basic database query pipeline. Okay, this architecture or this concept was used in the attention. okay, in terms of key value pair. Okay, now a key value and query. Okay, now let's understand that what exactly happens here. Okay, so let's move further and let's try and understand what is self-attention. Okay, so now we have now let's see what is self-attention. But before going into that, let's understand that what this positional encoding is and what it does. Okay, so we know that in sequential model, what happens that we provide the inputs, okay, sequentially. Okay, so the sequence is maintained. Okay, we are not vanishing the sequence, but in transformers we feed all the input at a once. Okay, so the sequence is not maintained. Okay, how we can know that like the sequence is maintained or not? Okay, so let's say that he is a good boy. Okay, or let's say there is a statement, is he a good boy? Okay, we have the same sentence. Okay, we have the same sentence, but due to the, let's remove this question mark. Okay, if we see this, there is no change in the tokens or there is no change in the words, but due to this positional changes, we can see that the entire meaning of the word gets changed. Okay, so how we can preserve the sequence of the words? Okay, this we can do with the help of positional encoding. We add a positional vector to it, okay, or positional encoding, okay, to it, to make each vectors unique. Okay, so this way we create a unique vectors with the help of positional encoding. Now once this is done, what we do, we duplicate the value, same vector, like this will become key, this will become query, and so what happens that we feed our input, we give our input to the model. Okay, then let's say word to vec. Okay, word to vec converts the into a vector. Okay, so we get some vector, and then these vectors, this will become value. Okay, and this before dividing it, what happens that as a residual connection, this goes to the add and normalizer. Okay, then this goes to the self attention, and then self attention, how self attention calculates or how self attention works. Let's understand this with another example. So let's see this. Okay, so this input, the three input, key, query, and value. Okay, now let's suppose the vector size or the embedding size is 7 cross 5. Okay, or let's say this is also 7 cross 5, this is also 7 cross 5. Okay, so to this, when we add to this linear, let's suppose that it has 5 cross 3 vector. Okay, this is also a vector okay, of vector weight file of 5 cross 3. Okay, so what happens that this goes to this multiplies together. Okay, and which gives you a 7 cross 3 vector. This also gives you a 7 cross 3 vectors. Okay, so what happens that we know that in matrix multiplication, let's say if it's a 7 cross 5 dot product of like 5 cross 3, what it will return, it will return a matrix of 7 cross 3. Okay, so this way we change our matrix to 7 cross 3. Okay, then this 7 cross 3 we find the matrix multiplication of it. For this we transpose this query vector. Okay, so this gives us a 7 cross 7 matrix. Okay, then we scale this matrix. Okay, what do? We just normalizes it. Okay, we scale it. Okay, after scaling it, we apply a softmax layer to this. Okay, which gives us a maximum probability. Okay, which gives a probability to each tokens, by which we can give highest weightage to the term whose like the probability is highest. Okay, to whom we want to give a attention. So what this self attention does, let's take an example to understand it. Okay, so let's suppose Rohan went to the bank, checked his account, which was 0. Okay, so his bank account was nil or 0. Then he went to the river bank and starts crying. Okay, or started crying. Okay, started crying. Okay, so how for a human being, it's very easy to understand that the first bank is nothing but it's a financial bank, and the second bank is nothing but it's a river bank. But is it same way? Is it easier for the machine to understand? No, it's not easier for the machine to understand, since what happens that in word to vec or in any other vectorization technique, we do not consider the context. Okay, so it's a context free. Okay, but if we do not know the context, how can we say that this is a river bank and this is a financial bank? Okay, so to keep the context vector with us, or to keep the context of the terms, we take the help of attention. Okay, or we take the help of self attention. Okay, so this is what we does. So when we pass this input to this attention, it gives attention to each words. Okay, like Rohan, an account. So it is clear that this is Rohan's bank account. Okay, then account and 0. So it will give importance to these words like this. Okay, each time. Okay, similarly, bank and river bank. So what happens here, that it gives a weightage to each words, or we can say the probability of each words. Okay, then this what happens that this is 7 cross 7 matrix. This was 7 cross 3 and this was 7 cross 3. Okay, then this goes to 7 cross 7. Okay, and this is 7 cross 5 matrix, that is our value matrix. Okay, then we do the matrix multiplication. Here we gets the 7 cross 5. Okay, now we see that earlier we had 7 cross 5 vector size, which gets multiplied into 5 cross 3, 5 cross 3, that is the weight file. Okay, then from those weight it multiplies and it gets 7 cross 7, and then at the end we get the 7 cross 5. Okay, then it's concatenate, or we can say that it flattens the 7 cross 5 array. Okay, to this, then this 7 cross 5 goes to a linear layer, and this linear layer goes to furthermore to the add and normalizer layer. Okay, so this is how attention works, or self attention works. Okay, like during the each epoch, what happens that we adjust the this 5 cross 3 weight files, that is in the linear layer. Okay, and it at the end we gets the correct weightage for each terms, and the attention for each words is given at the end. Okay, so this is the basic way self attention works. Now let's move further. So what is multi-head attention? In transformer, the computation, as we saw that in the earlier example, there are total 7 tokens. Okay, so for each tokens we will create a attention. Okay, and for the 7 we will create a 7 layer or 7 stacks of attention. Okay, and these attentions when gets together constitutes into a multi-head attention. Okay, so this is what multi-head attention is, and this is what it does. So now let's move on to next. Now we have understood that there are what is this positional encoding and what this self attention does to us. Okay, in transformer there are three basic steps. One is positional encoding, one is self-attention, and end is that is known as masked multi-head attention. Okay, which is this one. Okay, we can say masked multi-head attention. Okay, now let's see what happens that. Okay, so we will not go into this what this output is doing here. First we will see that what happens that from this decoder, okay, it goes to this encoder decoder attention, this we can say key query, and from this masked multi-head attention a value is given to this. Okay, and this value as a residual is goes to this add and normalizer to preserve the information. Okay, then this does the attention thing. Okay, how a self attention works, it calculates it and goes to this add and normalizer, then it goes to feed forward, and at the end it goes to the decoder 2, decoder 3, and after completion of this decoder 6, it goes to a linear layer or it flattens it. Okay, and then after that softmax is applied to it, which gives the probability to each tokens, and the maximum probability token is given out as a output. Okay, so let's say that this is a output O1. Okay, and this output O1 will go to this. Okay, and it gets compared here in this multi-head attention layer. Okay, that whether this output, which was the actual output and which is the predicted output, are they same or not. Okay, if they are not same, then with the help of optimization techniques, weights are of each neural networks get adjusted. Okay, and then again the same process happens. Okay, and which constitutes into the training of the transformers. This way we train the transformer model, and then we can apply the various transformer heads to it to use it further. Now let's move on to the next. Now we can see that we have our transformers that is trained. Okay, on top of this transformers we add a transformer head. Okay, which helps us in solving some use cases like question answer head. By applying question answer head, we can create a model that will be question answer model. Then MLM, this is nothing but mask language model. Then classification head to find the classification model. Okay, next sentence head to get the next sentence or next word prediction. These kind of a thing we can perform, or we can tweak the model after it gets trained. Okay, now let's move on to the next slide. Okay, what are the limitations of attention? Now we discussed about various things which are very good with attention. Okay, but there are few limitations of attention as well. Like it's very difficult to parallelize the entire process. Okay, attention works very good when the data size is very small. When the data size is very large, it performs not well as compared to when it performs with a smaller data sets. Okay, so now let's move on to the next slide. So now let's discuss some of the popular transformers model. Okay, there are so many transformers models available in the market that are very popular. Some of them are GPT series like GPT-1, GPT-2, GPT-3. Then there is T5 base model. Then there is T5 other models also, like small model, large model. Then BERT is there, Robota is there, DBERT is there, AxelNet is there, and so on. The list goes on. Okay, you can read about there are so many transformer models available in the market. Okay, but the basic things or how they works is same the way transformer works. Okay, so let's say for example, when we create a transformer, okay, and this is our encoder, this is our decoder. Okay, if we use only this encoder, this is nothing but a BERT. Okay, similarly, when we use this decoder only, this is nothing but this is GPT series. Okay, so this way we can tweak the transformers and get the different models. Okay, but these are the few transformers models which are very popular in the industry. Let's move on to the next slide. So now let's see some of the real life examples or the application which we use that are built on transformers. So there are language transformation the translation models are there, sentence completion model is there, sentiment analysis, long-term sentence classification, next word prediction, text summarization, grammar correction, okay, context correction. So there are text summary phrase rephrasing, okay, there are so many things available in the market where we use the transformers to implement NLP and to improve the results. Okay, now let's move on to the next slide. Now let's discuss very popular encoder decoder model that is attention based. Okay, so for that let's just see the architecture of it and then we will be able to understand it furthermore. Okay, so what happens in a normal encoder decoder model is that we give this, let's say this is I1, this is I2, and this is I3. Okay, so I1 goes to encoder, I2 goes to second, and I go to this one. Okay, from this encoder we gets a hidden state 1 which gets inserted into this encoder 2. Then from this hidden state 2 goes to encoder 3, and this hidden state 3, okay, this is known as context vector, goes to this. Okay, and then decoder decodes it same way. Okay, now what happens in encoder decoder, let's understand this. So in encoder decoder with attention, instead of sending the last hidden state, so we send all the hidden state together, okay, to keep the information which we get from encoder 1, encoder 2, and encoder 3. Okay, so this is how attention based encoder decoder model works. Now let's discuss few limitations of transformers. Transformers require a huge compute capabilities. You need to have a GPUs, you need to have a high RAM in order to execute it fastly, okay, which requires a huge costing. It requires a huge amount of data to train the model, as well as it's a very time consuming process. Okay, so these are the few limitations which we see in transformers. Rest, transformers are very good. They perform NLP tasks very efficiently and very like it has been seen that they have given us a very good result for very difficult tasks such as text summarization, context understanding or rephrasing of the phrases, question answering models. Okay, these are the some of the things like in which transformers works very well, but there are few limitations. Now let's move on to our next topic, that is introduction to BERT. So BERT stands for bidirectional encoder representation of transformers. So before we go and discuss what is BERT, let's try and understand what is MLM or what is masked language model. Okay, so masked language model takes a certain percentage of input token. Typically it takes 15% of the input and masks it, and model is supposed to predict the same input text along the certain correct token of the mask token. Okay, so what does it mean? Let's try and understand this with this example. Mary had a masked lamb. Okay, now the model is supposed to predict for this. Okay, so how it predicts or what it does, that is the way the model understand the context. Okay, in order to understand the context or in order to keep the context of the word, it is very important to apply the MLM. Okay, and that is the functionality which BERT uses. Okay, so it goes to this model and then model predicts out had a little. Okay, so we can take an example of sentence filling where we see that we given an input, there is a fill in the blanks, and then you are supposed to fill that output. Okay, the same way we train to the model for this MLM. Okay, now let's understand what is BERT. As we discussed, BERT stands for Bidirectional encoder representation of transformer is a language model unlike any context-free embedding model. Okay, BERT is a context embedding model. It is based on transformers model. Okay, so what this context-free and context embedding model? Let's try and understand that with two statements. Python is very dangerous. It can kill you. Okay. Then there is another sentence. I love Python. It's very easy to understand and code. Okay. Now, if you see the two sentences, if we apply word embedding to that, what it will do? So it will consider this Python together. Okay. Which is not the correct thing because one Python is a snake and in the another thing where we are talking about Python programming language. So how to keep those context with us? Okay, or how we cannot how we can apply something by which we do not lose this context. Okay, so BERT help us in this. Okay, by keeping the contextual embedding of the model. Okay, let's move on to the next slide. Okay, so what are the things which BERT can do? So BERT can do name entity recognition, that is NER. It can do next sentence prediction. It can give you good results on long text classification, sentiment analysis, question answering, text summarization, and the list goes on. Okay. So now let's try and understand the BERT architecture. So as we discussed that BERT is dependent on or is derived from this transformers. So this is the typical transformer architecture. Now, if you divide this, so if we divide it, or let's say if we do not keep this part, if we keep this part only, then this is BERT, and this is known as GPT, GPT-1, GPT-2, GPT-3. Okay, and so on. Okay, so this is the BERT architecture. The BERT architecture is nothing but an encoder. That's why it is bidirectional encoder representation of transformers. Okay. So if we further go deeper into that, how BERT architecture works or how it keeps the context of the word. So what happens that we saw that MLM model. So the input with masked input goes to this transformer encoder. Okay, and it understands that Mary had a little lamb. Okay, then there is a classification layer, that is fully connected layer with normalization with normalization layer, and it goes to the next layer, and then it gives you the output. Okay, so this is the basic architecture of masked language model, which we saw earlier that this was a kind of a black box for us, and here it was written model. Okay, so now we have understanding of how what here what happens here. Okay, now if you see that this transformer encoder, okay, so this is nothing but the E1, E2, E3, which we saw in the encoder. Okay, where it keeps the attention, self attention layer, and it gives a equal weightage or the importance to the words. Okay, now let's understand it furthermore. So what typically happens that any BERT architecture or any BERT model works on two things. One is this masked language model, and the next is next sentence prediction. Okay, so what typically happens that we feed two inputs to the model. Okay, one is this masked language model, and the another one is inputs. Okay, next sentence input, where we put two inputs. Okay, and model is supposed to predict that whether the next sentence or the sentence 2 belongs to is successor of sentence 1 or not. Okay, this way we feed this information to the encoder, where it takes help of self encoder self attention, with the help of which it predicts the this masked key. Okay, and it gives you a key. And similarly, there is a classification output which gives you either 0 or 1, with the help of which we can understand that whether the next sentence or the sentence B belongs to sentence A or not. Okay. Okay, so like we discussed, like till now what we have covered. Let's recapitulate it once again. In MLM model, what is supposed to do, we are supposed to fill this masked key. And in next sentence prediction, what we are supposed to do, we are supposed to find out that A, B, C, if input is given, then it will say that B is followed by A. But if we put this C followed by A, this it will give you 0 for that, and for this it will give you 1. Okay, so this is the way basically next sentence prediction and MLM, how we can apply BERT in Python. Okay, so there are two ways to apply it. Either we can use the transformer hub, that is TensorFlow hub, and the another one is Hugging Face. Okay, for this use case we will be using Hugging Face only. Okay, so now let's move on to the next slide. So how do a BERT model train? Okay, so like we discussed that in pre-training phase there is a MLM model. Okay, and there is another thing, that is next sentence prediction. Okay, and there is a fine tuning, or we can say that transformers head. We apply transformer head, okay, to fine tune it for further tasks. Okay, so now let's understand these two phases one by one. So what happens that when we pre-trained the model, we we do two unsupervised learning tasks, that is masked language model and next sentence prediction. Okay, the input goes to this self attention, and then it does all the encoder things which we have seen it. Okay, and it predicts the masked language model. Okay, a masked language, the next word, or the fill in the blanks for that. Similarly, it predicts the next sentence which we discussed earlier. Okay, so after training it, or after creating the embedding for that, okay, we get a embeddings. Okay, that embeddings we get it. In that embedding, what we add a fully connected neural networks. Okay, so this is the fine tuning phase. Okay, so this is nothing but this here. What we add this fully connected layer. This is known as transformer head. Okay, so by applying transformer head, we can apply question and answer. Okay, we can apply next word prediction. Okay, we can apply classification, we can apply let's say sentiment analysis. Okay, so things like that we can apply here. Okay, with the help of these layers. Okay, and let's move on to the next slide. So how BERT is different from a word to vector? Like we discussed initially, that it keeps the context of the words. Okay, then it keeps the words ordering with the help of positional encoding or positional vectors. Okay, then its embedding is little different. So what it has a token embedding. Okay, then it has how embeddings, or this BERT embedding is different from embeddings. So it has token embeddings, then it has sentence embeddings. Okay, plus it has positional embeddings. Okay, so making them all, this is the BERT embedding. Okay, so this embedding has a little different embedding as compared to the word to vec embedding. And out of vocabulary, it also keeps the out of word vocabulary. Okay, and by with the help of attention, it takes care of those keywords, those which are not present in the vocabulary, or which are present in the vocabulary, or if any words that needs an attention more or not, that is taken care by the BERT embedding. Okay, now let's jump into the next thing. Is BERT always better? In data science space, or in NLP, or let's say in machine learning, okay, in any of the space, never we can say that a model is always a go-to model. Okay, you cannot say that a particular model is always a go-to model. Okay, so there are so many things that goes behind that. Okay, like for example, BERT needs a huge amount of data. Okay, it requires a huge amount of data to train. It requires you to have GPUs with you. Okay, so these kind of a thing are required for that. Okay, if you do not have, then you won't be able to apply BERT, or if you apply BERT, you will not get a good result as you were expecting it to be. Okay, so we cannot say that BERT is always a go-to model, but yeah, definitely BERT has given us a good results in so many use cases which were not being solved by the normal or the conventional natural language processing models. Okay, move on to the next slide. So let's discuss some of the applications of BERT. So there are so many applications of BERT. Some of the popular applications are long text classification, sentiment analysis, next sentence prediction, then similarity between pair of sentences by keeping the context of the words, question answering, text summarization, sentiment analysis. Okay, now let's and the list is will go on. Okay, so there are so many applications of BERT that is currently available in the market.
We have just covered the exciting world of natural language processing, that is NLP, which is transformation of how machine understand and interact with human language. Next, we'll introduce you to generative AI and explore how machine can create content from text to images. We'll also discuss large language model, that is LLMs, the engine behind many AI advancement today. Finally, we'll move on to prompt engineering, the art of crafting inputs that guide these models to generate the best possible outputs. So let's begin.
Let me make you understand with a very simple example what is generative AI. Transport yourself back to your childhood. You had a lot of toys to play with. You would keep that toys in one box. Now, also imagine that if you wanted some toy which is different, you would not get in the market. But what if I tell you that this box is a magical box? And if you input your understanding of what you want in your new toy with instructions, it can create a new toy for you, which is not available in the market. Now, this toy can be a bear with unicorn features and wings. What if it generates for you? This magical box generates a toy which is very unique for you. This magical box is nothing but generative AI. Generative AI actually is not a magic, it's a fast and rapidly evolving artificial intelligence system which creates, generates, transforms content that can be text, video, audio, image, etc. based on your input. So, if we want to understand it technically, generative AI or Gen AI functions by employing a neural network to analyze data patterns and generates new content based on those patterns. Neural networks are nothing but a mimicry or a replication of your biological neuron based on how it gets from brain, the activity from brain, and you do your work. It's nothing but a mimicry of that. Based on that mimicry, it analyzes data patterns and generates new content for you. Let's now quickly see what is the difference between discriminative and generative AI. Suppose you have a data set of different images of dogs, cats. You provide this as an input to your discriminative AI, which acts like a judge, and it classifies all this into set of images between cats and dogs. This is discriminative AI. It classifies. Now let's understand what is generative AI. You have the similar set of cats and dogs, but now your generative AI is acting like an artist. It creates a new species of dogs for you. That's why generative AI is nothing but AI system that transforms, creates, generates your own content based on your instructions like an artist. Now that you have understood what is discriminative AI and what is generative AI and what is the difference between the two, let's understand why is generative AI or Gen AI trending. Gen AI has impacted various fields, be it text, audio, video, any input, and those inputs in various domains like data, management, tech, healthcare, and entertainment. It has creative applications such as DALL-E, ChatGPT, where you can input what you want and get output from it. For example, if you want to create an image, what you think or perceive as a concept and you want it, you give a prompt for your generative AI model and it will create that image for you. So your input is a text, but your output is an image. That's why it's trending. It does not depend how traditional AI is dependent on what form of input you give. The same form would be your output. However, Gen AI works on your inputs, on your instructions. That's why it's trending. It is impacting a lot of fields, be it creative field, be it research field, be it business. Professionals are using tools like ChatGPT to create or generate code so that they can create something new. The researchers are actually developing new and new large language models based on which we can create new generative models and can do new and new tasks each and every day. That's why generative AI is evolving rapidly, and that's why is close to magic for everyone. Now that you have understood why it is trending, now let's understand how it works. We give an input to generative models. Gen AI works on generative models. We give an input, it can be text, audio, video, any format. Those generative models are then pre-trained on the data and they are fine-tuned to do the task that you want. It can be text summarization, it can be sentiment analysis, it can be image generation, it can be audio generation for your YouTube channel, or analyzing your customer feedback if you are a brand or a marketing firm. It can create codes, whatever you want. You give a prompt what you want, explaining it that what you want, and it fine-tunes and gives you that task for you. So this is how, in a nutshell, generative AI model works. So now let's see what are the different types of generative AI. First one is Generative Adversarial Network, GANs. It's a type of AI where two models, one generating the content and one judging it, work together to produce realistic new data. Second is Variational Autoencoders. This AI learns to recreate and generate new similar data. Third is Transformers. Transformers is an AI which learns to produce sequences using context. Fourth is Diffusion Model, which generates data by refining noisy starting until it looks realistic. Now that you have understood what are the different types of generative AI, let's quickly walk through different applications of generative AI. First one is content generation. It creates, it generates whatever textual or any code that you want. Customer support and engagement. If you are a brand firm, it helps you with that. Data analysis and data science. It helps with visualization. It helps with analyzing any data. It be it any data you want. You are a brand firm or you are a technology firm. It will help you analyze your data and create new automated task for you, or it would create new perceptions for you to take over. Then it is code generation and software development. We have research and information retrieval as well, where it helps different researchers, it helps different professionals to grow and retrieve, extract information required from different or various data sources. Then we have machine translation. If you are a person who do not understand a language and you're watching something or reading something which is in different language, you can use generative models to translate text or audio or anything into the language that you require. Then we have sentiment analysis, which actually takes feedbacks or any text that you have to give you. Is it a positive, negative, or neutral sentiment? And so that you can analyze and take decisive decisions. Other domains here include healthcare, transport, everywhere it helps. Generative models, generative AI is helping each and every domain in their perspective, how they are applying this technology change in their domain.
Step into the fascinating world of generative AI, a technology that is transforming industries and creativity alike. We'll break down what generative AI is, explore the advantage it brings, and discuss its potential for the future. Additionally, we'll explain how generative models work and address the key ethical considerations that come with harnessing this powerful technology. So let's get started. Let's now understand the advantages of generative AI. Generative AI offers numerous benefits across various industries. It enhances creativity by allowing tools like DALL-E to create unique artwork and MuseNet to compose original music, thus expanding the creative possibilities for artists. In fashion and design, AI tools like Runway ML significantly increase efficiency by speeding up the creation process, saving both time and cost. Personalization is another key advantage, as AI can generate tailored content for marketing, improving user engagement and conversion rates. In the field of drug discovery, AI helps accelerate the development of new treatments by generating novel molecular structures. Additionally, AI's ability to handle large-scale content generation such as product design or media allow businesses to adapt quickly to market demands. Overall, generative AI is driving innovation, creativity, and efficiency across multiple sectors. Now let's talk about the future of generative AI, which holds exciting possibilities. We can expect AI to increasingly collaborate with artists and creators, pushing the boundaries of creativity by co-authoring works and composing music. As AI technology advances, it will offer even more personalized experience, such as tailored educational materials that adapt to individual learning styles. Integration with augmented reality, that is AR, and virtual reality, that is VR, will enhance these environments, creating more immersive and interactive experiences. Ethical consideration will be a major focus, with efforts directed toward ensuring responsibilities, use, and addressing issues like data privacy and authenticity. Furthermore, generative AI will drive innovation across various industries, including healthcare and finance, reshaping how we approach and solve complex problems. Let's understand about the ethical consideration in generative AI. Because as generative AI technology evolves, several ethical considerations must be addressed. One major concern in the potential for AI to create realistic but misleading content, such as deepfakes, which can contribute to misinformation. There is also the risk of perpetuating biases present in the training data, which can impact fairness and accuracy. Ownership of AI generated content poses another challenge, as it is important to establish clear guidelines for intellectual properties rights. Additionally, AI system might inadvertently reveal sensitive information from their training data, necessitating strong privacy measures. Finally, it is crucial to establish standards to ensure that generative AI is used ethically and responsibly, avoiding misuse and harmful applications. Now that we have covered the essentials of generative AI, let me ask you a brief question. Which aspect of generative AI are you most curious about and why? Let me know your responses in the comment section. Next, we'll explore the exciting realm of large language models, that is LLMs. We'll begin with an introduction to LLMs and take a closer look at some of the most popular ones, including GPT, Cloud 3.5 Sonnet, and Gemini. We'll also delve into OpenAI's GPT API and guide you through the process of creating an LLM app for Android. Ready to harness the power of LLMs? Let's begin.
What exactly is an LLM? Imagine you have a super smart friend who has read every book, article, and blog post in the world. This friend can chat with you about almost anything, help you with your homework, write stories, and even tell you jokes. That's pretty much what an LLM does. In technical terms, an LLM is a type of artificial intelligence that has been trained on vast amounts of data. It can understand and generate human-like text based on the pattern it has learned from all that reading. This is part of a broader field called generative AI, which focuses on creating content that resembles human output. Let's now break down the basics. Large language and model. Large just means that the model has been trained with a massive amount of data. We are talking about billions of words from books, websites, articles, and more. Model refers to a set of instructions or algorithms that helps the AI understand and generate language. Think of it like a recipe that guides how to make a cake. In this case, it is guiding the AI on how to create meaningful text. Let's talk about language. This is all about words, sentences, and how we communicate. When you text your friends, write an email, or post on social media, you are using language. So now that you understand what each word in LLMs stands for, let's quickly see what is the technical definition. LLMs are language models made up of neural network with billions of parameters that are trained by self-supervised learning on vast amounts of unlabeled text. Now let's dive into how do LLMs work. Let's simplify this with an example. Imagine you type the sky is dash dash dash. The LLM might predict the next word to be blue because it has seen that phrase so many times during its training. Large language models like GPT-4 operate based on complex neural networks trained on vast amounts of text data. Here is a simplified explanation of how they work in two phases. The first phase is the training phase, followed by the inference phase. The training phase has 4 steps. Step 1, data collection. That is gathering diverse text data from various sources. Step 2, pre-processing, which means cleaning and tokenizing text data into numerical representations. Step 3. Model architecture, which is nothing but designing the neural network structure, typically a transformer. Step 4. Training is adjusting model parameters by predicting the next word in sentences. By this training phase, the LLMs are being trained on vast amount of data to do further predictions. Now, coming to the next phase, which is inference phase. It also has 4 steps. Step 1, input processing. That means tokenizing and converting the input text into embeddings. Step 2, generating output. Now using the model to predict and generate the next words. Step 3, sampling, which is selecting words from predicted probability distribution. Step 4, last but not the least, post-processing, which means converting generated tokens back to readable text. After the training phase, in the inference phase, the LLMs will recognize the pattern, sample content, and give predictions. Apart from these steps, there are 3 key concepts which we should know to demystify LLMs. First, attention mechanism. This allows the model to focus on relevant part of the input text, improving its understanding of context and meaning. Second, embeddings, which are numerical representation of words or tokens that capture their meaning and relationship. Third, transformers. Transformers are the architecture that uses self-attention to process input data in parallel, making it efficient and more powerful. Let's see some examples of LLMs in action. Example 1, chatting. Your prompt can be, what is the capital of Japan? LLM replies, the capital of Japan is Tokyo. LLM knows this because it has read a lot of information about countries and capitals. Let's see example 2 about writing. Your prompt can be, can you help me write a story? LLM says, sure. Once upon a time in a land far away, there was a brave knight who ... The LLM can generate creative text based on what it has learned from reading stories. Example 3, let's see answering questions. Your prompt can be, explain photosynthesis in simple terms. LLM replies, photosynthesis is a process by which plants use sunlight to make food from carbon dioxide and water. It simplifies complex topics by using the patterns it has learned from educational content. There are different types of LLMs, each designed for specific tasks and application. Now let's explore these types. First are base models. They are trained on a wide range of data and can perform general language understanding and generation tasks. They aren't specialized for any particular type of instructions, but are versatile. For example, GPT-3, which is known for its versatility and ability to generate coherent and contextually relevant text. Another type is instruction-based models. They are fine-tuned to follow specific instructions better than base models. They can understand and execute tasks based on detailed prompts given by the user. For example, T5, that is text-to-text transfer transformer. It converts all NLP problems into a text-to-text format, making it highly versatile for tasks like translation, summarization, and question answering. Another example is Instruct GPT, which is tailored to follow specific user instructions better and provide more useful and safe responses. So, these were the types of LLMs. However, there are paid and open source LLMs as well in the market. Based on your usage and budget, you can explore them. Some paid LLMs are GPT-4, 4o, Microsoft Azure OpenAI services, etc. And open source are GPT Neo, BERT, etc. Let's see how are LLMs revolutionizing the world of AI. In education, they can help explain difficult concepts, answer questions, and even tutor students. In content creation, they assist writers, marketers, creators by generating ideas, drafting content, and editing. In coding, they assist professionals with generating code to their specific problems. In customer support, many companies use LLMs to power their chatbots, providing quick and accurate responses to their customer inquiries. Apart from all these fields, LLMs are being utilized in every field and domain. But it's not all smooth sailing. There are challenges too. Let's see one such challenge, which is bias. Since LLMs learn from human written text, they can pick up and reproduce biases present in the data. Another one is misinformation. They can sometimes provide incorrect or misleading information, especially if the data they were trained on was flawed. However, keeping challenges aside, the future of LLMs is exciting. As they continue to improve, we can expect them to become even more accurate, reliable, and versatile. They will be better at understanding context, handling complex tasks, and even learning from smaller amounts of data. So, there you have it. Large language models, LLMs, are like super smart friends powered by tons of data and advanced algorithms. They can chat, write, and help us in countless ways. As they continue to evolve, they are set to become even more integral in our daily lives. What is prompt engineering? Prompt engineering is as much an art as it is a science. A very creative line. We'll come back to this once we understand what is actually prompt engineering. Prompt engineering is made up of two words, prompt and engineering. Prompt is nothing but a detailed set of guidelines or instructions given to the LLM or generative model to do a task. Engineering is developing iteratively a task-specific prompt to enable the generative models or LLMs to output a perfect or near perfect outcome that you have focused for. So, if you see, prompt engineering is an iterative process. How? First is the idea that comes to you that you want this. Then you have prompt, you design a prompt. Then there are results. You give that to your model, your chat GPT, okay? And then you have to test, you have a feedback, right? So basically, it's a process, an iterative process. Now, once you have the prompt and you have the results, you might be not very much satisfied with the result. This is where you develop or you have a conversation with your chat GPT, with your model, and enforce or reinforce the model to give you a good result, a good output, which is what you want. For example, if you have a task on code generation, now a specific problem statement can be solved through various methods. For example, you want to output palindrome. Palindrome can be done by brute force. Palindrome can also be done by a recursive method, recursion. For example, when you give ChatGPT a prompt, it will first give you a brute force method. You have to keep on instructing and providing an attempt or providing a prompt to ChatGPT so that it gives you an optimized version for your code. This is an example for code generation. Similarly, suppose you have content creation. You want to create a content, and your content that you want to create is directed towards a specific target audience. Now, when you give ChatGPT a prompt, the results it will show you that might not be satisfying enough. You have to tell your ChatGPT or your generative model iteratively what you want. Give them a feedback. For example, you have not received a good output. What you will tell your ChatGPT, for example, this is not I want. Please generate the output based on my target audience or based on my feedback provided, right? That's where your feedback or test comes into picture. You have to have a conversation with your generative model, or in this case, if we say ChatGPT, give them a feedback, constant feedback. It is good, it is bad, it is what specific part you want it to be changed, right? All these things are an iterative process. That's why we say prompt engineering is an iterative process based on the guidelines or the detailed set of instructions that you provide for a specific task. Now let's go back a bit. We said when we started about prompt engineering that it is an art as it is a science. How it is an art? It is an art because when you conceive an idea and when you write a prompt, it is your creativity which comes into picture. However, the science part comes in when you provide your generative model or LLM, or in this case, ChatGPT, the prompt and it gives you the result. Because in the back end, there is something called generative models, there is something called different transformers or architectures that are going into picture where billions of parameters are playing a role to give you this result. That becomes your science part of it. That's why prompt engineering is combination of both an art and science. Now that you have understood what is prompt engineering, let's go and see the main element of prompt engineering, that is prompts, without which generative model ChatGPT will not work. Prompts are constituted, or it contains two parts majorly, that is parameters and structure. What will be the structure and what will be the parameters of your prompts? That when you design it, you have to think so that you have an optimized result. Now, structure is one thing that we'll talk more about, and parameters here, let me explain. I have only selected few parameters. You can search more. There are more parameters on which prompts work. Majorly, here we are highlighting only 3 parameters, that is temperature, top P and max length. Temperature is the randomness that comes into picture when you provide that parameter to your prompt. It ranges from 0 to 1. And if you want your model to be creative and generate creative answers or generate creative outcomes, your range, or you set your temperature to 0.7 to 0.8. However, in tasks such as code generation, you don't need creativity. So you can set your temperature to 0 also, where you do not want creativity. Now, top P is actually kind of same as temperature. It also has creativity. Top P is top probability that it selects from. So you have a generative model. It generates results based on your prompt. Now, there can be n number of results. How does that model decide what to put as a output for you? Here, top P comes into picture. More the top P, more you have different creative answers, right? So, low for factual, high for diverse. Last is max length. Again, it is written, manage your response length. This parameter is to control the cost of your generative model as well. So, now you have understood what is prompt engineering, what is a prompt, and what are the two main components of your prompt, that is parameter and structure. Now let's see components of a good prompt. What we mean by good prompt is that your chat GPT, your generative model, gives you a good output, your good outcome, and you have less feedbacks for your chat GPT or generative model. Now let's see. The first, or I would say the first two, are context and instruction. These are interchangeable how you want to design your prompt. If you want, you keep instruction first and then context in your prompt, you can do the same. If you want to keep the context first and then instruction, you can do the same. Context is an additional information that you want to provide to your model. Instruction is a specific task that you want your model to perform. For example, if you want to summarize some text, that is your instruction. Summarize your text. Summarize this text. Context is why you want to summarize. What is the outcome you want to achieve? For example, going back to Tesla, there you are providing an instruction to summarize, but the context is that you want a business report. From a business report, you want what is the profit from 2020 to 2023, right? So that is the context that you need to set. Why do you want this? Why it is needed? Next is the input data. Okay, what is your input data? For the example, Tesla example, the input data is your business report or business article that you will provide to ChatGPT. And output indicator is what and how you want as an output. For example, you want in a CSV format your output. Suppose you want in a tabular format or you want in a graphical format. So you have to tell what kind of output or what format of output you want. So these are the 4 components of a good prompt. If your prompt consists of these 4 things, you are enabling your generative model, your chat GPT, to give you better and good results. Now, let's see an example. Here we will see sentiment analysis. We are setting up a context. It is written, act as an analyst. You are asking your chat GPT to act like an analyst working for an OTT platform. You are saying your chat GPT that you will have to perform sentiment analysis based on the feedback provided by the consumers. You are working for an OTT platform. Your consumers are the users that are seeing your movies, your web series. Now, the feedback that they provide, on that you have to do sentiment analysis. This is the context that you are giving to your chat GPT. Now, giving this, your chat GPT knows that they need to think from an analyst perspective. They need to do sentiment analysis. Now, second is instruction. You are saying to ChatGPT to classify the feedback into neutral, negative, positive. Where you are instructing or telling your ChatGPT that what is positive. Positive means your consumer is your promoter. Negative means they are demoter. Neutral means they are neither promoter or demoter. They are neutral towards your content. This is the instruction that you give. What the ChatGPT or what generative model needs to do. This is what it is doing. Classifying. Next is your input data and your output indicator. Before that, let's see an example. A good prompt. While you are giving a good prompt, if you give examples for your generative model, here in this case, we are using ChatGPT. If you give them an example, they will learn from this example and train your input data to give the output. Here we have given two examples. Feedback. First feedback is, I think the series was okay. Second feedback is, the acting of each character in the series was awesome. So, I think the series was okay. It took this okay as neutral. So, this is a sentiment neutral. Here, awesome it took as positive. So, your sentiment becomes positive. Now, your input data is the storyline for the series was repetitive and abysmal. And your output indicator here is sentiment. What is the sentiment for this? You're asking your ChatGPT what will be the sentiment of this entire prompt. That is your context that you have given, which tells ChatGPT to act as an analyst and do sentiment analysis. It gives an instruction to classify the feedback provided, that is your input data, and classify that feedback into positive, negative, and neutral. Here you are giving examples for the same so that your ChatGPT can understand, learn, and then act accordingly. Now, the output for this particular feedback is negative. So, if you copy paste this into your ChatGPT, it gives you an output as negative for this sentence. So, this is how you should write your prompt, which is good. These are the components, good components for your prompt, so that the output that ChatGPT generates for you is exact for you to work upon. So, this is what we understood about components of a good prompt. Now that you have seen what are the different components of a good prompt, let's have a look at a good checklist that you can keep in mind while designing an effective prompt for better results. So, the first one is defining the goal. Telling ChatGPT what exactly you want to do. That is called defining the goal. Next is detail out the format. Format is output format that you want ChatGPT to provide you. For example, as I told you previously, it can be table, paragraph, list, CSVs, anything that you want. And you can give it in a priority order also. Ask ChatGPT to give you in a priority order if you are working on such content. Next is creating a role. If you remember the previous prompt that we discussed, while learning about components of a good prompt, we told as a context, act like an analyst. That is creating a role so that ChatGPT assigns or processes based on your request, based on that role that you have asked. Next is clarity who the audience is, or clarify who the audience is. Basically, you are telling ChatGPT, please generate the output based on the demography of my audience, whom I am catering to. It can be beginner level, intermediate, advanced, if you are creating any content. If you are creating code, it can be foundational, functional, expert, based on the audience. It can also, if you're a teacher and you are using ChatGPT, you can specify, I want to teach fractions from a 6th class learner perspective. Or if you want to create a content, or if you're working on something and you want to make someone understand that particular concept. For example, I want a 10-year-old to understand what is prompt. How would I make that particular learner understand? That kind of clarity, that kind of clarifications, when you put in your prompt, what is your target audience, it will generate tailored feedbacks, tailored outputs for your prompt. Next is giving context. Basically, you are giving every possible additional information for ChatGPT in your prompt so that the purpose of your request is clarified to ChatGPT and the response that it generates is what you want. Next is giving examples. We saw in the previous components, while we were understanding components, that giving example trains your ChatGPT or makes it understand that what you want, and it learns from it to produce accurate results. Next is specifying the style. It can be communication style. If you're working with a brand, it can be how your brand works. Communication style such as informal, formal, what do you want to do? So it's suitable for your response. Next is defining the scope. When you outline the scope with specifications, besides giving context and examples, ChatGPT operates within those parameters. For example, temperature, when you are telling, okay, I want to be creative, my temperature is this. I want my top P to be this, right? You are defining the scope for your ChatGPT. Applying restrictions. Restrictions becomes your, what is, supposing, length that you want. The output length, the token length that you want. There is a restriction, but what is that you want? When you apply those restrictions, that constraints will create right boundaries for ChatGPT to produce relevant responses. So, all these are checklists that you can keep in mind. Again, these all pointers in your checklist revolves around all the components of a good prompt that we have already seen. But as a checklist, you can keep in mind that, okay, these are my pointers which I can follow when I'm designing my prompt. So, this is how you can write a good prompt. So, now let's understand what are the different prompt patterns. One is your persona patterns. Act as X. Do the task as Y. As a yoga instructor, create a beginner-friendly routine for joint mobility. For example, this is your persona pattern. Next is your audience persona pattern. For example, in the previous bit I told, explain this concept, supposing prompt. Explain prompt to me assume that I am a 10-year-old child. Or another example that is there, explain the importance of eating greens, assume I am a skeptical child. So you are trying to tell ChatGPT that what is your audience persona, and you are writing your prompt or designing your prompt having the correct bits. Explain to me, assume I'm this. Or previously, persona pattern, act like this. Next is visualization generator pattern. Now, I have a tool. I want to generate a data, for example, and provide that data to my tool. So, it can be generate X that can be provided to tool Y for visualization, for data analysis, for anything. It can generate data in tabular format. It can generate CSVs that can be provided, that you can download and provide it to your tool for visualization, data analysis task, modeling, machine learning tasks, anything. So these are the first three prompt patterns: persona pattern, audience persona pattern, visualization generator pattern. Now let's see the next pattern, that is recipe pattern. For example, you want to do X task, but to perform this X task, there are steps or subtasks A, B, and C. So I want ChatGPT to have a complete itinerary generated for me if I'm traveling from Bangalore to Darjeeling, and from there I can take a train or a cab to Darjeeling. Now, based on this, I am telling ChatGPT to complete my itinerary. This is a recipe pattern where you know you want to do a X task, and you know that A, B, C are the sub tasks or the steps that are necessary for you to do that X task. So this is the recipe pattern. Next is your template pattern, where you provide, or as a user, I provide the ChatGPT or generative model with placeholder, with a template and a placeholder, so that my output, ChatGPT fits my outputs in those placeholders. For example, I want a day-wise travel itinerary. If I'm visiting to Paris, I'm telling ChatGPT to generate day-wise travel itinerary for visiting Paris. Now, my placeholders are day for the day of the travel, supposing Monday. Location in Paris, what location I'm traveling to. Activity, what in that location I plan to do. Time, what is the best time or best part of the day to travel or to go there. This is my entire template, and how I want the output, it's indicated for day, visit, location, at time, for activity. So if ChatGPT generates, it will give you for Monday, visit location X at time noon, for activity visiting museum, for example. So this becomes your entire output, and you're giving the template, you're giving placeholders that place my information in these and generate output in the form of this line for day, visit, location, at time, for activity, containing everything. So these are your 5 prompt patterns that you can imbibe while designing your prompts, so that you have better responses from ChatGPT. And also you understand what you want to do, you have a clarity what you want to do, and work accordingly. If you want a pattern where you want ChatGPT to act as a person, where, or you want to give a idea to ChatGPT what audience you are catering to, or you're doing visualization, or you're doing data analysis, what is your pattern? If you're doing a task which contains subtasks or sub steps, what is the pattern you follow? And if you have a template in mind, how you want your output to be generated, then you have template pattern. So all these 5 patterns you can keep in mind along with your checklist while designing your prompts. Let's now see common prompting errors. So, vague or ambiguous prompts, when you just write, what is joins? What is prompt engineering? That is your vague and ambiguous prompts where you do not have any context, instruction, what to do. Just vague prompts. Then there are biased prompts where you are designing the prompts, supposing you have 2 categories and the data or the instructions that you are providing, the examples you are providing is leaning towards one, and now the second category is left alone. That is your biased prompts. Third is lack of contextual information. You have just said, okay, generate the content for fractions. But what is the target audience that you are acting? Are you a teacher that you are teaching? Is there any template? Is there any flow that you want to follow? Are you looking at creating a course? Are you looking at teaching fractions as a slide you want, or as paragraph you want? Anything, any contextual information is missing. Then you have insufficient examples. You do not have examples. For example, you are just saying generate synthetic data for doing sentiment analysis. But what on? You need to provide some content, some information that, okay, this is my data. Now, based on this, you generate synthetic data in a CSV format for me to do sentiment analysis. That is lacking your training data or examples, insufficient examples. Then there is complex or confusing prompts. If you write full lengthy prompts, but it is very complex, it has several different informations, such as you have target information also. You are acting as a target audience information. You are acting as a analyst, and you have target audience. You have branding also. You have campaigning also in that. It is very confusing for ChatGPT to pick one persona and act. Or, for example, you are designing a campaign, but you have given a lot of information. Check out Coca-Cola campaign that happened at this year, or check out this campaign and design my campaign. It is confusing when you give different reference points. You need to be very clear. You need to be less complex. Your prompt needs to be very simplified so that ChatGPT can understand. Last is not testing prompts thoroughly. You have given a very good prompt. You have designed a very good prompt and given to ChatGPT. It generates something, but you are not reading it. You are blindly following what it generates. You're not giving it a feedback. You're not asking what it has understood from your designed prompt. That is not testing prompt thoroughly, and you will have less accurate responses, and in some cases, wrong responses. Now let's see what are the applications, different applications of prompt engineering. One is content generation. You want copywriting, advertising, creative writing, educational content. You can do anything and everything under content generation based on your target audience, based on who you are catering to. Next is customer support and engagement. There are various chatbots and virtual assistants that can use generative models and instructional guides as well, so that your customer is engaged. You do not need human as resources to reply to your customers. There are generative models that can help you with act as a human and reply to your customers at all times 24/7. Then there is data analysis and science. Data cleaning, data preparation, visualization, as we talked about. Whatever you want to do, you can give an input as your data. There would be a size limit you give, and you tell to clean. You generate the code. You can ask what to do when you are doing statistical analysis on this kind of data, what tests, hypothesis testing to do. So all these come under data analysis and data science. Then application comes under code generation and software development, that is automating your code writing, debugging, document generation, documentation. So all these, using ChatGPT or generative models, they can make your life easy. They can generate a code for you, whatever you are looking at. But you have to be very specific. You have to be very clear what you want, so that your output, your response from ChatGPT, your generative models are customized based on your prompts. Next is research and information retrieval. Like, for example, text summarization, question answering, anything and everything. You can give links as a context and tell that, okay, these are the specific researches done in this field. Based on this, give me your hypothesis. What next can be done? For example, next is machine translation, information sharing, internal communication, anything related to machine translation. Then sentiment analysis, consumer feedback analysis, brand management, marketing, all these things using sentiment analysis can be done. And prompt engineering is used to create tools for this. Other domains include healthcare, where you can do diagnosis. You can create a system using generative model to diagnosis for a disease, and you can design prompts that, okay, my patient is this, it has a history of this, now these are the symptoms, what is your diagnosis? Manufacturing. In manufacturing, if you want to supply your manufacturing and your suppliers, you create a LLM, you create a generative model where your users, your employees can ask, if I'm manufacturing this, if I have to transport here, what to do, what not to do, everything. The mesh, the network that you have in manufacturing industry, it can intake and give you output results based on your prompts. Then comes security. Security, there are attacks. They can be a lot of AI tools that can be used to prevent those attacks, to prevent your systems, without failing. Last is retail and shopping, that is e-commerce. In your OTT platforms or shopping, e-commerce, Myntra, different websites, Amazon, they can use generative models to intake all these things, and you prompt that, okay, I want this, and it helps you with retail and shopping. So these are the various applications for prompt engineering. Now let's write a few prompts so that you can understand what are prompts, how to write them. So we are on a prompt engineering course where you understanding the outcome of this course is for you to understand what is prompt engineering, how to write a good prompt, right? So let's give ChatGPT a simple prompt, that is, what is prompt engineering, and let's see what it tells us. It starts generating and it tells you what prompt engineering refers to, what is crafting and refinement of prompts, and generates responses from AI language models such as GPT. Then it's saying that prompt engineering involves considering various factors such as language used in prompt, structure of prompt, context. Effective prompt engineering can significantly improve performance and usefulness of AI models in various domains, such as including natural language understanding, text generation, dialogue systems, etc. If you see, this is a query that you have put, which you can also put on Google and get different links, not a text, not a paragraph, but different links where you can open the links and read it. Here on ChatGPT, when you enter what is prompt engineering, you get this, a definition, a elaborated explanation of what the generative model, that is ChatGPT, that uses GPT as a generative model, understands about prompt engineering, and it tells you their perspective of it based on the different parameters that it is trained on. Now, let's see another example. Suppose I want to travel 5 days in India. Please make me itinerary. I give this a prompt. According to ChatGPT understanding, it will give me this. Arrival in Delhi. I have not said that where am I arriving from. It assumed arrival in Delhi. Day 2, Delhi to Agra. Day 3, Agra to Jaipur. Day 4, Jaipur sightseeing. Day 5, Jaipur to Delhi. And it tells me when you are in that day, you arrive in Delhi, for example. It is capital of India. Visit historic landmarks like Red Fort. Explore bustling streets of Old Delhi. Experience, optional, visit is Humayun's tomb or Qutub Minar. Okay. Again, day 2, it's giving different, or day 3, it is giving different options. I have not said here what I like. I have not said whether I am a beach person or a mountain person or a normal, I want to travel, which kind of places, hot, cold, nothing. It has not asked also. This is my random prompt that I have given ChatGPT. Now, let's see a different kind of example. I have a passage of 3-4 sentences. I want to summarize in one sentence, right? I am giving an example. That my example text is, scientists have discovered a new species of orchid in rainforests of South America. And the output that I'm giving is a new species, the entire sentence. Okay. Now, my sentence or my passage is on prompt engineering. It involves crafting precise, context-specific instructions and queries, and these prompts provide guidance. We can enhance model performance, achieve better control over generated output, and address limitations associated with open-ended language generation. And I want to summarize this into 1 or 2 sentences, right? This is my prompt. I give this, and this is what it gives me. However, isn't it feeling as same? Now, if I say, please shorten this further. For example, I don't want this much. I want short and crisp. It still gives me this. Again, I say, please be concise. Now it gives me prompt engineering uses precise prompts to guide language models, improving performance, control, and overcoming limitations in generating responses. However, the first one, when I asked, please shorten this further, it said crafting precise instructions called prompts to guide language models and shape their output. It enhances Model performance offers better control over generated responses and addresses limitations of open-ended language generation. If you compare this output with this output, some information is lost. Some information is retained while making it concise. So you have to see what responses you are getting based on your prompts and give them a feedback what you want to do. So these are some examples of prompts. This is the first time you're looking at prompts in this course. So we try to cover from basic content generation, basic query-based prompts to traveling itinerary without any information to text summarization where you are given an example and asking to summarize and giving ChatGPT a feedback on it, right? So this is your first prompt. Now let's see different components and further analyze what is a good prompt. Now let's look at few examples so that we can analyze what are good prompts and the checklist that we have seen, the persona patterns we have seen, the components that we have seen, how to integrate that while designing your prompts. Now let's see how we have designed this prompt and what all components we have included. In content generation, where we have written provide a comprehensive overview of text summarization, which is our main topic or concept that we want to understand, empowering learners to grasp its significance and potential applications across diverse domains. So basically with this line, we are telling that we want our learners to grasp what is text summarization for different domains. It can be for manufacturing domain, it can be healthcare, but what is text summarization? We want our learners to understand that. Now we have given some guidelines also here. You need to follow below guidelines while answering. We are telling ChatGPT, provide an insight into text summarization, a tool for condensing lengthy text into shorter and more manageable versions. Second, we say explore various techniques like extraction, abstraction used to achieve this and provide clarity on how it works. Third, we are saying provide relevant examples of different domains and use cases where this text summarization can be applied. Fourth is explain text summarization, how it is evolving and innovating with advancement in AI and machine learning, offering customized solutions for diverse needs. We are also giving extra instructions also that while providing insights, the learners are from different domains and have just the preliminary knowledge of text summarization. Cover the basics. For that, you cover the basics of text summarization techniques, highlight key concepts without diving into overly technical details. What not to do, we have also specified. This approach will cater to our audience's level with familiarity of the topic. We can tell the level also here, but let's see how it responds. Give explanation in clear, straightforward American English. We are telling the scope also, we are telling the communication style also. Ensuring the accessibility and understanding, maintain a clear and straightforward tone. Ensuring accessibility and ease of understanding for all learners. Now let's give this prompt to ChatGPT and see how it responds. So, it gives text summarization is a powerful tool used to condense lengthy text into shorter, more manageable versions. It's basically taken what we have provided and given as a definition, making it easier for readers to grasp main points without going through entire document. Now, this is now breaking our key aspects into better understanding. Insights into text summarization, where it tells that it can be thought of a process similar to what humans naturally do when they summarize an article, a book, or a conversation. The goal is to extract the most important information and present in a concise form. That's okay. That is the insight that it is giving. Now, we also highlighted that please ensure that you are using extraction and abstraction also to explain text summarization. And along with that, use examples and use cases also, where it is highlighting what are the applications in various domains, in news aggregation, academic research, legal documents, that is your law, in branding, social media, in customer feedback analysis, which different companies uses. Then it is giving the evolution and advancements with time, what it has done. Customized summaries, multimodal summarization, real-time summarization, evaluation matrix, various things that has evolved in text summarization. Now, if you want more insights on text summarization, where you want different techniques for it to explain different techniques, you need to tell, please explain furthermore or elaborate furthermore on techniques used, on extraction or abstraction, or give me more examples, not application, examples. So if you see here, it has given use cases, the applications across, it has not given examples. So you can say, this is my feedback to you that the explanation that you have generated is missing example. I am not able to correlate what is given here, what you have generated here, right? So you can tell the examples are missing. You can also tell that evolution and advancements does not tell me when it started, does not tell me a history. Evolution means history. It is not telling me that. So all these are your feedbacks so that you can have a output, you can have a response, a final response that gives you what is text summarization, what is the significance of text summarization, what are different techniques of text summarization, what are the different examples of text summarization, what are the applications, how it evolved, when it started, what are the different things, what are the different advancements in using AI now. So you can definitely work furthermore. Now, this was ChatGPT 3.5. Let's now see in ChatGPT 4. We create a new chat and give the same prompt to ChatGPT 4 also and see how it responds. What is the difference between 4 and 3? We have given the same prompt, not changed a single line here. So it has generated an output where it generates a content on text summarization. And if you note the first line, it has not taken the same thing that we have given as prompt. It has written and explained in its different words or different explanation what is text summarization, which is a powerful tool in the field of natural language processing designed to condense long pieces of text into shorter, concise summaries. Now, it tells you the techniques of text summarization, which is abstraction and extraction, with tools and various examples of it, various applications of it. Now, it tells you applications across various domains as well, which is closely the same as 3.5. Again, this is also missing your examples. It has not given you any example. In evolution, if you see, it has given how it has evolved. You can also give a feedback to ChatGPT 4 that I want a timeline evolution for text summarization. And it has briefly explained some advancement. Again, as compared to 3.5, that is missing, which you can give as a feedback and it can improve upon. So this is what content generation example was in both ChatGPT 3.5 and ChatGPT 4. Now, let's see a different example, that is text summarization. We learned about text summarization. Now you have fairly a good idea what is text summarization. You give what you want to understand and it summarizes and gives you output. Summaries basically of what you provide. Now, let's provide ChatGPT an article and ask it to summarize it. So, we have the text summarization example here, where we are given an article on Indian Express based on Tesla policy, and we have asked that use Pinto pyramid principle, and we have given the link also to that to structure your communication from top down, ensuring swift and clear message delivery. Start with the conclusion, follow with key arguments, and then support with detailed information. Give only relevant information that is appropriate to understand business outcomes only. Use clear and straightforward language for better understanding. So, we have given a context and instruction. We have not given an example here, but we have given clear instruction and we have given restrictions also. We have given a style also that be straightforward, right? You can further give that, okay, make your word limit to this much only. Okay, so let's first see what it generates. So, in Pinto pyramid principle, we write a conclusion first. Then we write key argument, why we have concluded. So basically, if you are having a conversation and you want to conclude that conversation, you will write that conclusion first. Then you will write your key arguments. Okay, this is why I'm telling. And then you write the detailed information that is related. So basically, we want, because we are asking for business, right? Business needs conclusion first. So we have concluded this first, that India's decision to lower import taxes on EV could potentially pave the way for Tesla, led by Elon Musk, to enter Indian market. Now, key arguments are lowering import taxes, Tesla entry into Indian market, boost for India's EV industry. Then we have detailed inputs from that report only that are mentioned here, right? So, this is a text summarization in a structured way. Text summarization can also be, if you go back in the first prompt that you have written, where we had 4-5 lines and it summarized for us. That is also text summarization. This is a structured text summarization where you do not need to go through this whole article of Indian Express and it gave you a conclusion, it gave you key arguments, what it presented in the article, right? So, this is an example for text summarization. Now, let's do an example on code generation, which mostly from people from tech domain or data domain will use ChatGPT for, right? So, the prompt has a Python recursion code for calculating factorial, where we are defining a method to calculate factorial if n is equals to 1, equal to 1, return n, else return n into calculate factorial. We are doing recursively, right? Now, the same calculating factorial we have done with non-tail recursive function, right? We are giving an example on that as well. Now, what we want is to write a program with recursive function to check if a string is palindrome in Python or not, right? Where we have given 2 examples of recursion on factorial, and now we are asking ChatGPT to generate code for palindrome. Now, this has given that, okay, with comments that this is the base case. If the length of the string is 0 or 1, it's a palindrome. Compare the first and last characters of the string, false. Okay. Return false if it is not equal. Recursive call, check if the substring excluding the first and last characters, right? So this becomes your output. Now this function works by recursively checking if the first and last characters of the strings are same. Okay. You can also in your prompt say, please explain line by line as well if you want further elaborated explanation as well. Though it has given comments, right? You can further ask, give me further more explanation for this. Now let's see the same thing in ChatGPT 4. In ChatGPT 4, it actually has explained what is this function, what it does, where len is equals to 0, a single character, what it will do. Both cases will be true. It returns true. Okay. What is the recursive case first checks if the first and last characters of the string are same. Calls is palindrome. It is telling each and everything that the function is doing. This is equivalent. However, this is a little bit optimized version of 3.5. Now you can see a difference between how or what 3.5 generates code for a specific problem statement and how 4 generates. So basically 4 is more optimized for code generation rather than 3.5. In 3.5 you can iteratively ask, please optimize this, right? In 4, you can do once or twice and then actually it will give you an optimized version for the same. And you can write furthermore to refine your prompt. You can write, please give me the complexity, time complexity, storage complexity for the same, space complexity for the same, right? So these are the examples for a good prompt where you are giving a context, where you're giving an instruction, where you are giving restrictions, where you are following items from your checklist, where you are following a pattern to provide a pattern to your ChatGPT as well. So these are some of the examples that you can refine more, you can experiment more with. Advanced prompt strategies. These are different prompts or different types of prompts that exists. We are taking only 3 types: zero shot, few shot, chain of thought process. That's it. There are several different more strategies that exist, like self-consistency, tree of thought, respond, rephrase, etc. You can go and dive deeper into the same. Let's now see what is zero shot. Zero shot is directly instructing your model, that is ChatGPT, to perform a task without any additional examples. For example, I just say, classify my feedback into neutral, positive, and negative. And I give a line. That is the input. And it outputs the sentiment. That's it. This is my zero shot. Few shot is teaching with examples that we saw previously, where we gave 2 examples, and third is our input, where we are indicating how we want the output, and it gives the output for the same. So that is few shot. Zero shot is without any example. Any prompt without any example, where you are only telling the instruction. That's it. No context. Few shot is giving examples for ChatGPT to learn and produce your response. Now, chain of thought. Chain of thought is designed for logical tasks. Anything logical, it is the best prompt strategy to follow. You give in chain of thought an example how to do a process. For example, you are adding. You are given an example 2 plus 2 is equals to 4. Then you say 15 plus 4 is equals to 19. Then you give an input. Okay, I want 3,150 plus 10,500. What will be my answer? You are telling how to do the process. And then you are asking in your input what will be the output. This is very basic. There are complex problems. For example, blood relations. X is related to Y. So what will be the relation for Z with X? So all these logical questions, all these logical and complex bits is for chain of thought. Now let's see examples of these 3 prompt strategies on ChatGPT so that you understand it better how to work with these on actual playground. Let's now see few examples on these advanced prompt strategies: zero shot, few shot, and chain of thought. Now, zero shot is giving no examples, just giving the instruction, just giving what it needs to do. So we'll take a simple example, very generalized example, where we are generating a passage in the style of William Shakespeare. Okay, we are giving this prompt. Based on what ChatGPT would have been trained on, it has given a passage of William Shakespeare. But from where it is from? You can ask from where this passage is from. The passage I provided is an original composition written in the style of William Shakespeare. While it captures the language, imagery, and themes often found in Shakespearean work, it is not directly derived from any specific text by the bard. Did you want the same? Right? You need to give the feedback. Now, I did not want in this manner. I wanted a extract from his own plays or his own poetry and given as an example, right? Or is it following what you want, right? You can give that as a feedback as well. Now, this is zero shot. If we want to make this as a few shot, we need to give an example. We have given an example. Generate a passage in the style of William Shakespeare. Example is original text to be or not to be. That is the question. Shakespearean style rewrite is whether this nobler in the mind to suffer the slings and arrows of outrageous fortune. Similarly, in example 2, we have given all the worlds is a stage and all the men and women merely players, right? So now we say this is few shot. It has given an example: out brief candle, lives but a walking shadow, a poor player that struts and frits his hour upon the stage and then is heard no more. Right? And Shakespearean style for this. So, this is an example of zero shot And this is an example of few shot, right? Let's take another example where we say ChatGPT to translate. It's a lot of William Shakespeare, right? Let's take a more simpler example where I say, translate this English sentence to Spanish. I am a Spanish reader. This is the English sentence I want to translate into Spanish. I say this and it gives the translation for this. Now, if I want to make this few short, I'll add examples. I'll add more examples for the same. I'll add, say that, okay, this is my article. I can give an article also and say, please translate this. These are my examples. Now take this article and translate in Spanish for me. I can do that as well. So that becomes few short for the same. In ChatGPT 4, there is an option that we want to highlight is that you can click on this attachment, add any attachment. It can be data set, it can be images, and train your ChatGPT that, okay, for example, you want to train, these are the picture of roses, where you provide different pictures of roses. And in input, as an input data, you give lily and you ask, what is it? Is it a rose? And it tells you based on what images you have input, is it a rose or not? Just a random example. The same can be used for data science or data analysis, different activities, visualizations as well, where you can give the data and ask ChatGPT to analyze, visualize the data and give you outputs for the same. Now, let's see chain of thought. Chain of thought is said to be logical. It works on logical bits, right? Here in this prompt example, we have designed few question and answer that is on blood relation, where the first question is, if Michael says, Patrick's mother is the only daughter of my mother, how is Michael related to Patrick? We are giving the answer is, Michael is saying that Patrick's mother is Michael's own mother's only daughter. This means Patrick's mother is Michael's sister, making Michael Patrick's uncle. Okay. Second example we are giving, Emma is John's sister, Mark is John's father, Linda is Mark's sister, and Thomas is Linda's son. What is the relation between Emma and Thomas? Emma is John's son, making her Mark's daughter. Linda, being Mark's sister, is Emma's aunt, which makes Thomas, who is Linda's son, Emma's cousin. Right? Now, our input question is, Alex introduces Brad to his friend as the son of the only brother of his mother. How is Brad related to Alex? Output is, Brad is the son of the only brother of Alex's mother, which means Brad is Alex's cousin. Right? Logically, it correlates, the chain of thought correlates based upon your examples. Chain of thought can be of different types as well, where you can give different examples, complex examples as well, and it works. It is zero shot also, it is few shot also. So basically, this comes under few shot chain of thought prompt. Okay. Zero shot is separate, where you give directly what you want without more explanation in your prompt designs, right? And then there is automatic chain of thought as well. So there are various chain of thought prompts as well. You can explore more and deep dive there as well. Apart from chain of thought, we have different prompting strategies as highlighted earlier. We have self-consistency, we have prompt chaining, we have response, rephrase, we have tree of thought. We have many advanced prompt strategies which you can deep dive and apply based on your requirement, your prompt design what you want to do with your generative models with ChatGPT. Hope you have understood these three different advanced prompt strategies: zero shot, where you do not provide any examples; few shot, where you teach AI with few examples; and chain of thought, where it has three versions and is used for logical thinking and logical problems. Then we understood what are the components of a good prompt, what are the different checklists that you can follow to create a good prompt, to design a good prompt. Then we saw what are the different persona patterns that you can think of while designing your prompt, following the checklist. Then we understood different advanced strategies, prompt strategies, which is zero shot prompting, few shot prompting, chain of thought, with examples. We saw what are the common prompting errors that can happen if you miss something. And at last, we saw applications of prompt engineering. What are the different fields in which prompt engineering can be used? So, the key to becoming a proficient prompt engineer is to practice, experiment with different prompts. Again and again, give feedback to your generative models, be it ChatGPT, be it Gemini, be it any generative model. Analyze your outcomes, what response you are receiving, and giving them the feedback. Refine your techniques, refine your prompts based on the checklist that is provided, based on the different strategies. Read about different strategies and apply them. That is refining your techniques. Keep practicing, stay curious, explore various AI platforms to enhance your skills. This is how you can become a efficient prompt engineer.
We have covered generative AI and large language model. We also looked into prompt engineering and learned how to design inputs that steer these models to produce the most accurate and relevant results. For more insights into Gen AI, LLMs and prompt engineering, subscribe to our channel and stay updated with our latest release. Now let's move ahead and look into AI projects and case studies. We'll explore AI and case studies, a deep learning use case in face recognition, and wrap up with an NLP demo featuring NLP with BERT. Ready to see AI in action? Let's get started.
We have a credit data set. Again, we are now we have a tabular form of data. So that one, the example that we saw was image data, multi-class problem. Here we have binary classification problem where we have two classes, 0 and 1. We need to predict whether the individual will default or not default. Okay, how the data looks like, to show you, like, this is the data that we have. So I'm not explaining the data in detail, and also not I'm covering the EDA part here because I left it to you guys. You can do it because that we already have been doing so far, so many times. So that's why, but I wanted to focus more on the architecture and technical components part. So that's why I'm not covering EDA here, because the data is clean from my side. I've done that in the past and then using the clean data. But again, if you want to apply this, you can apply post the I'll go if you want to run the model here, but do the EDA part on your own. Okay. So yeah, the data set we have is credit data, and we have around 1,000 observations with 21 columns. Last column is actually the class column, which we want to predict here. So there are a couple of, again, numerical features and categorical features as we see in the tabular form of data. So yeah, so then we see the class distribution. We have 70% of zeros and 30% of 1. Which is pretty much fine. Like, we don't have to worry about the skewed distribution. Like 70-30 ratio is okay, acceptable in the industry. So, but in terms of credit industry, it's heavy. It's little heavy because data is modified. Generally, we find 5 to 10% of the defaulter, even lesser than that. So defaulter rate cannot be more than 5% because then it'll be a huge cost to the bank, right? So info on the data set. Yes, we have certain features. Couple of them are numerical or object type. So that is available. Credit data missing value, again, as I told you, we have treated this data, so there is no missing value in this data. So I'm not worried about the missing value part here. No EDA part is covered. But you can see here, then what we do is that, yeah, the credit data, and then let me start with the encoding part, which is the one hot encoding. So we have a couple of numerical and categorical features. Now let's start the the data pre-processing part, right? Get ourselves ready with for the model. Like neural network also take the same way, right? So it cannot take the text. We have to convert the string values or text value into numbers so that we can pass the data into the model. How do we do that? We typically apply the get dummies or PD one-hot encoding technique. You can say here, what I'm doing is I'm calling the, so first I'm capturing the categorical columns from the model, select type, object, all the categorical column into a list. And then I'm selecting that categorical, creating as a categorical data by taking all the categorical columns from my main data set. Okay. So which is these columns: status of existing checking account, credit history, purpose, foreign worker, and all these you can see these are all categories. Some of them are bureau data, so we have data. We should have ideally data dictionary for this one. I'm not covering that, but all of them categories have some meaning in themselves. Okay. Then we apply get dummies on the categorical data that we have. So then we have from 13 features of the categorical one, we've reached to 54 features, right? So like we after applying the one-hot encoding technique, right? So we have credit data encoded. Then what I'm doing is I'm taking my categorical data and dropping all the categorical columns from my main data set and combining one data. So which basically means that I'm preparing my data with all the columns, numerical and categorical, into one data form. So I have done that here. Credit data encoded has encoded features, categorical features, as well as numerical data here. From here onwards, you can see, right, from the credit amount or duration in month and credit amount, right? So that's a numerical column. So I've combined them. Now what I do is now I do train test split. So how do I do train test split? Simple. There's one technique I want to capture here, and I think we miss that most of the time, but some people do it. People who do it are good. People who don't do it, please take care of this one. What we are doing here is we do train test split on my credit main data. Okay. So and simply the code we apply is the train size we take, like we define a data, like we call the function train test split. We pass the data, our train size, the data set that we want to keep in the train data set, 70-30% ratio, and random state. What happens is you can see now that after creating this, I'm creating df train, df test, df y train, df y test. So you can see the distribution here. If you remember the previous distribution, the distribution was 70-30, right? 70% and 30%. Now, after changing after creating the train and split, the distribution changes. My train data becomes 71%, 28%. My test data reduces to 69 to 30%, right? So there's a distributional change, right? So it's happening. And if we have multi-class problem, here it is not visible that much. If we have multi-class problem or if we have skewed distribution, this distribution difference can be even bigger, right? You might have a test data set which might not be representative, right? Because you have a distributional change. What if you have 5% ones in your overall data? After doing the train test split, you are left with in the train data, you have 10%, you are there with the 10% 0 to 10 ratio of the 0 and 1s, and in the test data you have only 2%. So that is also possible. So in the skewed classes, it can also be even severe. But we need to be careful for that. To do that, there is a simple technique we do is stratified sampling. We must have heard about this in stats classes. So what we do is we stratified equal to y, and then what we do is we can see that we compare the distribution in the train and test. We make sure that our test and train are both on the same distribution. Okay, actual data in future can be different. That's a different scenario. But the idea of the train and test is that they should be the distributionally equal. Okay. So then after doing that, so now this is my train data and this is my test data. Now I'm doing the scaling part. Again, we do one more, sometime we miss here is that we do the scaling on overall data, right? We scale overall our main data set, and then we then do with train and test split. So if you see here, we have done the train and test split first and then doing the scaling part, right? How do we do that? We first extract the numerical columns, and what we do is we on our training data, which is we're creating training numerical data. I'm from my dfx train, I'm extracting all the numerical columns, and I am fitting a min-max scalar process on my train data only. So I'm doing fit transform on my train data, right? Just take care of this one. Some people do it in overall data. Don't do that, because then what happens is it is storing the mean and standard deviation, whatever the, like here we have minimum and maximum value from the train data itself, because that's what we are training our model. We don't want to fit transform on a test data. right? Or we only want to transform our test data so that whatever the data that we have test data in our test data should be not visible to the model should not know about anything about our test data, right? That is the whole purpose. So that's why we only do transform on the test and fit transform on the train part. So that's why we had to do like first train and test split and then apply these techniques here. So I am train data fit transform, you can say, and test data I'm doing the transformation part. Okay, so you can see here transform part, so that my whatever parameters that I've created, my min-max scaler is creating, that should be saved from the train data, should be applied to all the data which the model has not seen, which is one test data here as well as some future data set. Okay. Okay. So then, as I told you, that the model, the neural network deep learning model takes the data into array shape, as we have seen in the image example, right? The data has to be passed as an array. So then what we do is from the training and test, we create arrays of the data, right? So which means data looks like that. How do you see, like if I see train data first observation, we had 704, observations with 61 columns. But if after converting the array, how do the test data look? How do the X train looks like? It looks like this. You can say there will be 61 columns. It will be one row. Similarly, Y test or Y train, how it will look like? You can see that this is also an array form, right? You can say the 5 observations I'm seeing, 5 classes I'm seeing. It's a binary classification. So this belongs to one, like whole data is this one, and then this one class, and then second, third, fourth, and fifth. Okay. Yeah, you can see type here, which is NumPy array. Now the same process follow, define and compile Keras model. How do we define the model? I've created a function here, but the process is same. You can see layer 1, which is the the first hidden layer. We first call model sequential, and that in the model sequential, we are adding the layer. 10 neurons we are passing, right? We are not passing 100, 200 here. It's a small data set. We are passing 10 neurons. Again, it's subjective how much we want to pass. Looks like it's a small data set. We don't have very complex problems in this data, so we can pass less number of neurons. You can try with other values of neurons. Input shape, input dimension. The same way we entered the input shape 28 by 28. Here also we are adding the input dimension. Input dimension must have taken here, which is nothing but the value that we want to pass. Input dimension, how many columns we have. So we have 61 columns here. We'll enter 61 later, right? So then activation equal to ReLU. So we are adding ReLU activation here in the layer, in the first layer. Then we have second layer, same thing, model.add, then again 10 neurons, and then activation layer is ReLU. Activation function is ReLU. Third layer. So we are building 3-layer neural, in fact, 4-layer neural network. 3-layer neural network, because the third layer is output, that is sigmoid activation, right? So we need binary output 0 on 1. So that's why we need one node, right? And the sigmoid activation function. Okay. Optimizer, there we were using SGD, stochastic gradient descent. There is another algorithm called adaptive moment optimization. It's a mix of little advanced technique in the gradient descent algorithm. You can use that. Right now, we have not discussed this, so you don't have to worry about that part. You can use same SGD as well. But this Adam is one of the other optimized algorithm on the gradient descent algorithm that we pass with a certain learning rate. As I told you, that gradient descent takes learning rate. So we have passed 0.01 learning rate. Okay. People now can question, okay, how much learning we should start with? The idea is in the industry, whichever model it is, whether it's a gradient descent or gradient boosting algorithm, or it's a neural network algorithm, we start with a low learning rate. Start with the low learning rate, and then over the time improve the learning rate. Okay. Sorry, high learning rate and then reduce it. I'm doing the reverse way. Sorry. Then we are just printing the model summary, and then we are compiling the model. So I am defining and compiling the model in one function. You can also follow the same process. Binary cross entropy, why? Because we have two classes. Binary class we're predicting. Optimizer, the same, SGD or Adam, and then metrics equal to accuracy we are interested in. So we are passing as a parameter here. So if we are interested in F1 score, precision recall, we can put that as well. Okay. So then we return the model. Right, that's a function that we built. How do we fit the model? Again, input dimension. We know that we have 61 columns. So we pass the 61 features. Here, training epochs, 50 times we want to pass the whole training data set, right? So batch size, the same thing. Metrics equal to accuracy. Validation set is nothing but the validation set X test and Y test that we have. How do we call the model? I am calling the DNN binary classification KS here. Right, input dimension 61, metrics equal to metrics, or you can pass the name here as well, right? And you can see that how many parameters are we calculating. You can calculate the parameters. We have 61 features, 10 is the neurons that we're adding. So 61 multiplied by, sorry, 62 because we are adding the intercept as well in the model. So 62 plus 10 multiplied by 10, sorry, 620. And then next 10 as well in the next hidden layer, 110, then 11. So we get 741 is the total parameters that we have. So including the intercept, we are adding one more. That's why. Okay, so how do we call the, so this is the model summary that we get. And then how do we call the model? Bin class model I am calling, and then binary classification, the function that I'm calling, and passing the input and metrics here. And you can see how I'm running. So I'm fitting my model on my train data, validation data, batch size, epoch, right? So we have, you remember we had fixed 50 epochs. So you can see that we have 50 like times the model will run, and you can see how much accuracy we are getting. So at the end, we have 99.83 on the training data, and validation data, we have poor accuracy, 82%, right? So this is something we can say an overfitting problem, but again, overfitting, we have to make sure that whatever pre-processing part we follow in the train data, we also follow the test data, because if the difference is, yeah, 5-10%, then it's okay, it's overfitting problem. But if the difference is more than 15-20%, then it's a different problem altogether. You have a different distribution of the data. So that's where we need to take care of in the data pre-processing part. But yes, like by broadly, I can say, yeah, model is overfitting. We need to take care of that. How do we do that? That's the hyperparameter optimization process of the neural network, which I have captured, I've covered here, but we don't have time to cover that in detail. The 6th point here. But you can definitely have a look. What are the parameters we have? I told you the optimizer, like the stochastic gradient descent, mini batch, Adam, all these are hyperparameters. Learning rate is one of the hyperparameter. Batch size, epoch, all these are hyperparameters of a neural network. You can use grid search CV as well to tune them all together. But again, if you apply that, it'll take a lot of time. Okay, but how do we save the model? Yes, we have saved the model here. Once you do that, you will see that like it'll be folder, it'll be created. Once you follow this path, a folder will be created here. You will see the I mean, your model will be saved. How do you load the model? I have given the command here in this previous one. I think forgot to cover that. You can load the model back. It's the same way we load the machine learning model. Same thing. Predictions, recall, precision recall 99% on the train data, test data is 70%. So we are not that good in predicting the ones which we need actually. So that's why we definitely need an optimization technique to overcome this problem. Okay. How are we in terms of doing validation loss and accuracy loss? You can see the accuracy. You can see that this is what it's happening. Okay. See, dead neuron problem is the same thing. Like the activation function, if we talk about, right? So on the edges, I told you, right? The slope gets steeper. So flat, right? So there we have a dead neuron problem that we can't. Which means that what happens is that once the gradient or the slope gets lesser and lesser, smaller and smaller, the value of the neuron gets slower and slower. Lesser and lesser, right? It close to zero, which means that it's a kind of dead neuron problem. It's a kind of dead neuron, right? So sigmoid, tanh, all these functions where we see the flatness on the edges actually face a dead neuron issue. So that we need to. So there are techniques like momentum, you can say, or you can say RMS prop, or the other these techniques we try to overcome the dead neuron problems. Basically, there are better algorithms available in gradient descent, advanced algorithm, which tackles this problem, or other activation function as well, like parametric ReLU, ELU, all these ReLU function activation function we apply to handle the dead neuron problem.
Is scaling necessary in linear and logistic regression?
No, I told you, right? So it's not necessary in the neural network as well. But again, if we do it, like in linear and logistic, if I talk about, no, it's not necessary. We don't do that. But if you're running a ridge regression, lasso regression, then it becomes important because you have learning rate and other parameters like there you optimize the parameter which minimizes your the MAE and L1 regulation and L2 regularization problem. Sorry for that. I forgot that part. But in L1, L2 regulation, they require a normalized data. Although again, there as well, you don't have to, but it's better if you use that. The scaling part we do mainly in whichever algorithm it is, apart from few distance-based algorithm. If we try to use any other algorithm, they are to improve the speed and what you call the smoothing of the process. That's the only thing. The scaling helps. Otherwise, scaling doesn't improve your accuracy. Scaling doesn't improve your anything related to your model accuracy metrics, I would say. It only helps you in processing the data, optimizing, converging your algorithms. It might be little faster or optimized algorithm you will get. Apart from that, scaling doesn't help anywhere, but it doesn't harm definitely. So people, that's why people use it. Then question comes is, okay, why people use it all the time? It doesn't harm. It makes your process a little fast. It doesn't harm the algorithm. So why don't we apply that to get faster results?
So we will see how to, we've seen the concepts. Let's see how we can apply the same in the data set. So I'm just bringing in the usual pandas, NumPy brothers, and matplot. I'm reading the data set, read Excel, Bharti Excel, and this is my data set that I have. I just removed all this. This data set I downloaded from nseindia.com from historical prices, and of course it is free of cost. And it comes with a lot of prices: open, high, low, previous close, last traded price, and what is today's close. Right? And my subject of interest is on today's close. And this comes with VWAP. If someone is already in stock market, you will know this: VWAP, volume, value, number of trades, and all that. In terms of time series forecasting, you don't have just to predict the prices. You can also predict the number of trades also, whether a lot of people will be interested in my stock today or not. Right? It's not just the prices. With these mechanisms, you can predict the value, what will be the volume tomorrow, what will be the number of trades, will there be crowd, or the number of traders will be increasing tomorrow or not. Everything you can learn and start forecasting. Right? Today's interest is on predicting a stock price. So let's just focus on this. So my new data set will be just one column. You can do some multivariate analysis also. This feature engineering is something that I strongly recommend you to follow. Most of you must be already doing it. I'm quite sure about it. But if you don't know about it, please start exploring about this, because this is what will separate good data scientists from an average data scientist. Right? The data is one and the same for everyone. The algorithm is one and the same for everyone. Right? You can do some hyperparameter tuning and all that, but still not much of a difference that you can make. The difference that you can make is how well you read this data and how well you bring in some new information. Right? Let's say 5 days trend. I can create a new variable, 5 days trend. What is the last 5 days trend? Is it up, or is it down, or is it flat? Right? Was yesterday a high volume day? Right? If it is a high volume day yesterday, nobody will look at that stock today. They will move on to the next stock. Right? So if you want to trade, you want to know whether people will come into the market today or not. So I can say high volume, right? 1 or 0, and this perhaps can be 1, 0, or let's say this is 2, 1, and 0. I can create a label encoding also, and I can keep on increasing a lot of feature engineering. At once I went crazy and I built about 100 plus variables. And that is what the difference that makes, right? What are you teaching here? You are teaching the pattern to the data set, to the model. I'm sorry, right? You are getting the pattern and you're giving it to the model. This is just the data. If models are performing well on the data, think about model performing on the patterns. It will really relate to the real business world and it will give higher accuracy, right? And you can strongly rely on the output that you get from the model. Right? So that is basically multivariate time series. We will not be covering that. I hope that is not the same in your academics as well. But the algorithm is one and the same. The codes is one and the same. You just create feature engineering and get new variables and apply the algorithm. Okay? One thing I wanted to say. So I'm bringing in the data set along with pandas pd.read Excel. Of course, this is an Excel file, not CSV file. There is a super cool function called past dates. This helps you to help Python to identify the date by itself. Yeah, and I will be sharing this Colab file to all of you. So don't bother about typing now. Focus your time on listening to this. And past dates is equal to true will help the pandas to realize that this is a date variable and not a numerical variable. And if I mention index column is equal to date, it will automatically become a index column, right? And I get the info of it. We can say all the variables are in either float or integer. The variable that I'm interested is on the closing price of Bharti Airtel. Right? So I'm just getting that df close dot plot. This space is there because in the data set that you download from the NSC itself, there will be a space. There will be an intentional space. I think the data engineering team did not see this. So when you enter the close, you must ensure that there is a gap here. Right? So length of the DF, I have 496 days of data. And if I had plotted that, this is how the trend of Bharti Airtel for the past 496 days. In stock market, for a year, you will have 250 days, which means I have about 2 years of data. From 2009 of July till now, I have 2 years of data. And we can see the stock has moved from 350 to about 530, 525 levels currently. Right? And we can see there is no seasonality or trend or anything. Of course, yeah, trend is there. Trend is together, it is at the upside. And we will predict whether the current trend is on the negative side or not. Right? It is at the verge of coming down. As we can see, this is the bottom. And if it falls below that, there are a lot of chances it will come down. Let's see what neural network model thinks about this trend, whether it will go up or come down. Right? So I'm creating a data frame. Airtel close is equal to df close. So this is my data set. And I'm resetting it. I have the date with me. So when I just filter that, it will come with the index value also. So the new data set will be having date also. So I'm just dropping the index, resetting the index and dropping the same so that I will have only one column. And I'm just making it as a data frame. Now let's do a train test split. The way you can do is the data dot index location, and starting from 0, I can specify as 0 and I can just leave it as it is to 480th day. And the test data will start from 480. So if I say 480, it will start from 481. Right? 481 to whatever the length of the data. I can specify as 496, but it is always safe to leave it as it is. Sometimes you may not know what is the exact ending of your data. You can just leave it as it is rather than checking for the same and updating here. Right? And what if your test data changes tomorrow? So it is always better to leave it as it is. Right? So I'm giving 480 days to my train and only 16 days to test. Right? I cannot give 70-30% here because I don't want to predict what will happen to Bharti Airtel for next 100 days. Right? That's not going to make sense. I don't want to keep forecasting over forecast for next 100 days. I very well know there will be too much of noise. So I have splitted the data. Now let's do a scaling. See, scaling is not required at all, to be honest, but still you can do, because when you apply some deep learning models, it is going to take some computational power. And if the values are within the range, the computation time will be lesser. Right? So it is always better to scale them, and they don't change the variance in your data set. Right? So doing scaling is not going to harm at all. It can be standard scalar or min-max scalar. I prefer min-max because this is always going to have a positive value, right? It will always be within 0 to 1. X minus minimum divided by max minus min. So it will always be within a 0 to 1. So that's why I prefer min-max scalar always. And scalar.fit, I'm fitting it on the train data set. When I do this, I will get the max value and the min value of the training data set. Once I do that, I use the same maximum and minimum to transform the train values. And I'm going to use the same maximum minimum of my train data set on my test data set. This is a common pitfall. I think most of your mentors would have already told this. When you do scaling, you first split the data set. You apply the scaling on the train data set, get the parameters. In terms of min-max, you will get minimum and maximum values of train, and you will project the same on the test data set. In terms of z-score, you will get the mean and variance of train data set, mean and the standard deviation, and you will apply the same on the test data set. That is for the case of z-score. Now I'm using the deep learning models from TensorFlow This is the library for using a lot of deep learning models, Keras and TensorFlow. One advantage in using in Colab is that you don't have to install these libraries. It will come automatically. But when you want to install in your local machine, sometimes you will end up at a lot of errors. It requires some exceptions, and some libraries should be up to date. A lot of dependencies are there. Right? So it is always better to run these libraries in Google Colab. Only thing is you need internet connection. Right? From TensorFlow.keras preprocessing.sequence. Right? Under the sequence umbrella, we have n number of factors, and this is a sequential data which we already know. Right? So from there, I'm generating something called time series generator. This generator helps us to transform the values, and it will save in an array format. Right? We will shortly see what it does. And for any function, if you want to know what that function does, just do help within the same, pass in the function name, which is time series generator, and it tells you what it actually does, what kind of output that you can expect. And let's say this class takes in a sequence of data points gathered at equal intervals, which means on equal, let's say if it is daily, on daily basis, along with time series parameters such as length of the history to produce batches or training validation. Right? So what are the arguments it expects? The original data itself, and what is the length of the data that you are passing in. These are the two things that are required. What this will do is, let's say if I have 100 training data, and I want to give next 15 test values. So together I will have 150 data points, and the last 15 is basically the test data. Now I will have to validate it. I hope most of you know what is validation data set, right? Other than this is like a test data set wherein which we create, once again, we split the data into 3: train, validation, and test. Before passing on the data to test, we will pass it on to the validation to once again validate the model. This was the traditional practice, and the same can be followed in time series as well. Right? Now, so you can go through this generated at your available time. Now let's pass on this. So I have 16 days of my test data. So I will pass on this length as 16. My batch size is 32. See, this batch size can even be 1. If I say batch size is equal to 1, at every iteration, the entire batch will be considered. If I have 496 days, the entire 496 days will be taken. But if I split them into, let's say, 10 or 20 or 32, the computational power will be very, very lesser. If I give 1 at a time, the model has to be run on all the 496 points. But if I give 10, it will run parallelly on all the data points, 50 by 50 by 50. Right? So the time it is going to take is very, very lesser. Right? You can always play around this batch size. See, this entire neural network, if you run once, you will get different result. And the second time you run, you will get second different result. In your own machine, the same codes, same data set. That is how the neural network works. Right? The weight initialization is always random. Right? So it is always better to iterate over each batch size and identify which is the better for your model. I started from 1. I kept 5, 10, 20. Normally, for larger data set, people give 32. Of course, we don't have a larger data set here, but generally 32 works really well. Right? It can be 1 also. It can be anything. It is going to directly impact your computational power and the time. Now let's build a generator object, time series generator, your data set. This expects X data and Y data. And your time series, your data is X and Y, right? So that's why we give scale train, scale train. X is also scale train, Y is also scale train. Length is equal to 16, your test data size. The batch size is equal to batch size. Okay? This will create an object of train and minus length data. Let's say if my train data is 496, 16 days will be removed and 480 data points will be there. And the last 16 values will be predicted. That's why I give length of 16, which is equal to my test size. Right? Now I have the data set with me that is ready for model building. Now let's build the model. So from TensorFlow.keras.models, import sequential, and from TensorFlow import dense, simple RNN, LSTM, and dropout. We'll see what are these. Don't bother about these new terms. If it is new to you, don't bother about it. We will very shortly see what are these. Right. So I brought in the important functions. Let's build the model. Like in sklearn, what we normally do, we first build the model object, then we will fit it on the train data set. Right. We will say model is equal to sklearn.logistic regression, open and close. Right. We will say some parameters and we will project it on the train data set. The same is what we are going to do here. Only that there are some more functions that we will add to the model. Model is equal to sequential. This is my initial model. And model.add, I'm going to add some parameters, which is my algorithm name is simple RNN. And the number of neurons that I give here is 30. So it has to be minimum 16. If I'm predicting 16 outputs, it has to be minimum 16 and it can be anything. Right? If I want to keep more layers, if I want to create more neurons, I can create more neurons. It can even be 100 also, but going for more neurons will overfit your model. Right? So I just keep it as 30. You can also try with 16 or 20, 25. Right? I tried it and 30 worked really well for me. And input shape, what kind of data are you going to bring in? Length, which is the test size, and the number of features. How many features are you going to bring? Which is only one feature. I have only one feature. Right? If you have a multivariate time series wherein which you have 5 x variables and only one target variable, then you'll have to specify them clearly here. Right? X dot shape of the number of rows and the number of columns. Right? Here we have only one column, so we've made it quite simple. The next one is dropout. This dropout is nothing but this helps you to overcome the overfitting issue. Rather than learning from all the data points, let's say if I give 0.2, it means it will not learn from one data point out of 5 data points in the past. Right? So that is what dropout is. This helps you not to overfit the model. Right? The default rate is 0.2. It's not just here. The overall dropout default rate is 0.2, and I've just used it here, and it really worked well. And I add another layer. By adding it, what we are doing, we are actually adding layers to the model. This is one layer, and this is my output layer. Dense is basically the output layer, which is just one. Right? I'm going to predict only one data point for every layer. For every day, I'll have only one output, right? So dense is equal to 1. And model.compile, this is where I bring in the back propagation, wherein which optimizer is equal to Adam and loss is equal to MSC. So in terms of error, y minus y square, my error here is MSC, which is y minus y bar the whole square. Right? Based on that, the optimizer will start applying the gradient, and it will change the weights accordingly. It either increase or decrease. So get the model summary. This is my entire model. The model summary, it has 960 parameters, which is nothing but the input shape, the length into features, right? And once the model object is built, then we will put it on the data set, right? This is what we do in sklearn as well. Model.fit the train data set. Model.fit generator. Generator is the object that I've created here with my training data set. I'll just pass it this here. Epochs is nothing but the number of iteration, right? We will, the back propagation, we'll know how it actually works, and we'll have to stop at a certain level, right? If not, it will keep learning. So I'm going to fix a value that my number of iteration is going to be 10 times, right? If you give more number of epochs, your model will overfit. And if you give very lesser number of epochs, your model will underfit. Right? So you'll have to strike a balance between them. You cannot always decide which is a correct epoch. You will have to only iterate and look at the error, and you can see which one is a better one. Right? Essentially, I gave 10 here, and shuffle is equal to false. Why shuffle is equal to false? And this is a sequential data, right? I don't want to shuffle. And if you run it, this might take light of higher time than the ANN. So once I've run it, I can see in my each iteration how the loss is brought down. From 0.14, it has been brought down once again to much lesser level of 0.015. Right? This is my model history. I can get the same by pd.dataframe model.history.history. This function gives you the loss function, nothing but these numbers. I can just save them as losses data frame, and if I just plot it, I can see the way the error is starting to come down. And if I don't give the epochs, normally how ANN works is, if the error is getting stabilized, the iteration will get stopped. Right? Instead of doing that, I've given manually the number of epochs, and it looks like at the 10th epoch, the error is at the lowest level. Right? I don't want to furthermore reduce the error. If I do that, I will overfit my model. That is why I said, if you give higher epochs, the model will overfit. Right? Now we have built the model. Let us create a batch, and we will test the same. So in my train data set, I will get the last 16 values. If I say minus length, which is 16, it will give me the last 16 values. Right? These are my last 16 values in my train data set. Right? And we will use the same values, and we will predict the next value. Let's say this is 16 value. This is first test value. Let me predict the first test value, which is model.predict, the same that we've learned in sklearn. Model.predict first eval batch, which is basically the first value of this. And this gives me an output of 0.75. So the first actual value is somewhere around 0.79, and this is 0.75. About 4% of error here, but still looks like a good one to me. Now what I'm going to do is, the same way I predicted for first value, I will have to predict for all the 16 values. So I will have to apply for loop, right? That is what I'm doing here. I'm creating an empty list, test predictions, which will save all the predictions like this, and passing in the first batch, the last 16 values, and model.predict current batch for every first value. So it will keep predicting the first value. And this line of function will give me the predictions. I'm not going to spend too much time on explaining this. What happened is, as we speak, this code was there for past 2 years. As we speak, there is already a predict function that can do all this in TensorFlow. Right? I will also share that prediction code after this session when I share this collab file. So you don't have to do all this heavy lifting. Just like what we do in sklearn, we just predict it and it will do all the data sorting, making it as a data frame or array by itself. Right? So we have the predict function with TensorFlow also. So with that, you can do this quite easily. Once we get the prediction, this is a scaled value. Right? This is not my original value. So to bring back to the original value, I can use inverse transform function. True predictions is equal to scalar dot inverse transform function, the min-max scalar that I've already saved before building the models, pass in the test predictions. So this gives me these values. So the predictions are 538, 529, 534, and it says the stock is likely to be somewhere around 528 after 16 days. Right, so let's just add this to my test data set. So this is my original test data set, and these are my predictions. And we can see there is a good amount of error, 546, 538, about 1%, 1.5% of error. Here it is 2% of error. Right, 545 minus 534, about 10 points, which is 2% of error. Right, but we can see at the end they are converging together. The error is coming down. But let's just plot the same, and this is the plot of this test value. I'm not plotting the entire data frame, and we can see it has picked up the noise quite well. Only that it has missed out some trends here, but it has picked up the learning has been quite intense. We can understand the comparison, and this is the final prediction. Right? This is my original value, and just the part that we are actually looking here is this part. Now we have 496 days, and we built model only on 480 days, and we predicted the next 16 days, and we are quite happy with this accuracy. Right? Let's build full model. When I say full model, I will learn from all the 496 days, and I will predict next 16 days. Okay. So apply the min-max scaler on the full data set, the entire 496, and create a time series generator like we did earlier. The length is equal to the same 16 days. Batch size is equal to 32. Build the model, sequential, simple RNN, the same features. I'm not going to change anything here. The same model. Fit generator and check for the losses. Once again, the losses are at a minimum level. Take the predictions. These are my forecasted values for next 16 days. I'm just adding them to my data set. Let me just. So full data is equal to pd.dataframe, np.concatenate, forecast.flatten. I'm using flatten here because I will get an output in a 2D array. Right? This is basically in a 2D array. We can see two squares here, right? So this is in a 2D array. I'm just using the flatten function to make it a 1D array. So after doing that, I'm just plotting the full data set. So this has next 16 days trend also. If you look at the original plot, up till 500, this was the trend, and this is after 500, next 16 days. And it says the stock price is going to come down. And this was up till 29th July. The data I had was till 29th July. So this was, 29th June. This was the closing price on 29th June. And after that, the stock prices have come down. Right? And that is what is reflecting here also. And I said 29th July. So this is future. 30th July. 29th June was the ending date. 30th June. 1st July, 2nd July. And on 2nd July, my model says it should have been 516, but the actual price was 525. Right? There is a 2% error in this model. Right? So this is basically RNN that we have built. And one good thing about this is this was able to pick up the noise. Right? And 2% error is somewhere around you can accept. Okay? Now let's build LSTM model. What is LSTM? It will not forget the past values also. What if this kind of trend was there in the past? Let's say this kind of trend and this kind of trend. This is what we are having here. Right? If that is the case, what will happen? Right? It looks like if that is the case, the stock price will come down drastically. Let's see if LSTM is able to say that the trend is going to be on the downside or not by remembering the past values. Right? And here, this is practically not required, but I'm just giving you, when you work on a very large data set, this is something you need. What is this? When my model accuracy is coming down, I don't want to look at this plot and decide which kind of epochs that I have to give. I want my model to automatically predict the epochs where the error will start to stabilize. Right? So if you look at this, this is once again from callbacks in Keras function, early stopping. I'm saying in terms of validation loss. In terms of validation loss, if the loss is getting minimized and stabilized, stop the epochs. Even if I given 50 epochs, if the error is down and stabilized at the 10th epochs, at the 10th epoch, the model will stop at the 10th epoch. It will not go up till 50th epoch. This way, I can once again ensure that the model is not overfitting. right? So, and what kind of level I'm saying? I'm saying if for the next 2 epochs, the validation loss is not coming down, stop the iteration. Okay, so it will wait for 2. It's by default it is 0. I can say 2. You can, if it is a very large data set, you can say 5 or 10 also. Right. Once again, let's this length and everything is one and the same. Let's build the generator here. One small requirement for LSTM is that the length should not be one and the same. It should be one data point lesser than that. Right? It does not accept the lost data point. So I've kept length as 15 and I'm building a generator here. Additionally, I'm also building a validation generator. While LSTM is running, it will also have to look at the validation error. Right? Earlier, we did not added this. So we are adding it here so that parallelly my model will also run the validation test and it will stop at the number of iteration where the error is minimizing. And if you look at this model, the way you can build, once again, sequential model.add, this is one layer. To this neural network, I've just added one layer and the output layer. I've not added multiple layers. This is a very simple data set, right? So I'm bringing in LSTM, 13 neurons. Input shape is length, comma, number of features. Dropout is once again 0.2. And my optimizer is Adam and loss is equal to MSC. See, each parameter that you see in neural network can be tweaked, right? They are not hard and fast rules. It's not that the dropout has to be always 0.2. If you want to take risk, you can say 0.4 also. Or if you want to say play safe, 0.1. There are different Adam optimizers also, different solvers that are available in Python. And loss function also, you can use map, mean, absolute percentage error or absolute error, right? You can change over different values. Then you build the model.fit generated. I have built the model object, then apply it on the data set, which is generated. I'm giving 20 epochs. I'm giving higher epochs because I've given the early stop mechanism. So if the epoch is better, then it will stop automatically. And validation data is equal to validation generator. So when this is building the model, it will also look for the validation error. Based on that, it will stop. So callbacks is equal to early stop. Once again, shuffle is equal to false. Right? And this says at the 6th epoch itself, the validation error has brought down and it believes that further epoch is not required. Right? So this is the benefit of early stop. What is the difference between dropout and early stop? Dropout is basically to forget something in the past. Let's say if I keep 0.2%, out of past 5 values, 1 value will not be considered for my learning. Right? Why am I doing this? Because if my model learns all the past 5 days, there is a chance for overfitting. So you can avoid this also. You can run the model without this also. There is no error. But if you want to, when I ran this model without dropout, my model overfitted. So I just used the dropout here. Even when I used this, there was a chance of overfitting. As you can see here, the loss was here and the validation loss was much lesser. Right? There was a chances of overfitting here. So that's why I earlier used dropout and brought down. Earlier it was even worse. So to answer Sunil Kumar, yeah, the scaling is not required. That is what I said. Scaling is really not required, but this is a practice of making, let's say you work on some data which has 1 lakh values and it is going to take too much of computational power, right? When you calculate the MSC values will be very large, right? It is only going to take too much of computational values. But if I keep them in a scaling, the values will be, computation will be very, very lesser. That's why we scale it. And as I said, it is not compulsory. It's up to your own wish. Right? So the validation loss is attractive. So I can go out and predict the same. I'm predicting the same using the same line of codes, which we earlier used. I've also given the explanation here. If you want, you can just go through, run everything, print everything separately and understand what each line of codes are doing. But this is nothing but location, array location and reshaping the values. Okay. I've done the predictions. I will just inverse transform them. And when I plotted them, the RNN had actually worked really well, but the LSTM is far beyond the levels. Right? It is way out of the league. The actual values are blue ones, and the LSTM is way below that. Let's understand why that is the case. Right? This looks like a poor forecasting. I honestly agree that this is a poor forecasting, but what happens here, let us understand. I'm forecasting the future also. Now, I'm okay with this model. I will explain very shortly why I'm okay with this model. I'm going to forecast the future. The same formula, the codes and everything is one and the same. I'm just forecasting, inversing them, adding to the data frame. And this is how my original, the forecasted values are looking like. It says the stock price is going to fall down. And why it is the case? Because see, I can able to interpret this because I know the domain and I don't know this model as well. I know the Bharti Airtel as well. This is something that every day morning when I wake up, I look at this stock. And LSTM, even though this forecast looks weird to you, it has smartly picked up the downtrend that is going to come in Bharti Airtel. I'm not sure about it, what's going to happen tomorrow in Bharti Airtel. But if you look at the past events like this, which I shown earlier, this kind of trend, in this kind of slide, Bharti Airtel never have came up. Okay, only at a far below level it had came up. But other than that, most of the time it have come down. And in terms of memory, LSTM was able to pick up that, and it is actually giving you a downtrend. Right? And this was one of the smart things with the LSTM. And if I had run more epochs, see, when we got this output, I had ran the model with 10 epochs. But here I had ran only about 6 epochs. Maybe if I increase my epochs, look at this, I have only 6 epochs. So if I increase my epochs, probably my model might perform closer to the actual values. Right? That is something I can iterate over different parameters. But I'm quite okay with this. I'm going to select RNN as my best model only for this data set. Why? Because we can see more number of times Bharti Airtel will go into a range bound, then it will react. Then it will go into a range bound, then it will react. Most of the time it is within a range bound. So past 5 days or 10 days values were dictating the next day value. That's why RNN is more than enough rather than memorizing what happened past 2 years before. Right? But LSTM came in additionally and said there is a chance of downtrend, which your RNN was not able to say. Your RNN is saying the stock price is likely to go up. There is a chance that the stock will come down. But look at this prediction of RNN. What does it tells you? It is likely to go up and come down, which was not there in the training data. And it actually worked in the yesterday. It all of a sudden went up and it came down. Right? This was slightly picked up by RNN, but of course, as I said, don't take it as a recommendation. See, you can never forecast anything in the stock market. Right? There are thousands of algorithms, thousands of geniuses that have been in the stock market, but you can never say what will happen tomorrow. But you can build tools to most probably say what you can expect tomorrow. Right? That is why we do all these things. Tomorrow, what can happen? So I will have a probabilistic view on what can happen tomorrow, and based on that, I can take some precautionary actions. Let's say I am an investment banker and I handle a cash of 1,000 crores, and I cannot simply believe my intuition, right? I need some technical tools to say what will happen or what might happen tomorrow. That is where you can use these kind of deep learning models, right? And this trend says after 16 days, Bharti Airtel is likely to go to 512 rupees from June 29. So which means somewhere around July 20, because I'll have to neglect the Saturdays and Sundays. So around July 20, LSTM says Bharti Airtel is likely to go to 512.40. Right? Maybe check the next week or the next to next week of prices. You will understand this and see whether this model is powerful or not. I'm just thinking the prices are likely to come down. Let's see what happens in the future. And this is not in the academics. I'm just giving you another model, which is Facebook Prophet model. This was built inside the Facebook only, and this was particularly focused on very short-term data, like 1 minute data, 1 hour data, 10 seconds data. Facebook wanted to predict how many events will happen in next 1 hour throughout the world. And some employees in Facebook, they created this model, which is called as FP Prophet, right? Let's not go too much into this. Even the people who have built this have not given complete details about it. But one good thing about this model is it is very simple to apply. It just needs your X variable, which is date, and the close, which is your Y variable. I'm saving it here. And date should be saved as DS and close should be saved as Y. This is one of the requirements for this library. So I've renamed them. Then just apply the model, that's all. The way you can apply this, Prophet, change point scalar, this is some degree of change that I'm giving. And daily seasonality, I'm giving as true here. Right? This is a daily data, so I'm giving daily seasonality is equal to true. Of course, there is no seasonality in the data, but I'm just giving some parameters to test what is going to happen. And if you get the predictions, just follow these codes. These are very simple. This is the only line where you can predict the future. Think about LSTM, where we gave a lot line of codes, but in FB Prophet, this is simple. Right? These are just customizations. And FB Prophet is also saying that the Bharti Airtel price is going to come down. Right? All the dots are actually the actual data, and within which it have found out some trend. And based on that trend, FB Prophet is also saying the Bharti Airtel is going to come down. My LSTM is saying the same, and my FB Prophet is saying the same. Let's see what's going to happen in next 2 weeks. Right? I'm quite sure you will all be looking at that price. Just go to Google, check for Bharti Airtel share price. Let me know how it went. Okay? And this model once again can be decomposed. And when I decomposed it, this is the trend that the Prophet model has identified. And in terms of weekly seasonality, there is no seasonality. And it says sometimes on Thursday, the stock price comes down, on Friday, it goes up. Right? And daily seasonality, there is not much to look at this. This is a daily data from morning to evening. We don't have hourly data with us, so we'll just have to ignore this. Right? So, great. And I think this is it, guys. I hope the session was useful to you. I will just run through the questions that I received. I think I've answered most of them. Yeah. So why did I choose this company? Because I know I've been. You will also know for the next 1 month. This stock is always in a range. Right? This will always be in a range. There will be some sudden movement, then it will always be in a range. Right? If you look at some other stocks, they will not be in a range. Let's say Adani Ports, for that matter. You can select any stocks, they will. So this is also in a range. I'm not sure what kind of, let's say, Reliance Infra. Or let's get the Reliance Share. Right? They are not in a particular range. They always keep moving. And Reliance Infra, maybe this was in a trend. And right, see, these kind of stocks are always on the move. Right? You cannot predict the same. Right? Each share price. Someone wants to see each share price. Once again, this is always on the move. This is not on a break-even range. Right? It will always not be within a range. You see, you can also predict ITC. ITC and Bharti Airtel these days are one and the same, and we can see it will be in a range, then it will move, then once again it will be in a range. Right? You can apply the algorithm on ITC also. And I applied it and it said ITC is also likely to come down. So that is the reason I selected Bharti Airtel here. But you can ask me one question: what to do if my stock is moving all the time? Let's say I'm not sure if SBA is right. SBA is also moving. It is always in some trend, right? If that is the case, what can I do is I'll have to create a stacked model. I will create another layer of model here. Let's say I will say model.add. See, what is hidden? Why do we use hidden layer? Because our learning has to be deep, right? So for a data that has too many noise, you need more hidden layers, right? So that is where you can add another layer of LSTM. Then you run the model. Right? For this data set, I did not require, but if your model has too many noise, or if your data set has too many noise, you can use the same. Right? By this, you can, this is basically called as stacked LSTM. I will just thank this. This is basically stacked LSTM. So you are further deepening the learning so that the model will pick up that noise also.
Fantastic part of our particular session is we're going to actually dive right into Python, and we're going to take a look at this particular demo that I have planned for you guys, where we're going to be performing face detection with OpenCV, right? But then before we get to that, what is the most important thing that I told you all, right? The first most important thing that all of you all should really be concerned with is the data at hand, right? Now, let me quickly go on to my desktop. I'll open face detection files. I'll actually open up two files that I want to use to perform face detection, right? Again, both of these are my faces itself, but then both are very different. So I want to see if my this thing program can actually go on to solve and find and detect a face here, right? Let me open both the images in fact for you guys. Right now, these are my pictures itself. These are pictures of me, where one you can see that I have a straight pose, and this sort of looks like me in short hair. I mean, of course, it's me in short hair. And then I wanted to see if this particular model can also find a face if it is sideways, right? Now, looking at a face head on, you can probably tell what a face looks like, but maybe my computer might not understand what a face looks like, especially if it's at the side, and if it's especially near an ocean and I have a specs on, I have a huge beard on, and I have a ton of hair, right? So everything in the image that you see on your right is meant to confuse that particular, confuse the computer itself, confuse its learning to see if it can be confused or not. But of course, on the left hand side, it's just my face, right? Both have my faces, but let's just see how we can go on to use these two faces to see if we can have some sort of result that we can go on to use, right? Perfect. Now, what I'll do is I'm going to quickly open up Google Chrome here, and I'm going to open up Google Colab. Right now, Google Colab is basically it's a Jupyter notebook that's hosted on the Google Cloud platform. To get to Google Colab, all you have to do is you have to go to collab.research.google.com. Let me show that again here, right? collab.research.google.com, or you just go to Google and type Colab, COLAB, and that will be the first result that these guys will show you, because it's their own search engine from Google and it's their own product as well. Right? Okay, now what I'm going to do is I'm going to sign into my email ID. Alright guys, so I just logged into my particular account, my Google account. Basically, if you have a Gmail account or any other Google account, you can actually sign in for free. Google Colab is a free tool to use. So the most simple thing that you guys can do is just start entering your pieces of code and start running it. That's it. You don't have to install Python, you don't have to configure Python, you don't have to break your head about why something is not working, how do you program the path, how do you work with the environmental variable, how do you do this, how do you do that. Absolutely no confusion, right? Just start typing your code, hit enter, and if your code is syntactically correct with respect to Python, it will work for free, right? Now, this is not using the computing power of my laptop right now. It's going to be using the computing power of all the servers it has, right? Huge rugged servers Google has for their Google Cloud Computing Platform, right? GCP. So this is basically a Jupyter notebook hosted on the Google Cloud Platform itself, right? Now, anyway, guys, coming to our demo, we're going to be doing face detection with Python, and we're going to be using the OpenCV library here. Now, understand what we're doing. We're trying to detect a face, right? So to go on to do that, basically, if you are thinking about how many lines of code are required, 100 lines of code is required, as I just mentioned at the start of the session, I'm going to be doing this on how many lines? 1, 2, 3, 4, 5, 6, 7, 8 lines. In fact, you can actually do it in 6 lines of code, right? Think about it, 6 lines of code and you're doing face detection. How simple can Python get? How simple can OpenCV get? And how you can just understand that if you have a face recognition project, right? 8 lines of code and you're done with face detection. So rest of the time you can actually think about how you can work on building the neural network and all of that for your recognition applications, right? Now what I'll do, ladies and gentlemen, is I'll zoom in a little so that all of you all, right, I know a lot of you watch these videos on your mobile phone, so I just want to make sure that you all can see the code, and in fact you can do it alongside me as well, right guys? Let's get started. The first thing is I have to connect to the runtime here. I just connected. Let me go on to the runtime and see what type of runtime we have. It has to be a GPU based hardware accelerator because we're going to be using images a lot, right? GPU as in graphical processing unit. It's also called as a graphic card. Now it's not using my graphic card in the laptop. It just assigned me a virtual graphic card which is present in a server sitting anywhere across the globe in any of Google's data centers, right? So I'm using their hardware. I'm using everything from their side for computation purposes, and all I'm doing from my side is entering the Python code, hitting enter. That is it, right? Cool. Now, what is step number 1, ladies and gentlemen, when we're working with solving any problem? Step number 1 is to make sure you guys will always import every single library that you are going to require, right? So let me just click this button, and as soon as I hit that play and as soon as it stops rotating, you can see that I've imported the OpenCV library. If you had to manually do this, you have to download it, you have to pip install it or install it via Anaconda, you have to configure it. Sometimes it works, sometimes it doesn't work, right? I am sure you've been in that situation. But this time, all I did is hit that button and it's ready. Now, I told you about how most of the time we'll be using a pre-trained classifier from OpenCV to go on to detect faces for us, right? Or we'll have to just go through the entire step of having millions of images and training a network based on that. Look at this. One line of code, basically all we're trying to do is open an XML file which consists of it. It's called as the cascade. So when I go on to talk about how we'll have to go on to use this particular cascade, the first thing we'll have to do, ladies and gentlemen, is to upload the file, right? Or it's going to give us an error. So what I'm going to do, I'm going to go to my desktop and I have the files related for this, and I have this particular XML file called as face detector. Right now, I'm going to open it and I'm going to upload it to the Google Cloud Platform. Now it knows where the particular trained file is, right? So as you can see, it's rotating here on the left, yellow color. And as soon as it completes rotating, it's basically trying to upload it and have it ready for us to use. And can you see this file here, face underscore detector XML? Now our file is ready. So what do I do is as soon as I go on to run this, now there is this pre-trained network, all the data from our trained network, which is already pre-trained and ready. So we've loaded the cascade now. The next thing we need to go on to do is give it an input image, right? It needs an image of a face to see if it can detect anything. All I'm trying to do is use this method called as IamRead, and I'm just giving it the name of the file. Now, the name of the file that I wanted to understand is test1.jpg. Now what I'm going to do, I'm going to upload it, right? Now guys, just to save time, I'm going to upload both test1 and test2, okay? So as you can see, I'm uploading both the files, or I just have to do it again. So now you can see that test1 is uploaded, test2 is uploaded. In fact, let me click on test1. Let me double click on it. As soon as I double click on it, on the right side, you can see what this image is, right? This is me. This is my face. Fantastic. So I have the correct image. So let me just close all of these things. So guys, the next step after I've actually uploaded an image, as you just saw, is to make sure that we can perform face detection, right? Now, face detection is a fantastic thing, especially with OpenCVs. You can see this function called as detect multiscale, right? So this one function, this literally one function is going to be used by us to do the entire recognition aspect of things, to find where the face is, right? This is what is used. Now, as soon as I go on to click on this, now it has actually found out where my face is on the image. Now, how do I know if it understands this? How do I evaluate if it has detected my face correctly or not, right? That is when I'm going to have to actually draw a little rectangle on my face so that I understand, hey, my computer knows where my image is or where my face in the image is, right? Now, as soon as I go on to click on this, all we are trying to do is we're trying to create a rectangle on our own image. So basically, we're trying to copy an image, have the image ready, in that find the x and y coordinates, right? It's a two-dimensional image. It has x-axis and y-axis. Then I'm just going to try to add these values w and h to basically go on to just find where my face is, center it on my face, and put a small rectangle there, right? Now, as soon as I click on this, the rectangle is drawn on my face. Now, what's the next thing that I have to do? So after it has basically detected my face, right, the next thing that we're going to have to take a look at is seeing the result. So what I'm going to try to do is, again, one line of code. It says the photo is successfully exported. But where is the photo? Let me click on this, and it would have created one more file for us. It's called as face underscore detected .png, right? You can see that this is the output file. So this right now should be the output file, right? Let me right click on it. Let me hit download. And as soon as I click on download and I open it, you will be surprised to see that our face detection worked with 8 lines of code, right? Look at this. It found out in this image where my face is. It zeroed in on my face and it has put a blue rectangle on my face. Now, this is a very straightforward image where I'm looking into the camera where it looks like a guy. Now what I'm going to do is I'm going to want to confuse this particular model here. I'm going to change it to test2.jpg. Do you remember test2.jpg, ladies and gentlemen, where we actually go on to, have a picture of my face with really long hair and it's a sideways pose, right? So this is again me with long hair. Now I'm going to see if it detects my face here or not, if it knows what the face looks like sideways. Of course, it's been trained with multiple different millions and millions of images, so I'm sure it'll do it. So what I'm going to do is I'm going to start executing all these pieces of code again. I just changed test1 to test2. I'm going to run this piece of code, and as soon as I run this, it has detected my face. It has already seen it in the image, or it might not have, or it might have detected it wrong. We're not considering all those exceptional cases here. What is the next thing that we have to do? Draw a rectangle on the face. Once we draw a rectangle on the face, I'm going to see if it's correct or not. I'm going to export it. Now again, it might export it with the same name, or of course I can change the name here as well. Let me download it again. And this time, of course, it's going to be the latest one. It's going to be test2, right? Now, as soon as I open this, it might have detected. Yes, you can look at that, right? Even with the side post, even with shades on, a lot of beard, a lot of mustache, ton of hair, and a very confusing angle on the picture, this algorithm understood. This pre-trained network was intelligent enough to say, hey, here's your image. And what? We're doing all of these, ladies and gentlemen, with 8 lines of code, and I'm very confident that I can convert all the 8 lines of code, maybe bring it down to 5 or 6, right? Now, this is the entire magic of Python. This is the entire magic of how one would go on to use Python with respect to OpenCV and with respect to face detection, right? Now you can definitely write a lot of lines of code going ahead from here. Once your model has already detected a face, you can use the detection, make your model take a screenshot of it, send that into a neural network, convert it into vector embeddings. Once it understands who the person is, you can perform classification, you can perform, you can give a probability of an output saying, hey, right? So let me actually show you this. Now, let me go to downloads here. Let me go to downloads. Let me open up the first image that it gave me, right? This one. Now, as soon as I look at this, it can take a screenshot of my particular face. It can detect all the features of it, and it can use this, in fact, to learn for maybe other faces that I might give of my own, right? Now, if I just use one picture to train my model and say, hey, can you please tell me who the guy in the side pose is? There's a good chance it cannot do that. If I've just trained it on one image, but if I've trained it on hundreds of images, it can tell me that, hey, a face has been detected, right? Now, if this was a face recognition system, it would say face detected Anirudh Rao, right? It's not saying that because we've just done face detection here, but then this is the first step to get to recognition, right? Cool. So this was the simple demo that I wanted to show all of you all. And as I told you, it's very simple.
So now in this case, what we are going to do, we are going to create a model which will predict whether a sentence belongs to the is successor of the earlier sentence or not. Okay. Now we are at this Google Colab. Now what we are going to do, since we had discussed that we will be using a Hugging Face, so for that we will be installing this transformer. So now let's install it. It will take some time. Requirement satisfied. Since we have already installed it, so we don't need to do that. If you are using it for the first time, you need to install it. Okay. Now we will upload a text file. So this is a meditation novel data set. Okay. So now we will load this data. So we will load this data. This data is here. So you will get the access to this data. So now we are loading it. 100% done. Yes. Now we have loaded the data. Okay. So now let's access this data. So before accessing the data, what we are going to do, from transformers, we are loading this BERT tokenizer and BERT for pre-training. Okay. So, and we are applying PyTorch here. So we are loading torch. Okay. we are creating a tokenizer and model by calling bird tokenizer dot from pre-trained, that is bird base uncased. Okay, then from this pre-training, from pre-trained. Okay, so we are loading this pre-trained models architecture here, okay, into the model and into the token. Okay, now let's open this file. So this will take few seconds. Yes, we have loaded it. Now we are into loading the models. Now we have done it. Okay, so you can ignore this. Okay, this warning we can ignore for now. Now let's see the size of the text. So the text size is 507. Let's see few of the texts. Okay, now we have got the text. So let's see last words. Okay, now what we are going to create, we are going to create a bag of sentences. Okay, and by splitting the sentence by periods, and if we do not have this last keywords, okay, by not keeping the spaces. Okay, if you see the like what typically happens that in input sometimes that this is also a sentence. Okay, so we do not want to keep this with us. Okay, so if the item is not blank, we will keep it. Okay, so now let's execute it. Now let's see this bag 0. So first sentence we have with us. Okay, now let's calculate the length of the thing. Now the length is 1372. So let's calculate the length of the keywords whose length whose number of strings are highest. So we can see that 1946 is the highest number of length. Then we will create a test data from this data. Okay, so what we are going to do, we are training it on certain data, and then we will be testing that with the test data. Okay, so that test data will unseen to the model. Okay, so for that we will just applying this string slicing here. So we'll keep this. Now we'll just create update this bag by removing these last four texts. Okay, now what we are going to do is we will be setting up the test bag size. Okay, that is 4. Then bag size, that will be our input text size. Okay, now as we know that the this works on next word prediction as well as it works on MLM, so we need to prepare the data for that. Okay, so in order to prepare that data, we are creating sentence A, sentence B, and whether the sentence A is followed by B or not. Okay, so for that we have a label list. Okay, so we are taking each paragraph from the text, and then from that paragraph we are extracting the sentence. Okay, and then we are finding out the total length of the sentences. Then if the sentence size is greater than 1, then what we will be going to do, we will be applying a random. Okay, we will be taking a start random, and then we will be appending the next sentence 1 and the sentence B randomly. Else if it is not, then we will be not using that. Okay, so now let's execute it to prepare the data. So now our data is ready. So now let's see, for example, this sentence A. I will just put a sentence A. So you will see that sentence A is there. Okay, now like here we will be, if we apply label, we will see the labels whether it belongs to the next or not. Okay, this way we create a label data. Okay, now we will tokenize this sentence A and sentence B. Okay, and returning a PyTorch tensor. Okay, with keeping max length of 100. Okay, and truncation is true. That means if the length of the string is greater than 100, we will truncate to length 100. Okay, and padding will be the max length. So now let's execute it. So it is done. Now let's see the keys. So the key for this input is a dictionary. It has input IDs, token type IDs, and attention mask to that. Okay, Now what we will be doing, next sentence label, for that we will transposing that label and we will feeding that into this inputs. Okay, and we will clone this as an input label. Okay, now what we are going to do, we are going to create a mask array. Okay, by just giving a random float number to this rand. Okay, so let's create it. So now we have done this. Now let's create our sentence. Okay, now let's create a selection. Okay, selection list, and let's just append it. Okay, so we have done this. Now let's see what this selection is consisting of. So this sentence is nothing but this sentence is consisting of the tokens. Okay, input ID tokens. Okay, now let's just create it. Okay, now let's see input keys. Now we have keys as 2 keys extra, that is next sentence label and the labels. Okay, now we will be creating a meditation data set for the PyTorch. Okay, so here we are just creating a like constructor for that, for the encoding. Okay, and then we are getting the data, and then we are returning the length of the data. Okay, so let's create it, and now create a data for that class. Okay, and return a data set. Okay, now what we are going to do, we are just returning a data loader. Okay, into the loader. Okay, by providing this data set, batch size is 5 and the shuffle is true. Let's execute it. That is done. Now what we are going to do, okay, let me tell you one thing. Since we are using this Google Colab, so what you need to do, you need to go to the setting in the very beginning. Either you can choose TPU or you can choose GPU. If you choose none, you will not be able to use the CUDA, okay, or the GPU. So here what we are doing, it will find the torch will find if CUDA is available, it will use CUDA, else it will use CPU. Okay, so since we are using Google Colab, so we have this CUDA available with us. So to that model we will add CUDA. Okay, so now if you see, this is the architecture of the BERT. Okay, now if you see how many layers are there and how many parameters are there. Okay, so it's insane. If I say the parameters which it is consisting are insane. Okay, now let's move on to the next. Here what we are using Adam W as an optimizer. Okay, with learning rate of this much, that is 0. Like to the power -5. Okay, now create a optimizer for that. So we will model dot train and this. Okay, so now next what we are going to do, we are going to collect if there is any variable which we are not using and that is a garbage for us. So we will use that, and if CUDA, we will clear the empty cache. Okay, cache memory we will clear it. Okay, now next what we are going to do, we are going to train the model. Okay, one at a time. Okay, and the number of epochs are 5. Okay, and then what we are doing it here, for each epoch, loop is this loader. Okay, loader which we have defined it earlier here. If you go, let me come down. If you see this is loader, we have defined it here. So we are just creating a data set up a loop with tqdm and loader. So what it will do, it will just give you the progress bar. Then what we are going to do in that loop, we are applying batch for each loop. Okay, then optimizer, we are grading it to 0, initial calculated gradient. Okay, and then we are pulling out all the tensor batches. Okay, input IDs, this token ID, token type ID, attention mask, next sentence label, and the label. Okay, and this is returning us output, or here we are training the model. Okay, initializing the model by giving the inputs to that is input IDs, attention mask, this key type, next sentence, and the label. Okay, and to this we are extracting the loss of the model. Okay, and then we are applying the backward propagation, then we are applying this optimization. Okay, and we are just describing the each loop. Okay, and we are showing the loss. So now let's execute it. So if you see it closely, it will start, and it takes few minutes to complete. Okay, so what we will be doing, we will be resuming it once the training is done. Now our model is trained. Now we can see that epoch 0 is completed, epoch 1 is completed, 2 is completed, 3 and 4 is completed, with the loss of, you can see that 0.44, 1.08, 0.30, 0.218 and 0.36. So we can say that model was converging well, although in the last we can say that this loss is greater than this one. So we can say that after that the loss is getting increased. Okay, or we need to tweak it further, so we can improve the results. Now let's see, we have our test data with us. Okay, so this is our test data. We had initially extracted the 4 sentences from this. Okay, and what we are going to do, we are going to tokenize this. Let me show you what we are going to do here. So let's say this, we'll just feed these two information. Okay, and sentence 1, let's say. Okay, and here again we will do this with sentence 1. Okay, so now if you see this is the input and this is the next input. Okay, so we need to identify whether the model is able to identify that this text 1 is followed by text 0 or not. Okay, so for that we will create the input. So just create the input, and then these inputs will get feed into the model, and then we will see the outputs. Okay, so now we can see that we have prediction logic. Okay, and we have sequence relation logic. Okay, so now let's execute it. Now we can see that there is a tensor 0 is coming. Okay, that means it is the next keyword is following it. Okay, now if I do this, replace it by sentence 2, let's say. Okay, because the sequence should be sequence 0, then sequence 1, then sequence 2. Now let's suppose that we want to identify whether the sentence 2 is followed by sentence 0 or not. Okay, so now let's execute it. Now let's see this. Let's see this. So this is giving you a 1. That means it is not getting followed by the sentence. Okay, so this way we can tell our model that whether the next sentence is followed by the previous one or not. Okay, so yeah, that's about it from this with this use case.
We have come a long way in our exploration of artificial intelligence, starting with its fundamentals and history. We then clarified the key distinction between AI, machine learning and deep learning. Building on that foundation, we then looked into neural network deep learning, followed by hands-on insights into ANN TensorFlows. Next, we explored the dynamic field of computer vision with an overview of OpenCV and convolutional neural network. Our journey continued with natural language processing, where we covered text representation, TF-IDF. We also introduced generative AI, large language models, and prompt engineering, showcasing their transformative power. Finally, we wrapped up with the real-world application in AI project and case studies, exploring use cases in ANN and deep learning. Thanks for watching. If you found this journey enlightening, be sure to subscribe to our channel for more such videos. Keep exploring and pushing the boundaries of AI. See you in the next video.